A Popular History of Astronomy During the 19th Century. By Agnes M. Clerke. Introduction. We can distinguish three kinds of astronomy, each with a different origin and history, but all mutually dependent, and composing, in their fundamental unity, one science. First in order of time came the art of observing the returns, and measuring the places, of the heavenly bodies. This was the sole astronomy of the Chinese and Chaldeans. But to it the vigorous Greek mind added a highly complex geometrical plan of their movements, for which Copernicus substituted a more harmonious system, without as yet any idea of a compelling cause. The planets revolved in circles because it was their nature to do so, just as laudanum sets to sleep because it possesses a virtus dormitiva. This first and oldest branch is known as observational, or practical astronomy. Its business is to note facts as accurately as possible, and it is essentially unconcerned with schemes for connecting those facts in a manner satisfactory to the reason. The second kind of astronomy was founded by Newton. Its nature is best indicated by the term gravitational, but it is also called theoretical astronomy. It is based on the idea of cause. And the whole of its elaborate structure is reared according to the dictates of a single law, simple in itself, but the tangled web of whose consequences can be unraveled only by the subtle agency of an elaborate calculus. The third and last division of celestial science may properly be termed physical and descriptive astronomy. It seeks to know what the heavenly bodies are in themselves, leaving the how and the wherefore of their movements to be otherwise answered. Now, such inquiries became possible only through the invention of the telescope, so that Galileo was, in point of fact, their originator. But Herschel first gave them a prominence which the whole progress of science during the 19th century served to confirm and render more exclusive. Inquisitions begun with the telescope have been extended and made effective in unhoped-for directions by the aid of the spectroscope and photographic camera. And a large part of our attention in the present volume will be occupied with the brilliant results thus achieved. The unexpected development of this new physical celestial science is the leading fact in recent astronomical history. It was out of the regular course of events. In the degree in which it has actually occurred it could certainly not have been foreseen. It was a seizing of the prize by a competitor who had hardly been thought qualified to enter the lists. Orthodox astronomers of the old school looked with a certain contempt upon observers who spent their nights in scrutinizing the faces of the moon and planets rather than in timing their transits, or devoted daylight energies not to reductions and computations, but to counting and measuring spots on the sun. They were regarded as irregular practitioners, to be tolerated perhaps, but certainly not encouraged. The advance of astronomy in the 18th century ran in general an even and logical course. The age succeeding Newton's had for its special task to demonstrate the universal validity, and trace the complex results, of the law of gravitation. The accomplishment of that task occupied just 100 years. It was virtually brought to a close when Laplace explained to the French Academy, November 19, 1787, the cause of the moon's accelerated motion. As a mere machine, the solar system, so far as it was then known, was found to be complete and intelligible in all its parts. And in the Mécanique Céleste its mechanical perfections were displayed under a form of majestic unity which fitly commemorated the successive triumphs of analytical genius over problems amongst the most arduous ever dealt with by the mind of man. Theory, however, demands a practical test. All its data are derived from observation, and their insecurity becomes less tolerable as it advances nearer to perfection. Observation, on the other hand, is the pitiless critic of theory. It detects weak points, and provokes reforms which may be the beginnings of discovery. Thus, theory and observation mutually act and react, each alternately taking the lead in the endless race of improvement. Now, while in France Lagrange and Laplace were bringing the gravitational theory of the solar system to completion, work of a very different kind, yet not less indispensable to the future welfare of astronomy, was being done in England. The Royal Observatory at Greenwich is one of the few useful institutions which date their origin from the reign of Charles II. The leading position which it still occupies in the science of celestial observation was, for near a century and a half after its foundation, an exclusive one. Delambre remarked that, had all other materials of the kind been destroyed, the Greenwich records alone would suffice for the restoration of astronomy. The establishment was indeed absolutely without a rival. Systematic observations of sun, moon, stars, and planets were during the whole of the 18th century made only at Greenwich. Here materials were accumulated for the secure correction of theory, and here refinements were introduced by which the exquisite accuracy of modern practice in astronomy was eventually attained. The chief promoter of these improvements was James Bradley. Few men have possessed in an equal degree with him the power of seeing accurately, and reasoning on what they see. He let nothing pass. The slightest inconsistency between what appeared and what was to be expected roused his keenest attention, and he never relaxed his mental grip of a subject until it had yielded to his persistent inquisition. It was to these qualities that he owed his discoveries of the aberration of light and the nutation of the Earth's axis. The first was announced in 1729. What is meant by it is that, owing to the circumstance of light not being instantaneously transmitted, the heavenly bodies appear shifted from their true places by an amount depending upon the ratio which the velocity of light bears to the speed of the Earth in its orbit. Because light travels with enormous rapidity, the shifting is very slight, and each star returns to its original position at the end of a year. Bradley's second great discovery was finally ascertained in 1748. Nutation is a real nodding of the terrestrial axis produced by the dragging of the moon at the terrestrial equatorial protuberance. From it results an apparent displacement of the stars, each of them describing a little ellipse about its true or mean position, in a period of nearly 19 years. Now, an acquaintance with the fact and the laws of each of these minute irregularities is vital to the progress of observational astronomy, for without it the places of the heavenly bodies could never be accurately known or compared. So that Bradley, by their detection, at once raised the science to a higher grade of precision. Nor was this the whole of his work. Appointed Astronomer Royal in 1742, he executed during the years 1750 to 62 a series of observations which formed the real beginning of exact astronomy. Part of their superiority must, indeed, be attributed to the co-operation of John Bird, who provided Bradley in 1750 with a measuring instrument of till then unequaled excellence. For not only was the art of observing in the 18th century a peculiarly English art, but the means of observing were furnished almost exclusively by British artists. John Dolland, the son of a Spitalfields weaver, invented the achromatic lens in 1758, removing thereby the chief obstacle to the development of the powers of refracting telescopes. James Short, of Edinburgh, was without a rival in the construction of reflectors. The sectors, quadrants, and circles of Graham, Bird, Ramsden, and Carey were inimitable by continental workmanship. Thus practical and theoretical astronomy advanced on parallel lines in England and France respectively, the improvement of their several tools, the telescope and the quadrant on the one side, and the calculus on the other, keeping pace. The whole future of the science seemed to be theirs. The cessation of interest through a too speedy attainment of the perfection towards which each spurred the other, appeared to be the only danger it held in store for them. When all at once, a rival stood by their side, not, indeed, menacing their progress, but threatening to absorb their popularity. The rise of Herschel was the one conspicuous anomaly in the astronomical history of the 18th century. It proved decisive of the course of events in the 19th. It was unexplained by anything that had gone before, yet all that came after hinged upon it. It gave a new direction to effort, it lent a fresh impulse to thought. It opened a channel for the widespread public interest which was gathering towards astronomical subjects to flow in. Much of this interest was due to the occurrence of events calculated to arrest the attention and excite the wonder of the uninitiated. The predicted return of Halley's comet in 1759 verified, after an unprecedented fashion, the computations of astronomers. It deprived such bodies forever of their portentous character, it ranked them as denizens of the solar system. Again, the transits of Venus in 1761 and 1769 were the first occurrences of the kind since the awakening of science to their consequence. Imposing preparations, journeys to remote and hardly accessible regions, official expeditions, international communications, all for the purpose of observing them to the best advantage, brought their high significance vividly to the public consciousness. A result aided by the facile pen of Lalande, in rendering intelligible the means by which these elaborate arrangements were to issue in an accurate knowledge of the sun's distance. Lastly, Herschel's discovery of Uranus, March 13, 1781, had the surprising effect of utter novelty. Since the human race had become acquainted with the company of the planets, no addition had been made to their number. The event thus broke with immemorial traditions, and seemed to show astronomy as still young and full of unlooked-for possibilities. Further popularity accrued to the science from the sequel of a career so strikingly opened. Herschel's huge telescopes, his detection by their means of 2 Saturnian and as many Uranian moons, his piercing scrutiny of the sun, picturesque theory of its constitution, and sagacious indication of the route pursued by it through space. His discovery of stellar revolving systems, his bold soundings of the universe, his grandiose ideas, and the elevated yet simple language in which they were conveyed, formed a combination powerfully effective to those least susceptible of new impressions. Nor was the evoked enthusiasm limited to the British Isles. In Germany, Schroeder followed, longo intervallo, in Herschel's track. Von Zach set on foot from Gotha that general communication of ideas which gives life to a forward movement. Bode wrote much and well for unlearned readers. Lalande, by his popular lectures and treatises, helped to form an audience which Laplace himself did not disdain to address in the Exposition du Système du Monde. This great accession of public interest gave the impulse to the extraordinarily rapid progress of astronomy in the 19th century. Official patronage combined with individual zeal sufficed for the elder branches of the science. A few well-endowed institutions could accumulate the materials needed by a few isolated thinkers for the construction of theories of wonderful beauty and elaboration, yet precluded, by their abstract nature, from winning general applause. But the new physical astronomy depends for its prosperity upon the favor of the multitude whom its striking results are well fitted to attract. It is, in a special manner, the science of amateurs. It welcomes the most unpretending cooperation. There is no one, with a true eye and a faithful hand, but can do good work in watching the heavens. And not unfrequently, prizes of discovery which the most perfect appliances fail to grasp, have fallen to the share of ignorant or ill-provided assiduity. Observers, accordingly, have multiplied. Observatories have been founded in all parts of the world, associations have been constituted for mutual help and counsel. A formal astronomical congress met in 1789 at Gotha, then, under Duke Ernest II. And von Zach, the focus of German astronomy, and instituted a combined search for the planet suspected to revolve undiscovered between the orbits of Mars and Jupiter. The Astronomical Society of London was established in 1820, and a similar German institution in 1863. Both have been highly influential in promoting the interests, local and general, of the science they are devoted to forward. While functions corresponding to theirs have been discharged elsewhere by older or less specially constituted bodies, and new ones of a more popular character are springing up on all sides. Modern facilities of communication have helped to impress more deeply upon modern astronomy its associative character. The electric telegraph gives a certain ubiquity which is invaluable to an observer of the skies. With the help of a wire, a battery, and a code of signals, he sees whatever is visible from any portion of our globe, depending, however, upon other eyes than his own, and so entering as a unit into a widespread organization of intelligence. The press, again, has been a potent agent of cooperation. It has mainly contributed to unite astronomers all over the world into a body animated by the single aim of collecting particulars in their special branch for what Bacon termed a history of nature, eventually to be interpreted according to the sagacious insight of some one among them gifted above his fellows. The first really effective astronomical periodical was the Monatliche Correspondence, started by von Zach in the year 1800. It was followed in 1822 by the Astronomische Nachrichten, later by the Memoirs and Monthly Notices of the Astronomical Society, and by the host of varied publications which now, in every civilized country, communicate the discoveries made in astronomy to divers classes of readers, and so incalculably quicken the current of its onward flow. Public favor brings in its train material resources. It is represented by individual enterprise, and finds expression in an ample liberality. The first regular observatory in the southern hemisphere was founded at Parramatta by Sir Thomas MacDougall Brisbane in 1821. The Royal Observatory at the Cape of Good Hope was completed in 1829. Similar establishments were set to work by the East India Company at Madras, Bombay, and St. Helena, during the first third of the 19th century. The organization of astronomy in the United States of America was due to a strong wave of popular enthusiasm. In 1825 John Quincy Adams vainly urged upon Congress the foundation of a national observatory. But in 1843 the lectures on celestial phenomena of Ormsby McKnight Mitchell stirred an impressionable audience to the pitch of providing him with the means of erecting at Cincinnati the first astronomical establishment worthy the name in that great country. On the 1st of January, 1882, no less than 144 were active within its boundaries. The apparition of the great comet of 1843 gave an additional fillip to the movement. To the excitement caused by it the Harvard College Observatory, called the American Pulkowa, directly owed its origin, and the example was not ineffective elsewhere. The United States Naval Observatory was built in 1844, Lieutenant Maury being its first director. Corporations, universities, municipalities, vied with each other in the creation of such institutions, private subscriptions poured in. Emissaries were sent to Europe to purchase instruments and to procure instruction in their use. In a few years the young republic was, in point of astronomical efficiency, at least on a level with countries where the science had been fostered since the dawn of civilization. A vast widening of the scope of astronomy has accompanied, and in part occasioned, the great extension of its area of cultivation which our age has witnessed. In the last century its purview was a comparatively narrow one. Problems lying beyond the range of the solar system were almost unheeded, because they seemed inscrutable. Herschel first showed the sidereal universe as accessible to investigation, and thereby offered to science new worlds, majestic, manifold, infinitely infinite to our apprehension in number, variety, and extent, for future conquest. Their gradual appropriation has absorbed, and will long continue to absorb, the powers which it has served to develop. But this is not the only direction in which astronomy has enlarged, or rather has leveled, its boundaries. The unification of the physical sciences is perhaps the greatest intellectual feat of recent times. The process has included astronomy, so that, like Bacon, she may now be said to have taken all knowledge, of that kind, for her province. In return, she proffers potent aid for its increase. Every comet that approaches the Sun is the scene of experiments in the electrical illumination of rarefied matter, performed on a huge scale for our benefit. The Sun, stars, and nebulae form so many celestial laboratories, where the nature and mutual relations of the chemical elements may be tried by more stringent tests than sublunary conditions afford. The laws of terrestrial magnetism can be completely investigated only with the aid of a concurrent study of the face of the Sun. The solar spectrum will perhaps one day, by its recurrent modifications, tell us something of impending droughts, famines, and cyclones. Astronomy generalizes the results of the other sciences. She exhibits the laws of nature working over a wider area, and under more varied conditions, than ordinary experience presents. Ordinary experience, on the other hand, has become indispensable to her progress. She takes in at one view the indefinitely great and the indefinitely little. The mutual revolutions of the stellar multitude during tracts of time which seem to lengthen out to eternity as the mind attempts to traverse them, she does not admit to be beyond her ken. Nor is she indifferent to the constitution of the minutest atom of matter that thrills the ether into light. How she entered upon this vastly expanded inheritance, and how, so far, she has dealt with it, is attempted to be set forth in the ensuing chapters. Footnotes. The denomination, physical astronomy, first used by Kepler, and long appropriated to this branch of the science, has of late been otherwise applied. Histoire de l'astronomie au XVIIIe siècle, page 267. Part 1. Progress of astronomy during the first half of the 19th century. Chapter 1. Foundation of sidereal astronomy. Until nearly 100 years ago the stars were regarded by practical astronomers mainly as a number of convenient fixed points, by which the motions of the various members of the solar system could be determined and compared. Their recognized function, in fact, was that of milestones on the great celestial highway traversed by the planets, as well as on the byways of space occasionally pursued by comets. Not that curiosity as to their nature, and even conjecture as to their origin, were at any period absent. Both were from time to time powerfully stimulated by the appearance of startling novelties in a region described by philosophers as incorruptible, or exempt from change. The catalogue of Hipparchus probably, and certainly that of Tycho Brahe, some 17 centuries later, owed each its origin to the temporary blaze of a new star. The general aspect of the skies was thus, however imperfectly, recorded from age to age, and with improved appliances the enumeration was rendered more and more accurate and complete, but the secrets of the stellar sphere remained inviolate. In a qualified though very real sense, Sir William Herschel may be called the founder of sidereal astronomy. Before his time some curious facts had been noted, and some ingenious speculations hazarded, regarding the condition of the stars, but not even the rudiments of systematic knowledge had been acquired. The facts ascertained can be summed up in a very few sentences. Giordano Bruno was the first to set the suns of space in motion, but in imagination only. His daring surmise was, however, confirmed in 1718, when Halley announced that Sirius, Aldebaran, Betelgeuse, and Arcturus had unmistakably shifted their quarters in the sky since Ptolemy assigned their places in his catalogue. A similar conclusion was reached by J. Cassini in 1738, from a comparison of his own observations with those made at Cayenne by Richer in 1672. And Tobias Mayer drew up in 1756 a list showing the direction and amount of about 57 proper motions, founded on starplaces determined by Olaus Römer 50 years previously. Thus the stars were no longer regarded as fixed, but the question remained whether the movements perceived were real or only apparent, and this it was not yet found possible to answer. Already, in the previous century, the ingenious Robert Hooke had suggested an alteration of the very system of the sun, to account for certain suspected changes in stellar positions. Bradley in 1748, and Lambert in 1761, pointed out that such apparent displacements, by that time well ascertained, were in all probability a combined effect of motions both of sun and stars. And Mayer actually attempted the analysis, but without result. On the 13th of August, 1596, David Fabricius, an unprofessional astronomer in East Friesland, saw in the neck of the Whale a star of the third magnitude, which by October had disappeared. It was, nevertheless, visible in 1603, when Bayer marked it in his catalogue with the Greek letter omicron, and was watched, in 1638–39, through its phases of brightening and apparent extinction by a Dutch professor named Halwarda. From Hevelius this first known periodical star received the name of Mira, or the Wonderful, and Bulliod in 1667 fixed the length of its cycle of change at 334 days. It was not a solitary instance. A star in the Swan was perceived by Janssen in 1600 to show fluctuations of light, and Montanari found in 1669 that Algol in Perseus shared the same peculiarity to a marked degree. Altogether the class embraced in 1782 half a dozen members. When it is added that a few star couples had been noted in singularly, but it was supposed accidentally, close juxtaposition, and that the failure of repeated attempts to measure stellar parallaxes pointed to distances at least 400,000 times that of the Earth from the Sun, the picture of sidereal science, when the last quarter of the 18th century began, is practically complete. It included 3 items of information: that the stars have motions, real or apparent, that they are immeasurably remote, and that a few shine with a periodically variable light. Nor were these scantily collected facts ordered into any promise of further development. They lay at once isolated and confused before the inquirer. They needed to be both multiplied and marshaled, and it seemed as if centuries of patient toil must elapse before any reliable conclusions could be derived from them. The sidereal world was thus the recognized domain of far-reaching speculations, which remained wholly uncramped by systematic research until Herschel entered upon his career as an observer of the heavens. The greatest of modern astronomers was born at Hanover, November 15, 1738. He was the 4th child of Isaac Herschel, a hautboy player in the band of the Hanoverian Guard, and was early trained to follow his father's profession. On the termination, however, of the disastrous campaign of 1757, his parents removed him from the regiment, there is reason to believe, in a somewhat unceremonious manner. Technically, indeed, he incurred the penalties of desertion, remitted, according to the Duke of Sussex's statement to Sir George Airy, by a formal pardon handed to him personally by George III. On his presentation in 1782. At the age of 19, then, his military service having lasted 4 years, he came to England to seek his fortune. Of the life of struggle and privation which ensued little is known beyond the circumstances that in 1760 he was engaged in training the regimental band of the Durham militia, and that in 1765 he was appointed organist at Halifax. In the following year he removed to Bath as oboist in Linley's orchestra, and in October 1767 was promoted to the post of organist in the Octagon Chapel. The tide of prosperity now began to flow for him. The most brilliant and modish society in England was at that time to be met at Bath, and the young Hanoverian quickly found himself a favourite and the fashion in it. Engagements multiplied upon him. He became director of the public concerts. He conducted oratorios, engaged singers, organized rehearsals, composed anthems, chants, choral services, besides undertaking private tuitions, at times amounting to 35 or even 38 lessons a week. He in fact personified the musical activity of a place then eminently and energetically musical. But these multifarious avocations did not take up the whole of his thoughts. His education, notwithstanding the poverty of his family, had not been neglected, and he had always greedily assimilated every kind of knowledge that came in his way. Now that he was a busy and a prosperous man, it might have been expected that he would run on in the deep professional groove laid down for him. On the contrary, his passion for learning seemed to increase with the diminution of the time available for its gratification. He studied Italian, Greek, mathematics. Maclaurin's flux ions served to unbend his mind. Smith's harmonics and optics and Ferguson's astronomy were the nightly companions of his pillow. What he read stimulated without satisfying his intellect. He desired not only to know, but to discover. In 1772 he hired a small telescope, and through it caught a preliminary glimpse of the rich and varied fields in which for so many years he was to expatiate. Henceforward the purpose of his life was fixed, it was to obtain a knowledge of the construction of the heavens, and this sublime ambition he cherished to the end. A more powerful instrument was the first desideratum. And here his mechanical genius came to his aid. Having purchased the apparatus of a Quaker optician, he set about the manufacture of specula with a zeal which seemed to anticipate the wonders they were to disclose to him. It was not until 15 years later that his grinding and polishing machines were invented, so the work had at that time to be entirely done by hand. During this tedious and laborious process, which could not be interrupted without injury, and lasted on one occasion 16 hours, his strength was supported by morsels of food put into his mouth by his sister, and his mind amused by her reading aloud to him the Arabian Nights, Don Quixote, or other light works. At length, after repeated failures, he found himself provided with a reflecting telescope, a 5.5-foot Gregorian, of his own construction. A copy of his first observation with it, on the great nebula in Orion, an object of continual amazement and assiduous inquiry to him, is preserved by the Royal Society. It bears the date March 4, 1774. In the following year he executed his first review of the heavens, memorable chiefly as an evidence of the grand and novel conceptions which already inspired him, and of the enthusiasm with which he delivered himself up to their guidance. Overwhelmed with professional engagements, he still contrived to snatch some moments for the stars. And between the acts at the theatre was often seen running from the harpsichord to his telescope, no doubt with that uncommon precipitancy which accompanied all his actions. He now rapidly increased the power and perfection of his telescopes. Mirrors of 7, 10, even 20 feet focal length, were successively completed, and unprecedented magnifying powers employed. His energy was unceasing, his perseverance indomitable. In the course of 21 years no less than 430 parabolic specula left his hands. He had entered upon his 42nd year when he sent his first paper to the Philosophical Transactions. Yet during the ensuing 39 years his contributions, many of them elaborate treatises, numbered 69, forming a series of extraordinary importance to the history of astronomy. As a mere explorer of the heavens his labors were prodigious. He discovered 2,500 nebulae, 806 double stars, passed the whole firmament in review for several times, counted the stars in 3,400 gauge fields, and executed a photometric classification of the principal stars. Founded on an elaborate, and the first systematically conducted, investigation of their relative brightness. He was as careful and patient as he was rapid, spared no time and omitted no precaution to secure accuracy in his observations, yet in one night he would examine, singly and attentively, up to 400 separate objects. The discovery of Uranus was a mere incident of the scheme he had marked out for himself, a fruit, gathered as it were by the way. It formed, nevertheless, the turning point in his career. From a stargazing musician he was at once transformed into an eminent astronomer, he was relieved from the drudgery of a toilsome profession, and installed as royal astronomer, with a modest salary of £200 a year. Funds were provided for the construction of the 40-foot reflector, from the great space-penetrating power of which he expected unheard-of revelations. In fine, his future work was not only rendered possible, but it was stamped as authoritative. On Whitsunday 1782, William and Caroline Herschel played and sang in public for the last time in St. Margaret's Chapel, Bath. In August of the same year the household was moved to Datchet, near Windsor, and on April 3, 1786, to Slough. Here happiness and honors crowded on the fortunate discoverer. In 1788 he married Mary, only child of James Baldwin, a merchant of the city of London, and widow of Mr. John Pitt, a lady whose domestic virtues were enhanced by the possession of a large jointure. The fruit of their union was one son, of whose work, the worthy sequel of his father's, we shall have to speak further on. Herschel was created a Knight of the Hanoverian Guelphic Order in 1816, and in 1821 he became the first president of the Royal Astronomical Society, his son being its first foreign secretary. But his health had now for some years been failing, and on August 25, 1822, he died at Slough, in the 84th year of his age, and was buried in Upton churchyard. His epitaph claims for him the lofty praise of having burst the barriers of heaven. Let us see in what sense this is true. The first to form any definite idea as to the constitution of the stellar system was Thomas Wright, the son of a carpenter living at Byers Green, near Durham. With him originated what has been called the grindstone theory of the universe, which regarded the Milky Way as the projection on the sphere of a stratum or disk of stars, our sun occupying a position near the center. Similar in magnitude and distribution to the lucid orbs of the constellations. He was followed by Kant, who transcended the views of his predecessor by assigning to nebulae the position they long continued to occupy, rather on imaginative than scientific grounds, of island universes, external to, and coequal with the galaxy. Johann Heinrich Lambert, a tailor's apprentice from Mulhausen, followed, but independently. The conceptions of this remarkable man were grandiose, his intuitions bold, his views on some points a singular anticipation of subsequent discoveries. The sidereal world presented itself to him as a hierarchy of systems, starting from the planetary scheme, rising to throngs of suns within the circuit of the Milky Way, the ecliptic of the stars. As he phrased it, expanding to include groups of many Milky Ways. These again combining to form the unit of a higher order of assemblage, and so onwards and upwards until the mind reels and sinks before the immensity of the contemplated creations. Thus everything revolves, the earth round the sun. The sun round the center of his system, this system round a center common to it with other systems, this group, this assemblage of systems, round a center which is common to it with other groups of the same kind, and where shall we have done? The stupendous problem thus speculatively attempted, Herschel undertook to grapple with experimentally. The upshot of this memorable inquiry was the inclusion, for the first time, within the sphere of human knowledge, of a connected body of facts, and inferences from facts, regarding the sidereal universe. In other words, the foundation of what may properly be called a science of the stars. Tobias Mayer had illustrated the perspective effects which must ensue in the stellar sphere from a translation of the solar system. By comparing them to the separating in front and closing up behind of trees in a forest to the eye of an advancing spectator. But the appearances which he thus correctly described he was unable to detect. By a more searching analysis of a smaller collection of proper motions, Herschel succeeded in rendering apparent the very consequences foreseen by Mayer. He showed, for example, that Arcturus and Vega did, in fact, appear to recede from, and Sirius and Aldebaran to approach, each other by very minute amounts. And, with a striking effort of divinatory genius, placed the apex, or point of direction of the sun's motion, close to the star Lambda in the constellation Hercules. Within a few degrees of the spot indicated by later and indefinitely more refined methods of research. He resumed the subject in 1805, but though employing a more rigorous method, was scarcely so happy in his result. In 1806, he made a preliminary attempt to ascertain the speed of the sun's journey, fixing it, by doubtless much too low an estimate, at about 3 miles a second. Yet the validity of his general conclusion as to the line of solar travel, though long doubted, has been triumphantly confirmed. The question as to the secular parallax of the fixed stars was in effect answered. With their annual parallax, however, the case was very different. The search for it had already led Bradley to the important discoveries of the aberration of light and the nutation of the Earth's axis. It was now about to lead Herschel to a discovery of a different, but even more elevated character. Yet in neither case was the object primarily sought attained. From the very first promulgation of the Copernican theory the seeming immobility of the stars had been urged as an argument against its truth. For if the Earth really traveled in a vast orbit round the Sun, objects in surrounding space should appear to change their positions, unless their distances were on a scale which, to the narrow ideas of the universe then prevailing, seemed altogether extravagant. The existence of such apparent or parallactic displacements was accordingly regarded as the touchstone of the new views, and their detection became an object of earnest desire to those interested in maintaining them. Copernicus himself made the attempt, but with his triquetrum, a jointed wooden rule with the divisions marked in ink, constructed by himself, he was hardly able to measure angles of 10 minutes, far less fractions of a second. Galileo, a more impassioned defender of the system, strained his ears, as it were, from Arcetri, in his blind and sorrowful old age, for news of a discovery which 2 more centuries had still to wait for. Hooke believed he had found a parallax for the bright star in the head of the dragon, but was deceived. Bradley convinced himself that such effects were too minute for his instruments to measure. Herschel made a fresh attempt by a practically untried method. It is a matter of daily experience that 2 objects situated at different distances seem to a beholder in motion to move relatively to each other. This principle Galileo, in the 3rd of his dialogues on the systems of the world, proposed to employ for the determination of stellar parallax. For 2 stars, lying apparently close together, but in reality separated by a great gulf of space, must shift their mutual positions when observed from opposite points of the Earth's orbit. Or rather, the remoter forms a virtually fixed point, to which the movements of the other can be conveniently referred. By this means complications were abolished more numerous and perplexing than Galileo himself was aware of, and the problem was reduced to one of simple micrometrical measurement. The double star method was also suggested by James Gregory in 1675, and again by Wallis in 1693, Huygens first, and afterwards Dr. Long of Cambridge, about 1750, made futile experiments with it. And it eventually led, in the hands of Bessel, to the successful determination of the parallax of 61 Cygni. Its advantages were not lost upon Herschel. His attempt to assign definite distances to the nearest stars was no isolated effort, but part of the settled plan upon which his observations were conducted. He proposed to sound the heavens, and the first requisite was a knowledge of the length of his sounding line. Thus it came about that his special attention was early directed to double stars. I resolved, he writes, to examine every star in the heavens with the utmost attention and a very high power, that I might collect such materials for this research as would enable me to fix my observations upon those that would best answer my end. The subject has already proved so extensive, and still promises so rich a harvest to those who are inclined to be diligent in the pursuit, that I cannot help inviting every lover of astronomy to join with me in observations that must inevitably lead to new discoveries. The first result of these inquiries was a classed catalogue of 269 double stars presented to the Royal Society in 1782, followed, after 3 years, by an additional list of 434. In both these collections the distances separating the individuals of each pair were carefully measured. And, with a few exceptions, the angles made with the hour circle by the lines joining their centers, technically called angles of position, were determined with the aid of a revolving wire micrometer, specially devised for the purpose. Moreover, an important novelty was introduced by the observation of the various colors visible in the star couples, the singular and vivid contrasts of which were now for the first time described. Double stars were at that time supposed to be a purely optical phenomenon. Their components, it was thought, while in reality indefinitely remote from each other, were brought into fortuitous contiguity by the chance of lying nearly in the same line of sight from the earth. Yet Bradley had noticed a change of 30 degrees, between 1718 and 1759, in the position angle of the two stars forming Castor, and was thus within a hair's breadth of the discovery of their physical connection. While the Rev. John Michell, arguing by the doctrine of probabilities, wrote as follows in 1767, "It is highly probable in particular, and next to a certainty in general, that such double stars as appear to consist of two or more stars placed very near together, do really consist of stars placed near together, and under the influence of some general law." And in 1784, "It is not improbable that a few years may inform us that some of the great number of double, triple stars, etc., which have been observed by Mr. Herschel, are systems of bodies revolving about each other." This remarkable speculative anticipation had a practical counterpart in Germany. Father Christian Mayer, a Jesuit astronomer at Mannheim, set himself, in January 1776, to collect examples of stellar pairs, and shortly after published the supposed discovery of satellites to many of the principal stars. But his observations were neither exact nor prolonged enough to lead to useful results in such an inquiry. His disclosures were derided, his planet stars treated as results of hallucination. "On ne point cru à de choses aussi extraordinaires," wrote Lalande within 1 year of a better grounded announcement to the same effect. Herschel at first shared the general opinion as to the merely optical connection of double stars. Of this the purpose for which he made his collection is in itself sufficient evidence, since what may be called the differential method of parallaxes depends, as we have seen, for its efficacy upon disparity of distance. It was much too soon, he declared in 1782, to form any theories of small stars revolving round large ones. While in the year following, he remarked that the identical proper motions of the two stars forming, to the naked eye, the single bright orb of Castor could only be explained as both equally due to the systematic parallax caused by the sun's movement in space, plainly showing that the notion of a physical tie, compelling the two bodies to travel together, had not as yet entered into his speculations. But he was eminently open to conviction, and had, moreover, by observations unparalleled in amount as well as in kind, prepared ample materials for convincing himself and others. In 1802 he was able to announce the fact of his discovery, and in the 2 ensuing years, to lay in detail before the Royal Society proofs, gathered from the labors of a quarter of a century. Of orbital revolution in the case of as many as 50 double stars, henceforth, he declared, to be held as real binary combinations, intimately held together by the bond of mutual attraction. The fortunate preservation in Dr. Maskelyne's notebook of a remark made by Bradley about 1759, to the effect that the line joining the components of Castor was an exact prolongation of that joining Castor with Pollux. Added 18 years to the time during which the pair were under scrutiny, and confirmed the evidence of change afforded by more recent observations. Approximate periods were fixed for many of the revolving suns, for Castor 342 years, for Gamma Leonis, 1200, Delta Serpentis, 375, Epsilon Bootis, 1681 years. Epsilon Lyrae was noted as a double-double star, a change of relative situation having been detected in each of the 2 pairs composing the group. And the occultation was described of one star by another in the course of their mutual revolutions, as exemplified in 1795 by the rapidly circulating system of Zeta Herculis. Thus, by the sagacity and perseverance of a single observer, a firm basis was at last provided upon which to raise the edifice of sidereal science. The analogy long presumed to exist between the mighty star of our system and the bright points of light spangling the firmament was shown to be no fiction of the imagination, but a physical reality. The fundamental quality of attractive power was proved to be common to matter so far as the telescope was capable of exploring, and law, subordination, and regularity to give testimony of supreme and intelligent design no less in those limitless regions of space than in our narrow terrestrial home. The discovery was emphatically, in Arago's phrase, one with a future, since it introduced the element of precise knowledge where more or less probable conjecture had previously held almost undivided sway. And precise knowledge tends to propagate itself and advance from point to point. We have now to speak of Herschel's pioneering work in the skies. To explore with line and plummet the shining zone of the Milky Way, to delineate its form, measure its dimensions, and search out the intricacies of its construction, was the primary task of his life, which he never lost sight of, and to which all his other investigations were subordinate. He was absolutely alone in this bold endeavor. Unaided, he had to devise methods, accumulate materials, and sift out results. Yet it may safely be asserted that all the knowledge we possess on this sublime subject was prepared, and the greater part of it anticipated, by him. The ingenious method of star-gauging, and its issue in the delineation of the sidereal system as an irregular stratum of evenly scattered suns, is the best-known part of his work. But it was, in truth, only a first rude approximation, the principle of which maintained its credit in the literature of astronomy a full half-century after its abandonment by its author. This principle was the general equality of star distribution. If equal portions of space really held equal numbers of stars, it is obvious that the number of stars visible in any particular direction would be strictly proportional to the range of the system in that direction. Apparent accumulation being produced by real extent. The process of gauging the heavens, accordingly, consisted in counting the stars in successive telescopic fields, and calculating thence the depths of space necessary to contain them. The result of 3,400 such operations was the plan of the galaxy familiar to every reader of an astronomical textbook. Widely varying evidence was, as might have been expected, derived from an examination of different portions of the sky. Some fields of view were almost blank, while others, in or near the Milky Way, blazed with the radiance of many hundred stars compressed into an area about one-fourth that of the full moon. In the most crowded parts 116,000 were stated to have been passed in review within a quarter of an hour. Here the length of his sounding line was estimated by Herschel at about 497 times the distance of Sirius, in other words, the bounding orb, or farthest sun of the system in that direction, so far as could be seen with the 20-foot reflector, was thus inconceivably remote. But since the distance of Sirius, no less than of every other fixed star, was as yet an unknown quantity, the dimensions inferred for the galaxy were of course purely relative. A knowledge of its form and structure might, admitting the truth of the fundamental hypothesis, be obtained, but its real or absolute size remained altogether undetermined. Even as early as 1785, however, Herschel perceived traces of a tendency which completely invalidated the supposition of any approach to an average uniformity of distribution. This was the action of what he called a clustering power in the Milky Way. Many gathering clusters were already discernible to him even while he endeavored to obtain a true mean result, on the assumption that each star in space was separated from its neighbors as widely as the Sun from Sirius. It appears, he wrote in 1789, that the heavens consist of regions where suns are gathered into separate systems. And in certain assemblages he was able to trace a course or tide of stars setting towards a center, denoting, not doubtfully, the presence of attractive forces. 13 years later, he described our Sun and his constellated companions as surrounded by a magnificent collection of innumerable stars, called the Milky Way, which must occasion a very powerful balance of opposite attractions to hold the intermediate stars at rest. For though our Sun, and all the stars we see, may truly be said to be in the plane of the Milky Way, yet I am now convinced, by a long inspection and continued examination of it, that the Milky Way itself consists of stars very differently scattered from those which are immediately about us. This immense aggregation, he added, is by no means uniform. Its component stars show evident signs of clustering together into many separate allotments. The following sentences, written in 1811, contain a definite retractation of the view frequently attributed to him. I must freely confess, he says, that by continuing my sweeps of the heavens my opinion of the arrangement of the stars and their magnitudes, and of some other particulars, has undergone a gradual change. And indeed, when the novelty of the subject is considered, we cannot be surprised that many things formerly taken for granted should on examination prove to be different from what they were generally but incautiously supposed to be. For instance, an equal scattering of the stars may be admitted in certain calculations. But when we examine the Milky Way, or the closely compressed clusters of stars of which my catalogues have recorded so many instances, this supposed equality of scattering must be given up. Another assumption, the fallacy of which he had not the means of detecting since become available, was retained by him to the end of his life. It was that the brightness of a star afforded an approximate measure of its distance. Upon this principle he founded in 1817 his method of limiting apertures, by which two stars, brought into view in two precisely similar telescopes, were equalized by covering a certain portion of the object glass collecting the more brilliant rays. The distances of the orbs compared were then taken to be in the ratio of the reduced to the original apertures of the instruments with which they were examined. If indeed the absolute luster of each were the same, the result might be accepted with confidence. But since we have no warrant for assuming a standard star to facilitate our computations, but much reason to suppose an indefinite range, not only of size but of intrinsic brilliancy, in the suns of our firmament, conclusions drawn from such a comparison are entirely worthless. In another branch of sidereal science besides that of stellar aggregation, Herschel may justly be styled a pioneer. He was the first to bestow serious study on the enigmatical objects known as nebulae. The history of the acquaintance of our race with them is comparatively short. The only one recognized before the invention of the telescope was that in the girdle of Andromeda, certainly familiar in the middle of the 10th century to the Persian astronomer Abdurrahman al-Sufi, and marked with dots on Spanish and Dutch constellation charts of the 14th and 15th centuries. Yet so little was it noticed that it might practically be said, as far as Europe is concerned, to have been discovered in 1612 by Simon Marius, mayor of Genzenhausen, who aptly described its appearance as that of a candle shining through horn. The first mention of the great Orion Nebula is by a Swiss Jesuit named Cysatus, who succeeded Father Scheiner in the chair of mathematics at Ingolstadt. He used it, apparently without any suspicion of its novelty, as a term of comparison for the comet of December 1618. A novelty, nevertheless, to astronomers it still remained in 1656, when Huygens discerned, as it were, an hiatus in the sky, affording a glimpse of a more luminous region beyond. Halley in 1716 knew of 6 nebulae, which he believed to be composed of a lucid medium diffused through the ether of space. He appears, however, to have been unacquainted with some previously noticed by Hevelius. Lacaille brought back with him from the Cape a list of 42, the first fruits of observation in southern skies, arranged in 3 numerically equal classes, and Messier, nicknamed by Louis XV. The ferret of comets, finding such objects a source of extreme perplexity in the pursuit of his chosen game, attempted to eliminate by methodizing them, and drew up a catalogue comprising, in 1781, 103 entries. These preliminary attempts shrank into insignificance when Herschel began to sweep the heavens with his giant telescopes. In 1786 he presented to the Royal Society a descriptive catalogue of 1,000 nebulae in clusters, followed, 3 years later, by a second of as many more, to which he added in 1802 a further gleaning of 500. On the subject of their nature his views underwent a remarkable change. Finding that his potent instruments resolved into stars many nebulous patches in which no signs of such a structure had previously been discernible, he naturally concluded that resolvability was merely a question of distance and telescopic power. He was, as he said himself, led on by almost imperceptible degrees from evident clusters, such as the Pleiades, to spots without a trace of stellar formation. The gradations being so well connected as to leave no doubt that all these phenomena were equally stellar. The singular variety of their appearance was thus described by him. I have seen, he says, double and treble nebulae variously arranged, large ones with small, seeming attendants, narrow, but much extended lucid nebulae or bright dashes. Some of the shape of a fan, resembling an electric brush, issuing from a lucid point, others of the cometic shape, with a seeming nucleus in the center, or like cloudy stars surrounded with a nebulous atmosphere. A different sort, again, contain a nebulosity of the milky kind, like that wonderful, inexplicable phenomenon about Theta Orionis, while others shine with a fainter, mottled kind of light, which denotes their being resolvable into stars. These curious objects he considered to be no less than whole sidereal systems, some of which might well outvie our Milky Way in grandeur. He admitted, however, a wide diversity in condition as well as compass. The system to which our Sun belongs he described as a very extensive branching congeries of many millions of stars, which probably owes its origin to many remarkably large as well as pretty closely scattered small stars. That may have drawn together the rest. But the continued action of this same clustering power would, he supposed, eventually lead to the breaking up of the original majestic galaxy into 200 or 300 separate groups, already visibly gathering. Such minor nebulae, due to the decay of other branching nebulae similar to our own, he recognized by the score, lying, as it were, stratified in certain quarters of the sky. One of these nebulous beds, he informs us, is so rich that in passing through a section of it, in the time of only 36 minutes, I detected no less than 31 nebulae, all distinctly visible upon a fine blue sky. The stratum of Coma Berenices he judged to be the nearest to our system of such layers, nor did the marked aggregation of nebulae towards both poles of the circle of the Milky Way escape his notice. By a continuation of the same process of reasoning, he was enabled, as he thought, to trace the life history of nebulae from a primitive loose and extended formation, through clusters of gradually increasing compression, down to the kind named by him planetary, because of the defined and uniform disks which they present. These he regarded as very aged, and drawing on towards a period of change or dissolution. This method of viewing the heavens, he concluded, seems to throw them into a new kind of light. They now are seen to resemble a luxuriant garden which contains the greatest variety of productions in different flourishing beds. And one advantage we may at least reap from it is, that we can, as it were, extend the range of our experience to an immense duration. For, to continue the simile which I have borrowed from the vegetable kingdom, is it not almost the same thing whether we live successively to witness the germination, blooming, foliage, fecundity, fading, withering, and corruption of a plant? Or whether a vast number of specimens, selected from every stage through which the plant passes in the course of its existence, be brought at once to our view? But already this supposed continuity was broken. After mature deliberation on the phenomena presented by nebulous stars, Herschel was induced, in 1791, to modify essentially his original opinion. When I pursued these researches, he says, I was in the situation of a natural philosopher who follows the various species of animals and insects from the height of their perfection down to the lowest ebb of life. When, arriving at the vegetable kingdom, he can scarcely point out to us the precise boundary where the animal ceases and the plant begins, and may even go so far as to suspect them not to be essentially different. But, recollecting himself, he compares, for instance, one of the human species to a tree, and all doubt upon the subject vanishes before him. In the same manner we pass through gentle steps from a coarse cluster of stars, such as the Pleiades, till we find ourselves brought to an object such as the nebula in Orion, where we are still inclined to remain in the once adopted idea of stars exceedingly remote and inconceivably crowded, as being the occasion of that remarkable appearance. It seems, therefore, to require a more dissimilar object to set us right again. A glance like that of the naturalist, who casts his eye from the perfect animal to the perfect vegetable, is wanting to remove the veil from the mind of the astronomer. The object I have mentioned above is the phenomenon that was wanting for this purpose. View, for instance, the 19th cluster of my 6th class, and afterwards cast your eye on this cloudy star, and the result will be no less decisive than that of the naturalist we have alluded to. Our judgment, I may venture to say, will be, that the nebulosity about the star is not of a starry nature. The conviction thus arrived at of the existence in space of a widely diffused, shining fluid, a conviction long afterwards fully justified by the spectroscope, led him into a field of endless speculation. What was its nature? Should it be compared to the coruscation of the electric fluid in the aurora borealis? Or to the more magnificent cone of the zodiacal light? Above all, what was its function in the cosmos? And on this point he already gave a hint of the direction in which his mind was moving by the remark that this self-luminous matter seemed more fit to produce a star by its condensation, than to depend on the star for its existence. This was not a novel idea. Tycho Brahe had tried to explain the blaze of the star of 1572 as due to a sudden concentration of nebulous material in the Milky Way, even pointing out the space left dark and void by the withdrawal of the luminous stuff. And Kepler, theorizing on a similar stellar apparition in 1604, followed nearly in the same track. But under Herschel's treatment the nebular origin of stars first acquired the consistency of a formal theory. He meditated upon it long and earnestly, and in 2 elaborate treatises, published respectively in 1811 and 1814, he at length set forth the arguments in its favor. These rested entirely upon the principle of continuity. Between the successive classes of his assortment of developing objects there was, as he said, perhaps not so much difference as would be in an annual description of the human figure. Were it given from the birth of a child till he comes to be a man in his prime. From diffused nebulosity, barely visible in the most powerful light-gathering instruments, but which he estimated to cover nearly 152 square degrees of the heavens, to planetary nebulae, supposed to be already centrally solid. Instances were alleged of every stage and phase of condensation. The validity of his reasoning, however, was evidently impaired by his confessed inability to distinguish between the dim rays of remote clusters and the milky light of true gaseous nebulae. It may be said that such speculations are futile in themselves, and necessarily barren of results. But they gratify an inherent tendency of the human mind, and, if pursued in a becoming spirit, should be neither reproved nor disdained. Herschel's theory still holds the field, the testimony of recent discoveries with regard to it having proved strongly confirmatory of its principle, although not of its details. Strangely enough, it seems to have been propounded in complete independence of Laplace's nebular hypothesis as to the origin of the solar system. Indeed, it dated, as we have seen, in its first inception, from 1791, while the French geometrician's view was not advanced until 1796. We may now briefly sum up the chief results of Herschel's long years of watching the heavens. The apparent motions of the stars had been disentangled, one portion being clearly shown to be due to a translation towards a point in the constellation Hercules of the Sun and his attendant planets. While a large balance of displacement was left to be accounted for by real movements, various in extent and direction, of the stars themselves. By the action of a central force similar to, if not identical with, gravity, suns of every degree of size and splendor, and sometimes brilliantly contrasted in color, were seen to be held together in systems, consisting of 2, 3, 4, even 6 members, whose revolutions exhibited a wide range of variety both in period and in orbital form. A new department of physical astronomy was thus created, and rigid calculation for the first time made possible within the astral region. The vast problem of the arrangement and relations of the millions of stars forming the Milky Way was shown to be capable of experimental treatment, and of at least partial solution, notwithstanding the variety in complexity seen to prevail, to an extent previously undreamt of, in the arrangement of that majestic system. The existence of a luminous fluid, diffused through enormous tracts of space, and intimately associated with stellar bodies, was virtually demonstrated, and its place and use in creation attempted to be divined by a bold but plausible conjecture. Change on a stupendous scale was inferred or observed to be everywhere in progress. Periodical stars shone out and again decayed. Progressive ebbings or flowings of light were indicated as probable in many stars under no formal suspicion of variability. Forces were everywhere perceived to be at work, by which the very structure of the heavens themselves must be slowly but fundamentally modified. In all directions groups were seen to be formed or forming. Tides and streams of suns to be setting towards powerful centers of attraction, new systems to be in process of formation, while effete ones hastened to decay or regeneration when the course appointed for them by infinite wisdom was run. And thus, to quote the words of the observer who had looked farther into space than ever human being did before him, the state into which the incessant action of the clustering power has brought the Milky Way at present is a kind of chronometer that may be used to measure the time of its past and future existence. And although we do not know the rate of going of this mysterious chronometer, it is nevertheless certain that, since the breaking up of the parts of the Milky Way affords a proof that it cannot last forever, it equally bears witness that its past duration cannot be admitted to be infinite. Footnotes. Phil. Trans, Volume 30, page 737. Out of 80 stars compared, 57 were found to have changed their places by more than 10. Lesser discrepancies were at that time regarded as falling within the limits of observational error. Tobii Mayeri op Inedita, T.I., pages 80, 81, and Herschel in Phil. Trans, Volume 73, pages 275 to 278. Posthumous Works, page 701. Arago in Enware du Bureau de Longitudes, 1842, page 313. Bradley to Halley, Phil. Trans, Volume 35. 1728, page 660. His observations were directly applicable to only 2 stars, Gamma Draconis and Eta Ursae Majoris, but some lesser ones were included in the same result. Holden, Sir William Herschel, His Life and Works, page 17. Phil. Trans, Volume CI, page 269. Caroline Lucretia Herschel, born at Hanover, March 16, 1750, died in the same place, January 9, 1848. She came to England in 1772, and was her brother's devoted assistant, first in his musical undertakings, and afterwards, down to the end of his life, in his astronomical labors. Holden, Op. Cit., page 39. Memoir of Caroline Herschel, page 37. See Holden's Sir William Herschel, page 54. An Original Theory or New Hypothesis of the Universe, London, 1750. See also De Morgan's summary of his views in Philosophical Magazine, April, 1848. Allgemeine Nedergeschichte und Theorie des Himmels, 1755. Kosmologische Brief, Augsburg, 1761. The System of the World, page 125, London, 1800, a translation of Kosmologische Brief. Lambert regarded nebulae as composed of stars crowded together, but not as external universes. In the case of the Orion Nebula, indeed, he throws out such a conjecture, but afterward suggests that it may form a center for that one of the subordinate systems composing the Milky Way to which our Sun belongs. Opera Inedita, T.I., page 79. Phil. Trans, volume 73. 1783, page 273. Pierre Prévost's similar investigation, communicated to the Berlin Academy of Sciences 4 months later, July 3, 1783, was inserted in the memoirs of that body for 1781, and thus seems to claim a priority not its due. George Simon Klugel at Halle gave about the same time an analytical demonstration of Herschel's result. Wolf, Gesch. Der Astronomy, page 733. Phil. Trans, volume 95, page 233. Ibid, volume 96, page 205. Ingens bolus deverandus est, Kepler admitted to Herwart in May, 1603. Described in Prefatio Editoris, to De Revolutionibus, page 19. Edition 1854. Opere, T.I., page 415. Phil. Trans, volume 17, page 848. Ibid, volume 72, page 97. Doberk, Observatory, volume 2, page 110. Phil. Trans, volume 57, page 249. Ibid, volume 74, page 56. Beobachtungen von Fixsterntrabanten, 1778, and De Novis in Scylla Sidereal Phenomenis, 1779. Bibliography, page 569. Phil. Trans, volume 72, page 162. Ibid, volume 73, page 272. Ibid, volume 93, page 340. Phil. Trans, volume 75, page 255. Ibid, volume 79, pages 214, 222. Ibid, volume 92, pages 479, 495. Phil. Trans, volume CI, page 269. Ibid, volume CFI, page 311. Bullialdus, De Nebulosa Stella in Singulo Andromedae, 1667, see also G. P. Bond MEM. AM. AC, volume 3, page 75, Holden's monograph on the Orion Nebula, Washington Observations, volume 25, 1878, pub. 1882, and Lady Huggins's drawing, Atlas of Spectra, page 119. Mathemata Astronomica, page 75. Systema Saturnium, page 9. Phil. Trans, volume 29, page 390. MEM. AC, De Sciences, 1755. Con de Temps, 1784, pub. 1781, page 227. A previous list of 45 had appeared in MEM. AC, De Sciences, 1771. Phil. Trans, volume 74, page 442. Ibid, volume 79, page 213. Ibid, volume 75, page 254. Ibid, volume 79, page 225. Phil. Trans, volume 79, page 226. Ibid, volume 81. Page 72. Ibid, page 85. Phil. Trans, volume CI, page 271. Ibid, page 277. J. Herschel, Phil. Trans, volume XVI, part 3, page 1. His own words to the poet Campbell cited by Holden, Life and Works, page 109. Phil. Trans, volume Civ, page 283. Chapter 2. Progress of Sidereal Astronomy. We have now to consider labors of a totally different character from those of Sir William Herschel. Exploration and discovery do not constitute the whole business of astronomy. The less adventurous, though not less arduous, task of gaining a more and more complete mastery over the problems immemorially presented to her, may, on the contrary, be said to form her primary duty. A knowledge of the movements of the heavenly bodies has, from the earliest times, been demanded by the urgent needs of mankind, and science finds its advantage, as in many cases it has taken its origin, in condescension to practical claims. Indeed, to bring such knowledge as near as possible to absolute precision has been defined by no mean authority as the true end of astronomy. Several causes concurred about the beginning of the last century to give a fresh and powerful impulse to investigations having this end in view. The rapid progress of theory almost compelled a corresponding advance in observation. Instrumental improvements rendered such an advance possible. Herschel's discoveries quickened public interest in celestial inquiries, royal, imperial, and grand-ducal patronage widened the scope of individual effort. The heart of the new movement was in Germany. Hitherto the observatory of Flamsteed and Bradley had been the acknowledged center of practical astronomy. Greenwich observations were the standard of reference all over Europe. And the art of observing prospered in direct proportion to the fidelity with which Greenwich methods were imitated. Dr. Maskelyne, who held the post of Astronomer Royal during 46 years, from 1765 to 1811, was no unworthy successor to the eminent men who had gone before him. His foundation of the Nautical Almanac, in 1767, alone constitutes a valid title to fame. He introduced at the observatory the important innovation of the systematic publication of results. And the careful and prolonged series of observations executed by him formed the basis of the improved theories, and corrected tables of the celestial movements, which were rapidly being brought to completion abroad. His catalogue of 36 fundamental stars was besides excellent in its way, and most serviceable. Yet he was devoid of Bradley's instinct for divining the needs of the future. He was fitted rather to continue a tradition than to found a school. The old ways were dear to him, and, indefatigable as he was, a definite purpose was wanting to compel him, by its exigencies, along the path of progress. Thus, for almost 50 years after Bradley's death, the acquisition of a small achromatic was the only notable change made in the instrumental equipment of the observatory. The transit, the zenith sector, and the mural quadrant, with which Bradley had done his incomparable work, retained their places long after they had become deteriorated by time and obsolete by the progress of invention. And it was not until the very close of his career that Maskelyne, compelled by Pond's detection of serious errors, ordered a Trotten circle, which he did not live to employ. Meanwhile, the heavy national disasters with which Germany was overwhelmed in the early part of the 19th century seemed to stimulate rather than impede the intellectual revival already for some years in progress there. Astronomy was amongst the first of the sciences to feel the new impulse. By the efforts of Bode, Olbers, Schroeder, and von Zach, just and elevated ideas on the subject were propagated, intelligence was diffused, and a firm ground prepared for common action in mutual sympathy and disinterested zeal. They received powerful aid through the foundation, in 1804, by a young artillery officer named von Reichenbach, of an optical and mechanical institute at Munich. Here the work of English instrumental artists was for the first time rivaled, and that of English opticians, when Fraunhofer entered the new establishment, far surpassed. The development given to the refracting telescope by this extraordinary man was indispensable to the progress of that fundamental part of astronomy which consists in the exact determination of the places of the heavenly bodies. Reflectors are brilliant engines of discovery, but they lend themselves with difficulty to the prosaic work of measuring right ascensions and polar distances. A signal improvement in the art of making and working flint glass thus most opportunely coincided with the rise of a German school of scientific mechanicians, to furnish the instrumental means needed for the reform which was at hand. Of the leader of that reform it is now time to speak. Friedrich Wilhelm Bessel was born at Minden, in Westphalia, July 22, 1784. A certain taste for figures, coupled with a still stronger distaste for the Latin accidence, directed his inclination and his father's choice towards a mercantile career. In his 15th year, accordingly, he entered the house of Kulenkamp and Sons, in Bremen, as an apprenticed clerk. He was now thrown completely upon his own resources. From his father, a struggling government official, heavily weighted with a large family, he was well aware that he had nothing to expect. His dormant faculties were roused by the necessity for self-dependence, and he set himself to push manfully forward along the path that lay before him. The post of supercargo on one of the trading expeditions sent out from the Hanseatic towns to China and the East Indies was the aim of his boyish ambition, for the attainment of which he sought to qualify himself by the industrious acquisition of suitable and useful knowledge. He learned English in 2 or 3 months, picked up Spanish with the casual aid of a gunsmith's apprentice, studied the geography of the distant lands which he hoped to visit, collected information as to their climates, inhabitants, products, and the courses of trade. He desired to add some acquaintance with the art, then much neglected, of taking observations at sea. And thus, led on from navigation to astronomy, and from astronomy to mathematics, he groped his way into a new world. It was characteristic of him that the practical problems of science should have attracted him before his mind was as yet sufficiently matured to feel the charm of its abstract beauties. His first attempt at observation was made with a sextant, rudely constructed under his own directions, and a common clock. Its object was the determination of the longitude of Bremen, and its success, he tells us himself, filled him with a rapture of delight, which, by confirming his tastes, decided his destiny. He now eagerly studied Bode's Jahrbuch and von Zach's monatliche correspondence, overcoming each difficulty as it arose with the aid of Lalande's Traité d'Astronomie, and supplying, with amazing rapidity, his early deficiency in mathematical training. In 2 years he was able to attack a problem which would have tasked the patience, if not the skill, of the most experienced astronomer. Amongst the Earl of Egremont's papers von Zach had discovered Harriot's observations on Halley's comet at its appearance in 1607, and published them as a supplement to Bode's Annual. With an elaborate care inspired by his youthful ardor, though hardly merited by their loose nature, Bessel deduced from them an orbit for that celebrated body, and presented the work to Olbers, whose reputation in cometary researches gave a special fitness to the proffered homage. The benevolent physician-astronomer of Bremen welcomed with surprised delight such a performance emanating from such a source. 15 years previously, the French Academy had crowned a similar work. Now its equal was produced by a youth of 20, busily engaged in commercial pursuits, self-taught, and obliged to snatch from sleep the hours devoted to study. The paper was immediately sent to von Zach for publication, with a note from Olbers explaining the circumstances of its author, and the name of Bessel became the common property of learned Europe. He had, however, as yet no intention of adopting astronomy as his profession. For 2 years he continued to work in the counting-house by day, and to pore over the Mécanique Céleste and the differential calculus by night. But the post of assistant in Schroeder's observatory at Lilienthal having become vacant by the removal of Harding to Göttingen in 1805, Olbers procured for him the offer of it. It was not without a struggle that he resolved to exchange the desk for the telescope. His reputation with his employers was of the highest. He had thoroughly mastered the details of the business, which his keen practical intelligence followed with lively interest. His years of apprenticeship were on the point of expiring, and an immediate, and not unwelcome prospect of comparative affluence lay before him. The love of science, however, prevailed. He chose poverty and the stars, and went to Lilienthal with a salary of 100 thalers yearly. Looking back over his life's work, Olbers long afterwards declared that the greatest service which he had rendered to astronomy was that of having discerned, directed, and promoted the genius of Bessel. For 4 years he continued in Schroeder's employment. At the end of that time the Prussian government chose him to superintend the erection of a new observatory at Königsberg, which after many vexatious delays, caused by the prostrate condition of the country, was finished towards the end of 1813. Königsberg was the first really efficient German observatory. It became, moreover, a center of improvement, not for Germany alone, but for the whole astronomical world. During 230 years it was the scene of Bessel's labors, and Bessel's labors had for their aim the reconstruction, on an amended and uniform plan, of the entire science of observation. A knowledge of the places of the stars is the foundation of astronomy. Their configuration lends to the skies their distinctive features, and marks out the shifting tracks of more mobile objects with relatively fixed, and generally unvarying points of light. A more detailed and accurate acquaintance with the stellar multitude, regarded from a purely uranographical point of view, has accordingly formed at all times a primary object of celestial science, and was, during the last century, cultivated with a zeal and success by which all previous efforts were dwarfed into insignificance. In Lalande's Histoire Céleste, published in 1801, the places of no less than 47,390 stars were given, but in the rough, as it were, and consequently needing laborious processes of calculation to render them available for exact purposes. Piazzi set an example of improved methods of observation, resulting in the publication, in 1803 and 1814, of two catalogues of about 7,600 stars, the second being a revision and enlargement of the first, which for their time were models of what such works should be. Stephen Groombridge at Blackheath was similarly and most beneficially active. But something more was needed than the diligence of individual observers. A systematic reform was called for, and it was this which Bessel undertook and carried through. Direct observation furnishes only what has been called the raw material of the positions of the heavenly bodies. A number of highly complex corrections have to be applied before their mean can be disengaged from their apparent places on the sphere. Of these, the most considerable and familiar is atmospheric refraction, by which objects seem to stand higher in the sky than they in reality do, the effect being evanescent at the zenith, and attaining, by gradations varying with conditions of pressure and temperature, a maximum at the horizon. Moreover, the points to which measurements are referred are themselves in motion, either continually in one direction, or periodically to and fro. The precession of the equinoxes is slowly progressive, or rather retrogressive. The nutation of the pole oscillatory in a period of about 18 years. Added to which, the non-instantaneous transmission of light, combined with the movement of the Earth in its orbit, causes a small annual displacement known as aberration. Now it is easy to see that any uncertainty in the application of these corrections saps the very foundations of exact astronomy. Extremely minute quantities, it is true, are concerned. But the life and progress of modern celestial science depends upon the sure recognition of extremely minute quantities. In the early years of the 19th century, however, no uniform system of reduction, so the complete correction of observational results is termed, had been established. Much was left to the individual caprice of observers, who selected for the several elements of reduction such values as seemed best to themselves. Hence arose much hurtful confusion, tending to hinder united action and mar the usefulness of laborious researches. For this state of things, Bessel, by the exercise of consummate diligence, sagacity, and patience, provided an entirely satisfactory remedy. His first step was an elaborate investigation of the precious series of observations made by Bradley at Greenwich from 1750 until his death in 1762. The catalogue of 3,222 stars which he extracted from them gave the earliest example of the systematic reduction on a uniform plan of such a body of work. It is difficult, without entering into details out of place in a volume like the present, to convey an idea of the arduous nature of this task. It involved the formation of a theory of the errors of each of Bradley's instruments, and a difficult and delicate inquiry into the true value of each correction to be applied. Before the entries in the Greenwich journals could be developed into a finished and authentic catalogue. Although completed in 1813, it was not until 5 years later that the results appeared with the proud, but not inappropriate title of Fundamenta Astronomiae. The eminent value of the work consisted in this, that by providing a mass of entirely reliable information as to the state of the heavens at the epoch 1755, it threw back the beginning of exact astronomy almost half a century. By comparison with Piazzi's catalogues, the amount of precession was more accurately determined, the proper motions of a considerable number of stars became known with certainty. and definite prediction, the certificate of initiation into the secrets of nature, at last became possible as regards the places of the stars. Bessel's final improvements in the methods of reduction were published in 1830 in his Tabulae Regiomontanae. They not only constituted an advance in accuracy, but afforded a vast increase of facility in application, and were at once and everywhere adopted. Thus astronomy became a truly universal science. Uncertainties and disparities were banished, and observations made at all times and places rendered mutually comparable. More, however, yet remained to be done. In order to verify with greater strictness the results drawn from the Bradley and Piazzi catalogues, a third term of comparison was wanted, and this Bessel undertook to supply. By a course of 75,011 observations, executed during the years 1821 to 33, with the utmost nicety of care, the number of accurately known stars was brought up to above 50,000. And an ample store of trustworthy facts laid up for the use of future astronomers. In this department Argelander, whom he attracted from finance to astronomy, and trained in his own methods, was his assistant and successor. The great Bonn Durchmusterung, in which 324,198 stars visible in the northern hemisphere are enumerated, and the corresponding atlas, published in 1857-63. Constituting a picture of our sidereal surroundings of heretofore unapproached completeness, may be justly said to owe their origin to Bessel's initiative, and to form a sequel to what he commenced. But his activity was not solely occupied with the promotion of a comprehensive reform in astronomy, it embraced special problems as well. The long-baffled search for a parallax of the fixed stars was resumed with fresh zeal as each mechanical or optical improvement held out fresh hopes of a successful issue. Illusory results abounded. Piazza in 1805 perceived, as he supposed, considerable annual displacements in Vega, Aldebaran, Sirius, and Procyon, the truth being that his instruments were worn out with constant use, and could no longer be depended upon. His countryman, Calandrelli, was similarly deluded. The celebrated controversy between the Astronomer Royal and Dr. Brinkley, director of the Dublin College Observatory, turned on the same subject. Brinkley, who was in possession of a first-rate meridian circle, believed himself to have discovered relatively large parallaxes for 4 of the brightest stars. Pond, relying on the testimony of the Greenwich instruments, asserted their nullity. The dispute, protracted for 14 years, from 1810 until 1824, was brought to no definite conclusion, but the strong presumption on the negative side was abundantly justified in the event. There was good reason for incredulity in the matter of parallaxes. Announcements of their detection had become so frequent as to be discredited before they were disproved. And Struve, who investigated the subject at Dorpat in 1818-21, had clearly shown that the quantities concerned were too small to come within the reliable measuring powers of any instrument then in use. Already, however, the means were being prepared of giving to those powers a large increase. On the July 21, 1801, 2 old houses in an alley of Munich tumbled down, burying in their ruins the occupants, of whom one alone was extricated alive, though seriously injured. This was an orphan lad of 14 named Joseph Fraunhofer. The Elector Maximilian Joseph was witness of the scene, became interested in the survivor, and consoled his misfortune with a present of 18 ducats. Seldom was money better bestowed. Part of it went to buy books and a glass polishing machine, with the help of which young Fraunhofer studied mathematics and optics, and secretly exercised himself in the shaping and finishing of lenses. The remainder purchased his release from the tyranny of one Weichselberger, a looking-glass maker by trade, to whom he had been bound apprentice on the death of his parents. A period of struggle and privation followed, during which, however, he rapidly extended his acquirements, and was thus eminently fitted for the task awaiting him, when, in 1806, he entered the optical department of the establishment founded 2 years previously by von Reichenbach and Utzschneider. He now zealously devoted himself to the improvement of the achromatic telescope. And, after a prolonged study of the theory of lenses, and many toilsome experiments in the manufacture of flint glass, he succeeded in perfecting, December 12, 1817, an object glass of exquisite quality in finish, 9.5 inches in diameter, and of 14 feet focal length. This, as it was then considered, gigantic lens was secured by Struve for the Russian government, and the great Dorpat refractor, the first of the large achromatics which have played such an important part in modern astronomy, was, late in 1824, set up in the place which it still occupies. By ingenious improvements in mounting and fitting, it was adapted to the finest micrometrical work, and thus offered unprecedented facilities both for the examination of double stars, in which Struve chiefly employed it, and for such subtle measurements as might serve to reveal or disprove the existence of a sensible stellar parallax. Fraunhofer, moreover, constructed for the observatory at Königsberg the first really available heliometer. The principle of this instrument, termed with more propriety a divided object glass micrometer, is the separation, by a strictly measurable amount, of two distinct images of the same object. If a double star, for instance, be under examination, the two half-lenses into which the object glass is divided are shifted until the upper star, say, in one image is brought into coincidence with the lower star in the other, when their distance apart becomes known by the amount of motion employed. This virtually new engine of research was delivered and mounted in 1829, 3 years after the termination of the life of its deviser. The Dorpat lens had brought to Fraunhofer a title of nobility and the sole management of the Munich Optical Institute, completely separated since 1814 from the mechanical department. What he had achieved, however, was but a small part of what he meant to achieve. He saw before him the possibility of nearly quadrupling the light-gathering capacity of the great achromatic acquired by Struve. He meditated improvements in reflectors as important as those he had already effected in refractors, and was besides eagerly occupied with investigations into the nature of light, the momentous character of which we shall by and by have an opportunity of estimating. But his health was impaired, it is said, from the weakening effects of his early accident, combined with excessive and unwholesome toil, and, still hoping for its restoration from a projected journey to Italy, he died of consumption, June 7, 1826. Aged 39 years. His tomb in Munich bears the concise eulogy, Approximavit Sidera. Bessel had no sooner made himself acquainted with the exquisite defining powers of the Königsberg heliometer, than he resolved to employ them in an attack upon the now secular problem of star distances. But it was not until 1837 that he found leisure to pursue the inquiry. In choosing his test star he adopted a new principle. It had hitherto been assumed that our nearest neighbors in space must be found among the brightest ornaments of our skies. The knowledge of stellar proper motions afforded by the critical comparison of recent with earlier star places suggested a different criterion of distance. It is impossible to escape from the conclusion that the apparently swiftest moving stars are, on the whole, also the nearest to us, however numerous the individual exceptions to the rule. Now, as early as 1792, Piazzi had noted as an indication of relative vicinity to the Earth, the unusually large proper motion, 5.2 annually, of a double star of the fifth magnitude in the constellation of the Swan. Still more emphatically in 1812 Bessel drew the attention of astronomers to the fact, and 61 Cygni became known as the flying star. The seeming rate of its flight, indeed, is of so leisurely a kind, that in 1,000 years it will have shifted its place by less than 3.5 lunar diameters. And that 250,000 would be required to carry it round the entire circuit of the visible heavens. Nevertheless, it has few rivals in rapidity of movement, the apparent displacement of the vast majority of stars being, by comparison, almost insensible. This interesting, though inconspicuous object, then, was chosen by Bessel to be put to the question with his heliometer, while Struve made a similar and somewhat earlier trial with the bright gem of the Lyre, whose Arabic title of the falling eagle survives as a time-worn remnant in Vega. Both astronomers agreed to use the differential method, for which their instruments and the vicinity to their selected stars of minute, physically detached companions offered special facilities. In the last month of 1838 Bessel made known the result of 1 year's observations, showing for 61 Cygni a parallax of about a third of a second, 0.3136. He then had his heliometer taken down and repaired, after which he resumed the inquiry, and finally terminated a series of 402 measures in March 1840. The resulting parallax of 0.3483, corresponding to a distance about 600,000 times that of the Earth from the Sun, seemed to be ascertained beyond the possibility of cavil, and is memorable as the first published instance of the fathom line. So industriously thrown into celestial space, having really and indubitably touched bottom. It was confirmed in 1842-43 with curious exactness by C.A.F. Peters at Pulkowa, but later researches showed that it required increase to nearly half a second. Struve's measurements inspired less confidence. They extended over 3 years, 1835-38, but were comparatively few, and were frequently interrupted. The parallax, accordingly, of about a quarter of a second, 0.2613, which he derived from them for Alpha Lyrae, and announced in 1840, has proved considerably too large. Meanwhile a result of the same kind, but of a more striking character than either Bessel's or Struve's, had been obtained, one might almost say casually, by a different method and in a distant region. Thomas Henderson, originally an attorney's clerk in his native town of Dundee, had become known for his astronomical attainments, and was appointed in 1831 to direct the recently completed observatory at the Cape of Good Hope. He began observing in April, 1832, and, the serious shortcomings of his instrument notwithstanding, executed during the 13 months of his tenure of office a surprising amount of first-rate work. With a view to correcting the declination of the lustrous double star Alpha Centauri, which ranks after Sirius and Canopus as the third brightest orb in the heavens, he effected a number of successive determinations of its position. And on being informed of its very considerable proper motion, 3-6 annually, he resolved to examine the observations already made for possible traces of parallactic displacement. This was done on his return to Scotland, where he filled the office of Astronomer Royal from 1834 until his premature death in 1844. The result justified his expectations. From the declination measurements made at the Cape and duly reduced, a parallax of about 1 second of arc clearly emerged, diminished by Gill's and Elkin's observations, 1882-1883, to 0.75. But, by perhaps an excess of caution, was withheld from publication until fuller certainty was afforded by the concurrent testimony of Lieutenant Meadows's determinations of the same star's right ascension. When at last, January 9, 1839, Henderson communicated his discovery to the Astronomical Society, he could no longer claim the priority which was his due. Bessel had anticipated him with the parallax of 61 Cygni by just 2 months. Thus from 3 different quarters, 3 successful and almost simultaneous assaults were delivered upon a long-beleaguered citadel of celestial secrets. The same work has since been steadily pursued, with the general result of showing that, as regards their overwhelming majority, the stars are far too remote to show even the slightest trace of optical shifting from the revolution of the Earth in its orbit. In nearly 100 cases, however, small parallaxes have been determined, some certainly, that is, within moderate limits of error, others more or less precariously. The list is an instructive one, in its omissions no less than in its contents. It includes stars of many degrees of brightness, from Sirius down to a nameless telescopic star in the Great Bear. Yet the vicinity to the Earth of this minute object is so much greater than that of the brilliant Vega, that the latter transported to its place would increase in luster 38 times. Moreover, many of the brightest stars are found to have no sensible parallax, while the majority of those ascertained to be nearest to the Earth are of 5th, 6th, even 9th magnitudes. The obvious conclusions follow that the range of variety in the sidereal system is enormously greater than had been supposed, and that estimates of distance based upon apparent magnitude must be wholly futile. Thus, the splendid Canopus, Betelgeuse, and Rigel can be inferred, from their indefinite remoteness, to exceed our Sun thousands of times in size and luster. While many inconspicuous objects, which prove to be in our relative vicinity, must be notably his inferiors. The limits of real stellar magnitude are then set very widely apart. At the same time, the so-called optical and geometrical methods of relatively estimating star distances are both seen to have a foundation of fact, although so disguised by complicated relations as to be of very doubtful individual application. On the whole, the chances are in favor of the superior vicinity of a bright star over a faint one, and, on the whole, the stars in swiftest apparent motion are amongst those whose actual remoteness is least. Indeed, there is no escape from either conclusion, unless on the supposition of special arrangements in themselves highly improbable, and, we may confidently say, non-existent. The distances even of the few stars found to have measurable parallaxes are on a scale entirely beyond the powers of the human mind to conceive. In the attempt both to realize them distinctly, and to express them conveniently, a new unit of length, itself of bewildering magnitude, has originated. This is what we may call the light journey of 1 year. The subtle vibrations of the ether, propagated on all sides from the surface of luminous bodies, travel at the rate of 186,300 miles a second, or, in round numbers, 6 billions of miles a year. 4 1/3 such measures are needed to span the abyss that separates us from the nearest fixed star. In other words, light takes 4 years and 4 months to reach the Earth from Alpha Centauri. Yet Alpha Centauri lies some 10 billions of miles nearer to us, so far as is yet known, than any other member of the sidereal system. The determination of parallax leads, in the case of stars revolving in known orbits, to the determination of mass. For the distance from the Earth of the two bodies forming a binary system being ascertained, the seconds of arc apparently separating them from each other can be translated into millions of miles. And we only need to add a knowledge of their period to enable us, by an easy sum in proportion, to find their combined mass in terms of that of the Sun. Thus, since, according to Dr. Dobberg's elements, the components of Alpha Centauri revolve round their common center of gravity at a mean distance nearly 25 times the radius of the Earth's orbit, in a period of 88 years. The attractive force of the two together must be just twice the solar. We may gather some idea of their relations by placing in imagination a second luminary like our Sun in circulation between the orbits of Neptune and Uranus. But systems of still more majestic proportions are reduced by extreme remoteness to apparent insignificance. A double star of the fourth magnitude in Cassiopeia, Eta, to which a small parallax is ascribed on the authority of O. Struve, appears to be above 8 times as massive as the central orb of our world, while a much less conspicuous pair, 85 Pegasi, exerts, if the available data can be depended upon, no less than 13 times the solar gravitating power. Further, the actual rate of proper motions, so far as regards that part of them which is projected upon the sphere, can be ascertained for stars at known distance. The annual journey, for instance, of 61 Cygni across the line of sight amounts to 1,000, and that of Alpha Centauri to 446 millions of miles. A small star, numbered 1,830 in Groombridge's circumpolar catalogue, devours the way, at the rate of at least 150 miles a second, a speed, in Newcomb's opinion, beyond the gravitating power of the entire sidereal system to control. And Mu Cassiopeiae possesses above 2/3 of that surprising velocity, while for both objects, radial movements of just 60 miles a second were disclosed by Professor Campbell's spectroscopic measurements. Herschel's conclusion as to the advance of the Sun among the stars was not admitted as valid by the most eminent of his successors. Bessel maintained that there was absolutely no preponderating evidence in favor of its supposed direction towards a point in the constellation Hercules. By it, Burckhardt, even Herschel's own son, shared his incredulity. But the appearance of Argelander's prize essay in 1837 changed the aspect of the question. Herschel's first memorable solution in 1783 was based upon the motions of 13 stars, imperfectly known. His second, in 1805, upon those of no more than 6. Argelander now obtained an entirely concordant result from the large number of 390, determined with the scrupulous accuracy characteristic of Bessel's work and his own. The reality of the fact thus persistently disclosed could no longer be doubted. It was confirmed 5 years later by the younger Struve, and still more strikingly in 1847 by Galloway's investigations, founded exclusively on the apparent displacements of southern stars. In 1859 and 1863, Sir George Airy and Mr. Duncan, 1821–1898, employing all the resources of modern science, and commanding the wealth of material furnished by 1,167 proper motions carefully determined by Mr. Main, reached conclusions closely similar to that indicated nearly 80 years previously by the first great sidereal astronomer, which Mr. Plummer's reinvestigation of the subject in 1883 served but slightly to modify. Yet astronomers were not satisfied. Dr. Auwers of Berlin completed in 1866 a splendid piece of work, for which he received in 1888 the gold medal of the Royal Astronomical Society. It consisted in reducing afresh, with the aid of the most refined modern data, Bradley's original stars, and comparing their places thus obtained for the year 1755 with those assigned to them from observations made at Greenwich after the lapse of 90 years. In the interval, as was to be anticipated, most of them were found to have traveled over some small span of the heavens, and there resulted a stock of nearly 3,000 highly authentic proper motions. These ample materials were turned to account by M. Ludwig Struve for a discussion of the sun's motion, of which the upshot was to shift its point of aim to the bordering region of the constellations Hercules and Lyra. And the more easterly position of the solar apex was fully confirmed by the experiments, with variously assorted lists of stars, of Louis Boss of Albany, and Oscar Stump of Bonn. Fresh precautions of refinement were introduced into the treatment of the subject by Rissenpart of Karlsruhe, by Kapteyn of Groningen, by Newcomb and Porter in America, who ably availed themselves of the copious materials accumulated before the close of the century. Their results, although not more closely accordant than those of their predecessors, combine to show that the journey of our system is directed towards a point within a circle about 10 degrees in radius, having the brilliant Vega for its center. To determine its rate was a still more arduous problem. It involved the assumption, very much at discretion, of an average parallax for the stars investigated. And Otto Struve's estimate of 154 million miles as the span yearly traversed was hence wholly unreliable. Fortunately, however, as will be seen further on, a method of determining the sun's velocity independently of any knowledge of star distances, has now become available. As might have been expected, speculation has not been idle regarding the purpose and goal of the strange voyage of discovery through space upon which our system is embarked, but altogether fruitlessly. The variety of the conjectures hazarded in the matter is in itself a measure of their futility. Long ago, before the construction of the heavens had as yet been made the subject of methodical inquiry, Kant was disposed to regard Sirius as the central sun of the Milky Way, while Lambert surmised that the vast Orion nebula might serve as the regulating power of a subordinate group including our Sun. Herschel threw out the hint that the great cluster in Hercules might prove to be the supreme seat of attractive force. Argelander placed his central body in the constellation Perseus. Fomalhaut, the brilliant of the southern fish, was set in the post of honor by Boguslawski of Breslau. Madler, who succeeded Struve at Dorpat in 1839, concluded from a more formal inquiry that the ruling power in the sidereal system resided, not in any single prepondering mass, but in the center of gravity of the self-controlled revolving multitude. In the former case, as we know from the example of the planetary scheme, the stellar motions would be most rapid near the center, in the latter, they would become accelerated with remoteness from it. Madler showed that no part of the heavens could be indicated as a region of exceptionally swift movements, such as would result from the presence of a gigantic, though possibly obscure, ruling body. But that a community of extremely sluggish movements undoubtedly existed in and near the group of the Pleiades, where, accordingly, he placed the center of gravity of the Milky Way. The bright star Alcyone thus became the central sun, but in a purely passive sense, its headship being determined by its situation at the point of neutralization of opposing tendencies, and of consequent rest. By an avowedly conjectural method, the solar period of revolution round this point was fixed at 18,200,000 years. The scheme of sidereal government framed by the Dorpat astronomer was, it may be observed, of the most approved constitutional type. Deprivation, rather than increase of influence accompanying the office of chief dignitary. But while we are still ignorant, and shall perhaps ever remain so, of the fundamental plan upon which the galaxy is organized, recent investigations tend more and more to exhibit it, not as monarchical, so to speak, but as federative. The community of proper motions detected by Madler in the vicinity of the Pleiades may accordingly possess a significance altogether different from what he imagined. Bessel's so-called foundation of an astronomy of the invisible now claims attention. His prediction regarding the planet Neptune does not belong to the present division of our subject. A strictly analogous discovery in the sidereal system was, however, also very clearly foreshadowed by him. His earliest suspicions of non-uniformity in the proper motion of Sirius dated from 1834, they extended to Procyon in 1840. And after a series of refined measurements with the new Repsold circle, he announced in 1844 his conclusion that these irregularities were due to the presence of obscure bodies round which the two bright dog stars revolved as they pursued their way across the sphere. He even assigned to each an approximate period of half a century. I adhere to the conviction, he wrote later to Humboldt, that Procyon and Sirius form real binary systems, consisting of a visible and an invisible star. There is no reason to suppose luminosity an essential quality of cosmical bodies. The visibility of countless stars is no argument against the invisibility of countless others. An inference so contradictory to received ideas obtained little credit, until Peters found, in 1851, that the apparent anomalies in the movements of Sirius could be completely explained by an orbital revolution in a period of 50 years. Bessel's prevision was destined to be still more triumphantly vindicated. On the 31st of January, 1862, while in the act of trying a new 18-inch refractor, Mr. Alvin G. Clarke, one of the celebrated firm of American opticians, actually discovered the hypothetical Sirian companion in the precise position required by theory. It has now been watched through nearly an entire revolution, period 49, 4 years, and proves to be very slightly luminous in proportion to its mass. Its attractive power, in fact, is nearly half that of its primary, while it emits only 1/10,000th of its light. Sirius itself, on the other hand, possesses a far higher radiative intensity than our Sun. It gravitates, admitting Sir David Gill's parallax of 0.38 to be exact, like 2 suns, but shines like 20. Possibly it is much distended by heat, and undoubtedly its atmosphere intercepts a very much smaller proportion of its light than in stars of the solar class. As regards Procyon, visual verification was awaited until November 13, 1896, when Professor Skeeberl, with the Great Lick refractor, detected the long-sought object in the guise of a 13th magnitude star. Dar. C's calculations showed it to possess 1/5 the mass of its primary, or rather more than half that of our Sun. Yet it gives barely 1/20,000th of the Sun's light, so that it is still nearer to total obscurity than the dusky satellite of Sirius. The period of 40 years assigned to the system by Auers in 1862 appears to be singularly exact. But Bessel was not destined to witness the recognition of the invisible as a legitimate and profitable field for astronomical research. He died March 17, 1846, just 6 months before the discovery of Neptune, of an obscure disease, eventually found to be occasioned by an extensive fungus growth in the stomach. The place which he left vacant was not one easy to fill. His life's work might be truly described as epoch-making. Rarely indeed shall we find one who reconciled with the same success the claims of theoretical and practical astronomy, or surveyed the science which he had made his own with a glance equally comprehensive, practical, and profound. The career of Friedrich Georg Wilhelm Struve illustrates the maxim that science differentiates as it develops. He was, while much besides, a specialist in double stars. His earliest recorded use of the telescope was to verify Herschel's conclusion as to the revolving movement of Castor, and he never varied from the predilection which this first observation at once indicated and determined. He was born at Altena, of a respectable yeoman family, April 15, 1793, and in 1811 took a degree in philology at the new Russian University of Dorpat. He then turned to science, was appointed in 1813 to a professorship of astronomy and mathematics, and began regular work in the Dorpat Observatory just erected by Parrot for Alexander I. It was not, however, until 1819 that the acquisition of a 5-foot refractor by Troughton enabled him to take the position angles of double stars with regularity and tolerable precision. The resulting catalogue of 795 stellar systems gave the signal for a general resumption of the Herschelian labors in this branch. His success, so far, and the extraordinary facilities for observation afforded by the Fraunhofer achromatic encouraged him to undertake, February 11, 1825, a review of the entire heavens down to 15 degrees south of the celestial equator, which occupied more than 2 years, and yielded, from an examination of above 120,000 stars, a harvest of about 2,200 previously unnoticed composite objects. The ensuing 10 years were devoted to delicate and patient measurements, the results of which were embodied in Mentari Micrometricae, published at St. Petersburg in 1837. This monumental work gives the places, angles of position, distances, colors, and relative brightness of 3,112 double and multiple stars, all determined with the utmost skill and care. The record is one which gains in value with the process of time, and will for ages serve as a standard of reference by which to detect change or confirm discovery. It appears from Struve's researches that about 1 in 40 of all stars down to the 9th magnitude is composite, but that the proportion is doubled in the brighter orders. This he attributed to the difficulty of detecting the faint companions of very remote orbs. It was also noticed, both by him and Bessel, that double stars are in general remarkable for large proper motions. Struve's catalogue included no star of which the components were more than 32 apart, because beyond that distance the chances of merely optical juxtaposition become considerable. But the immense preponderance of extremely close over, as it were, loosely yoked bodies is such as to demonstrate their physical connection, even if no other proof were forthcoming. Many stars previously believed to be single divided under the scrutiny of the Dorpat refractor. While in some cases, one member of a supposed binary system revealed itself as double, thus placing the surprised observer in the unexpected presence of a triple group of suns. 5 instances were noted of 2 pairs lying so close together as to induce a conviction of their mutual dependence. Besides which, 124 examples occurred of triple, quadruple, and multiple combinations, the reality of which was open to no reasonable doubt. It was first pointed out by Bessel that the fact of stars exhibiting a common proper motion might serve as an unfailing test of their real association into systems. This was, accordingly, one of the chief criteria employed by Struve to distinguish true binaries from merely optical couples. On this ground alone, 61 Cygni was admitted to be a genuine double star. And it was shown that, although its components appeared to follow almost strictly rectilinear paths, yet the probability of their forming a connected pair is actually greater than that of the sun rising tomorrow morning. Moreover, this tie of an identical movement was discovered to unite bodies far beyond the range of distance ordinarily separating the members of binary systems, and to prevail so extensively as to lead to the conclusion that single do not outnumber conjoined stars more than twice or thrice. In 1835 Struve was summoned by the Emperor Nicholas to superintend the erection of a new observatory at Pulkowa, near St. Petersburg, destined for the special cultivation of sidereal astronomy. Boundless resources were placed at his disposal, and the institution created by him was acknowledged to surpass all others of its kind in splendor, efficiency, and completeness. Its chief instrumental glory was a refractor of 15 inches aperture by Merz and Mahler, Fraunhofer's successors, which left the famous Dorpat telescope far behind, and remained long without a rival. On the completion of this model establishment, August 19, 1839, Struve was installed as its director, and continued to fulfill the important duties of the post with his accustomed vigor until 1858. When illness compelled his virtual resignation in favor of his son Otto Struve, born at Dorpat in 1819. He died November 23, 1864. An inquiry into the laws of stellar distribution, undertaken during the early years of his residence at Pulkowa, led Struve to confirm in the main the inferences arrived at by Herschel as to the construction of the heavens. According to his view, the appearance known as the Milky Way is produced by a collection of irregularly condensed star clusters, within which the Sun is somewhat eccentrically placed. The nebulous ring which thus integrates the light of countless worlds was supposed by him to be made up of stars scattered over a bent or broken plane, or to lie in two planes slightly inclined to each other, our system occupying a position near their intersection. He further attempted to show that the limits of this vast assemblage must remain forever shrouded from human discernment, owing to the gradual extinction of light in its passage through space, and sought to confer upon this celebrated hypothesis a definiteness and certainty far beyond the aspirations of its earlier advocates, Chasseaux and Olbers. But arbitrary assumptions vitiated his reasonings on this, as well as on some other points. In his special line as a celestial explorer of the most comprehensive type, Sir William Herschel had but one legitimate successor, and that successor was his son. John Frederick William Herschel was born at Slough, March 17, 1792, graduated with the highest honours from St. John's College, Cambridge, in 1813, and entered upon legal studies with a view to being called to the bar. But his share in an early compact with Peacock and Babbage, to do their best to leave the world wiser than they found it, was not thus to be fulfilled. The acquaintance of Dr. Wollaston decided his scientific vocation. Already, in 1816, we find him reviewing some of his father's double stars, and he completed in 1820 the 18-inch speculum which was to be the chief instrument of his investigations. Soon afterwards, he undertook, in conjunction with Mr. Later Sir James South, a series of observations, issuing in the presentation to the Royal Society of a paper containing micrometrical measurements of 380 binary stars, by which the elder Herschel's inferences of orbital motion were, in many cases, strikingly confirmed. A star in the northern crown, for instance, Eta Coroni, had completed more than one entire circuit since its first discovery. Another, Tau Ophiuchi, had closed up into apparent singleness, while the motion of a third, Psi Ursae Majoris, in an obviously eccentric orbit, was so rapid as to admit of being traced and measured from month to month. It was from the first confidently believed that the force retaining double stars in curvilinear paths was identical with that governing the planetary revolutions. But that identity was not ascertained until Savary of Paris showed, in 1827, that the movements of the above-named binary in the Great Bear could be represented with all attainable accuracy by an ellipse calculated on orthodox gravitational principles with a period of 58¼ years. Encke followed at Berlin with a still more elegant method. And Sir John Herschel, pointing out the uselessness of analytical refinements where the data were necessarily so imperfect, described in 1832 a graphical process by which the aid of the eye and hand was brought in to guide the judgment in a case where judgment only, and not calculation, could be of any avail. Improved methods of the same kind were published by Dr. C. in 1893, and by Mr. Burnham in 1894, and our acquaintance with stellar orbits is steadily gaining precision, certainty, and extent. In 1825 Herschel undertook, and executed with great assiduity during the ensuing 8 years, a general survey of the northern heavens, directed chiefly towards the verification of his father's nebular discoveries. The outcome was a catalogue of 2,306 nebulae in clusters, of which 525 were observed for the first time, besides 3,347 double stars discovered almost incidentally. Strongly invited, as he tells us himself, by the peculiar interest of the subject, and the wonderful nature of the objects which presented themselves, he resolved to attempt the completion of the survey in the southern hemisphere. With this noble object in view, he embarked his family and instruments on board the Mount Stuart Elphinstone, and, after a prosperous voyage, landed at Cape Town on the 16th of January, 1834. Choosing as the scene of his observations a rural spot under the shelter of Table Mountain, he began regular sweeping on the 5th of March. The site of his great reflector is now marked with an obelisk, and the name of Feldhausen has become memorable in the history of science. For the 4 years' work done there may truly be said to open the chapter of our knowledge as regards the southern skies. The full results of Herschel's journey to the Cape were not made public until 1847, when a splendid volume embodying them was brought out at the expense of the Duke of Northumberland. They form a sequel to his father's labors such as the investigations of one man have rarely received from those of another. What the elder observer did for the northern heavens, the younger did for the southern, and with generally concordant results. Reviving the paternal method of star-gauging, he showed, from a count of 2,299 fields, that the Milky Way surrounds the solar system as a complete annulus of minute stars. Not, however, quite symmetrically, since the Sun was thought to lie somewhat nearer to those portions visible in the southern hemisphere, which display a brighter luster and a more complicated structure than the northern branches. The singular cosmical agglomerations known as the Magellanic Clouds were now, for the first time, submitted to a detailed, though admittedly incomplete, examination. The almost inconceivable richness and variety of their contents being such that a lifetime might with great profit be devoted to their study. In the Greater Nubecula, within a compass of 42 square degrees, Herschel reckoned 278 distinct nebulae in clusters, besides 50 or 60 outliers, and a large number of stars intermixed with diffused nebulosity, in all 919 catalogued objects, and, for the lesser cloud, 244. Yet this was only the most conspicuous part of what his 20-foot revealed. Such an extraordinary concentration of bodies so various led him to the inevitable conclusion that the nubeculae are to be regarded as systems sui generis, and which have no analogues in our hemisphere. He noted also the blankness of surrounding space, especially in the case of Nubecula Minor, the access to which on all sides, he remarked, is through a desert. As if the cosmical material in the neighborhood had been swept up and garnered in these mighty groups. Of southern double stars, he discovered and gave careful measurements of 2,102, and described 1,708 nebulae, of which at least 300 were new. The list was illustrated with a number of drawings, some of them extremely beautiful and elaborate. Sir John Herschel's views as to the nature of nebulae were considerably modified by Lord Rosse's success in resolving, with his great reflectors, a crowd of these objects into stars. His former somewhat hesitating belief in the existence of phosphorescent matter, disseminated through extensive regions of space in the manner of a cloud or fog, was changed into a conviction that no valid distinction could be established between the faintest wisp of cosmical vapor just discernible in a powerful telescope, and the most brilliant and obvious cluster. He admitted, however, an immense range of possible variety in the size and mode of aggregation of the stellar constituents of various nebulae. Some might appear nebulous from the closeness of their parts, some from their smallness. Others, he suggested, might be formed of discrete luminous bodies floating in a non-luminous medium, while the annular kind probably consisted of hollow shells of stars. That a physical, and not merely an optical, connection unites nebulae with the embroidery, so to speak, of small stars with which they are in many instances profusely decorated, was evident to him. As it must be to all who look as closely and see as clearly as he did. His description of number 2093 in his Northern Catalogue as a network or tracery of nebula following the lines of a similar network of stars, would alone suffice to dispel the idea of accidental scattering. And many other examples of a like import might be quoted. The remarkably frequent occurrence of one or more minute stars in the close vicinity of planetary nebulae led him to infer their dependent condition. And he advised the maintenance of a strict watch for evidences of circulatory movements, not only over these supposed stellar satellites, but also over the numerous double nebulae, in which, as he pointed out, all the varieties of double stars as to distance, position, and relative brightness, have their counterparts. He, moreover, investigated the subject of nebular distribution by the simple and effectual method of graphic delineation or charting, and succeeded in showing that while a much greater uniformity of scattering prevails in the southern than in the northern heavens, a condensation is nevertheless perceptible about the constellations Pisces and Cetus, roughly corresponding to the nebular region in Virgo by its vicinity, within 20 degrees or 30 degrees, to the opposite pole of the Milky Way. He concluded that the nebulous system is distinct from the sidereal, though involving, and perhaps to a certain extent intermixed with, the latter. Towards the close of his residence at Feldhausen, Herschel was fortunate enough to witness one of those singular changes in the aspect of the firmament which occasionally challenge the attention even of the incurious, and excite the deepest wonder of the philosophical observer. Immersed apparently in the Argo Nebula is a star denominated Eta Carinii. When Halley visited St. Helena in 1677, it seemed of the fourth magnitude, but Lacaille in the middle of the following century, and others after him, classed it as of the second. In 1827 the traveller Burchell, being then at St. Paul, near Rio Janeiro, remarked that it had unexpectedly assumed the first rank, a circumstance the more surprising to him because he had frequently, when in Africa during the years 1811 to 1815, noted it as of only fourth magnitude. This observation, however, did not become generally known until later. Herschel, on his arrival at Feldhausen, registered the star as a bright second, and had no suspicion of its unusual character until December 16, 1837, when he suddenly perceived its light to be almost tripled. It then far outshone Rigel in Orion, and on the 2nd of January following it very nearly matched Alpha Centauri. From that date it declined. But a second and even brighter maximum occurred in April, 1843, when MacLear, then director of the Cape Observatory, saw it blaze out with a splendor approaching that of Sirius. Its waxings and wanings were marked by curious trepidations of brightness extremely perplexing to theory. In 1863 it had sunk below the fifth magnitude, and in 1869 was barely visible to the naked eye. Yet it was not until 18 years later that it touched a minimum of 7.6 magnitude. Soon afterwards a recovery of brightness set in, but was not carried very far. And the star now shines steadily as of the seventh magnitude, its reddish light contrasting effectively with the silvery rays of the surrounding nebula. An attempt to include its fluctuations within a cycle of 70 years has signally failed. The extent and character of the vicissitudes to which it is subject stamping it rather as a species of connecting link between periodic and temporary stars. Among the numerous topics which engaged Herschel's attention at the Cape was that of relative stellar brightness. Having contrived an astrometer, in which an artificial star, formed by the total reflection of moonlight from the base of a prism, served as a standard of comparison, he was able to estimate the luster of the natural stars examined by the distances at which the artificial object appeared equal respectively to each. He thus constructed a table of 191 of the principal stars, both in the northern and southern hemispheres, setting forth the numerical values of their apparent brightness relatively to that of Alpha Centauri, which he selected as a unit of measurement. Further, the light of the full moon being found by him to exceed that of his standard star 27,408 times, and Dr. Wollaston having shown that the light of the full moon is to that of the sun as 1 to 801,072, Zollner made the ratio 1 to 618,000, it became possible to compare stellar with solar radiance. Hence was derived, in the case of the few stars at ascertained distances, a knowledge of real luster. Alpha Centauri, for example, emits less than twice, Capella 100 times as much light as our sun. While Arcturus, at its enormous distance, must display the splendor of 1,300 such luminaries. Herschel returned to England in the spring of 1838, bringing with him a wealth of observation and discovery such as had perhaps never before been amassed in so short a time. Deserved honors awaited him. He was created a baronet on the occasion of the Queen's coronation, he had been knighted in 1831, universities and learned societies vied with each other in showering distinctions upon him. And the success of an enterprise in which scientific zeal was tinctured with an attractive flavor of adventurous romance, was justly regarded as a matter of national pride. His career as an observing astronomer was now virtually closed, and he devoted his leisure to the collection and arrangement of the abundant trophies of his father's and his own activity. The resulting great catalogue of 5,079 nebulae, including all then certainly known, published in the Philosophical Transactions for 1864, is, and will probably long remain, the fundamental source of information on the subject. But he unfortunately did not live to finish the companion work on double stars, for which he had accumulated a vast store of materials. He died at Collingwood in Kent, May 11, 1871, in the 80th year of his age, and was buried in Westminster Abbey, close beside the grave of Sir Isaac Newton. The consideration of Sir John Herschel's Cape observations brings us to the close of the period we are just now engaged in studying. They were given to the world, as already stated, 3 years before the middle of the century, and accurately represent the condition of sidereal science at that date. Looking back over the 50 years traversed, we can see at a glance how great was the stride made in the interval. Not alone was acquaintance with individual members of the cosmos vastly extended, but their mutual relations, the laws governing their movements, their distances from the earth, masses, and intrinsic luster, had begun to be successfully investigated. Begun to be, for only regarding a scarcely perceptible minority had even approximate conclusions been arrived at. Nevertheless, the whole progress of the future lay in that beginning. It was the thin end of the wedge of exact knowledge. The principle of measurement had been substituted for that of probability, a basis had been found large and strong enough to enable calculation to ascend from it to the sidereal heavens. And refinements had been introduced, fruitful in performance, but still more in promise. Thus, rather the kind than the amount of information collected was significant for the time to come, rather the methods employed than the results actually secured rendered the first half of the 19th century of epochal importance in the history of our knowledge of the stars. Footnotes. Bessel, Popular Vorlesungen, pages 6, 408. Fitted to the old transit instrument, July 11, 1772. Briefwechsel mit Olbers, page 16. R. Wolf, Gesch. Der Astron, page 518. Bessel, Pop Vorl, page 22. A new reduction of the observations upon which they were founded was undertaken in 1896 by Herman S. Davis, of the U.S. Coast Survey. Bessel, Pop Vorl, page 440. Durage, Bessel's Leben und Werken, page 28. Bonner Beobachtungen, BD, 3 v. 1859-62. Bessel, Pop Vorl, page 238. The heads of the screws applied to move the halves of the object glass in the Königsberg heliometer are of so considerable a size that 1,000th part of a revolution, equivalent to 1/20th of a second of arc, can be measured with the utmost accuracy. Main, R. A. S. MEM, Volume 12, page 53. Specola Astronomica di Palermo, Lib 6, page 10, note. Monatliche Correspondence, Volume 26, page 162. Astronomische Nachrichten, numbers 365 to 366. It should be explained that what is called the annual parallax of a star is only half its apparent displacement. In other words, it is the angle subtended at the distance of that particular star by the radius of the Earth's orbit. Astr. Nach. Numbers 401 to 402. Sir R. Ball's measurements at Dunsink gave to 61 Cygni a parallax of 0.47, Professor Pritchard obtained, by photographic determinations, one of 0.43. Additamentum in Mensuras Micrometricas, page 28. Elkin's corrected result, in 1897, for the parallax of Vega is 0.082. MEM. Roy. Astr. SOC, Volume 11, page 61. That number 21,185 in Lalande's History Cell, found by Argelander to have a proper motion of 4/734, and by Winnock a parallax of 0.511. Month. Not, Volume 18, page 289. Fund. Astr, page 309. MEM. Press. LAC. De St. Peters, T. 3. Phil. Trans, Volume XXVI, page 79. MEM. Roy. Astronomy. SOC, Volumes 28 and 32. Ibid, Volume 47, page 327. Memoirs de St. Petersburg, t. 35. Number 3, 1887, revised in Astronomy. Knock, numbers 3729-30, 1901. Astronomical Journal, numbers 213, 501. Astronomy. Knock, numbers 2999, 3000. Veröffentlichungen der Grosch. Sternwart zu Karlsruhe, BD, 4, 1892. Proceedings Amsterdam Academic of Sciences, Jan. 27, 1900. Astronomy. Jour, number 457. Ibid, numbers 276, 497. Phil. Trans, volume 96, page 230. MEM. Press. LAC. De St. Petersburg, t. 3, page 603, read February 5, 1837. Die Centralson, Astronomy. Knock, numbers 566 to 567, 1846. Sir J. Herschel, Note to Treatise on Astronomy, and Phil. Trans, Volume XI, Part 2, page 502. The position is, as Sir J. Herschel pointed out, Outlines of Astronomy, page 631, 10th edition. Placed beyond the range of reasonable probability by its remoteness, fully 26 degrees, from the galactic plane. Madler and Westermann's Jahrbuch, 1867, page 615. Letter from Bessel to Sir J. Herschel, month. Not, volume 6, page 139. Wolf, Gesch. D. Astronomy, p. 743, note. Astronomy. Knock, numbers 745 to 748. Astronomy. Jour, number 440. Adopting Elkin's revised parallax for Procyon of 0-325. Astronomy. Knock, numbers 1371 to 1373. Über die Doppelstern, Bericht, 1827, page 22. Über die Doppelstern, Bericht, 1827, page 25. Menturium ICR, page 99. Stellarum fixarum imprimus duplicium et multiplicum positions medii, pages CXC, Chi. For instance, the southern stars, 36A Ophiuchi, itself double, and 30 Scorpii, which are 12-10 apart. Ibid, P. Chi. Stellarum fixarum, etc., P. Cliii. Etudes d'Astronomie Stellaire, 1847, page 82. Ibid, page 86. See Encke's Criticism in Astronomy. Knock, number 622. Phil. Trans, volume XIV, part 3, 1824. Con D. Temps, 1830. R.A.S. MEM, volume 5, page 178, 1833. Astronomy. And Astrophysics, volume 12, page 581. Popular Astronomy, volume 1, page 243. Phil. Trans, volume XI, and Results, etc., Introd. Results of astronomical observations made during the years 1834-8 at the Cape of Good Hope. Results, etc., page 147. See Proctor's Universe of Stars, page 92. A Treatise on Astronomy, 1833, page 406. Results, etc., page 139. Ibid, pages 24, 142. Phil. Trans, volume XI, page 503. Results, etc., page 136. Loomis, month. Not, volume 29, page 298. See the author's System of the Stars, pages 116 to 120. Outlines of Astronomy, App I. Phil. Trans, Volume 6, page 27. Dr. Dreyer's New General Catalogue, published in 1888 as Volume 49. Of the Royal Astronomical Society's Memoirs, is an enlargement of Herschel's work. It includes 7,840 entries, and was supplemented, in 1895, by an index catalogue of 1,529 nebulae discovered 1888 to 1894. MEM. R.A.S., Volume 51. A list of 10,320 composite stars was drawn out by him in order of right ascension, and has been published in Volume 40. Of MEM. R.A.S., but the data requisite for their formation into a catalogue were not forthcoming. See Mayne's and Pritchard's preface to above, and Duncan's obituary notices, page 73. Chapter 3. Progress of knowledge regarding the Sun. The discovery of sunspots in 1610 by Fabricius and Galileo first opened a way for inquiry into the solar constitution, but it was long before that way was followed with system or profit. The seeming irregularity of the phenomena discouraged continuous attention, casual observations were made the basis of arbitrary conjectures, and real knowledge received little or no increase. In 1620 we find Jean Tard, canon of Sarlat, arguing that because the sun is the eye of the world, and the eye of the world cannot suffer from ophthalmia, therefore the appearances in question must be due not to actual specks or stains on the bright solar disk, but to the transits of a number of small planets across it. To this new group of heavenly bodies he gave the name of Borbonia Sidera, and they were claimed in 1633 for the House of Habsburg, under the title of Austriaca Sidera, by Father Malapertius, a Belgian Jesuit. A similar view was temporarily maintained against Galileo by the justly celebrated Father Scheiner of Ingolstadt, and later by William Gascoigne, the inventor of the micrometer. But most of those who were capable of thinking at all on such subjects, and they were but few, adhered either to the cloud theory or to the slag theory of sunspots. The first was championed by Galileo, the second by Simon Marius, astronomer and physician, to the brother Margraves of Brandenburg. The latter opinion received a further notable development from the fact that in 1618, a year remarkable for the appearance of 3 bright comets, the sun was almost free from spots. Whence it was inferred that the cindery refuse from the great solar conflagration, which usually appeared as dark blotches on its surface, was occasionally thrown off in the form of comets, leaving the sun, like a snuff taper, to blaze with renewed brilliancy. In the following century, Derham gathered from observations carried on during the years 1703 to 11, that the spots on the sun are caused by the eruption of some new volcano therein, which at first pouring out a prodigious quantity of smoke and other opacous matter, causeth the spots. And as that fuliginous matter decayeth and spendeth itself, and the volcano at last becomes more torrid and flaming, so the spots decay, and grow to umbræ, and at last to faculae. The view, confidently upheld by Lalande, that spots were rocky elevations uncovered by the casual ebbing of a luminous ocean, the surrounding penumbræ representing shoals or sandbanks, had even less to recommend it than Derham's volcanic theory. Both were, however, significant of a growing tendency to bring solar phenomena within the compass of terrestrial analogies. For 164 years, then, after Galileo first leveled his telescope at the setting sun, next to nothing was learned as to its nature. And the facts immediately ascertained, of its rotation on an axis nearly erect to the plane of the ecliptic, in a period of between 25 and 26 days. And of the virtual limitation of the spots to a so-called royal zone extending some 30 degrees north and south of the solar equator, gained little either in precision or development from 5 generations of astronomers. But in November, 1769, a spot of extraordinary size engaged the attention of Alexander Wilson, professor of astronomy in the University of Glasgow. He watched it day by day, and to good purpose. As the great globe slowly revolved, carrying the spot towards its western edge, he was struck with the gradual contraction and final disappearance of the penumbra on the side next the center of the disk. And when on the 6th of December the same spot re-emerged on the eastern limb, he perceived, as he had anticipated, that the shady zone was now deficient on the opposite side, and resumed its original completeness as it returned to a central position. In other spots subsequently examined by him, similar perspective effects were visible, and he proved in 1774, by strict geometrical reasoning, that they could only arise in vast photospheric excavations. It was not, indeed, the first time that such a view had been suggested. Father Scheiner's later observations plainly foreshadowed it. A conjecture to the same effect was emitted by Leonard Rost of Nuremberg early in the 18th century. Both by Lahire in 1703 and by J. Cassini in 1719 spots had been seen as notches on the solar limb, while in 1770 Pastor Schulin of Essingen, from the careful study of phenomena similar to those noted by Wilson, concluded their depressed nature. Modern observations, nevertheless, prove those phenomena to be by no means universally present. Wilson's general theory of the sun was avowedly tentative. It took the modest form of an interrogatory. Is it not reasonable to think, he asks, that the great and stupendous body of the sun is made up of two kinds of matter, very different in their qualities? That by far the greater part is solid and dark, and that this immense and dark globe is encompassed with a thin covering of that resplendent substance from which the sun would seem to derive the whole of his vivifying heat and energy? He further suggests that the excavations or spots may be occasioned by the working of some sort of elastic vapor which is generated within the dark globe, and that the luminous matter, being in some degree fluid, and being acted upon by gravity, tends to flow down and cover the nucleus. From these hints, supplemented by his own diligent observations and sagacious reasonings, Herschel elaborated a scheme of solar constitution which held its ground until the physics of the sun were revolutionized by the spectroscope. A cool, dark, solid globe, its surface diversified with mountains and valleys, clothed in luxuriant vegetation, and richly stored with inhabitants, protected by a heavy cloud canopy from the intolerable glare of the upper luminous region, where the dazzling coruscations of a solar aurora some thousands of miles in depth evolved the stores of light and heat which vivify our world. Such was the central luminary which Herschel constructed with his wonted ingenuity, and described with his wonted eloquence. This way of considering the sun and its atmosphere, he says, removes the great dissimilarity we have hitherto been used to find between its condition and that of the rest of the great bodies of the solar system. The sun, viewed in this light, appears to be nothing else than a very eminent, large, and lucid planet, evidently the first, or, in strictness of speaking, the only primary one of our system, all others being truly secondary to it. Its similarity to the other globes of the solar system with regard to its solidity, its atmosphere, and its diversified surface, the rotation upon its axis, and the fall of heavy bodies, leads us on to suppose that it is most probably also inhabited, like the rest of the planets, by beings whose organs are adapted to the peculiar circumstances of that vast globe. We smile at conclusions which our present knowledge condemns as extravagant and impossible, but such incidental flights of fancy in no way derogate from the high value of Herschel's contributions to solar science. The cloud-like character which he attributed to the radiant shell of the sun, first named by Schroeder the photosphere, is borne out by all recent investigations. He observed its mottled or corrugated aspect, resembling, as he described it, the roughness on the rind of an orange, showed that faculae are elevations or heaped-up ridges of the disturbed photospheric matter, and threw out the idea that spots may ensue from an excess of the ordinary luminous emissions. A certain imperial gas was, he supposed, very much as Wilson had done, generated in the body of the sun, and rising everywhere by reason of its lightness, made for itself, when in moderate quantities, small openings or pores, abundantly visible as dark points on the solar disk. But should an uncommon quantity be formed, it will, he maintained, burst through the planetary regions of clouds, and thus will produce great openings. Then, spreading itself above them, it will occasion large shallows, penumbræ, and mixing afterwards gradually with other superior gases, it will promote the increase, and assist in the maintenance, of the general luminous phenomena. This partial anticipation of the modern view that the solar radiations are maintained by some process of circulation within the solar mass, was reached by Herschel through prolonged study of the phenomena in question. The novel and important idea contained in it, however, it was at that time premature to attempt to develop. But though many of the subtler suggestions of Herschel's genius passed unnoticed by his contemporaries, the main result of his solar researches was an unmistakable one. It was nothing less than the definitive introduction into astronomy of the paradoxical conception of the central fire and hearth of our system as a cold, dark, terrestrial mass, wrapped in a mantle of innocuous radiance, an earth, so to speak. Within, a sun without. Let us pause for a moment to consider the value of this remarkable innovation. It certainly was not a step in the direction of truth. On the contrary, the crude notions of Anaxagoras and Zeno approached more nearly to what we now know of the sun than the complicated structure devised for the happiness of a nobler race of beings than our own by the benevolence of 18th-century astronomers. And yet it undoubtedly constituted a very important advance in science. It was the first earnest attempt to bring solar phenomena within the compass of a rational system, to put together into a consistent whole the facts ascertained. To fabricate, in short, a solar machine that would in some fashion work. It is true that the materials were inadequate and the design faulty. The resulting construction has not proved strong enough to stand the wear and tear of time and discovery, but has had to be taken to pieces and remodeled on a totally different plan. But the work was not therefore done in vain. None of Bacon's aphorisms show a clearer insight into the relations between the human mind and the external world than that which declares truth to emerge sooner from error than from confusion. A definite theory, even if a false one, gives holding ground to thought. Facts acquire a meaning with reference to it. It affords a motive for accumulating them and a means of coordinating them. It provides a framework for their arrangement, and a receptacle for their preservation, until they become too strong and numerous to be any longer included within arbitrary limits, and shatter the vessel originally framed to contain them. Such was the purpose subserved by Herschel's theory of the sun. It helped to clarify ideas on the subject. The turbid sense of groping and viewless ignorance gave place to the lucidity of a possible scheme. The persuasion of knowledge is a keen incentive to its increase. Few men care to investigate what they are obliged to admit themselves entirely ignorant of, but once started on the road of knowledge, real or supposed, they are eager to pursue it. By the promulgation of a confident and consistent view regarding the nature of the sun, accordingly, research was encouraged, because it was rendered hopeful. And inquirers were shown a path leading indefinitely onwards where an impassable thicket had before seemed to bar the way. We have called the terrestrial theory of the sun's nature and innovation, and so, as far as its general acceptance is concerned, it may justly be termed, but, like all successful innovations, it was a long time brewing. It is extremely curious to find that Herschel had a predecessor in its advocacy who never looked through a telescope, nor, indeed, imagined the possibility of such an instrument, who knew nothing of sunspots. Was still, mistaken assertions to the contrary notwithstanding, in the bondage of the geocentric system, and regarded nature from the lofty standpoint of an idealist philosophy. This was the learned and enlightened Cardinal Cusa, a fisherman's son from the banks of the Moselle, whose distinguished career in the church and in literature extended over a considerable part of the 15th century, 1401–64. In his singular treatise De Docta Ignorantia, one of the most notable literary monuments of the early Renaissance, the following passage occurs: "To a spectator on the surface of the sun, the splendor which appears to us would be invisible. Since it contains, as it were, an earth for its central mass, with a circumferential envelope of light and heat, and between the two an atmosphere of water and clouds and translucent air." The luminary of Herschel's fancy could scarcely be more clearly portrayed. Some added words, however, betray the origin of the cardinal's idea. The earth also, he says, would appear as a shining star to any one outside the fiery element. It was, in fact, an extension to the sun of the ancient elemental doctrine. But an extension remarkable at that period, as premonitory of the tendency, so powerfully developed by subsequent discoveries, to assimilate the orbs of heaven to the model of our insignificant planet, and to extend the brotherhood of our system and our species to the farthest limit of the visible or imaginable universe. In later times we find Flamsteed communicating to Newton, March 7, 1681, his opinion, that the substance of the sun is terrestrial matter, his light but the liquid menstruum encompassing him. Bode in 1776 arrived independently at the conclusion that the sun is neither burning nor glowing, but in its essence a dark planetary body, composed like our earth of land and water, varied by mountains and valleys, and enveloped in a vaporous atmosphere. And the learned in general applauded and acquiesced. The view, however, was in 1787 still so far from popular, that the holding of it was alleged as a proof of insanity in Dr. Eliot when accused of a murderous assault on Miss Boydell. His friend Dr. Symonds stated on his behalf that he had received from him in the preceding January a letter giving evidence of a deranged mind, wherein he asserted that the sun is not a body of fire, as hath been hitherto supposed, but that its light proceeds from a dense and universal aurora, which may afford ample light to the inhabitants of the surface beneath, and yet be at such a distance aloft as not to annoy them. No objection, he saith, to that great luminaries being inhabited, vegetation may obtain there as well as with us. There may be water and dry land, hills and dales, rain and fair weather. And as the light, so the season must be eternal, consequently it may easily be conceived to be by far the most blissful habitation of the whole system. The recorder, nevertheless, objected that if an extravagant hypothesis were to be adduced as proof of insanity, the same might hold good with regard to some other speculators, and desired Dr. Symonds to tell the court what he thought of the theories of Burnet and Buffon. 8 years later, this same extravagant hypothesis, backed by the powerful recommendation of Sir William Herschel, obtained admittance to the venerable halls of science, there to abide undisturbed for nearly 7 decades. Individual objectors, it is true, made themselves heard, but their arguments had little effect on the general body of opinion. Ruder blows were required to shatter an hypothesis flattering to human pride of invention in its completeness, in the plausible detail of observations by which it seemed to be supported, and in its condescension to the natural pleasure in discovering resemblance under all but total dissimilarity. Sir John Herschel included among the results of his multifarious labors at the Cape of Good Hope a careful study of the sunspots conspicuously visible towards the end of the year 1836 and in the early part of 1837. They were remarkable, he tells us, for their forms and arrangement, as well as for their number and size. One group, measured on the 29th of March in the latter year, covering, apart from what may be called its outlying dependencies, the vast area of 5 square minutes or 3,780 million square miles. We have at present to consider, however, not so much these observations in themselves, as the chain of theoretical suggestions by which they were connected. The distribution of spots, it was pointed out, on 2 zones parallel to the equator, showed plainly their intimate connection with the solar rotation, and indicated as their cause fluid circulations analogous to those producing the terrestrial trade and anti-trade winds. The spots, in this view of the subject, he went on to say, would come to be assimilated to those regions on the earth's surface where, for the moment, hurricanes and tornadoes prevail. The upper stratum being temporarily carried downwards, displacing by its impetus the 2 strata of luminous matter beneath, the upper of course to a greater extent than the lower, and thus wholly or partially denuding the opaque surface of the sun below. Such processes cannot be unaccompanied by vorticose motions, which, left to themselves, die away by degrees and dissipate, with the peculiarity that their lower portions come to rest more speedily than their upper, by reason of the greater resistance below, as well as the remoteness from the point of action, which lies in a higher region, so that their centers, as seen in our waterspouts, which are nothing but small tornadoes, appear to retreat upwards. Now this agrees perfectly with what is observed during the obliteration of the solar spots, which appear as if filled in by the collapse of their sides, the penumbra closing in upon the spot and disappearing after it. But when it comes to be asked whether a cause can be found by which a diversity of solar temperature might be produced corresponding with that which sets the currents of the terrestrial atmosphere in motion, we are forced to reply that we know of no such cause. For Sir John Herschel's hypothesis of an increased retention of heat at the sun's equator, due to the slightly spheroidal or bulging form of its outer atmospheric envelope, assuredly gives no sufficient account of such circulatory movements as he supposed to exist. Nevertheless, the view that the sun's rotation is intimately connected with the formation of spots is so obviously correct, that we can only wonder it was not thought of sooner. While we are even now unable to explain with any certainty how it is so connected. Mere scrutiny of the solar surface, however, is not the only means of solar observation. We have a satellite, and that satellite from time to time acts most opportunely as a screen, cutting off a part or the whole of those dazzling rays in which the master orb of our system veils himself from over-curious regards. The importance of eclipses to the study of the solar surroundings is of comparatively recent recognition. Nevertheless, much of what we know concerning them has been snatched, as it were, by surprise under favor of the moon. In former times, the sole astronomical use of such incidents was the correction of the received theories of the solar and lunar movements. The precise time of their occurrence was the main fact to be noted, and subsidiary phenomena received but casual attention. Now, their significance as a geometrical test of tabular accuracy is altogether overshadowed by the interest attaching to the physical observations for which they afford propitious occasions. This change may be said to date, in its pronounced form, from the great eclipse of 1842. Although a necessary consequence of the general direction taken by scientific progress, it remains associated in a special manner with the name of Francis Baily. The philosopher of Newbury was by profession a London stockbroker, and a highly successful one. Nevertheless, his services to science were numerous and invaluable, though not of the brilliant kind which attract popular notice. Born at Newbury in Berkshire, April 28, 1774, and placed in the city at the age of 14, he derived from the acquaintance of Dr. Priestley a love of science which never afterwards left him. It was, however, no passion such as flames up in the brain of the destined discoverer, but a regulated inclination, kept well within the bounds of an actively pursued commercial career. After traveling for a year or two in what were then the wilds of North America, he went on the Stock Exchange in 1799, and earned during 24 years of assiduous application to affairs a high reputation for integrity and ability, to which corresponded an ample fortune. In the meantime the Astronomical Society, largely through his co-operation, had been founded. He had for 3 years acted as its secretary, and he now felt entitled to devote himself exclusively to a subject which had long occupied his leisure hours. He accordingly in 1825 retired from business, purchased a house in Tavistock Place, and fitted up there a small observatory. He was, however, by preference a computator rather than an observer. What Sir John Herschel calls the archaeology of practical astronomy found in him an especially zealous student. He re-edited the star catalogues of Ptolemy, Ulugh Bey, Tycho Brahe, Hevelius, Halley, Flamsteed, Lacaille, and Mayer. Calculated the eclipse of Thales and the eclipse of Agathocles, and vindicated the memory of the first astronomer royal. But he was no less active in meeting present needs than in revising past performances. The subject of the reduction of observations, then, as we have already explained, in a state of deplorable confusion, attracted his most earnest attention. And he was close on the track of Bessel when made acquainted with the method of simplification devised at Königsberg. Anticipated as an inventor, he could still be of eminent use as a promoter of these valuable improvements. And, carrying them out on a large scale in the Star Catalogue of the Astronomical Society, published in 1827, he put, in the words of Herschel, the astronomical world in possession of a power which may be said, without exaggeration, to have changed the face of sidereal astronomy. His reputation was still further enhanced by his renewal, with vastly improved apparatus, of the method, first used by Henry Cavendish in 1797–98, for determining the density of the earth. From a series of no less than 2,153 delicate and difficult experiments, conducted at Tavistock Place during the years 1838–42, he concluded our planet to weigh 5/66 as much as a globe of water of the same bulk. And this result slightly corrected is still accepted as a very close approximation of the truth. What we have thus glanced at is but a fragment of the truly surprising mass of work accomplished by Bailey in the course of a variously occupied life. A rare combination of qualities fitted him for his task. Unvarying health, undisturbed equanimity, methodical habits, the power of directed and sustained thought, combined to form in him an intellectual toiler of the surest, though not perhaps of the highest quality. He was in harness almost to the end. He was destined scarcely to know the miseries of enforced idleness or of consciously failing powers. In 1842 he completed the laborious reduction of Lalande's great catalogue, undertaken at the request of the British Association, and was still engaged in seeing it through the press when he was attacked with what proved his last. As it was probably his first serious illness. He, however, recovered sufficiently to attend the Oxford commemoration of July 2, 1844, where an honorary degree of D.C.L. was conferred upon him in company with Airy and Struve. But sank rapidly after the effort, and died on the 30th of August following, at the age of 70, lamented and esteemed by all who knew him. It is now time to consider his share in the promotion of solar research. Eclipses of the sun, both ancient and modern, were a speciality with him, and he was fortunate in those which came under his observation. Such phenomena are of three kinds: partial, annular, and total. In a partial eclipse, the moon, instead of passing directly between us and the sun, slips by, as it were, a little on one side, thus cutting off from our sight only a portion of his surface. An annular eclipse, on the other hand, takes place when the moon is indeed centrally interposed, but falls short of the apparent size required for the entire concealment of the solar disk, which consequently remains visible as a bright ring or annulus, even when the obscuration is at its height. In a total eclipse, on the contrary, the sun completely disappears behind the dark body of the moon. The difference of the two latter varieties is due to the fact that the apparent diameter of the sun and moon are so nearly equal as to gain alternate preponderance one over the other through the slight periodical changes in their respective distances from the earth. Now, on the 15th of May, 1836, an annular eclipse was visible in the northern parts of Great Britain, and was observed by Bailey at Inchbonny, near Jedburgh. It was here that he saw the phenomenon which obtained the name of Bailey's beads, from the notoriety conferred upon it by his vivid description. When the cusps of the sun, he writes, were about 40 degrees asunder, a row of lucid points, like a string of bright beads, irregular in size and distance from each other, suddenly formed round that part of the circumference of the moon that was about to enter on the sun's disk. Its formation, indeed, was so rapid that it presented the appearance of having been caused by the ignition of a fine train of gunpowder. Finally, as the moon pursued her course, the dark intervening spaces, which, at their origin, had the appearance of lunar mountains in high relief, and which still continued attached to the sun's border, were stretched out into long, black, thick, parallel lines, joining the limbs of the sun and moon. When all at once they suddenly gave way, and left the circumference of the sun and moon in those points, as in the rest, comparatively smooth and circular, and the moon perceptibly advanced on the face of the sun. These curious appearances were not an absolute novelty. Weber in 1791, and von Zach in 1820, had seen the beads. Van Swinden had described the belts or threads. These last were, moreover, as Bailey clearly perceived, completely analogous to the black ligament which formed so troublesome a feature in the transits of Venus in 1764 and 1769, and which, to the regret and confusion, though no longer to the surprise of observers, was renewed in that of 1874. The phenomenon is largely an effect of what is called irradiation, by which a bright object seems to encroach upon a dark one, but under good atmospheric and instrumental conditions it becomes inconspicuous. The beads must always appear when the projected lunar edge is serrated with mountains. In Bailey's observation, they were exaggerated and distorted by an irradiative clinging together of the limbs of sun and moon. The immediate result, however, was powerfully to stimulate attention to solar eclipses in their physical aspect. Never before had an occurrence of the kind been expected so eagerly or prepared for so actively as that which was total over Central and Southern Europe on the 8th of July, 1842. Astronomers hastened from all quarters to the favored region. The Astronomer Royal, Airy, repaired to Turin, Bailey to Pavia, Otto Struve threw aside his work amidst the stars at Pulkowa, and went south as far as Leipzig. Schumacher travelled from Altona to Vienna, Arago from Paris to Perpignan. Nor did their trouble go unrewarded. The expectations of the most sanguine were outdone by the wonders disclosed. Bailey, to whose narrative we again have recourse, had set up his Dollond's achromatic in an upper room of the University of Pavia, and was eagerly engaged in noting a partial repetition of the singular appearances seen by him in 1836. When he was astounded by a tremendous burst of applause from the streets below, and at the same moment was electrified at the sight of one of the most brilliant and splendid phenomena that can well be imagined. For at that instant the dark body of the moon was suddenly surrounded with a corona, or kind of bright glory similar in shape and relative magnitude to that which painters draw around the heads of saints, and which by the French is designated an aureole. Pavia contains many thousand inhabitants, the major part of whom were, at this early hour, walking about the streets and squares or looking out of windows, in order to witness this long-talked-of phenomenon. And when the total obscuration took place, which was instantaneous, there was a universal shout from every observer, which made the welkin ring, and, for the moment, withdrew my attention from the object with which I was immediately occupied. I had indeed anticipated the appearance of a luminous circle round the moon during the time of total obscurity. But I did not expect, from any of the accounts of preceding eclipses that I had read, to witness so magnificent an exhibition as that which took place. The breadth of the corona, measured from the circumference of the moon, appeared to me to be nearly equal to half the moon's diameter. It had the appearance of brilliant rays. The light was most dense close to the border of the moon, and became gradually and uniformly more attenuate as its distance therefrom increased, assuming the form of diverging rays in a rectilinear line, which at the extremity were more divided, and of an unequal length. So that in no part of the corona could I discover the regular and well-defined shape of a ring at its outer margin. It appeared to me to have the sun for its center, but I had no means of taking any accurate measures for determining this point. Its color was quite white, not pearl color, nor yellow, nor red, and the rays had a vivid and flickering appearance, somewhat like that which a gaslight illumination might be supposed to assume if formed into a similar shape. Splendid and astonishing, however, as this remarkable phenomenon really was, and although it could not fail to call forth the admiration and applause of every beholder, yet I must confess that there was at the same time something in its singular and wonderful appearance that was appalling. And I can readily imagine that uncivilized nations may occasionally have become alarmed and terrified at such an object, more especially at times when the true cause of the occurrence may have been but faintly understood, and the phenomenon itself wholly unexpected. But the most remarkable circumstance attending the phenomenon was the appearance of three large protuberances apparently emanating from the circumference of the moon, but evidently forming a portion of the corona. They had the appearance of mountains of a prodigious elevation, their color was red, tinged with lilac or purple, perhaps the color of the peach blossom would more nearly represent it. They somewhat resembled the snowy tops of the Alpine mountains when colored by the rising or setting sun. They resembled the Alpine mountains also in another respect, inasmuch as their light was perfectly steady, and had none of that flickering or sparkling motion so visible in other parts of the corona. All the three projections were of the same roseate cast of color, and very different from the brilliant vivid white light that formed the corona, but they differed from each other in magnitude. The whole of these three protuberances were visible even to the last moment of total obscuration, at least, I never lost sight of them when looking in that direction. And when the first ray of light was admitted from the sun, they vanished, with the corona, altogether, and daylight was instantaneously restored. Notwithstanding unfavorable weather, the red flames were perceived with little less clearness and no less amazement from the Superga than at Pavia, and were even discerned by Mr. Airy with the naked eye. Their form, the Astronomer Royal wrote, was nearly that of saw teeth in the position proper for a circular saw turned round in the same direction in which the hands of a watch turn. Their color was a full lake red, and their brilliancy greater than that of any other part of the ring. The height of these extraordinary objects was estimated by Arago at 2 minutes of arc, representing, at the sun's distance, an actual elevation of 54,000 miles. When carefully watched, the rose flush of their illumination was perceived to fade through violet to white as the light returned, the same changes in a reversed order having accompanied their first appearance. Their forms, however, during about 3 minutes of visibility, showed no change, although of so apparently unstable a character as to suggest to Arago mountains on the point of crumbling into ruins, through top-heaviness. The corona, both as to figure and extent, presented very different appearances at different stations. This was no doubt due to varieties in atmospheric conditions. At the Superga, for instance, all details of structure seem to have been effaced by the murky air, only a comparatively feeble ring of light being seen to encircle the moon. Elsewhere, a brilliant radiated formation was conspicuous, spreading at 4 opposite points into 4 vast luminous expansions, compared to feather plumes or aigrettes. Arago at Perpignan noticed considerable irregularities in the divergent rays. Some appeared curved and twisted, a few lay across the others, in a direction almost tangential to the moon's limb, the general effect being described as that of a hank of thread in disorder. At Leipzig, where the sun stood much higher above the horizon than in Italy or France, the corona showed with surprising splendor. Its apparent extent was judged by Struve to be no less than 25 minutes, more than 6 times Airy's estimate, while the great plumes spread their radiance to 3 or 4 degrees from the dark lunar edge. So dazzling was the light that many well-instructed persons denied the totality of the eclipse. Nor was the error without precedent, although the appearances attending respectively a total and an annular eclipse are in reality wholly dissimilar. In the latter case, the surviving ring of sunlight becomes so much enlarged by irradiation, that the interposed dark lunar body is reduced to comparative insignificance, or even invisibility. Maclaurin tells us that during an eclipse of this character which he observed at Edinburgh in 1737, gentlemen by no means short-sighted declared themselves unable to discern the moon upon the sun without the aid of a smoked glass. And Bailly, who, however, was short-sighted, could distinguish, in 1836, with the naked eye, no trace of the globe of purple velvet, which the telescope revealed as projected upon the face of the sun. Moreover, the diminution of light is described by him as little more than might be caused by a temporary cloud passing over the sun. The birds continued in full song, and one cock in particular was crowing with all his might while the annulus was forming. Very different were the effects of the eclipse of 1842, as to which some interesting particulars were collected by Arago. Beasts of burthen, he tells us, paused in their labor, and could by no amount of punishment be induced to move until the sun reappeared. Birds and beasts abandoned their food, linnets were found dead in their cages, even ants suspended their toil. Diligence horses, on the other hand, seemed as insensible to the phenomenon as locomotives. The convolvulus and some other plants closed their leaves, but those of the mimosa remained open. The little light that remained was of a livid hue. One observer described the general coloration as resembling the lees of wine, but human faces showed pale olive or greenish. We may, then, rest assured that none of the remarkable obscurations recorded in history were due to eclipses of the annular kind. The existence of the corona is no modern discovery. Indeed, it is too conspicuous an apparition to escape notice from the least attentive or least practiced observer of a total eclipse. Nevertheless, explicit references to it are rare in early times. Plutarch, however, speaks of a certain splendor, compassing round the hidden edge of the sun, as a regular feature of total eclipses, and the corona is expressly mentioned in a description of an eclipse visible at Corfu in 968 AD. The first to take the phenomenon into scientific consideration was Kepler. He showed, from the orbital positions at the time of the sun and moon, that an eclipse observed by Clavius at Rome in 1567 could not have been annular, as the dazzling coronal radiance visible during the obscuration had caused it to be believed. Although he himself never witnessed a total eclipse of the sun, he carefully collected and compared the remarks of those more fortunate, and concluded that the ring of flame-like splendor seen on such occasions was caused by the reflection of the solar rays from matter condensed in the neighborhood either of the sun or moon. To the solar explanation he gave his own decided preference, but, with one of those curious flashes of half-prophetic insight characteristic of his genius, declared that it should be laid by ready for use, not brought into immediate requisition. So literally was his advice acted upon, that the theory, which we now know to be, broadly speaking, the correct one, only emerged from the repository of anticipated truths after 236 years of almost complete retirement. And even then timorously and with hesitation. The first eclipse of which the attendant phenomena were observed with tolerable exactness was that which was central in the south of France, May 12, 1706. Cassini then put forward the view that the crown of pale light seen round the lunar disk was caused by the illumination of the zodiacal light, but it failed to receive the attention which, as a step in the right direction, it undoubtedly merited. 9 years later we meet with Halley's comments on a similar event, the first which had occurred in London since March 20, 1140. By 9 in the morning of May 3, 1715, the obscuration, he tells us, was about 10 digits, when the face and color of the sky began to change from perfect serene azure blue to a more dusky livid color, having an eye of purple intermixed. A few seconds before the sun was all hid, there discovered itself round the moon a luminous ring, about a digit or perhaps a tenth part of the moon's diameter in breadth. It was of a pale whiteness, or rather pearl color, seeming to be a little tinged with the colors of the iris, and to be concentric with the moon, whence I concluded it the moon's atmosphere. But the great height thereof, far exceeding our earth's atmosphere, and the observation of some, who found the breadth of the ring to increase on the west side of the moon as immersion approached, together with the contrary sentiments of those whose judgment I shall always revere, Newton is most probably referred to, makes me less confident, especially in a matter whereto I confess I gave not all the attention requisite. He concludes by declining to decide whether the enlightened atmosphere, which the appearance, in all respects resembled, belonged to sun or moon. A French academician, who happened to be in London at the time, was less guarded in expressing an opinion. The Chevalier de Louville declared emphatically for the lunar atmospheric theory of the corona, and his authority carried great weight. It was, however, much discredited by an observation made by Maraldi in 1724, to the effect that the luminous ring, instead of traveling with the moon, was traversed by it. This was in reality decisive, though, as usual, belief lagged far behind demonstration. In 1715 a novel explanation had been offered by Delisle and Lahire, supported by experiments regarded at the time as perfectly satisfactory. The aureole around the eclipsed sun, they argued, is simply a result of the diffraction, or apparent bending of the sunbeams that graze the surface of the lunar globe, an effect of the same kind as the colored fringes of shadows. And this view prevailed amongst men of science until, and even after, Brewster showed, with clear and simple decisiveness, that such an effect could by no possibility be appreciable at our distance from the moon. Don José Joaquim de Ferrer, however, who observed a total eclipse of the sun at Kinderhook, in the state of New York, on June 16, 1806, ignoring this refined optical rationale, considered two alternative explanations of the phenomenon as alone possible. The bright ring round the moon must be due to the illumination either of a lunar or of a solar atmosphere. If the former, he calculated that it should have a height 50 times that of the Earth's gaseous envelope. Such an atmosphere, he rightly concluded, cannot belong to the moon, but must without any doubt belong to the sun. But he stood alone in this unhesitating assertion. The importance of the problem was first brought fully home to astronomers by the eclipse of 1842. The brilliant and complex appearance which on that occasion challenged the attention of so many observers, demanded and received, no longer the casual attention hitherto bestowed upon it, but the most earnest study of those interested in the progress of science. Nevertheless, it was only by degrees, and through a process of exclusions, to use a Baconian phrase, that the corona was put in its right place as a solar appendage. As every other available explanation proved inadmissible and dropped out of sight, the broad presentation of fact remained, which, though of sufficiently obvious interpretation, was long and persistently misconstrued. Nor was it until 1869 that absolutely decisive evidence on the subject was forthcoming, as we shall see further on. Sir John Herschel, writing to his venerable aunt, relates that when the brilliant red flames burst into view behind the dark moon on the morning of the 8th of July, 1842, the populace of Milan, with the usual inconsequence of a crowd, raised the shout, "Es leben die Astronomen." In reality, none were less prepared for their apparition than the class to whom the applause due to the magnificent spectacle was thus adjudged. And in some measure through their own fault, for many partial hints and some distinct statements from earlier observers had given unheeded notice that some such phenomenon might be expected to attend a solar eclipse. What we now call the chromosphere is an envelope of glowing gases, by which the sun is completely covered, and from which the prominences are emanations, eruptive or flame-like. Now, continual indications of the presence of this fire ocean had been detected during eclipses in the 18th and 19th centuries. Captain Stannyan, describing in a letter to Flamsteed an occurrence of the kind witnessed by him at Bern on May 1, OS, 1706, says that the sun's getting out of the eclipse was preceded by a blood-red streak of light from its left limb. A precisely similar appearance was noted by both Halley and de Louville in 1715. During annular eclipses by Lord Aberdour in 1737, and by Short in 1748, the tint of the ruby border being, however, subdued to brown or dusky red by the surviving sunlight. While observations identical in character were made at Amsterdam in 1820, at Edinburgh by Henderson in 1836, and at New York in 1838. Flames, or prominences, if more conspicuous, are less constant in their presence than the glowing stratum from which they spring. The first to describe them was a Swedish professor named Vicenius, who observed a total eclipse at Gothenburg, May 2, OS, 1733. His astonishment equaled his admiration when he perceived, just outside the edge of the lunar disk, and suspended, as it seemed, in the coronal atmosphere, 3 or 4 reddish spots or clouds, one of which was so large as to be detected with the naked eye. As to their nature, he did not even offer a speculation, further than by tacitly referring them to the moon. The observation was repeated in 1778 by a Spanish admiral, but with no better success in directing efficacious attention to the phenomenon. Don Antonio Ulloa was on board his ship the Espagne in passage from the Azores to Cape St. Vincent on the 24th of June in that year, when a total eclipse of the sun occurred, of which he has left a valuable description. His notices of the corona are full of interest. But what just now concerns us is the appearance of a red luminous point near the edge of the moon, which gradually increased in size as the moon moved away from it, and was visible during about a minute and a quarter. He was satisfied that it belonged to the sun because of its fiery color and growth in magnitude, and supposed that it was occasioned by some crevice or inequality in the moon's limb, through which the solar light penetrated. Allusions less precise, both prior and subsequent, which it is now easy to refer to similar objects, such as the slender columns of smoke seen by Ferrer, might be detailed. But the evidence already adduced suffices to show that the prominences viewed with such amazement in 1842 were no unprecedented or even unusual phenomenon. It was more important, however, to decide what was their nature than whether their appearance might have been anticipated. They were generally, and not very incorrectly, set down as solar clouds. Arago believed them to shine by reflected light, but the Abbé Padel rightly considered them to be self-luminous. Writing in a Montpellier paper of July 16, 1842, he declared that we had now become assured of the existence of a third or outer solar envelope, composed of a glowing substance of a bright rose tint, forming mountains of prodigious elevation, analogous in character to the clouds piled above our horizons. This first distinct recognition of a very important feature of our great luminary was probably founded on an observation made by Burrard at Toulon during the then recent eclipse, of a very fine red band, irregularly dentelated, or, as it were, crevassed here and there, encircling a large arc of the moon's circumference. It can hardly, however, be said to have attracted general notice until July 28, 1851. On that day a total eclipse took place, which was observed with considerable success in various parts of Sweden and Norway by a number of English astronomers. Mr. Hind saw, on the south limb of the moon, a long range of rose-colored flames, described by Dawes as a low ridge of red prominences, resembling in outline the tops of a very irregular range of hills. Airy termed the portion of this rugged lines of projections visible to him the Sierra, and was struck with its brilliant light and nearly scarlet color. Its true character of a continuous solar envelope was inferred from these data by Grant, Swan, and Littrove, and was by Father Secchi, after the great eclipse of 1860, formally accepted as established. Several prominences of remarkable forms, especially one variously compared to a Turkish scimitar, a sickle, and a boomerang, were seen in 1851. In connection with them two highly significant circumstances were pointed out. First, that of the approximate coincidence between their positions and those of sunspots previously observed. Next, that the moon passed over them, leaving them behind, and revealing successive portions as she advanced. This latter perfectly well-attested fact was justly considered by the Astronomer Royal and others as affording absolute certainty of the solar dependence of these singular objects. Nevertheless skeptics were still found. M. Fay, of the French Academy, inclined to a lunar origin for them. Filich of Greifswald published in 1852 a treatise for the express purpose of proving all the luminous phenomena attendant on solar eclipses, corona, prominences, and sierra, to be purely optical appearances. Happily, however, the unanswerable arguments of the photographic camera were soon to be made available against such hardy incredulity. Thus, the virtual discovery of the solar appendages, both coronal and chromospheric, may be said to have been begun in 1842, and completed in 1851. The current Herschelian theory of the solar constitution remained, however, for the time, intact. Difficulties, indeed, were thickening around it, but their discussion was perhaps felt to be premature, and they were permitted to accumulate without debate, until fortified by fresh testimony into unexpected and overwhelming preponderance. Footnotes. Cosmos, B.D. 3, page 409, Lalande, Bibliographie Astronomique, pages 179, 202. Arth Wolf, Die Sonde und ihr Flecken, page 9. Marius himself, however, seems to have held the Aristotelian terrestrial exhalation theory of cometary origin. See his curious little tract, Astronomische und astrologische Beschreibung der Kommeten, Nürnberg, 1619. Phil. Trans, Volume 27, page 274. Umbri, now called penumbræ, are spaces of half-shadow which usually encircle spots. Faculae, little torches, so named by Scheiner, are bright streaks or patches closely associated with spots. MEM. AC, SC, 1776, Pub. 1779, page 507. D. Cassini, however, first put forward about 1671 the hypothesis alluded to in the text. C. de Lambert, Histoire de l'Astre. Maud, T. 2, page 694, and Cosmos, B.D. 3, page 410. Phil. Trans, Volume 64, Part 1, pages 7 to 11. Rosa Acina, Lib 4, page 507. Arth Wolf, Die Sonde und ihr Flecken, page 12. Schellen, Die Spektralanalyse, B.D. 2, p. 56, 3rd edition. Phil. Trans, Volume 64, page 20. Ibid, Volume 85, 1795, page 63. Phil. Trans, Volume 91, 1801, page 303. The supposed opaque or protective stratum beneath the photosphere was named by him planetary, from the analogy of terrestrial clouds. Ibid, page 305. Novum Organum, Lib 2. Aff. 20. Brewster's Life of Newton, Volume 2, page 103. Beschäftigung D. Burrell. Guess. Naderverschender Freund, BD, 2, page 233. Gentleman's Magazine, 1787, Volume 2, page 636. Results, etc., page 432. Ibid, page 434. C. Ante, page 31. Memoir of Francis Bailey, M.E.M. R.A.S., Volume 15, page 524. M.E.M. R.A.S., Volume 10, pages 5 to 6. Ibid, pages 14 to 17. M.E.M. R.A.S., Volume 15, pages 4 to 6. Ibid, page 16. Anware, 1846, page 409. Ibid, page 317. Ibid, page 322. Phil. Trans, Volume 40, page 192. M.E.M. R.A.S., Volume 10, page 17. And Du Bureau de Langue, 1846, page 309. De Facey in Orb Luni, 1910. C.F. Grant, Astronomy. Knock, number 1838. As to the phenomenon mentioned by Philostratus in his Life of Apollonius, 8. 23, C. W. T. Lynn, Observatory, Volume 9, page 128. Schmidt, Astronomy. Knock, number 1832. Astronomie pars optica, op omnia, t. 2, page 317. De Stella Nova, op. t. 2, pages 696, 697. Astronomy. Pars op, page 320. M.E.M. De Lac. De Sciences, 1706, page 119. A digit equals 1/12 of the solar diameter. Phil. Trans, Volume 29, pages 247 to 249. M.E.M. De Lac. De Sciences, 1715, Histoire, page 49, Memoirs, pages 93 to 98. Ibid, 1724, page 178. M.E.M. De Lac. De Sciences, 1715, pages 161, 166 to 169. Ed. Encyclopedia, Art. Astronomy, page 635. Trans A.M. Phil. SOC, Volume 6, page 274. Memoir of Caroline Herschel, p. 327. Phil. Trans, Volume 25, page 2240. Ibid, Volume 40, page 182. Ibid, Volume 45, page 586. M.E.M. R.A.S., Volume 1, pages 145, 148. American Journal of Science, Volume 42, page 396. Phil. Trans, Volume 38, page 134. Father Secchi, however, adverted to a distinct mention of a prominence observed in 1239 AD. A description of a total eclipse of that date includes the remark, Aequatum foramen erat ignitum in circulo solis ex part inferior, muratori, rare. It. Scriptors, T. 14, Colonel 1097. The circulus solis, of course, signifies the corona. Phil. Trans, Volume 69, page 114. Trans A.M. Phil. SOC, Volume 6, 1809, page 267. Anware, 1846, page 460. Ibid, page 439, note. Ibid, page 416. M.E.M. R.A.S., Volume 21, page 82. Ibid, page 90. Ibid, pages 7, 8. Le Soleil, T.I., page 386. By Williams and Stanistreet, M.E.M. R.A.S., volume 21, pages 54, 56. Santini had made a similar observation at Padua in 1842. Grant, Histoire Astre, page 401. Lassell in Month. Not. Volume 12, page 53. Comptes Rendus, T. 34, page 155. Optische Untersuchungen and Zeitschrift für populäre Mitteilungen, B.D. I. 1860, page 201. Chapter 4. Planetary Discoveries. In the course of his early gropings towards a law of the planetary distances, Kepler tried the experiment of setting a planet, invisible by reason of its smallness, to revolve in the vast region of seemingly desert space separating Mars from Jupiter. The disproportionate magnitude of the same interval was explained by Kant as due to the overweening size of Jupiter. The zone in which each planet moved was, according to the philosopher of Königsberg, to be regarded as the empty storehouse from which its materials had been derived. A definite relation should thus exist between the planetary masses and the planetary intervals. Lambert, on the other hand, sportively suggested that the body or bodies, for it is noticeable that he speaks of them in the plural, which once bridged this portentous gap in the solar system, might, in some remote age, have been swept away by a great comet, and forced to attend its wanderings through space. These speculations were destined before long to assume a more definite form. Johann Daniel Titius, a professor at Wittenberg, where he died in 1796, pointed out in 1772, in a note to a translation of Bonnet's Contemplation de la Nature, the existence of a remarkable symmetry in the disposition of the bodies constituting the solar system. By a certain series of numbers, increasing in regular progression, he showed that the distances of the 6 known planets from the Sun might be represented with a close approach to accuracy. But with one striking interruption. The term of the series succeeding that which corresponded to the orbit of Mars was without a celestial representative. The orderly flow of the sequence was thus singularly broken. The space where a planet should, in fulfillment of the law, have revolved, was, it appeared, untenanted. Johann Alert Bode, then just about to begin his long career as leader of astronomical thought and work at Berlin, marked at once the anomaly, and filled the vacant interval with a hypothetical planet. The discovery of Uranus, at a distance falling but slightly short of perfect conformity with the law of Titius, lent weight to a seemingly hazardous prediction, and von Zach was actually at the pains, in 1785, to calculate what he termed analogical elements for this unseen and, by any effect or influence, unfelt body. The search for it, through confessedly scarcely less chimerical than that of alchemists for the philosopher's stone, he kept steadily in view for 15 years, and at length, September 21, 1800, succeeded in organizing, in combination with 5 other German astronomers assembled at Lilienthal, a force of what he jocularly termed celestial police, for the express purpose of tracking and intercepting the fugitive subject of the Sun. The zodiac was accordingly divided for purposes of scrutiny into 24 zones. Their apportionment to separate observers was in part effected, and the association was rapidly getting into working order, when news arrived that the missing planet had been found, through no systematic plan of search, but by the diligent, though otherwise directed labors of a distant watcher of the skies. Giuseppe Piazzi was born at Ponte in the Valtelline, July 16, 1746. He studied at various places and times under Tiraboschi, Beccaria, Jacquer, and Lesueur. And having entered the Theatine order of monks at the age of 18, he taught philosophy, science, and theology in several of the Italian cities, as well as in Malta, until 1780. When the chair of mathematics in the University of Palermo was offered to and accepted by him, Prince Caramanico, then Viceroy of Sicily, had scientific leanings, and was easily won over to the project of building an observatory, a commodious foundation for which was afforded by one of the towers of the vice-regal palace. This architecturally incongruous addition to an ancient Saracenic edifice, once the abode of Kelbite and Zirite emirs, was completed in February, 1791. Piazzi, meanwhile, had devoted nearly 3 years to the assiduous study of his new profession, acquiring a practical knowledge of Lalande's methods at the École Militaire, and of Maskelyne's at the Royal Observatory. And returned to Palermo in 1789, bringing with him, in the great 5-foot circle which he had prevailed upon Ramsden to construct, the most perfect measuring instrument hitherto employed by an astronomer. He had been above 9 years at work on his star catalogue, and was still profoundly unconscious that a place amongst the Lilienthal band of astronomical detectives was being held in reserve for him, when, on the first evening of the 19th century, January 1, 1801, he noticed the position of an 8th magnitude star in a part of the constellation Taurus to which an error of Wollaston's had directed his special attention. Re-observing, according to his custom, the same set of 50 stars on 4 consecutive nights, it seemed to him, on the second, that the one in question had slightly shifted its position to the west. On the third he assured himself of the fact, and believed that he had chanced upon a new kind of comet without tail or coma. The wandering body, whatever its nature, exchanged retrograde for direct motion on January 14, and was carefully watched by Piazzi until February 11, when a dangerous illness interrupted his observations. He had, however, not omitted to give notice of his discovery. But so precarious were communications in those unpeaceful times, that his letter to Oriani of January 23 did not reach Milan until April 5, while a missive of 1 day later addressed to Bode came to hand at Berlin, March 20. The delay just afforded time for the publication, by a young philosopher of Jena named Hegel, of a dissertation showing, by the clearest light of reason, that the number of the planets could not exceed 7. And exposing the folly of certain devotees of induction who sought a new celestial body merely to fill a gap in a numerical series. Unabashed by speculative scorn, Bode had scarcely read Piazzi's letter when he concluded that it referred to the precise body in question. The news spread rapidly, and created a profound sensation, not unmixed with alarm lest this latest addition to the solar family should have been found only to be again lost. For by that time Piazzi's moving star was too near the sun to be any longer visible, and in order to rediscover it after conjunction a tolerably accurate knowledge of its path was indispensable. But a planetary orbit had never before been calculated from such scanty data as Piazzi's observation afforded. And the attempts made by nearly every astronomer of note in Germany to compass the problem were manifestly inadequate, failing even to account for the positions in which the body had been actually seen. And a fortiori serving only to mislead as to the places where, from September, 1801, it ought once more to have become discernible. It was in this extremity that the celebrated mathematician Gauss came to the rescue. He was then in his 25th year, and was earning his bread by tuition at Brunswick, with many possibilities, but no settled career before him. The news from Palermo may be said to have converted him from an arithmetician into an astronomer. He was already in possession of a new and more general method of computing elliptical orbits. And the system of least squares, which he had devised though not published, enabled him to extract the most probable result from a given set of observations. Armed with these novel powers, he set to work. And the communication in November of his elements and ephemeris for the lost object revived the drooping hopes of the little band of eager searchers. Their patience, however, was to be still further tried. Clouds, mist, and sleet seemed to have conspired to cover the retreat of the fugitive. But on the last night of the year the sky cleared unexpectedly with the setting in of a hard frost, and there, in the northwestern part of Virgo, nearly in the position assigned by Gauss to the runaway planet, a strange star was discerned by von Zach at Gotha, and on a subsequent evening, the anniversary of the original discovery, by Olbers at Bremen. The name of Ceres, as the tutelary goddess of Sicily, was, by Piazzi's request, bestowed upon this first known of the numerous, and probably all but innumerable family of the minor planets. The recognition of the second followed as the immediate consequence of the detection of the first. Olbers had made himself so familiar with the positions of the small stars along the track of the long-missing body, that he was at once struck, March 28, 1802, with the presence of an intruder near the spot where he had recently identified Ceres. He at first believed the newcomer to be a variable star usually inconspicuous, but just then at its maximum of brightness, but within 2 hours he had convinced himself that it was no fixed star, but a rapidly moving object. The aid of Gauss was again invoked, and his prompt calculations showed that this fresh celestial acquaintance, named Pallas by Olbers, revolved round the Sun at nearly the same mean distance as Ceres, and was beyond question of a strictly analogous character. This result was perplexing in the extreme. The symmetry and simplicity of the planetary scheme appeared fatally compromised by the admission of many, where room could, according to old-fashioned rules, only be found for one. A daring hypothesis of Olbers's invention provided an exit from the difficulty. He supposed that both Ceres and Pallas were fragments of a primitive trans-Martian planet, blown to pieces in the remote past, either by the action of internal forces or by the impact of a comet, and predicted that many more such fragments would be found to circulate in the same region. He, moreover, pointed out that these numerous orbits, however much they might differ in other respects, must all have a common line of intersection, and that the bodies moving in them must consequently pass, at each revolution, through two opposite points of the heavens, one situated in the Whale, the other in the constellation of the Virgin, where already Pallas had been found and Ceres recaptured. The intimation that fresh discoveries might be expected in those particular regions was singularly justified by the detection of two bodies now known respectively as Juno and Vesta. The first was found near the predicted spot in Cetus by Harding, Schroeder's assistant at Lilienthal, September 2, 1804, the second by Olbers himself in Virgo, after 3 years of persistent scrutiny, March 29, 1807. The theory of an exploded planet now seemed to have everything in its favor. It required that the mean or average distances of the newly discovered bodies should be nearly the same, but admitted a wide range of variety in the shapes and positions of their orbits, provided always that they preserved common points of intersection. These conditions were fulfilled with a striking approach to exactness. 3 of the 4 asteroids, a designation introduced by Sir W. Herschel, conformed with very approximate precision to Bode's law of distances. They all traversed, in their circuits round the Sun, nearly the same parts of Cetus and Virgo, while the eccentricities and inclinations of their paths departed widely from the planetary type, that of Pallas, to take an extreme instance, making with the ecliptic an angle of nearly 35 degrees. The minuteness of these bodies appeared further to strengthen the imputation of a fragmentary character. Herschel estimated the diameter of Ceres at 162, that of Pallas at 147 miles. But these values are now known to be considerably too small. A suspected variability of brightness in some of the asteroids, somewhat hazardously explained as due to the irregularities of figure to be expected in cosmical potsherds, so to speak, was added to the confirmatory evidence. The strong point of the theory, however, lay not in what it explained, but in what it had predicted. It had been twice confirmed by actual exploration of the skies, and had produced, in the recognition of Vesta, the first recorded instance of the premeditated discovery of a heavenly body. The view not only commended itself to the facile imagination of the unlearned, but received the sanction of the highest scientific authority. The great Lagrange bestowed upon it his analytical imprimatur, showing that the explosive forces required to produce the supposed catastrophe came well within the bounds of possibility. Since a velocity of less than 20 times that of a cannonball leaving the gun's mouth would have sufficed, according to his calculation, to launch the asteroidal fragments on their respective paths. Indeed, he was disposed to regard the hypothesis of disruption as more generally available than its author had designed it to be, and proposed to supplement with it, as explanatory of the eccentric orbits of comets, the nebular theory of Laplace, thereby obtaining, as he said, a complete view of the origin of the planetary system more conformable to nature and mechanical laws than any yet proposed. Nevertheless, the hypothesis of Olbers has not held its ground. It seemed as if all the evidence available for its support had been produced at once and spontaneously, while the unfavorable items were elicited slowly, and, as it were, by cross-examination. A more extended acquaintance with the group of bodies whose peculiarities it was framed to explain has shown them, after all, as recalcitrant to any such explanation. Coincidences at the first view significant and striking have been swamped by contrary examples, and a hasty general conclusion has, by a not uncommon destiny, at last perished under the accumulation of particulars. Moreover, as has been remarked by Professor Newcomb, mutual perturbations would rapidly efface all traces of a common disruptive origin, and the catastrophe, to be perceptible in its effects, should have been comparatively recent. A new generation of astronomers had arisen before any additions were made to the little family of the minor planets. Piazzi died in 1826, Harding in 1834, Olbers in 1840. All those who had prepared or participated in the first discoveries passed away without witnessing their resumption. In 1830, however, a certain Henk, ex-postmaster in the Prussian town of Dresden, set himself to watch for new planets, and after 15 long years his patience was rewarded. The asteroid found by him, December 8, 1845, received the name of Astrea, and his further prosecution of the search resulted, July 1, 1847, in the discovery of Hebe. A few weeks later, August 13, John Russell Hind, 1823–1893, after many months' exploration from Mr. Bishop's observatory in the Regent's Park, picked up Iris, and October 18, Flora. The next on the list was Métis, found by Mr. Graham, April 25, 1848, at Markry, in Ireland. At the close of the period to which our attention is at present limited, the number of these small bodies known to astronomy was 13. And the course of discovery has since proceeded far more rapidly and with less interruption. Both in itself and in its consequences, the recognition of the minor planets was of the highest importance to science. The traditional ideas regarding the constitution of the solar system were enlarged by the admission of a new class of bodies, strongly contrasted, yet strictly coordinate with the old established planetary order. The profusion of resource, so conspicuous in the living kingdoms of nature, was seen to prevail no less in the celestial spaces. And some faint preliminary notion was afforded of the indefinite complexity of relations underlying the apparent simplicity of the majestic scheme to which our world belongs. Both theoretical and practical astronomy derived profit from the admission of these apparently insignificant strangers to the rights of citizenship of the solar system. The disturbance of their motions by their giant neighbors afforded a more accurate knowledge of the Jovian mass, which Laplace had taken about 1/50th too small. The anomalous character of their orbits presented geometers with highly stimulating problems in the theory of perturbation. While the exigencies of the first discovery had produced the Theoria Motus, and won Gauss over to the ranks of calculating astronomy. Moreover, the sure prospect of further detections powerfully incited to the exploration of the skies. Observers became more numerous and more zealous in view of the prizes held out to them. Star maps were diligently constructed. And the sidereal multitude strewn along the great zodiacal belt acquired a fresh interest, and it was perceived that its least conspicuous member might be a planetary shred or projectile in the dignified disguise of a distant sun. Harding's Celestial Atlas, designed for the special purpose of facilitating asteroidal research, was the first systematic attempt to represent to the eye the telescopic aspect of the heavens. It was while engaged on its construction that the Lilienthal observer successfully intercepted Juno on her passage through the Whale in 1804. Whereupon promoted to Göttingen, he there completed, in 1822, the arduous task so opportunely entered upon a score of years previously. Still more important were the great star maps of the Berlin Academy, undertaken at Bessel's suggestion, with the same object of distinguishing errant from fixed stars, and executed, under Encke's supervision, during the years 1830–59. They have played a noteworthy part in the history of planetary discovery, nor of the minor kind alone. We have now to recount an event unique in scientific history. The discovery of Neptune has been characterized as the result of a movement of the age, and with some justice. It had become necessary to the integrity of planetary theory. Until it was accomplished, the phantom of an unexplained anomaly in the orderly movements of the solar system must have continued to haunt astronomical consciousness. Moreover, it was prepared by many, suggested as possible by not a few, and actually achieved, simultaneously, independently, and completely, by 2 investigators. The position of the planet Uranus was recorded as that of a fixed star no less than 20 times between 1690 and the epoch of its final detection by Herschel. But these early observations, far from affording the expected facilities for the calculation of its orbit, proved a source of grievous perplexity. The utmost ingenuity of geometers failed to combine them satisfactorily with the later Uranian places, and it became evident, either that they were widely erroneous, or that the revolving body was wandering from its ancient track. The simplest course was to reject them altogether, and this was done in the new tables published in 1821 by Alexis Bouvard, the indefatigable computating partner of Laplace. But the trouble was not thus to be got rid of. After a few years fresh irregularities began to appear, and continued to increase until absolutely intolerable. It may be stated as illustrative of the perfection to which astronomy had been brought, that divergencies regarded as menacing the very foundation of its theories never entered the range of unaided vision. In other words, if the theoretical and the real Uranus had been placed side by side in the sky, they would have seemed, to the sharpest eye, to form a single body. The idea that these enigmatical disturbances were due to the attraction of an unknown exterior body was a tolerably obvious one, and we accordingly find it suggested in many different quarters. Bouvard himself was perhaps the first to conceive it. He kept the possibility continually in view, and bequeathed to his nephew's diligence the inquiry into its reality when he felt that his own span was drawing to a close. But before any progress had been made with it, he had already, June 7, 1843, ceased to breathe and to calculate. The Reverend T.J. Hussey actually entertained in 1834 the notion, but found his powers inadequate to the task, of assigning an approximate place to the disturbing body. And Bessel, in 1840, laid his plans for an assault in form upon the Uranian difficulty, the triumphant exit from which fatal illness frustrated his hopes of effecting or even witnessing. The problem was practically untouched when, in 1841, an undergraduate of St. John's College, Cambridge, formed the resolution of grappling with it. The projected task was an arduous one. There were no guiding precedents for its conduct. Analytical obstacles had to be encountered so formidable as to appear invincible even to such a mathematician as Airy. John Couch Adams, however, had no sooner taken his degree, which he did as senior wrangler in January, 1843, than he set resolutely to work, and on October 21, 1845, was able to communicate to the Astronomer Royal numerical estimates of the elements and mass of the unknown planet, together with an indication of its actual place in the heavens. These results, it has been well said, gave the final and inexorable proof of the validity of Newton's law. The date October 21, 1845, may therefore be regarded as marking a distinct epoch in the history of gravitational astronomy. Sir George Biddell Airy had begun in 1835 his long and energetic administration of the Royal Observatory, and was already in possession of data vitally important to the momentous inquiry then on foot. At his suggestion, and under his superintendence, the reduction of all the planetary observations made at Greenwich from 1750 onwards had been undertaken in 1833. The results, published in 1846, constituted a permanent and universal stock of materials for the correction of planetary theory. But in the meantime, investigators, both native and foreign, were freely supplied with the places and errors, which, clearly exhibiting the discrepancies between observation and calculation, between what was and what was expected, formed the very groundwork of future improvements. Mr. Adams had no reason to complain of official discourtesy. His labors received due and indispensable aid, but their purpose was regarded as chimerical. I have always, Sir George Airy wrote, considered the correctness of a distant mathematical result to be a subject rather of moral than of mathematical evidence. And that actually before him seemed, from its very novelty, to incur a suspicion of unlikelihood. No problem in planetary disturbance had heretofore been attacked, so to speak, from the rear. The inverse method was untried, and might well be deemed impracticable. For the difficulty of determining the perturbations produced by a given planet is small compared with the difficulty of finding a planet by its resulting perturbations. Laplace might have quailed before it, yet it was now grappled with as a first essay in celestial dynamics. Moreover, Adams unaccountably neglected to answer until too late a question regarded by Airy in the light of an experimentum crucis as to the soundness of the new theory. Nor did he himself take any steps to obtain a publicity which he was more anxious to merit than to secure. The investigation consequently remained buried in obscurity. It is now known that had a search been instituted in the autumn of 1845 for the remote body whose existence had been so marvelously foretold, it would have been found within 3½ lunar diameters, 1° 49, of the spot assigned to it by Adams. A competitor, however, equally daring and more fortunate, audax fortuna adjutus, as Gauss said of him, was even then entering the field. Urbain Jean-Joseph Leverrier, the son of a small government employee in Normandy, was born at Saint-Lô, March 11, 1811. He studied with brilliant success at the École Polytechnique, accepted the post of astronomical teacher there in 1837, and, docile to circumstance, immediately concentrated the whole of his vast, though as yet undeveloped powers upon the formidable problems of celestial mechanics. He lost no time in proving to the mathematical world that the race of giants was not extinct. 2 papers on the stability of the solar system, presented to the Academy of Sciences, September 16 and October 14, 1839, showed him to be the worthy successor of Lagrange and Laplace, and encouraged hopes destined to be abundantly realized. His attention was directed by Arago to the Uranian difficulty in 1845, when he cheerfully put aside certain intricate cometary researches upon which he happened to be engaged, in order to obey with dutiful promptitude the summons of the astronomical chief of France. In his first memoir on the subject, communicated to the Academy, November 10, 1845, he proved the inadequacy of all known causes of disturbance to account for the vagaries of Uranus. In a second, June 1, 1848, he demonstrated that only an exterior body, occupying at a certain date a determinate position in the zodiac, could produce the observed effects. In a third, August 31, 1846, he assigned the orbit of the disturbing body, and announced its visibility as an object with a sensible disk about as bright as a star of the 8th magnitude. The question was now visibly approaching an issue. On September 10, Sir John Herschel declared to the British Association respecting the hypothetical new planet, "We see it as Columbus saw America from the coast of Spain. Its movements have been felt, trembling along the far-reaching line of our analysis with a certainty hardly inferior to that of ocular demonstration." Less than a fortnight later, September 23, Professor Gall, of the Berlin Observatory, received a letter from Leverrier requesting his aid in the telescopic part of the inquiry already analytically completed. He directed his refractor to the heavens that same night, and perceived, within less than a degree of the spot indicated, an object with a measurable disk nearly 3 seconds in diameter. Its absence from Bremiker's recently completed map of that region of the sky showed it to be no star, and its movement in the predicted direction confirmed without delay the strong persuasion of its planetary nature. In this remarkable manner the existence of the remote member of our system known as Neptune was ascertained. But the discovery, which faithfully reflected the duplicate character of the investigation which led to it, had been already secured at Cambridge before it was announced from Berlin. Sir George Airy's incredulity vanished in the face of the striking coincidence between the position assigned by Leverrier to the unknown planet in June, and that laid down by Adams in the previous October. And on the 9th of July he wrote to Professor Challis, director of the Cambridge Observatory, recommending a search with the Great Northumberland Equatorial. Had a good star map been at hand, the process would have been a simple one. But of Bremiker's Aura XXI no news had yet reached England, and there was no other sufficiently comprehensive to be available for an inquiry which, in the absence of such aid, promised to be both long and laborious. As the event proved, it might have been neither. After 4 days of observing, Challis wrote, October 12, 1846, to Airy, "The planet was in my grasp if only I had examined or mapped the observations." Had he done so, the first honors in the discovery, both theoretical and optical, would have fallen to the University of Cambridge. But Professor Challis had other astronomical avocations to attend to, and, moreover, his faith in the precision of the indications furnished to him was, by his own confession, a very feeble one. For both reasons he postponed to a later stage of the proceedings the discussion and comparison of the data nightly furnished to him by his telescope, and thus allowed to lie, as it were, latent in his observations the momentous result which his diligence had ensured, but which his delay suffered to be anticipated. Nevertheless, it should not be forgotten that the Berlin astronomer had two circumstances in his favor apart from which his swift success could hardly have been achieved. The first was the possession of a good star map. The second was the clear and confident nature of Leverrier's instructions. "Look where I tell you," he seemed authoritatively to say, "and you will see an object such as I describe." And in fact, not only Gall on the 23rd of September, but also Challis on the 29th, immediately after reading the French geometer's lucid and impressive treatise, picked out from among the stellar points strewing the zodiac, a small planetary disk, which eventually proved to be that of the precise body he had been in search of during 2 months. The controversy that ensued had its ignominious side, but it was entered into by neither of the parties principally concerned. Adams bore the disappointment, which the dilatory proceedings at Greenwich and Cambridge had inflicted upon him, with quiet heroism. His silence on the subject of what another man would have called his wrongs remained unbroken to the end of his life, and he took every opportunity of testifying his admiration for the genius of Leverrier. Personal questions, however, vanish in the magnitude of the event they relate to. By it the last lingering doubts as to the absolute exactness of the Newtonian law were dissipated. Recondite analytical methods received a confirmation brilliant and intelligible even to the minds of the vulgar, and emerged from the patient solitude of the study to enjoy an hour of clamorous triumph. Forever invisible to the unaided eye of man, a sister globe to our earth was shown to circulate, in perpetual frozen exile, at 30 times its distance from the sun. Nay, the possibility was made apparent that the limits of our system were not even thus reached, but that yet profounder abysses of space might shelter obedient, though little favored, members of the solar family. By future astronomers to be recognized through the sympathetic thrillings of Neptune, even as Neptune himself was recognized through the telltale deviations of Uranus. It is curious to find that the fruit of Adams's and Leverrier's laborious investigations had been accidentally all but snatched half a century before it was ripe to be gathered. On the 8th, and again on the 10th of May, 1795, Lalande noted the position of Neptune as that of a fixed star, but perceiving that the two observations did not agree, he suppressed the first as erroneous, and pursued the inquiry no further. An immortality which he would have been the last to despise hung in the balance. The featherweight of his carelessness, however, kicked the beam, and the discovery was reserved to be more hardly won by later comers. Bode's law did good service in the quest for a trans-Uranian planet by affording ground for a probable assumption as to its distance. A starting point for approximation was provided by it, but it was soon found to be considerably at fault. Even Uranus is about 36 millions of miles nearer to the Sun than the order of progression requires. And Neptune's vast distance of 2,800 million should be increased by no less than 800 million miles, and its period of 165 lengthened out to 225 years. In order to bring it into conformity with the curious and unexplained rule which planetary discoveries have alternately tended to confirm and to invalidate. Within 17 days of its identification with the Berlin achromatic, Neptune was found to be attended by a satellite. This discovery was the first notable performance of the celebrated 2-foot reflector erected by Mr. Lassell at his suggestively named residence of Starfield, near Liverpool. William Lassell was a brewer by profession, but by inclination an astronomer. Born at Bolton in Lancashire, June 18, 1799, he closed a life of eminent usefulness to science, October 5, 1818, thus spanning with his well-spent years 4/5 of the momentous period which we have undertaken to traverse. At the age of 21, being without the means to purchase, he undertook to construct telescopes, and naturally turned his attention to the reflecting sort, as favoring amateur efforts by the comparative simplicity of its structure. His native ingenuity was remarkable, and was developed by the hourly exigencies of his successive enterprises. Their uniform success encouraged him to enlarge his aims, and in 1844 he visited Bear Castle for the purpose of inspecting the machine used in polishing the giant speculum of Parsonstown. In the construction of his new instrument, however, he eventually discarded the model there obtained, and worked on a method of his own, assisted by the supreme mechanical skill of James Naismith. The result was a Newtonian of exquisite definition, with an aperture of 2, and a focal length of 20 feet, provided by a novel artifice with the equatorial mounting, previously regarded as available only for refractors. This beautiful instrument afforded to its maker, October 10, 1846, a cursory view of a Neptunian attendant. But the planet was then approaching the Sun, and it was not until the following July that the observation could be verified, which it was completely, first by Lassell himself, and somewhat later by Otto Struve and Bond of Cambridge, U.S. When it is considered that this remote object shines by reflecting sunlight reduced by distance to 1/900th of the intensity with which it illuminates our moon, the fact of its visibility, even in the most perfect telescopes, is a somewhat surprising one. It can only, indeed, be accounted for by attributing to it dimensions very considerable for a body of the secondary order. It shares with the moons of Uranus the peculiarity of retrograde motion. That is to say, its revolutions, running counter to the grand current of movement in the solar system, are performed from east to west, in a plane inclined at an angle of 35 degrees to that of the ecliptic. Their swiftness serves to measure the mass of the globe round which they are performed. For while our moon takes 27 days and nearly 8 hours to complete its circuit of the earth, the satellite of Neptune, at a distance not greatly inferior, sweeps round its primary in 5 days and 21 hours. Showing, according to a very simple principle of computation, that it is urged by a force 17 times greater than the terrestrial pull upon the lunar orb. Combining this result with those of Professor Barnard's and Dr. C's recent measurements of the small telescopic disk of this farthest known planet, it is found that while in mass Neptune equals 17, in bulk it is equivalent to 49 Earths. This is as much as to say that it is composed of relatively very light materials, or more probably of materials distended by internal heat, as yet unwasted by radiation into space. To about 5 times the volume they would occupy in the interior of our globe. The fact, at any rate, is fairly well ascertained, that the average density of Neptune is about twice that of water. We must now turn from this late recognized member of our system to bestow some brief attention upon the still fruitful field of discovery offered by one of the immemorial 5. The family of Saturn, unlike that of its brilliant neighbor, has been gradually introduced to the notice of astronomers. Titan, the 6th Saturnian moon in order of distance, led the way, being detected by Huygens, March 25, 1655. Cassini made the acquaintance of 4 more between 1671 and 1684, while Mimas and Enceladus, the 2 innermost, were caught by Herschel in 1789, as they threaded their lucid way along the edge of the almost vanished ring. In the distances of these 7 revolving bodies from their primary, an order of progression analogous to that pointed out by Titius in the planetary intervals was found to prevail. But with one conspicuous interruption, similar to that which had first suggested the search for new members of the solar system. Between Titan and Japetus, the 6th and 7th reckoning outwards, there was obviously room for another satellite. It was discovered on both sides of the Atlantic simultaneously, on the 19th of September, 1848. Mr. W. C. Bond, employing the splendid 15-inch refractor of the Harvard Observatory, noticed, September 16, a minute star situated in the plane of Saturn's rings. The same object was discerned by Mr. Lassell on the 18th. On the following evening, both observers perceived that the problematical speck of light kept up with, instead of being left behind by the planet as it moved, and hence inferred its true character. Hyperion, the 7th by distance and 8th by recognition of Saturn's attendant train, is of so insignificant a size when compared with some of its fellow moons. Titan is but little inferior to the planet Mars. As to have suggested to Sir John Herschel the idea that it might be only one of several bodies revolving very close together, in fact, an asteroidal satellite. But the conjecture has, so far, not been verified. The coincidence of its duplicate discovery was singularly paralleled 2 years later. Galileo's amazement when his optic glass revealed to him the triple form of Saturn, Planeta Tergeminus, has proved to be, like the laughter of the gods, inextinguishable. It must revive in every one who contemplates anew the unique arrangements of that world apart known to us as the Saturnian system. The resolution of the so-called ANSI, or handles, into one encircling ring by Huygens in 1655, the discovery by Cassini in 1675 of the division of that ring into 2 concentric ones. Together with Laplace's investigation of the conditions of stability of such a formation, constituted, with some minor observations, the sum of the knowledge obtained, up to the middle of the last century, on the subject of this remarkable formation. The first place in the discovery now about to be related belongs to an American astronomer. William Cranch Bond, born in 1789 at Portland, in the state of Maine, was a watchmaker, whom the solar eclipse of 1806 attracted to study the wonders of the heavens. When, in 1815, the erection of an observatory in connection with Harvard College, Cambridge, was first contemplated, he undertook a mission to England for the purpose of studying the working of similar institutions there. And on his return erected a private observatory at Dorchester, where he worked diligently for many years. Then at last, in 1843, the long-postponed design of the Harvard authorities was resumed, and on the completion of the new establishment, Bond, who had been from 1838 officially connected with the college and had carried on his scientific labors within its precincts, was offered and accepted the post of its director. Placed in 1847 in possession of one of the finest instruments in the world, a masterpiece of Mers and Mahler, he headed the now long list of distinguished transatlantic observers. Like the elder Struve, he left an heir to his office and to his eminence, but George Bond unfortunately died in 1865, at the early age of 39, having survived his father but 6 years. On the night of November 15, 1850, the air, remarkably enough, being so hazy that only the brightest stars could be perceived with the naked eye, William Bond discerned a dusky ring, extending about halfway between the inner brighter one and the globe of Saturn. A fortnight later, but before the observation had been announced in England, the same appearance was seen by the Reverend W. R. Dawes with the comparatively small refractor of his observatory at Wateringbury, and on December 3 was described by Mr. Lassell, then on a visit to him, as something like a crape veil covering a part of the sky within the inner ring. Next morning the Times containing the report of Bond's discovery reached Wateringbury. The most surprising circumstance in the matter was that the novel appendage had remained so long unrecognized. As the rings opened out to their full extent, it became obvious with very moderate optical assistance. Yet some of the most acute observers who have ever lived, using instruments of vast power, had heretofore failed to detect its presence. It soon appeared, however, that Gall of Berlin had noticed, June 10, 1838, a veil-like extension of the lucid ring across half the dark space separating it from the planet. But the observation, although communicated at the time to the Berlin Academy of Sciences, had remained barren. Traces of the dark ring, moreover, were found in drawings executed by Campani in 1664 and by Hooke in 1666. While Picard, June 15, 1673, Hadley, spring of 1720, and Herschel, had all undoubtedly seen it under the aspect of a dark bar or belt crossing the Saturnian globe. It was, then, of no recent origin. But there seemed reason to think that it had lately gained considerably in brightness. The full meaning of this suspected change it was reserved for later investigations to develop. What we may, in a certain sense, call the closing result of the race for discovery, in which several observers seemed at that time to be engaged, was the establishment, on a satisfactory footing, of our acquaintance with the dependent system of Uranus. Sir William Herschel, whose researches formed, in so many distinct lines of astronomical inquiry, the starting points of future knowledge, detected, January 11, 1787, 2 Uranian moons, since called Oberon and Titania. and ascertained the curious circumstance of their motion in a plane almost at right angles to the ecliptic, in a direction contrary to that of all previously known denizens, other than cometary, of the solar kingdom. He believed that he caught occasional glimpses of four more, but never succeeded in assuring himself of their substantial existence. Even the two first remained unseen save by himself until 1828, when his son re-observed them with a 20-foot reflector, similar to that with which they had been originally discovered. Thenceforward they were kept fairly within view, but their four questionable companions, in spite of some false alarms of detection, remained in the dubious condition in which Herschel had left them. At last, on October 24, 1851, after some years of fruitless watching, Lassell espied Ariel and Umbriel, two Uranian attendants, interior to Oberon and Titania, and of about half their brightness. So that their disclosure is still reckoned amongst the very highest proofs of instrumental power and perfection. In all probability they were then for the first time seen. For although Professor Holden made out a plausible case in favor of the fitful visibility to Herschel of each of them in turn, Lassell's argument that the glare of the planet in Herschel's great specula must have rendered almost impossible the perception of objects so minute and so close to its disk, appears tolerably decisive to the contrary. Uranus is thus attended by four moons, and, so far as present knowledge extends, by no more. Among the most important of the negative results secured by Lassell's observations at Malta during the years 1852–53 and 1861–65, were the convincing evidence afforded by them that, without great increase of optical power, no further Neptunian or Uranian satellites can be perceived, and the consequent relegation of Herschel's baffling quartet, notwithstanding the unquestioned place long assigned to them in astronomical textbooks, to the nirvana of non-existence. Footnotes. Op. T.I., page 107. He interposed, but tentatively only, another similar body between Mercury and Venus. Allgemeine Naturgeschichte, edition 1798, pages 118, 119. Kosmologische Brief, No. 1, quoted by von Zach, Monat. Cor, Volume 3, p. 592. Second edition, page 7. C. Bode, von dem neuen Hauptplaneten, page 43, note. The representative numbers are obtained by adding 1 to the following series, irregular, it will be observed, in its first member, which should be 1/2 instead of 0. 0, 3, 6, 12, 24, 48, etc. The formula is a purely empirical one, and is, moreover, completely at fault as regards the distance of Neptune. Monat. Cor, Volume 3, page 596. Wolf, Geschichte der Astronomie, page 648. Such reversals of direction in the apparent movements of the planets are a consequence of the Earth's revolution in its orbit. Dissertatio Philosophica de Orbitis Planetarum, 1801. C. Wolf, Gesch. D. Astre, page 685. Observations on Uranus, as a supposed fixed star, went back to 1690. He had caught a glimpse of it on December 7, but was prevented by bad weather from verifying his suspicion. Monat. Cor, Volume 5, page 171. Planetary fragments, hurled in any direction, and with any velocity short of that which would forever release them from the solar sway, would continue to describe elliptic orbits round the Sun, all passing through the scene of the explosion, and thus possessing a common line of intersection. Phil. Trans, Volume 92, Part 2, page 228. Ibid, page 218. In a letter to von Zach of June 24, 1802, he speaks of Pallas as almost incredibly small, and makes it only 70 English miles in diameter. Monat. Cor, Volume 6, pages 89, 90. Olbers, Monat. Cor, Volume 6, page 88. Con D. Thames for 1814, page 218. Popular Astronomy, page 327. Month. Not, Volume 7, page 299, Volume 8, page 1. Ibid, page 146. Airy, M.E.M. R.A.S., Volume 16, page 386. C. Newcomb's Pop Astre, page 359. The error of Uranus amounted, in 1844, to 2, but even the tailor of Breslau, whose extraordinary powers of vision Humboldt commemorates, Cosmos, B.D. 2, page 112, could only see Jupiter's first satellite at its greatest elongation, 215. He might, however, possibly have distinguished two objects of equal luster at a lesser interval. J. W. L. Glacier, Observatory, Volume 15, page 177. M.E.M. R.A.S., Volume 16, page 399. For an account of D'Aristè's share in the detection, see Copernicus, Volume 2, pages 63, 96. M.E.M. R.A.S., Volume 16, page 412. He had recorded the places of 3,150 stars, 3 of which were different positions of the planet, and was preparing to map them, when, October 1, news of the discovery arrived from Berlin. Professor Challis's report, quoted in Obituary Notice, month. Not, February, 1883, page 170. See Airy in M.E.M. R.A.S., Volume 16, page 411. He died January 21, 1892, in his 71st year. Ledger, The Sun, Its Planets and Their Satellites, page 414. Presented by the Misses Lassell, after their father's death, to the Greenwich Observatory. Astre. Jour, No. 508. Report of U.S. Naval Observatory for 1900, page 15. Grant, History of Astre, page 271. Month. Knott, Volume 9, page 91. Month. Knott, Volume 11, p. 21. Astre. Nock, No. 756, May 2, 1851. Phil. Trans, Volume 1, page 246. C. H. T. Vivian, England, Mech, April 20, 1894. Secchi, Month. Knott, Volume 13, page 248. Hind, Ibid, Volume 15, page 32. Lynn, Observatory, October 1, 1883, Hadley, Phil. Trans, Volume 32, page 385. Proctor, Saturn and Its System, page 64. Phil. Trans, Volume 77, page 125. Month. Knott, Volume 11, page 248. Ibid, Volume 35, pages 16 to 22. Ibid, page 26. Ibid, Volume 41, page 190. Chapter 5. Comets. Newton showed that the bodies known as comets or hirsute stars obey the law of gravitation. But it was by no means certain that the individual of the species observed by him in 1680 formed a permanent member of the solar system. The velocity, in fact, of its rush round the sun was quite possibly sufficient to carry it off forever into the depths of space, there to wander, a celestial casual, from star to star. With another comet, however, which appeared 2 years later, the case was different. Edmund Halley, who afterward succeeded Flamsteed as Astronomer Royal, calculated the elements of its orbit on Newton's principles, and found them to resemble so closely those similarly arrived at for comets observed by Peter Apian in 1531. And by Kepler in 1607, as almost to compel the inference that all three were apparitions of a single body. This implied its revolution in a period of about 76 years, and Halley accordingly fixed its return for 1758-9. So fully alive was he to the importance of the announcement that he appealed to a candid posterity, in the event of its verification, to acknowledge that the discovery was due to an Englishman. The prediction was one of the test questions put by science to nature, on the replies to which largely depend both the development of knowledge and the conviction of its reality. In the present instance, the answer afforded may be said to have laid the foundation of this branch of astronomy. Halley's comet punctually reappeared on Christmas Day, 1758, and effected its perihelion passage on the 12th of March following, thus proving beyond dispute that some at least of these erratic bodies are domesticated within our system, and strictly conform, if not to its unwritten customs, so to speak, at any rate to its fundamental laws. Their movements, in short, were demonstrated by the most unanswerable of all arguments, that of verified calculation, to be calculable, and their investigation was erected into a legitimate department of astronomical science. This notable advance was the chief result obtained in the field of inquiry just now under consideration during the 18th century. But before it closed, its cultivation had received a powerful stimulus through the invention of an improved method. The name of Olbers has already been brought prominently before our readers in connection with asteroidal discoveries. These, however, were but chance excursions from the path of cometary research which he steadily pursued through life. An early predilection for the heavens was fixed in this particular direction by one of the happy inspirations of genius. As he was watching, one night in the year 1779, by the sick bed of a fellow student in medicine at Göttingen, an important simplification in the mode of computing the paths of comets occurred to him. Although not made public until 1797, Olbers's method was then universally adopted, and is still regarded as the most expeditious and convenient in cases where absolute rigor is not required. By its introduction, not only many a toilsome and thankless hour was spared, but workers were multiplied, and encouraged in the prosecution of labors more useful than attractive. The career of Heinrich Olbers is a brilliant example of what may be done by an amateur in astronomy. He at no time did regular work in an observatory, he was never the possessor of a transit or any other fixed instrument. Moreover, all the best years of his life were absorbed in the assiduous exercise of a toilsome profession. Born in 1758 at the village of Arbergen, where his father was pastor, he settled in 1781 as a physician in the neighboring town of Bremen, and continued in active practice there for over 40 years. It was thus only the hours which his robust constitution enabled him to spare from sleep that were available for his intellectual pleasures. Yet his recreation was, as von Zach remarked, no less prolific of useful results than the severest work of other men. The upper part of his house in the Sandgas was fitted up with such instruments and appliances as restrictions of space permitted, and there, night after night during half a century and upwards, he discovered, calculated, or observed the cometary visitants of northern skies. Almost as effective in promoting the interests of science as the valuable work actually done by him, was the influence of his genial personality. He engaged confidence by his ready and discerning sympathy. He inspired affection by his benevolent disinterestedness, he quickened thought and awakened zeal by the suggestions of a lively and inventive spirit, animated with the warmest enthusiasm for the advancement of knowledge. Nearly every astronomer in Germany enjoyed the benefits of a frequently active correspondence with him, and his communications to the scientific periodicals of the time were numerous and striking. The motive power of his mind was thus widely felt and continually in action. Nor did it wholly cease to be exerted even when the advance of age and the progress of infirmity rendered him incapable of active occupation. He was, in fact, alive even to the last day of his long life of 81 years, and his death, which occurred March 2, 1840, left vacant a position which a rare combination of moral and intellectual qualities had conspired to render unique. Amongst the many younger men who were attracted and stimulated by intercourse with him was Johann Franz Encke. But while Olbers became a mathematician because he was an astronomer, Encke became an astronomer because he was a mathematician. A born geometer, he was naturally sent to Göttingen and placed under the tuition of Gauss. But geometers are men, and the contagion of patriotic fervor which swept over Germany after the Battle of Leipzig did not spare Gauss's promising pupil. He took up arms in the Hanseatic Legion, and marched and fought until the oppressor of his country was safely ensconced behind the ocean walls of St. Helena. In the course of his campaigning he met Lindenau, the militant director of the Seeberg Observatory, and by his influence was appointed his assistant, and eventually, in 1822, became his successor. Thence he was promoted in 1825 to Berlin, where he superintended the building of the new observatory, so actively promoted by Humboldt, and remained at its head until within some 18 months of his death in August, 1865. On the 26th of November, 1818, Pons of Marseilles discovered a comet, whose inconspicuous appearance gave little promise of its becoming one of the most interesting objects in our system. Encke at once took the calculation of its elements in hand, and brought out the unexpected result that it revolved round the Sun in a period of about 3 1/3 years. He, moreover, detected its identity with comets seen by M'Kane in 1786, by Caroline Herschel in 1795, by Pons, Huth, and Bavard in 1805. And after 6 laborious weeks of research into the disturbances experienced by it from the planets during the entire interval since its first ascertained appearance, he fixed May 24, 1822, as the date of its next return to perihelion. Although on that occasion, owing to the position of the Earth, invisible in the northern hemisphere, Sir Thomas Brisbane's observatory at Parramatta was fortunately ready equipped for its recapture, which Runcker effected quite close to the spot indicated by Encke's ephemeris. The importance of this event can be better understood when it is remembered that it was only the second instance of the recognized return of a comet, that of Halley's, 63 years previously, having, as already stated, been the first. And that it, moreover, established the existence of a new class of celestial objects, somewhat loosely distinguished as comets of short period. These bodies, of which about 30 have been found to circulate within the orbit of Saturn, are remarkable as showing certain planetary affinities in the manners of their motions not at all perceptible in the wider traveling members of their order. They revolve, without exception, in the same direction as the planets, from west to east. They exhibit a marked tendency to conform to the zodiacal track which limits planetary excursions north and south. And their paths round the Sun, although much more eccentric than the approximately circular planetary orbits, are far less so than the extravagantly long ellipses in which comets comparatively untrained, as it were, in the habits of the solar system ordinarily perform their revolutions. No great comet is of the planetary kind. These are, indeed, only by exception visible to the naked eye. They possess extremely feeble tail-producing powers, and give small signs of central condensation. Thin wisps of cosmical cloud, they flit across the telescopic field of view without sensibly obscuring the smallest star. Their appearance, in short, suggests, what some notable facts in their history will presently be shown to confirm, that they are bodies already effete and verging towards dissolution. If it be asked what possible connection can be shown to exist between the shortness of period by which they are essentially characterized, and what we may call their superannuated condition, we are not altogether at a loss for an answer. Kepler's remark, that comets are consumed by their own emissions, has undoubtedly a measure of truth in it. The substance ejected into the tail must, in overwhelmingly large proportion, be forever lost to the central mass from which it issues. True, it is of a nature inconceivably tenuous, but unrepaired waste, however small in amount, cannot be persisted in with impunity. The incitement to such self-spoliation proceeds from the Sun. It accordingly progresses more rapidly the more numerous are the returns to the solar vicinity. Comets of short period may thus reasonably be expected to wear out quickly. They are, moreover, subject to many adventures and vicissitudes. Their aphelia, or the farthest points of their orbits from the Sun, are usually, if not invariably, situated so near to the path either of Jupiter or of Saturn, as to permit these giant planets to act as secondary rulers of their destinies. By their influence they were, in all likelihood, originally fixed in their present tracks, and by their influence, exerted in an opposite sense, they may, in some cases, be eventually ejected from them. Careers so varied, as can easily be imagined, are apt to prove instructive, and astronomers have not been backward in extracting from them the lessons they are fitted to convey. Encke's comet, above all, has served as an index to much curious information, and it may be hoped that its function in that respect is by no means at an end. The great extent of the solar system traversed by its eccentric path makes it peculiarly useful for the determination of the planetary masses. At perihelion it penetrates within the orbit of Mercury. It considerably transcends at aphelion the farthest excursion of Pallas. Its vicinity to the former planet in August, 1835, offered the first convenient opportunity of placing that body in the astronomical balance. Its weight or mass had previously been assumed, not ascertained, and the comparatively slight deviation from its regular course impressed upon the comet by its attractive power showed that it had been assumed nearly twice too great. That fundamental datum of planetary astronomy, the mass of Jupiter, was corrected by similar means, and it was reassuring to find the correction in satisfactory accord with that already introduced from observations of the asteroidal movements. The fact that comets contract in approaching the Sun had been noticed by Hevelius, Pinger admitted it with hesitating perplexity. The example of Encke's comet rendered it conspicuous and undeniable. On the 28th of October, 1828, the diameter of the nebulous matter composing this body was estimated at 312,000 miles. It was then about 1.5 times further from the Sun than the Earth is at the time of the equinox. On the 24th of December following, its distance being reduced by nearly 2/3, it was found to be only 14,000 miles across. That is to say, it had shrunk during those 2 months of approach to 1/11,000th part of its original volume. Yet it had still 17 days' journey to make before reaching perihelion. The same curious circumstance was even more markedly apparent at its return in 1838. Its bulk, or the actual space occupied by it, appeared to be reduced, as it drew near the hearth of our system, in the enormous proportion of 800,000 to 1. A corresponding expansion accompanied on each occasion its retirement from the sphere of observation. Similar changes of volume, though rarely to the same astounding extent, have been perceived in other comets. They still remain unexplained. But it can scarcely be doubted that they are due to the action of the same energetic internal forces which reveal themselves in so many splendid and surprising cometary phenomena. Another question of singular interest was raised by Encke's acute inquiries into the movements and disturbances of the first known comet of short period. He found from the first that its revolutions were subject to some influence besides that of gravity. After every possible allowance had been made for the pulls, now backward, now forward, exerted upon it by the several planets, there was still a surplus of acceleration left unaccounted for. Each return to perihelion took place about 2.5 hours sooner than received theories warranted. Here, then, was a residual phenomenon of the utmost promise for the disclosure of novel truths. Encke, in accordance with the opinion of Olbers, explained it as due to the presence in space of some such subtle matter as was long ago invoked by Euler to be the agent of eventual destruction for the fair scheme of planetary creation. The apparent anomaly of accounting for an accelerative effect by a retarding cause disappears when it is considered that any check to the motion of bodies revolving round a center of attraction causes them to draw closer to it, thus shortening their periods and quickening their circulation. If space were filled with a resisting medium capable of impeding, even in the most infinitesimal degree, the swift course of the planets, their orbits should necessarily be, not ellipses, but very close elliptical spirals along which they would slowly, but inevitably, descend into the burning lap of the Sun. The circumstance that no such tendency can be traced in their revolutions by no means sets the question at rest. For it might well be that an effect totally imperceptible until after the lapse of countless ages, as regards the solid orbs of our system, might be obvious in the movements of bodies like comets of small mass and great bulk. Just as a feather or a gauze veil at once yields its motion to the resistance of the air, while a cannonball cuts its way through with comparatively slight loss of velocity. It will thus be seen that issues of the most momentous character hang on the timekeeping of comets, for plainly all must in some degree suffer the same kind of hindrance as Encke's, if the cause of that hindrance be the one suggested. None of its congeners, however, show any trace of similar symptoms. True, the late Professor Appolzer announced, in 1880, that a comet, first seen by Pons in 1819, and rediscovered by Winnock in 1858, having a period of 2052 days, 5-6 years. Was accelerated at each revolution precisely in the manner required by Encke's theory. But M. von Hertel's subsequent investigation, the materials for which included numerous observations of the body in question at its return to the Sun in 1886, decisively negatived the presence of any such effect. Moreover, the researches of von Aston and Backlund into the movements of Encke's comet revealed a perplexing circumstance. They confirmed Encke's results for the period covered by them, but exhibited the acceleration as having suddenly diminished by nearly one-half in 1868. The reality and permanence of this change were fully established by observations of the ensuing return in March, 1885. Some physical alteration of the retarded body seems indicated, but visual evidence countenances no such assumption. In aspect the comet is no less thin and diffuse than in 1795 or in 1848. The character of the supposed resistance in interplanetary space has, it may be remarked, been often misapprehended. What Encke stipulated for was not a medium equally diffused throughout the visible universe, such as the ethereal vehicle of the vibrations of light, but a rare fluid, rapidly increasing in density towards the Sun. This cannot be a solar atmosphere, since it is mathematically certain, as Laplace has shown, that no envelope partaking of the Sun's axial rotation can extend farther from his surface than 9/10 of the mean distance of Mercury. While physical evidence assures us that the actual depth of the solar atmosphere bears a very minute proportion to the possible depth theoretically assigned to it. That matter, however, not atmospheric in its nature, that is, neither forming one body with the Sun nor altogether aeriform, exists in its neighborhood, can admit of no reasonable doubt. The great lens-shaped mass of the zodiacal light, stretching out at times far beyond the Earth's orbit, may indeed be regarded as an extension of the corona, the streamers of which themselves mark the wide diffusion, all round the solar globe, of granular or gaseous materials. Yet comets have been known to penetrate the sphere occupied by them without perceptible loss of velocity. The hypothesis, then, of a resisting medium receives at present no countenance from the movements of comets, whether of short or of long periods. Although Encke's comet has made 35 complete rounds of its orbit since its first detection in 1786, it shows no certain signs of decay. Variations in its brightness are, it is true, conspicuous, but they do not proceed continuously. The history of the next known planet-like comet has proved of even more curious interest than that of the first. It was discovered by an Austrian officer named Wilhelm von Biela at Josephstadt in Bohemia, February 27, 1826, and 10 days later by the French astronomer Gambart at Marseilles. Both observers computed its orbit, showed its remarkable similarity to that traversed by comets visible in 1772 and 1805. And connected them together as previous appearances of the body just detected by assigning to its revolutions a period of between 6 and 7 years. The two brief letters conveying these strikingly similar inferences were printed side by side in the same number of the Astronomische Nachrichten, number 94. But Biela's priority in the discovery of the comet was justly recognized by the bestowal upon it of his name. The object in question was at no time, subsequently to 1805, visible to the naked eye. Its aspect in Sir John Herschel's great reflector on the 23rd of September, 1832, was described by him as that of a conspicuous nebula, nearly 3 minutes in diameter. No trace of a tail was discernible. While he was engaged in watching it, a small knot of minute stars was directly traversed by it, and when on the cluster, he tells us, it presented the appearance of a nebula resolvable and partly resolved into stars. The stars of the cluster being visible through the comet. Yet the depth of cometary matter through which such faint stellar rays penetrated undimmed, was, near the central parts of the globe, not less than 50,000 miles. It is curious to find that this seemingly harmless, and we may perhaps add effete body, gave occasion to the first, and not the last, cometary scare of an enlightened century. Its orbit at the descending node may be said to have intersected that of the Earth. Since, according as it bulged in or out under the disturbing influence of the planets, the passage of the comet was effected inside or outside the terrestrial track. Now, certain calculations published by Olbers in 1828 showed that, on October 29, 1832, a considerable portion of its nebulous surroundings would actually sweep over the spot which, a month later, would be occupied by our planet. It needed no more to set the popular imagination in a ferment. Astronomers, after all, could not, by an alarmed public, be held to be infallible. Their computations, it was averred, which a trifling oversight would suffice to vitiate, exhibited clearly enough the danger, but afforded no guarantee of safety from a collision, with all the terrific consequences frigidly enumerated by Laplace. Nor did the panic subside until Arago formally demonstrated that the Earth and the comet could by no possibility approach within less than 50 millions of miles. The return of the same body in 1845–46 was marked by an extraordinary circumstance. When first seen, November 28, it wore its usual aspect of a faint round patch of cosmical fog, but on December 19, Mr. Hind noticed that it had become distorted somewhat into the form of a pear. And 10 days later, it had divided into two separate objects. This singular duplication was first perceived at New Haven in America, December 29, by Messrs. Herrick and Bradley, and by Lieutenant Maury at Washington, January 13, 1846. The earliest British observer of the phenomenon, noticed by Wickman the same evening at Königsberg, was Professor Challis. "I see two comets," he exclaimed, putting his eye to the great equatorial of the Cambridge Observatory on the night of January 15. Then, distrustful of what his senses had told him, he called in his judgment to correct their improbable report by resolving one of the dubious objects into a hazy star. On the 23rd, however, both were again seen by him in unmistakable cometary shape, and until far on in March, Otto Struve caught a final glimpse of the pair on the 16th of April. Continued to be watched with equal curiosity and amazement by astronomers in every part of the northern hemisphere. What Seneca reproved Ephorus for supposing to have taken place in 373 BC, what Pinger blamed Kepler for conjecturing in 1618, had then actually occurred under the attentive eyes of science in the middle of the 19th century. At a distance from each other of about 2/3 the distance of the Moon from the Earth, the twin comets meantime moved on tranquilly, so far, at least, as their course through the heaven was concerned. Their extreme lightness, or the small amount of matter contained in each, could not have received a more signal illustration than by the fact that their revolutions round the sun were performed independently. That is to say, they traveled side by side without experiencing any appreciable mutual disturbance, thus plainly showing that at an interval of only 157,250 miles their attractive power was virtually inoperative. Signs of internal agitation, however, were not wanting. Each fragment threw out a short tail in a direction perpendicular to the line joining their centers, and each developed a bright nucleus, although the original comet had exhibited neither of these signs of cometary vitality. A singular interchange of brilliancy was, besides, observed to take place between the coupled objects, each of which alternately outshone and was outshone by the other, while an arc of light, apparently proceeding from the more lustrous, at times bridged the intervening space. Obviously, the gravitational tie, rendered powerless by exiguity of matter, was here replaced by some other form of mutual action, the nature of which can as yet be dealt with only by conjecture. Once more, in August, 1852, the double comet returned to the neighborhood of the Sun, but under circumstances not the most advantageous for observation. Indeed, the companion was not detected until September 16, when Father Secchi at Rome perceived it to have increased its distance from the originating body to 1.25 million of miles, or about 8 times the average interval at the former appearance. Both vanished shortly afterwards, and have never since been seen, notwithstanding the eager watch kept for objects of such singular interest, and the accurate knowledge of their track supplied by Santini's investigations. A dangerously near approach to Jupiter in 1841 is believed to have occasioned their disruption, and the disaggregating process thus started was likely to continue. We can scarcely doubt that the fate has overtaken them which Newton assigned as the end of all cometary existence. Defundi tandem et spargi Persillas universos. Biela's is not the only vanished comet. Brorsen's, discovered at Kiel in 1846, and observed at 4 subsequent returns, failed unaccountably to become visible in 1890. Yet numerous sentinels were on the alert to surprise its approach along a well-ascertained track, traversed in 5.5 years. The object presented from the first a somewhat time-worn aspect. It was devoid of tail, or any other kind of appendage, and the rapid loss of the light acquired during perihelion passage was accompanied by inordinate expansion of an already tenuous globular mass. Another lost or mislaid comet is one found by de Vico at Rome, August 22, 1844. It was expected to return early in 1850, but did not, and has never since been seen, unless its reappearance as E. Swift's comet of 1894 should be ratified by closer inquiry. A telescopic comet with a period of 7.5 years, discovered November 22, 1843, by M. Fay of the Paris Observatory, formed the subject of a characteristically patient and profound inquiry on the part of Leverrier, designed to test its suggested identity with Lexell's comet of 1770. The result was decisive against the hypothesis of Valls, the divergences between the orbits of the two bodies being found to increase instead of to diminish, as the history of the newcomer was traced backward into the previous century. Fay's comet pursues the most nearly circular path of any similar known object. Even at its nearest approach to the Sun it remains farther off than Mars when he is most distant from it. And it was proved by the admirable researches of Professor Axel Mahler, director of the Swedish Observatory of Lund, to exhibit no trace of the action of a resisting medium. Periodical comets are evidently bodies which have each lived through a chapter of accidents. And a significant hint as to the nature of their adventures can be gathered from the fact that their aphelia are pretty closely grouped about the tracks of the major planets. Halley's, and 5 other comets are thus related to Neptune, 3 connect themselves with Uranus, 2 with Saturn, above a score with Jupiter. Some form of dependence is plainly indicated, and the researches of Tisserand, Calandro, and Newton of Yale College, leave scarcely a doubt that the capture theory represents the essential truth in the matter. The original parabolic paths of these comets were then changed into ellipses by the backward pull of a planet, whose sphere of attraction they chanced to enter when approaching the Sun from outer space. Moreover, since a body thus affected should necessarily return at each revolution to the scene of encounter, the same process of retardation may, in some cases, have been repeated many times, until the more restricted cometary orbits were reduced to their present dimensions. The prevalence, too, among periodical comets, of direct motion, is shown to be inevitable by M. Calandro's demonstration that those traveling in a retrograde direction would, by planetary action, be thrown outside the probable range of terrestrial observation. The scarcity of hyperbolic comets can be similarly explained. They would be created whenever the attractive influence of the disturbing planet was exerted in a forward or accelerative sense, but could come only by a rare exception to our notice. The inner planets, including the Earth, have also unquestionably played their parts in modifying cometary orbits, and Mr. Plummer suggests, with some show of reason, that the capture of Encke's comet may be a feat due to Mercury. No great comet appeared between the star which presided at the birth of Napoleon and the vintage comet of 1811. The latter was first described by Flaugergues at Viviers, March 26, 1811. Wisniewski, at Nutz-Cherkask in southern Russia, caught a final glimpse of it, August 17, 1812. 2 disappearances in the solar rays as the Earth moved round in its orbit, and 2 reappearances after conjunction, were included in this unprecedentedly long period of visibility of 510 days. This relative permanence, so far as the inhabitants of Europe were concerned, was due to the high northern latitude attained near perihelion, combined with a certain leisureliness of movement along a path everywhere external to that of the Earth. The magnificent luminous train of this body, on October 15, the day of its nearest terrestrial approach, covered an arc of the heavens 23.1/2 degrees in length, corresponding to a real extension of 100 millions of miles. Its form was described by Sir William Herschel as that of an inverted hollow cone, and its color as yellowish, strongly contrasted with the bluish-green tint of the head, round which it was flung like a transparent veil. The planetary disk of the head, 127,000 miles across, appeared to be composed of strongly condensed nebulous matter. But somewhat eccentrically situated within it was a star-like nucleus of a reddish tinge, which Herschel presumed to be solid, and ascertained, with his usual care, to have a diameter of 428 miles. From the total absence of phases, as well as from the vivacity of its radiance, he confidently inferred that its light was not borrowed, but inherent. This remarkable apparition formed the subject of a memoir by Olbers, the striking yet steadily reasoned-out suggestions contained in which there was at that time no means of following up with profit. Only of late has the electrical theory, of which Zollner regarded Olbers as the founder, assumed a definite and measurable form, capable of being tested by the touchstone of fact. As knowledge makes its slow inroads on the fundamental mystery of the physical universe. The paraboloidal shape of the bright envelope separated by a dark interval from the head of the great comet of 1811, and constituting, as it were, the root of its tail, seemed to the astronomer of Bremen to reveal the presence of a double repulsion. The expelled vapors accumulating where the two forces, solar and cometary, balanced each other, and being then swept backwards in a huge train. He accordingly distinguished three classes of these bodies. First, comets which develop no matter subject to solar repulsion. These have no tails, and are probably mere nebulosities, without solid nuclei. Secondly, comets which are acted upon by solar repulsion only, and consequently throw out no emanations towards the sun. Of this kind was a bright comet visible in 1807. Thirdly, comets like that of 1811, giving evidence of action of both kinds. These are distinguished by a dark hoop encompassing the head and dividing it from the luminous envelope, as well as by an obscure caudal axis, resulting from the hollow, cone-like structure of the tail. Again, the ingenious view subsequently propounded by M. Brédikhine as to the connection between the form of these appendages and the kind of matter composing them, was very clearly anticipated by Olbers. The amount of tail curvature, he pointed out, depends in each case upon the proportion borne by the velocity of the ascending particles to that of the comet in its orbit. The swifter the outrush, the straighter the resulting tail. But the velocity of the ascending particles varies with the energy of their repulsion by the sun, and this again, it may be presumed, with their quality. Thus multiple tails are developed when the same comet throws off, as it approaches perihelion, specifically distinct substances. The long, straight ray which proceeded from the comet of 1807, for example, was doubtless made up of particles subject to a much more vigorous solar repulsion than those formed into the shorter curved emanation issuing from it nearly in the same direction. In the comet of 1811 he calculated that the particles expelled from the head traveled to the remote extremity of the tail in 11 minutes. Indicating by this enormous rapidity of movement, comparable to that of the transmission of light, the action of a force much more powerful than the opposing one of gravity. The not uncommon phenomena of multiple envelopes, on the other hand, he explained as due to the varying amounts of repulsion exercised by the nucleus itself on the different kinds of matter developed from it. The movements and perturbations of the comet of 1811 were no less profoundly studied by Argelander than its physical constitution by Olbers. The orbit which he assigned to it is of such vast dimensions as to require no less than 3,065 years for the completion of its circuit, and to carry the body describing it at each revolution to 14 times the distance from the sun of the frigid Neptune. Thus, when it last visited our neighborhood, Achilles may have gazed on its imposing train as he lay on the sands all night bewailing the loss of Patroclus. And when it returns, it will perhaps be to shine upon the ruins of empires and civilizations still deep buried among the secrets of the coming time. On the 26th of June, 1819, while the head of a comet passed across the face of the sun, the earth was in all probability involved in its tail. But of this remarkable double event nothing was known until more than a month later, when the fact of its past occurrence emerged from the calculations of Olbers. Nor had the comet itself been generally visible previous to the first days of July. Several observers, however, on the publication of these results, brought forward accounts of singular spots perceived by them upon the sun at the time of the transit, and an original drawing of one of them, by Pastorff of Buchholz, has been preserved. This undoubtedly authentic delineation represents a round nebulous object with a bright spot in the center, of decidedly cometary aspect, and not in the least like an ordinary solar macula. Mr. Hind, nevertheless, showed its position on the Sun to be irreconcilable with that which the comet must have occupied, and Mr. Ranyard's discovery of a similar smaller drawing by the same author, dated May 26, 1828, reduces to evanescence the probability of its connection with that body. Indeed, recent experience renders very doubtful the possibility of such an observation. The return of Halley's comet in 1835 was looked forward to as an opportunity for testing the truth of floating cometary theories, and did not altogether disappoint expectation. As early as 1817, its movements and disturbances since 1759 were proposed by the Turin Academy of Sciences as the subject of a prize ultimately awarded to Baron Damoiseau. Ponteculant was adjudged a similar distinction by the Paris Academy in 1829. While Rosenberger's calculations were rewarded with the gold medal of the Royal Astronomical Society. They were verified by the detection at Rome, August 6, 1835, of a nearly circular misty object not far from the predicted place of the comet. It was not, however, until the middle of September that it began to throw out a tail, which by the 15th of October had attained a length of about 24 degrees, on the 19th, at Madras, it extended to fully 30. The head showing to the naked eye as a reddish star rather brighter than Aldebaran or Antares. Some curious phenomena accompanied the process of tail formation. An outrush of luminous matter, resembling in shape a partially opened fan, issued from the nucleus towards the Sun, and at a certain point, like smoke driven before a high wind, was vehemently swept backwards in a prolonged train. The appearance of the comet at this time was compared by Bessel, who watched it with minute attention, to that of a blazing rocket. He made the singular observation that this fan of light, which seemed the source of supply for the tail, oscillated like a pendulum to and fro across a line joining the Sun and nucleus, in a period of 4 3/5 days. And he was unable to escape from the conclusion that a repulsive force, about twice as powerful as the attractive force of gravity, was concerned in the production of these remarkable effects. Nor did he hesitate to recur to the analogy of magnetic polarity, or to declare, still more emphatically than Olbers, the emission of the tail to be a purely electrical phenomenon. The transformations undergone by this body were almost as strange and complete as those which affected the brigands in Dante's Inferno. When first seen, it wore the aspect of a nebula, later it put on the distinctive garb of a comet. It next appeared as a star. Finally, it dilated, first in a spherical, then in a paraboloidal form, until May 5, 1836, when it vanished from Herschel's observation at Feldhausen as if by melting into adjacent space from the excessive diffusion of its light. A very uncommon circumstance in its development was that it lost all trace of tail previous to its arrival at perihelion on the 16th of November. Nor did it begin to recover its elongated shape for more than 2 months afterwards. On the 23rd of January, Boguslawski perceived it as a star of the 6th magnitude, without measurable disk. Only 2 nights later, Maclear, director of the Cape Observatory, found the head to be 131 seconds across. And so rapidly did the augmentation of size progress, that Sir John Herschel estimated the actual bulk of this singular object to have increased 40-fold in the ensuing week. I can hardly doubt, he remarks, that the comet was fairly evaporated in perihelio by the heat, and resolved into transparent vapor, and is now in process of rapid condensation and reprecipitation on the nucleus. A plausible, but no longer admissible, interpretation of this still unexplained phenomenon. The next return of this body, which will be considerably accelerated by Jupiter's influence, is expected to take place in 1910. By means of an instrument devised to test the quality of light, Arago obtained decisive evidence that some at least of the radiance proceeding from Halley's comet was derived by reflection from the Sun. Indications of the same kind had been afforded by the comet which suddenly appeared above the northwestern horizon of Paris, July 3, 1819, after having enveloped, as already stated, our terrestrial abode in its filmy appendages. But the polariscope had not then reached the perfection subsequently given to it, and its testimony was accordingly far less reliable than in 1835. Such experiments, however, are in reality more beautiful and ingenious than instructive, since ignited as well as obscure bodies possess the power of throwing back light incident upon them, and will consequently transmit to us from the neighborhood of the sun rays partly direct, partly reflected, of which a certain proportion will exhibit the peculiarity known as polarization. The most brilliant comets of the century were suddenly rivaled if not surpassed by the extraordinary object which blazed out beside the Sunday, February 28, 1843. It was simultaneously perceived in Mexico and the United States, in southern Europe, and at sea off the Cape of Good Hope, where the passengers on board the Owen Glendower were amazed by the sight of a short, dagger-like object, closely following the sun towards the western horizon. At Florence, Amici found its distance from the sun's center at noon to be only 1 degree 23, and spectators at Parma were able, when sheltered from the direct glare of midday, to trace the tail to a length of 4 or 5 degrees. The full dimensions of this astonishing appurtenance began to be disclosed a few days later. On the 3rd of March it measured 25 degrees, and on the 11th, at Calcutta, Mr. Clerke observed a second streamer, nearly twice as long as the first, and making an angle with it of 18 degrees, to have been emitted in a single day. This rapidity of projection, Sir John Herschel remarked, conveys an astounding impression of the intensity of the forces at work. It is clear, he continued, that if we have to deal here with matter, such as we conceive it, viz. possessing inertia, at all, it must be under the dominion of forces incomparably more energetic than gravitation, and quite of a different nature. On the 17th of March a silvery ray, some 40 degrees long and slightly curved at its extremity, shone out above the sunset clouds in this country. No previous intimation had been received of the possibility of such an apparition, and even astronomers, no lightning messages across the seas being as yet possible, were perplexed. The nature of the phenomenon, indeed, soon became evident, but the wonder of it did not diminish with the study of its attendant circumstances. Never before, within astronomical memory, had our system been traversed by a body pursuing such an adventurous career. The closest analogy was offered by the great comet of 1680, Newton's, which rushed past the sun at a distance of only 144,000 miles. But even this, on the cosmical scale, scarcely perceptible interval was reduced nearly one-half in the case we are now concerned with. The center of the comet of 1843 approached the formidable luminary within 78,000 miles, leaving, it is estimated, a clear space of not more than 32,000 between the surfaces of the bodies brought into such perilous proximity. The escape of the wanderer was, however, secured by the extraordinary rapidity of its flight. It swept past perihelion at a rate, 366 miles a second, which, if continued, would have carried it right round the sun in 2 hours. And in only 11 minutes more than that short period it actually described half the curvature of its orbit, an arc of 180 degree, although in traveling over the remaining half many hundreds of sluggish years will doubtless be consumed. The behavior of this comet may be regarded as an experimentum crucis as to the nature of tails. For clearly no fixed appendage many millions of miles in length could be whirled like a brandished saber from one side of the sun to the other in 131 minutes. Cometary trains are then, as Olbers rightly conceived them to be, emanations, not appendages, inconceivably rapid outflows of highly rarefied matter, the greater part, if not all, of which becomes permanently detached from the nucleus. That of the comet of 1843 reached, about the time that it became visible in this country, the extravagant length of 200 millions of miles. It was narrow, and bounded by nearly parallel and nearly rectilinear lines, resembling, to borrow a comparison of Aristotle's, a road through the constellations. And after the 3rd of March showed no trace of hollowness, the axis being, in fact, rather brighter than the edges. Distinctly perceptible in it were those singular aurora-like coruscations which gave to the tresses of Charles V's comet the appearance, as Cardan described it, of a torch agitated by the wind, and have not unfrequently been observed to characterize other similar objects. A consideration first adverted to by Olbers proves these to originate in our own atmosphere. For owing to the great difference in the distances from the Earth of the origin and extremity of such vast effluxes, the light proceeding from their various parts is transmitted to our eyes in notably different intervals of time. Consequently a luminous undulation, even though propagated instantaneously from end to end of a comet's tail, would appear to us to occupy many minutes in its progress. But the coruscations in question pass as swiftly as a falling star. They are, then, of terrestrial production. Periods of the utmost variety were by different computators assigned to the body, which arrived at perihelion, February 27, 1843, at 9:47 p.m. Professor Hubbard of Washington found that it required 533 years to complete a revolution, and Laudier and Mauvais of Paris considered the true term to be 35, Clausen looked for its return at the end of between 6 and 7. A recent discussion by Professor Kreutz of all the available data gives a probable period of 512 years for this body, and precludes its hypothetical identity with the comet of 1668, known as the Spina of Cassini. It may now be asked, what were the conclusions regarding the nature of comets drawn by astronomers from the considerable amount of novel experience accumulated during the first half of this century? The first and best assured was that the matter composing them is in a state of extreme tenuity. Numerous and trustworthy observations showed that the feeblest rays of light might traverse some hundreds of thousands of miles of their substance, even where it was apparently most condensed, without being perceptibly weakened. Nay, instances were recorded in which stars were said to have gained in brightness from the process. On the 24th of June, 1825, Olbers saw the comet then visible all but obliterated by the central passage of a star too small to be distinguished with the naked eye, its own light remaining wholly unchanged. A similar effect was noted December 1, 1811, when the great comet of that year approached so close to Altair, the Lucida of the Eagle, that the star seemed to be transformed into the nucleus of the comet. Even the central blaze of Halley's comet in 1835 was powerless to impede the passage of stellar rays. Struve observed at Dorpat, on September 17, an all but central occultation. Glacier 1, so far as he could ascertain, absolutely so 8 days later at Cambridge. In neither case was there any appreciable diminution of the star's light. Again, on the 11th of October, 1847, Mr. Dawes, an exceptionally keen observer, distinctly saw a star of the 10th magnitude through the exact center of a comet discovered on the 1st of that month by Maria Mitchell of Nantucket. Examples, on the other hand, are not wanting of the diminution of stellar light under similar circumstances, and we meet 2 alleged instances of the vanishing of a star behind a comet. Wortmann of Geneva observed the first, November 28, 1828. But his instrument was defective, and the eclipsing body, Encke's comet, has shown itself otherwise perfectly translucent. The second case of occultation occurred September 13, 1890, when an 11th magnitude star was stated to have completely disappeared during the transit over it of Denning's comet. From the failure to detect any effects of refraction in the light of stars occulted by comets, it was inferred, though, as we know now, erroneously, that their composition is rather that of dust than that of vapor. That they consist not of any continuous substance, but of discrete solid particles, very finely divided and widely scattered. In conformity with this view was the known smallness of their masses. Laplace had shown that if the amount of matter forming Lexell's comet had been as much as January 50th of that contained in our globe, the effect of its attraction, on the occasion of its approach within 1,438,000 miles of the Earth, July 1, 1770, must have been apparent in the lengthening of the year. And that some comets, at any rate, possess masses immeasurably below this maximum value was clearly proved by the undisturbed parallel march of the 2 fragments of Biela's in 1846. But the discovery in this branch most distinctive of the period under review is that of short-period comets, of which 4 were known in 1850. These, by the character of their movements, serve as a link between the planetary and cometary worlds, and by the nature of their construction, seem to mark a stage in cometary decay. For that comets are rather transitory agglomerations, than permanent products of cosmical manufacture, appeared to be demonstrated by the division and disappearance of one amongst their number, as well as by the singular and rapid changes in appearance undergone by many, and the seemingly irrevocable diffusion of their substance visible in nearly all. They might then be defined, according to the ideas respecting them prevalent 50 years ago, as bodies unconnected by origin with the solar system, but encountered, and to some extent appropriated, by it in its progress through space. Owing their visibility in great part, if not altogether, to light reflected from the sun, and their singular and striking forms to the action of repulsive forces emanating from him. The penalty of their evanescent splendor being paid in gradual waste and final dissipation and extinction. Footnotes. Allgemeine Geographische Ephemeriden, Volume 4, page 287. Astre. Jahrbuch, 1823, page 217. The period, 1,208 days, of this body is considerably shorter than that of any other known comet. Sic et bombas's philo fundendo, sic cometas cauda experanda consumi et denique mori. De Comtes, Op., Volume 7, page 110. Considerable uncertainty, however, still prevails on the point. The inverse relation assumed by Lagrange to exist between distance from the Sun and density brought out the Mercurian mass 1/2025810, that of the Sun, Laplace, Exposition d'Ouest du Monde, t. 2, page 50, edition 1824. Von Aston deduced from the movements of Encke's comet, 1818-48, a value of 1/7636440, while Backlund from its 7 returns, 1871-1891, derived 1/9647000, Comptes Rendus, October 1, 1894. Arago, Unware, 1832, page 218. Hind, The Comets, page 20. Phil. Trans, volume 46, page 204. Astre. Nock, number 2134. Comptes Rendus, T. Kvi, page 588. MEM. De St. Petersburg, T. 32, number 3, 1884, Astre. Nock, number 2727. Month. Knot, volume 19, page 72. Mécanique Céleste, T. 2, page 197. C. Berberic, Astre. Nock, numbers 2836-7, 3125, Deichmuller, Ibid, number 3123. Month. Knot, volume 2, page 117. Astre. Nock, number 128. Unware, 1832, page 186. A.M. Journ. Of Science, Volume 1, 2nd Series, page 293. Prof. Hubbard's calculations indicated a probability that the definitive separation of the two nuclei occurred as early as September 30, 1884. Astronomical Journal, Gould's, Volume 4, page 5. See also, on the subject of this comet, W. T. Lynn, Intellectual Observer, Volume 11, page 208, E. Ledger, Observatory, August, 1883, page 244, and H. A. Newton, A.M. Journ. Of Science, Volume 31, page 81, February, 1886. Month. Knot, Volume 7, page 73. Bulletin A.C., Imp de St. Petersburg, T. 6. Kernel 77. The latest observation of the parent nucleus was that of Argelander, April 27, at Bonn. Darist, Astre. Nock, number 1624. Der Brorsinski Comet. Vaughan Drive E. Lamp, Kiel, 1892, Plummer, Knowledge, Volume 19, page 41. Schulhoff, Astre. Nock, No. 3267, Observatory, Volume 18, page 64, F. H. Sears, Astr. Knock, numbers 3606-7, Plummer, Knowledge, Volume 19, page 156. Comptes Rendus, T. 25, page 570. Month. Knot, Volume 12, page 248. Bull. Astr. T. 6, pages 241, 289. Études sur la théorie des comètes périodiques. Annales de l'Observatoire, T. XX, Paris, 1891. America Journal of Science, Volume 42, pages 183, 482, 1891. Observatory, Volume 14, page 194. Phil. Trans, Volume CII, pages 118 to 124. Über den Schweif de großen Comten von 1811, Monat. Core, Volume 25, pages 3 to 22. Reprinted by Zollner. Über die Natur der Comten, pages 3 to 15. Natur der Comten, page 148. The subject of a classical memoir by Bessel, published in 1810. A fresh investigation of its orbit has been published by N. Herz of Vienna. See Bull. Astr. T. 9, page 427. Astr. Jarbuch, Bodes, 1823, page 134. Reproduced in Web Celestial Objects, 4th ed. Month. Knot, Volume 36, page 309. Celestial Objects, page 40, note. See Aries Address MEM. R.A.S., Volume 10, page 376. Rosenberger calculated no more, though he lived until 1890. W. T. Lynn, Observatory, Volume 13, page 125. Hind, The Comets, page 47. Arago, Unware, 1836, page 228. Astr. Knock, number 300. It deserves to be recorded that Robert Hooke drew a very similar inference from his observations of the comets of 1680 and 1682. Month. Knot, Volume 14, pages 77 to 83. Briefwechsel zwischen Olbers und Bessel, BD, 2, page 390. Herschel, Results, page 405. MEM. R.A.S., Volume 10, page 92. Results, page 401. Ponteculant, Comptes Rendus, T. 58, page 825. Unware, 1836, page 233. Cosmos, Volume 1, page 90, note, Aut trans. Herschel, Outlines of Astronomy, page 399, 9th ed. Outlines, page 398. Boguslawski calculated that it extended on the 21st of March to 581 millions. Report. Brit. As, 1845, page 89. Comptes Rendus, T. 16, page 919. Observatory, Volume 24, page 167, Astra. Knock, number 3320. Piazzi noticed a considerable increase of luster in a very faint star of the 12th magnitude viewed through a comet. Madler, Reedon, etc., page 248, note. Astra. Jarbuch, 1828, page 151. Madler, Gesch. D. Astra, BD, 2, page 412. Recul de l'Ac. Imp. De St. Petersburg, 1835, page 143. Guillemets World of Comets, Trans, by J. Glacier, page 294, note. Month. Knot, Volume 8, page 9. A real, though only partial stoppage of light seems indicated by Herschel's observations on the comet of 1807. Stars seen through the tail, October 18, lost much of their luster. One near the head was only faintly visible by glimpses. Phil. Trans, Volume 97, page 153. Arago, Unware, 1832, page 205. Ibid, 1891, page 290. Viz. Enkes, Biela's, Fays, and Brorson's. Chapter 6. Instrumental Advances. It is impossible to follow with intelligent interest the course of astronomical discovery without feeling some curiosity as to the means by which such surpassing results have been secured. Indeed, the bare acquaintance with what has been achieved, without any corresponding knowledge of how it has been achieved, supplies food for barren wonder rather than for fruitful and profitable thought. Ideas advance most readily along the solid ground of practical reality, and often find true sublimity while laying aside empty marvels. Progress is the result, not so much of sudden flights of genius, as of sustained, patient, often commonplace endeavor. And the true lesson of scientific history lies in the close connection which it discloses between the most brilliant developments of knowledge and the faithful accomplishment of his daily task by each individual thinker and worker. It would be easy to fill a volume with the detailed account of the long succession of optical and mechanical improvements by means of which the observation of the heavens has been brought to its present degree of perfection. But we must here content ourselves with a summary sketch of the chief amongst them. The first place in our consideration is naturally claimed by the telescope. This marvelous instrument, we need hardly remind our readers, is of two distinct kinds, that in which light is gathered together into a focus by refraction, and that in which the same end is attained by reflection. The image formed is in each case viewed through a magnifying lens, or combination of lenses, called the eyepiece. Not for above a century after the optic glasses, invented or stumbled upon by the spectacle maker of Middelburg, 1608, had become diffused over Europe, did the reflecting telescope come, even in England, the place of its birth, into general use. Its principle, a sufficiently obvious one, had indeed been suggested by Mersenne as early as 1639, James Gregory in 1663 described in detail a mode of embodying that principle in a practical shape. And Newton, adopting an original system of construction, actually produced in 1668 a tiny speculum, 1 inch across, by means of which the apparent distance of objects was reduced 39 times. Nevertheless, the exorbitantly long tubeless refractors, introduced by Huygens, maintained their reputation until Hadley exhibited to the Royal Society, January 12, 1721, a reflector of 6 inches aperture, and 62 in focal length, which rivaled in performance, and of course indefinitely surpassed in manageability, one of the Theriot, kind of 123 feet. The concave mirror system now gained a decided ascendant, and was brought to unexampled perfection by James Short of Edinburgh during the years 1732–68. Its resources were, however, first fully developed by William Herschel. The energy and inventiveness of this extraordinary man marked an epoch wherever they were applied. His ardent desire to measure and gauge the stupendous array of worlds which his specula revealed to him, made him continually intent upon adding to their space-penetrating power, by increasing their light-gathering surface. These, as he was the first to explain, are in a constant proportion one to the other. For a telescope with twice the linear aperture of another will collect 4 times as much light, and will consequently disclose an object 4 times as faint as could be seen with the first, or, what comes to the same, an object equally bright at twice the distance. In other words, it will possess double the space-penetrating power of the smaller instrument. Herschel's great mirrors, the first examples of the giant telescopes of modern times, were then primarily engines for extending the bounds of the visible universe. And from the sublimity of this final cause was derived the vivid enthusiasm which animated his efforts to success. It seems probable that the 7-foot telescope constructed by him in 1775, that is within little more than a year after his experiments in shaping and polishing metal had begun, already exceeded in effective power any work by an earlier optician. And both his skill and his ambition rapidly developed. His efforts culminated, after mirrors of 10, 20, and 30 feet focal length had successively left his hands, in the gigantic 40-foot, completed August 28, 1789. It was the first reflector in which only a single mirror was employed. In the Gregorian form, the focused rays are, by a second reflection from a small concave mirror, thrown straight back through a central aperture in the larger one, behind which the eyepiece is fixed. The object under examination is thus seen in the natural direction. The Newtonian, on the other hand, shows the object in a line of sight at right angles to the true one, the light collected by the speculum being diverted to one side of the tube by the interposition of a small plane mirror, situated at an angle of 45 degrees to the axis of the instrument. Upon these two systems Herschel worked until 1787, when, becoming convinced of the supreme importance of economizing light, necessarily wasted by the second reflection, he laid aside the small mirror of his 40-foot then in course of construction, and turned it into a front-view reflector. This was done, according to the plan proposed by Lemaire in 1732, by slightly inclining the speculum so as to enable the image formed by it to be viewed with an eyeglass fixed at the upper margin of the tube. The observer thus stood with his back turned to the object he was engaged in scrutinizing. The advantages of the increased brilliancy afforded by this modification were strikingly illustrated by the discovery, August 28 and September 17, 1789, of the two Saturnian satellites nearest the ring. Nevertheless, the monster telescope of Slough cannot be said to have realized the sanguine expectations of its constructor. The occasions on which it could be usefully employed were found to be extremely rare. It was injuriously affected by every change of temperature. The great weight, 25 cwt, of a speculum 4 feet in diameter rendered it peculiarly liable to distortion. With all imaginable care, the delicate luster of its surface could not be preserved longer than 2 years, when the difficult process of repolishing had to be undertaken. It was accordingly never used after 1811, when, having gone blind from damp, it lapsed by degrees into the condition of a museum inmate. The exceedingly high magnifying powers employed by Herschel constituted a novelty in optical astronomy, to which he attached great importance. The work of ordinary observation would, however, be hindered rather than helped by them. The attempt to increase in this manner the efficacy of the telescope is speedily checked by atmospheric, to say nothing of other difficulties. Precisely in the same proportion as an object is magnified, the disturbances of the medium through which it is seen are magnified also. Even on the clearest and most tranquil nights, the air is never for a moment really still. The rays of light traversing it are continually broken by minute fluctuations of refractive power caused by changes of temperature and pressure, and the currents which these engender. With such luminous quiverings and waverings the astronomer has always more or less to reckon. Their absence is simply a question of degree. If sufficiently magnified, they are at all times capable of rendering observation impossible. Thus, such powers as 3,000, 4,000, 5,000, even 6,652, which Herschel now and again applied to his great telescopes, must, save on the rarest occasions, prove an impediment rather than an aid to vision. They were, however, used by him only for special purposes, experimentally, not systematically, and with the clearest discrimination of their advantages and drawbacks. It is obvious that perfectly different ends are subserved by increasing the aperture and by increasing the power of a telescope. In the one case, a larger quantity of light is captured and concentrated. In the other, the same amount is distributed over a wider area. A diminution of brilliancy in the image accordingly attends, coeteris paribus, upon each augmentation of its apparent size. For this reason, such faint objects as nebulae are most successfully observed with moderate powers applied to instruments of a great capacity for light, the details of their structure actually disappearing when highly magnified. With stellar groups the reverse is the case. Stars cannot be magnified, simply because they are too remote to have any sensible dimensions, but the space between them can. It was thus for the purpose of dividing very close double stars that Herschel increased to such an unprecedented extent the magnifying capabilities of his instruments. And to this improvement incidentally the discovery of Uranus, March 13, 1781, was due. For by the examination with strong lenses of an object which, even with a power of 227, presented a suspicious appearance, he was able at once to pronounce its disk to be real, not merely spurious. And so to distinguish it unerringly from the crowd of stars amidst which it was moving. While the reflecting telescope was astonishing the world by its rapid development in the hands of Herschel, its unpretending rival was slowly making its way towards the position which the future had in store for it. The great obstacle which long stood in the way of the improvement of refractors was the defect known as chromatic aberration. This is due to no other cause than that which produces the rainbow and the spectrum, the separation, or dispersion, in their passage through a refracting medium, of the variously colored rays composing a beam of white light. In an ordinary lens there is no common point of concentration, each color has its own separate focus. And the resulting image, formed by the superposition of as many images as there are hues in the spectrum, is indefinitely terminated with a tinted border, eminently baffling to exactness of observation. The extravagantly long telescopes of the 17th century were designed to avoid this evil, as well as another source of indistinct vision in the spherical shape of lenses. But no attempt to remedy it was made until an Essex gentleman succeeded, in 1733, in so combining lenses of flint and crown glass as to produce refraction without color. Mr. Chester More Hall was, however, equally indifferent to fame and profit, and took no pains to make his invention public. The effective discovery of the achromatic telescope was, accordingly, reserved for John Dolland, whose method of correcting at the same time chromatic and spherical aberration was laid before the Royal Society in 1758. Modern astronomy may be said to have been thereby rendered possible. Refractors have always been found better suited than reflectors to the ordinary work of observatories. They are, so to speak, of a more robust, as well as of a more plastic nature. They suffer less from vicissitudes of temperature and climate. They retain their efficiency with fewer precautions and under more trying circumstances. Above all, they cooperate more readily with mechanical appliances, and lend themselves with far greater facility to purposes of exact measurement. A practical difficulty, however, impeded the realization of the brilliant prospects held out by Dolland's invention. It was found impossible to procure flint glass, such as was needed for optical use, that is, of perfectly homogeneous quality, except in fragments of insignificant size. Discs of more than 2 or 3 inches in diameter were of extreme rarity. And the crushing excise duty imposed upon the article by the financial unwisdom of the government, both limited its production, and, by rendering experiments too costly for repetition, barred its improvement. Up to this time, Great Britain had left foreign competitors far behind in the instrumental department of astronomy. The quadrants and circles of Bird, Carey and Ramsden were unapproached abroad. The reflecting telescope came into existence and reached maturity on British soil. The refracting telescope was cured of its inherent vices by British ingenuity. But with the opening of the 19th century, the almost unbroken monopoly of skill and contrivance which our countrymen had succeeded in establishing was invaded. And British workmen had to be content to exchange a position of supremacy for one of at least partial temporary inferiority. Somewhat about the time that Herschel set about polishing his first speculum, Pierre-Louis Guinand, a Swiss artisan, living near Chaux-de-Fonds, in the canton of Neuchâtel, began to grind spectacles for his own use. And was thence led on to the rude construction of telescopes by fixing lenses in pasteboard tubes. The sight of an England achromatic stirred a higher ambition, and he took the first opportunity of procuring some flint glass from England, then the only source of supply. With the design of imitating an instrument the full capabilities of which he was destined to be the humble means of developing. The English glass proving of inferior quality, he conceived the possibility, unaided and ignorant of the art as he was, of himself making better, and spent 7 years, 1784–90, in fruitless experiments directed to that end. Failure only stimulated him to enlarge their scale. He bought some land near Les Brenets, constructed upon it a furnace capable of melting 2 quintals of glass, and reducing himself and his family to the barest necessaries of life. He poured his earnings, he at this time made bells for repeaters, unstintingly into his crucibles. His undaunted resolution triumphed. In 1799 he carried to Paris and there showed to Lalande several discs of flawless crystal 4 to 6 inches in diameter. Lalande advised him to keep his secret, but in 1805 he was induced to remove to Munich, where he became the instructor of the immortal Fraunhofer. His return to Les Brunets in 1814 was signalized by the discovery of an ingenious mode of removing striated portions of glass by breaking and resoldering the product of each melting. And he eventually attained to the manufacture of perfect discs up to 18 inches in diameter. An object glass for which he had furnished the material to Cauchois, procured him, in 1823, a royal invitation to settle in Paris, but he was no longer equal to the change, and died at the scene of his labors, February 13 following. This same lens, 12 inches across, was afterwards purchased by Sir James South, and the first observation made with it, February 13, 1830, disclosed to Sir John Herschel the 6th-minute star in the central group of the Orion Nebula. Known as the trapezium. Bequeathed by South to Trinity College, Dublin, it was employed at the Dunsink Observatory by Bruno and Ball in their investigations of stellar parallax. A still larger objective, of nearly 14 inches, made of Guinand's glass was secured in Paris, about the same time, by Mr. Edward Cooper of Markrey Castle, Ireland. The peculiarity of the method discovered at Les Brunets resided in the manipulation, not in the quality of the ingredients. The secret, that is to say, was not chemical, but mechanical. It was communicated by Henry Guinand, a son of the inventor, to Bontemps, one of the directors of the glassworks at Choisy-le-Roi, and by him transmitted to Messrs. Chance of Birmingham, with whom he entered into partnership when the revolutionary troubles of 1848 obliged him to quit his native country. The celebrated American opticians, Alvan Clark and Sons, derived from the Birmingham firm the materials for some of their early telescopes, notably the 19-inch Chicago and 26-inch Washington equatorials. But the discs for the Great Lick refractor, and others shaped by them in recent years, have been supplied by File of Paris. Two distinguished amateurs, meanwhile, were preparing to reassert on behalf of reflecting instruments their claim to the place of honor in the van of astronomical discovery. Of Mr. Lassell's specula something has already been said. They were composed of an alloy of copper and tin, with a minute proportion of arsenic, after the example of Newton, and were remarkable for perfection of figure and brilliancy of surface. The capabilities of the Newtonian plan were developed still more fully, it might almost be said to the uttermost, by the enterprise of an Irish nobleman. William Parsons, known as Lord Oxmantown until 1841, when, on his father's death, he succeeded to the title of Earl of Ross, was born at York, June 17, 1800. His public duties began before his education was completed. He was returned to Parliament as member for King's County while still an undergraduate at Oxford, and continued to represent the same constituency for 13 years, 1821 to 34. From 1845 until his death, which took place, October 31, 1867, he sat, silent but assiduous, in the House of Lords as an Irish representative peer. He held the not unlaborious post of President of the Royal Society from 1849 to 1854. Presided over the meeting of the British Association at Cork in 1843, and was elected Vice-Chancellor of Dublin University in 1862. In addition to these extensive demands upon his time and thoughts, were those derived from his position as practically the feudal chief of a large body of tenantry in times of great and anxious responsibility. To say nothing of the more genial claims of an unstinted hospitality. Yet, while neglecting no public or private duty, this model nobleman found leisure to render to science services so conspicuous as to entitle his name to a lasting place in its annals. He early formed the design of reaching the limits of the attainable in enlarging the powers of the telescope, and the qualities of his mind conspired with the circumstances of his fortune to render the design a feasible one. From refractors it was obvious that no such vast and rapid advance could be expected. English glass manufacture was still in a backward state. So late as 1839, Sims, successor to the distinguished instrumentalist Edward Troughton, reported a specimen of crystal scarcely 7.5 inches in diameter, and perfect only over 6, to be unique in the history of English glassmaking. Yet at that time the 15-inch achromatic of Pulkowa had already left the workshop of Fraunhofer's successors at Munich. It was not indeed until 1845, when the impost which had so long hampered their efforts was removed, that the optical artists of these islands were able to compete on equal terms with their rivals on the continent. In the case of reflectors, however, there seemed no insurmountable obstacle to an almost unlimited increase of light-gathering capacity. And it was here, after some unproductive experiments with fluid lenses, that Lord Oxmantown concentrated his energies. He had to rely entirely on his own invention, and to earn his own experience. James Short had solved the problem of giving to metallic surfaces a perfect parabolic figure, the only one by which parallel incident rays can be brought to an exact focus. But so jealous was he of his secret, that he caused all his tools to be burnt before his death, nor was anything known of the processes by which Herschel had achieved his astonishing results. Moreover, Lord Oxmantown had no skilled workmen to assist him. His implements, both animate and inanimate, had to be formed by himself. Peasants taken from the plough were educated by him into efficient mechanics and engineers. The delicate and complex machinery needed in operations of such hairbreadth nicety as his enterprise involved, the steam engine which was to set it in motion, at times the very crucibles in which his specula were cast, issued from his own workshops. In 1827 experiments on the composition of specula metal were set on foot, and the first polishing machine ever driven by steam power was contrived in 1828. But 12 arduous years of struggle with recurring difficulties passed before success began to dawn. A material less tractable than the alloy selected, of 4 chemical equivalents of copper to 1 of tin, can scarcely be conceived. It is harder than steel, yet brittle as glass, crumbling into fragments with the slightest inadvertence of handling or treatment, and the precision of figure requisite to secure good definition is almost beyond the power of language to convey. The quantities involved are so small as not alone to elude sight, but to confound imagination. Sir John Herschel tells us that, the total thickness to be abraded from the edge of a spherical speculum 48 inches in diameter and 40 feet focus, to convert it into a paraboloid, is only 1/21333 of an inch. Yet upon this minute difference of form depends the clearness of the image, and, as a consequence, the entire efficiency of the instrument. Almost infinite, indeed, in the phrase of the late Dr. Robinson, must be the exactitude of the operation adapted to bring about so delicate a result. At length, in 1839, 2 specula, each 3 feet in diameter, were turned out in such perfection as to prompt a still bolder experiment. The various processes needed to ensure success were now ascertained and under control, all that was necessary was to repeat them on a larger scale. A gigantic mirror, 6 feet across and 54 in focal length, was accordingly cast on the 13th of April, 1842, in 2 months it was ground down to figure by abrasion with emery and water, and daintily polished with rouge. And by the month of February, 1845, the Leviathan of Parsonstown was available for the examination of the heavens. The suitable mounting of this vast machine was a problem scarcely less difficult than its construction. The shape of a speculum needs to be maintained with an elaborate care equal to that used in imparting it. In fact, one of the most formidable obstacles to increasing the size of such reflecting surfaces consists in their liability to bend under their own weight. That of the great Ross speculum was no less than 4 tons. Yet, although 6 inches in thickness, and composed of a material only a degree inferior in rigidity to wrought iron, the strong pressure of a man's hand at its back produced sufficient flexure to distort perceptibly the image of a star reflected in it. Thus the delicacy of its form was perishable equally by the stress of its own gravity, and by the slightest irregularity in the means taken to counteract that stress. The problem of affording a perfectly equable support in all possible positions was solved by resting the speculum upon 27 platforms of cast iron, felt covered, and carefully fitted to the shape of the areas they were to carry. Which platforms were themselves borne by a complex system of triangles and levers, ingeniously adapted to distribute the weight with complete uniformity. A tube which resembled, when erect, one of the ancient round towers of Ireland, served as the habitation of the Great Mirror. It was constructed of deal staves bound together with iron hoops, was 58 feet long, including the speculum box, and 7 in diameter. A reasonably tall man may walk through it, as Dean Peacock once did, with umbrella uplifted. 2 piers of solid masonry, about 50 feet high, 70 long, and 23 apart, flanked the huge engine on either side. Its lower extremity rested on a universal joint of cast iron. Above, it was slung in chains, and even in a gale of wind remained perfectly steady. The weight of the entire, although amounting to 15 tons, was so skillfully counterpoised, that the tube could with ease be raised or depressed by 2 men working a windlass. Its horizontal range was limited by the lofty walls erected for its support to about 10 degrees on each side of the meridian, but it moved vertically from near the horizon through the zenith as far as the pole. Its construction was of the Newtonian kind, the observer looking into the side of the tube near its upper end, which a series of galleries and sliding stages enabled him to reach in any position. It has also, though rarely, been used without a second mirror, as a Herschelian reflector. The splendor of the celestial objects as viewed with this vast light grasper surpassed all expectation. "Never in my life," exclaimed Sir James South, "did I see such glorious sidereal pictures." The orb of Jupiter produced an effect compared to that of the introduction of a coach lamp into the telescope. And certain star clusters exhibited an appearance, we again quote Sir James South, such as man before had never seen, and which for its magnificence baffles all description. But it was in the examination of the nebulae that the superiority of the new instrument was most strikingly displayed. A large number of these misty objects, which the utmost powers of Herschel's specula had failed to resolve into stars, yielded at once to the Parsonstown reflector. While many others showed under entirely changed forms through the disclosure of previously unseen details of structure. One extremely curious result of the increase of light was the abolition of any sharp distinction between the 2 classes of annular and planetary nebulae. Up to that time, only 4 ring-shaped systems, 2 in the northern and 2 in the southern hemisphere, were known to astronomers. They were now reinforced by 5 of the planetary kind, the disks of which were observed to be centrally perforated. While the definite margins visible in weaker instruments were replaced by ragged edges or filamentous fringes. Still more striking was the discovery of an entirely new and most remarkable species of nebulae. These were termed spiral, from the more or less regular convolutions, resembling the whorls of a shell, in which the matter composing them appeared to be distributed. The first and most conspicuous specimen of this class was met with in April, 1845, it is situated in Canes Venatici, close to the tail of the Great Bear, and wore, in Sir J. Herschel's instruments, the aspect of a split ring encompassing a bright nucleus, thus presenting, as he supposed, a complete analogue to the system of the Milky Way. In the Rosse mirror it shone out as a vast whirlpool of light, a stupendous witness to the presence of cosmical activities on the grandest scale, yet regulated by laws as to the nature of which we are profoundly ignorant. Professor Stephen Alexander of New Jersey, however, concluded, from an investigation, necessarily founded on highly precarious data, of the mechanical condition of these extraordinary agglomerations, that we see in them the partially scattered fragments of enormous masses once rotating in a state of dynamical equilibrium. He further suggested that the separation of these fragments may still be in progress, and traced back their origin to the disruption, through its own continually accelerated rotation, of a primitive spheroid of inconceivably vast dimensions. Such also, it was added, the curvilinear form of certain outliers of the Milky Way giving evidence of a spiral structure, is probably the history of our own cluster. The stars composing which, no longer held together in a delicately adjusted system like that of the Sun and planets, are advancing through a period of seeming confusion towards an appointed goal of higher order and more perfect and harmonious adaptation. The class of spiral nebulae included, in 1850, 14 members, besides several in which the characteristic arrangement seemed partial or dubious. A tendency in the exterior stars of other clusters to gather into curved branches, as in our galaxy, was likewise noted. And the existence of unsuspected analogies was proclaimed by the significant combination in the Owl Nebula, a large planetary in Ursa Major, of the twisted forms of a spiral with the perforated effect distinctive of an annular nebula. Once more, by the achievements of the Parsonstown reflector, the supposition of a shining fluid filling vast regions of space was brought into, as it has since proved, undeserved discredit. Although Lord Rosse himself rejected the inference, that because many nebulae had been resolved, all were resolvable, very few imitated his truly scientific caution. And the results of Bond's investigations with the Harvard College refractor quickened and strengthened the current of prevalent opinion. It is now certain that the evidence furnished on both sides of the Atlantic as to the stellar composition of some conspicuous objects of this class, notably the Orion and Dumbbell nebulae, was delusive. But the spectroscope alone was capable of meeting it with a categorical denial. Meanwhile there seemed good ground for the persuasion, which now, for the last time, gained the upper hand, that nebulae are, without exception, true island universes, or assemblages of distant suns. Lord Rosse's telescope possesses a nominal power of 6,000, that is, it shows the moon as if viewed with the naked eye at a distance of 40 miles. But this seeming advantage is neutralized by the weakening of the available light through excessive diffusion, as well as by the troubles of the surging sea of air through which the observation must necessarily be made. Professor Newcomb, in fact, doubts whether with any telescope our satellite has ever been seen to such advantage as it would be if brought within 500 miles of the unarmed eye. The French optician's rule of doubling the number of millimeters contained in the aperture of an instrument to find the highest magnifying power usually applicable to it, would give 3,600 as the maximum for the Leviathan of Bear Castle. But in a climate like that of Ireland the occasions must be rare when even that limit can be reached. Indeed, the experience acquired by its use plainly shows that atmospheric rather than mechanical difficulties impede a still further increase of telescopic power. Its construction may accordingly be said to mark the ne plus ultra of effort in one direction, and the beginning of its conversion towards another. It became thenceforward more and more obvious that the conditions of observation must be ameliorated before any added efficacy could be given to it. The full effect of an uncertain climate in nullifying optical improvements was recognized, and the attention of astronomers began to be turned towards the advantages offered by more tranquil and more translucent skies. Scarcely less important for the practical uses of astronomy than the optical qualities of the telescope is the manner of its mounting. The most admirable performance of the optician can render but unsatisfactory service if its mechanical accessories are ill-arranged or inconvenient. Thus the astronomer is ultimately dependent upon the mechanician. And so excellently have his needs been served, that the history of the ingenious contrivances by which discoveries have been prepared would supply a subject, here barely glanced at, not far inferior in extent and instruction to the history of those discoveries themselves. There are two chief modes of using the telescope, to which all others may be considered subordinate. Either it may be invariably directed towards the south, with no motion save in the plane of the meridian, so as to intercept the heavenly bodies at the moment of transit across that plane. Or it may be arranged so as to follow the daily revolution of the sky, thus keeping the object viewed permanently in sight instead of simply noting the instant of its flitting across the telescopic field. The first plan is that of the transit instrument, the second that of the equatorial. Both were, by a remarkable coincidence, introduced about 1690 by Olaus Rømer, the brilliant Danish astronomer who first measured the velocity of light. The uses of each are entirely different. With the transit, the really fundamental task of astronomy, the determination of the movements of the heavenly bodies, is mainly accomplished. While the investigation of their nature and peculiarities is best conducted with the equatorial. One is the instrument of mathematical, the other of descriptive astronomy. One furnishes the materials with which theories are constructed and the tests by which they are corrected, the other registers new facts, takes note of new appearances, sounds the depths and peers into every nook of the heavens. The great improvement of giving to a telescope equatorially mounted an automatic movement by connecting it with clockwork, was proposed in 1674 by Robert Hooke. Bradley in 1721 actually observed Mars with a telescope moved by a machine that made it keep pace with the stars, and von Zach relates that he had once followed Sirius for 12 hours with a heliostat of Ramsden's construction. But these 18th-century attempts were of no practical effect. Movement by clockwork was virtually a complete novelty when it was adopted by Fraunhofer in 1824 to the Dorpat refractor. By simply giving to an axis unvaryingly directed towards the celestial pole an equable rotation with a period of 24 hours, a telescope attached to it, and pointed in any direction, will trace out on the sky a parallel of declination, thus necessarily accompanying the movement of any star upon which it may be fixed. It accordingly forms part of the large sum of Fraunhofer's merits to have secured this inestimable advantage to observers. Sir John Herschel considered that Lassel's application of equatorial mounting to a 9-inch Newtonian in 1840 made an epoch in the history of that eminently British instrument, the reflecting telescope. Nearly a century earlier, it is true, Short had fitted one of his Gregorians to a complicated system of circles in such a manner that, by moving a handle, it could be made to follow the revolution of the sky. But the arrangement did not obtain, nor did it deserve, general adoption. Lassel's plan was a totally different one. He employed the crossed axes of the true equatorial, and his success removed, to a great extent, the fatal objection of inconvenience in use, until then unanswerably urged against reflectors. The very largest of these can now be mounted equatorially. Even the Rosse, within its limited range, has been for some years provided with a movement by clockwork along declination parallels. The art of accurately dividing circular arcs into the minute equal parts which serve as the units of astronomical measurement, remained, during the whole of the 18th century, almost exclusively in English hands. It was brought to a high degree of perfection by Graham, Bird and Ramsden, all of whom, however, gave the preference to the old-fashioned mural quadrant in zenith sector over the entire circle, which Romer had already found the advantage of employing. The 5-foot vertical circle, which Piazzi with some difficulty induced Ramsden to complete for him in 1789, was the first divided instrument constructed in what may be called the modern style. It was provided with magnifiers for reading off the divisions, one of the neglected improvements of Romer, and was set up above a smaller horizontal circle, forming an altitude and azimuth combination, again Romer's invention, by which both the elevation of a celestial object above the horizon and its position as referred to the horizon could be measured. In the same year, Borda invented the repeating circle, the principle of which had been suggested by Tobias Mayer in 1756, a device for exterminating, so far as possible, errors of graduation by repeating an observation with different parts of the limb. This was perhaps the earliest systematic effort to correct the imperfections of instruments by the manner of their use. The manufacture of astronomical circles was brought to a very refined state of excellence early in the 19th century by Reichenbach at Munich, and after 1818 by Repsold at Hamburg. Bessel states that the reading off on an instrument of the kind by the latter artist was accurate to about 1/80th of a human hair. Meanwhile the traditional reputation of the English school was fully sustained. And Sir George Airy did not hesitate to express his opinion that the new method of graduating circles, published by Troughton in 1809, was the greatest improvement ever made in the art of instrument making. But a more secure road to improvement than that of mere mechanical exactness was pointed out by Bessel. His introduction of a regular theory of instrumental errors might almost be said to have created a new art of observation. Every instrument, he declared in memorable words, must be twice made, once by the artist, and again by the observer. Knowledge is power. Defects that are ascertained and can be allowed for are as good as non-existent. Thus the truism that the best instrument is worthless in the hands of a careless or clumsy observer, became supplemented by the converse maxim, that defective appliances may, through skillful use, be made to yield valuable results. The Königsberg Observations, of which the first installment was published in 1815, set the example of regular reduction for instrumental errors. Since then, it has become an elementary part of an astronomer's duty to study the idiosyncrasy of each one of the mechanical contrivances at his disposal, in order that it's inevitable. But now certified deviations from ideal accuracy may be included amongst the numerous corrections by which the pure essence of even approximate truth is distilled from the rude impressions of sense. Nor is this enough, for the casual circumstances attending each observation have to be taken into account with no less care than the inherent or constitutional peculiarities of the instrument with which it is made. There is no once for all in astronomy. Vigilance can never sleep, patience can never tire. Variable as well as constant sources of error must be anxiously heeded, one infinitesimal inaccuracy must be weighed against another. All the forces and vicissitudes of nature, frosts, dews, winds, the interchanges of heat, the disturbing effects of gravity, the shiverings of the air, the tremors of the earth, the weight and vital warmth of the observer's own body, nay, the rate at which his brain receives and transmits its impressions, must all enter into his calculations, and be sifted out from his results. It was in 1823 that Bessel drew attention to discrepancies in the times of transits given by different astronomers. The quantities involved were far from insignificant. He was himself nearly a second in advance of all his contemporaries, Argelander lagging behind him as much as a second and a quarter. Each individual, in fact, was found to have a certain definite rate of perception, which, under the name of personal equation, now forms so important an element in the correction of observations that a special instrument for accurately determining its amount in each case is in actual use at Greenwich. Such are the refinements upon which modern astronomy depends for its progress. It is a science of hairbreadths and fractions of a second. It exists only by the rigid enforcement of arduous accuracy and unwearying diligence. Whatever secrets the universe still has in store for man will only be communicated on these terms. They are, it must be acknowledged, difficult to comply with. They involve an unceasing struggle against the infirmities of his nature and the instabilities of his position. But the end is not unworthy the sacrifices demanded. One additional ray of light thrown on the marvels of creation, a single, minutest encroachment upon the strongholds of ignorance, is recompense enough for a lifetime of toil. Or rather, the toil is its own reward, if pursued in the lofty spirit which alone becomes it. For it leads through the abysses of space and the unending vistas of time to the very threshold of that infinity and eternity of which the disclosure is reserved for a life to come. Footnotes. Grant, Histoire Astre, page 527. Optica Promota, p. 93. Phil. Trans, volume 32, page 383. Ibid, volume 90, page 65. Cassegrain, a Frenchman, substituted in 1672 a convex for a concave secondary speculum. The tube was thereby enabled to be shortened by twice the focal length of the mirror in question. The Great Melbourne reflector, 4 feet aperture, by Grubb, is constructed upon this plan. Phil. Trans, volume Civ, page 275, note. Phil. Trans, volume 90, page 70. With the 40-foot, however, only very moderate powers seem to have been employed, whence Dr. Robinson argued a deficiency of defining power. Proc. Roy. Irish A.C., volume 2, page 11. Phil. Trans, volume 71, page 492. It is remarkable that, as early as 1695, the possibility of an achromatic combination was inferred by David Gregory from the structure of the human eye. See his Catoptricae et Dioptricae Sphericae Elementa, page 98. Wolf, Biographian, B.D., 2, page 301. Month. Knot, volume 1, page 153. Note. Henravox, Encyclopédie Chimique, T.V., Fasc 5, page 363. C. Ante, page 83. Phil. Trans, volume 7, page 4007. J. Herschel, The Telescope, page 39. Month. Knot, volume 29, page 125. A slight excess of copper renders the metal easier to work, but liable to tarnish. Robinson, Proc. Roy. Irish A.C., Volume 2, page 4. Brit. As, 1843, Dr. Robinson's Closing Address. Athenaeum, September 23, page 866. The Telescope, page 82. Lord Ross in Phil. Trans, Volume CXL, page 302. This method is the same in principle with that applied by Grubb in 1834 to a 15-inch speculum for the Observatory of Armagh. Phil. Trans, Volume Clicks, page 145. Robinson, Proc. Roy. IRAC, Volume 3, p. 120. Astre. Knock, number 536. Airy, Month. Knot, Volume 9, page 120. Astronomical Journal, Gould's, Volume 2, page 97. Ibid, page 160. Lord Ross in Phil. Trans, Volume CXL, page 505. Number 2343 of Herschel's, 1864, Catalogue. Before 1850 a star was visible in each of the two larger openings by which it is pierced, since then, one only. Webb, Celestial Objects, 4th edition, page 409. MEM. AM. AC, Volume 3, page 87, Astre. Knock, number 611. Pop Astre, page 145. This statement must be taken in the most general sense. Supplementary observations of great value are now made at Greenwich with the altitude and azimuth instrument, which likewise serve Piazzi to determine the places of his stars. While a prime vertical instrument is prominent at Pulkowa. As early as 1620, according to R. Wolf, Guess. Der Astre, p. 587, Father Scheiner made the experiment of connecting a telescope with an axis directed to the pole, while Chinese equatorial armilli, dating from the 13th century, existed at Pekin until 1900. When they were carried off as loot to Berlin. J. L. E. Dreyer, Copernicus, Volume 1, page 134. Miscellaneous Works, page 350. Astre. Jarbuch, 1799, published 1796, page 115. Month. Knot, Volume 41, page 189. Phil. Trans, Volume 46, page 242. Grant, History of Astre, page 487. Pop Vorel, page 546. Phil. Trans, Volume 99, page 105. Report Brit. As, 1832, page 132. Pop Vorel, page 432. C. T. Enger, Grundzüge der Nuclearen Astronomischen Beobachtungskunst, page 3. Part 2. Recent Progress of Astronomy. Chapter 1. Foundation of Astronomical Physics. In the year 1826, Heinrich Schwab of Dessau, elated with the hope of speedily delivering himself from the hereditary incubus of an apothecary's shop, obtained from Munich a small telescope and began to observe the sun. His choice of an object for his researches was instigated by his friend Harding of Göttingen. It was a peculiarly happy one. The changes visible in the solar surface were then generally regarded as no less capricious than the changes in the skies of our temperate regions. Consequently, the reckoning and registering of sunspots was a task hardly more inviting to an astronomer than the reckoning and registering of summer clouds. Cassini, Kiel, Lemonnier, Lalande, were unanimous in declaring that no trace of regularity could be detected in their appearances or effacements. D'Alembert pronounced them more curious than really useful. Even Herschel, profoundly as he studied them, and intimately as he was convinced of their importance as symptoms of solar activity, saw no reason to suspect that their abundance and scarcity were subject to orderly alternation. One man alone in the 18th century, Christian Horbo of Copenhagen, divined their periodical character, and foresaw the time when the effects of the sun's vicissitudes upon the globes revolving round him might be investigated with success. But this prophetic utterance was of the nature of a soliloquy rather than of a communication, and remained hidden away in an unpublished journal until 1859, when it was brought to light in a general ransacking of archives. Indeed, Schwab himself was far from anticipating the discovery which fell to his share. He compared his fortune to that of Saul, who, seeking his father's asses, found a kingdom. For the hope which inspired his early resolution lay in quite another direction. His patient ambush was laid for a possible intramercurial planet, which, he thought, must sooner or later betray its existence in crossing the face of the sun. He took, however, the most effectual measures to secure whatever new knowledge might be accessible. During 43 years his imperturbable telescope never failed, weather and health permitting, to bring in its daily report as to how many, or if any, spots were visible on the sun's disk. The information obtained being day by day recorded on a simple and unvarying system. In 1843 he made his first announcement of a probable decennial period, but it met with no general attention. Although Julius Schmidt of Bonn, afterwards director of the Athens Observatory, and Gautier of Geneva were impressed with his figures, and Littrow had himself, in 1836, hinted at the likelihood of some kind of regular recurrence. Schwab, however, worked on, gathering each year fresh evidence of a law such as he had indicated. And when Humboldt published in 1851, in the third volume of his Cosmos, a table of the sunspot statistics collected by him from 1826 downwards, the strength of his case was perceived with, so to speak, a start of surprise. The reality and importance of the discovery were simultaneously recognized, and the persevering Hofrath of Dessau found himself famous among astronomers. His merit, recognized by the bestowal of the Astronomical Society's gold medal in 1857, consisted in his choice of an original and appropriate line of work, and in the admirable tenacity of purpose with which he pursued it. His resources and acquirements were those of an ordinary amateur. He was distinguished solely by the unfortunately rare power of turning both to the best account. He died where he was born and had lived, April 11, 1875, at the ripe age of 86. Meanwhile an investigation of a totally different character, and conducted by totally different means, had been prosecuted to a very similar conclusion. 2 years after Schwab began his solitary observations, Humboldt gave the first impulse, at the Scientific Congress of Berlin in 1828, to a great international movement for attacking simultaneously, in various parts of the globe, the complex problem of terrestrial magnetism. Through the genius and energy of Gauss, Göttingen became its center, thence new apparatus, and a new system for its employment, issued. There, in 1833, the first regular magnetic observatory was founded, whilst at Göttingen was fixed the universal time standard for magnetic observations. A letter addressed by Humboldt in April, 1836, to the Duke of Sussex as President of the Royal Society, enlisted the cooperation of England. A network of magnetic stations was spread all over the British dominions, from Canada to Van Diemen's Land. Measures were concerted with foreign authorities, and an expedition was fitted out, under the able command of Captain, afterwards Sir James, Clark Ross, for the special purpose of bringing intelligence on the subject from the dismal neighborhood of the South Pole. In 1841, the elaborate organization created by the disinterested efforts of scientific agitators was complete. Gauss's magnetometers were vibrating under the view of attentive observers in 5 continents, and simultaneous results began to be recorded. 10 years later, in September, 1851, Dr. John Lamont, the Scotch director of the Munich Observatory, in reviewing the magnetic observations made at Göttingen and Munich from 1835 to 1850, perceived with some surprise that they gave unmistakable indications of a period which he estimated at 10 1/3 years. The manner in which this periodicity manifested itself requires a word of explanation. The observations in question referred to what is called the declination of the magnetic needle, that is, to the position assumed by it with reference to the points of the compass when moving freely in a horizontal plane. Now this position, as was discovered by Graham in 1722, is subject to a small daily fluctuation, attaining its maximum towards the east about 8 a.m., and its maximum towards the west shortly before 2 p.m. In other words, the direction of the needle approaches, in these countries at the present time, nearest to the true north some 4 hours before noon, and departs farthest from it between 1 and 2 hours after noon. It was the range of this daily variation that Lamont found to increase and diminish once in every 10 1/3 years. In the following winter, Sir Edward Sabine, ignorant as yet of Lamont's conclusion, undertook to examine a totally different set of observations. The materials in his hands had been collected at the British colonial stations of Toronto and Hobarton from 1843 to 1848, and had reference, not to the regular diurnal swing of the needle, but to those curious spasmodic vibrations. The inquiry into the laws of which was the primary object of the vast organization set on foot by Humboldt and Gauss. Yet the upshot was practically the same. Once in about 10 years, magnetic disturbances, termed by Humboldt storms, were perceived to reach a maximum of violence and frequency. Sabine was the first to note the coincidence between this unlooked-for result and Schwab's sunspot period. He showed that, so far as observation had yet gone, the two cycles of change agreed perfectly both in duration and phase, maximum corresponding to maximum, minimum to minimum. What the nature of the connection could be that bound together by a common law effects so dissimilar as the rents in the luminous garment of the sun, and the swayings to and fro of the magnetic needle, was and still remains beyond the reach of well-founded theory. But the fact was from the first undeniable. The memoir containing this remarkable disclosure was presented to the Royal Society, March 18, and read May 6, 1852. On the 31st of July following, Rudolf Wolff at Bern, and on the 18th of August, Alfred Gautier at Schaun, announced, separately and independently, perfectly similar conclusions. This triple event is perhaps the most striking instance of the successful employment of the Baconian method of cooperation in discovery, by which particulars are amassed by one set of investigators, corresponding to the depredators and inoculators of Solomon's house, while inductions are drawn from them by another and a higher class, the interpreters of nature. Yet even here the convergence of two distinct lines of research was wholly fortuitous, and skillful combination owed the most brilliant part of its success to the unsought bounty of what we call fortune. The exactness of the coincidence thus brought to light was fully confirmed by further inquiries. A diligent search through the scattered records of sunspot observations, from the time of Galileo and Scheiner onwards, put Wolff in possession of materials by which he was enabled to correct Schwab's loosely indicated decennial period to one of slightly over 11 years, and he further showed that this fell in with the ebb and flow of magnetic change even better than Lamont's 10 1/3 year cycle. The analogy was also pointed out between the light curve, or zigzagged line representing on paper the varying intensity in the luster of certain stars, and the similar delineation of spot frequency. The ascent from minimum to maximum being, in both cases, usually steeper than the descent from maximum to minimum, while an additional point of resemblance was furnished by the irregularities in height of the various maxima. In other words, both the number of spots on the sun and the brightness of variable stars increase, as a rule, more rapidly than they decrease, nor does the amount of that increase, in either instance, show any approach to uniformity. The endeavor, suggested by the very nature of the phenomenon, to connect sunspots with weather was less successful. The first attempt of the kind was made by Sir William Herschel in 1801, and a very notable one it was. Meteorological statistics, save of the scantiest and most casual kind, did not then exist, but the price of corn from year to year was on record, and this, with full recognition of its inadequacy, he adopted as his criterion. Nor was he much better off for information respecting the solar condition. What little he could obtain, however, served, as he believed, to confirm his surmise that a copious emission of light and heat accompanies an abundant formation of openings in the dazzling substance whence our supply of those indispensable commodities is derived. He gathered, in short, from his inquiries very much what he had expected to gather, namely, that the price of wheat was high when the sun showed an unsullied surface, and that food and spots became plentiful together. Yet this plausible inference was scarcely borne out by a more exact collocation of facts. Schwab failed to detect any reflection of the sunspot period in his meteorological register. Gautier reached a provisional conclusion the reverse, though not markedly the reverse, of Herschel's. Wolf, in 1852, derived from an examination of Vogel's collection of Zurich Chronicles, 1000 to 1800 AD. Evidence showing, as he thought, that minimum years were usually wet and stormy, maximum years dry and genial, but a subsequent review of the subject in 1859 convinced him that no relation of any kind between the two kinds of effects was traceable. With the singular affection of our atmosphere known as the aurora borealis, more properly aurora polaris, the case was different. Here the Zurich Chronicles set Wolf on the right track in leading him to associate such luminous manifestations with a disturbed condition of the sun. Since subsequent detailed observation has exhibited the curve of auroral frequency as following with such fidelity the jagged lines figuring to the eye the fluctuations of solar and magnetic activity, as to leave no reasonable doubt that all three rise and sink together under the influence of a common cause. As long ago as 1716, Halley had conjectured that the northern lights were due to magnetic effluvia, but there was no evidence on the subject forthcoming until Hyarter observed at UPS in 1741 their agitating influence upon the magnetic needle. That the effect was no casual one was made superabundantly clear by Arago's researches in 1819 and subsequent years. Now both were perceived to be swayed by the same obscure power of cosmical disturbance. The sun is not the only one of the heavenly bodies by which the magnetism of the earth is affected. Proofs of a similar kind of lunar action were laid by Kreil in 1841 before the Bohemian Society of Sciences, and with minor corrections were fully substantiated by Sabine's more extended researches. It was thus ascertained that each lunar day, or the interval of 24 hours and about 54 minutes between two successive meridian passages of our satellite, is marked by a perceptible, though very small, double oscillation of the needle, 2 progressive movements from east to west, and 2 returns from west to east. Moreover, the lunar, like the solar influence, as was proved in each case by Sabine's analysis of the Hobarton and Toronto observations, extends to all 3 magnetic elements, affecting not only the position of the horizontal or declination needle, but also the dip and intensity. It seems not unreasonable to attribute some portion of the same subtle power to the planets and even to the stars, though with effects rendered imperceptible by distance. We have now to speak of the discovery and application to the heavenly bodies of a totally new method of investigation. Spectrum analysis may be shortly described as a mode of distinguishing the various species of matter by the kind of light proceeding from each. This definition at once explains how it is that, unlike every other system of chemical analysis, it has proved available in astronomy. Light, so far as quality is concerned, ignores distance. No intrinsic change, that we yet know of, is produced in it by a journey from the farthest bounds of the visible universe. So that, provided only that in quantity it remains sufficient for the purpose, its peculiarities can be equally well studied whether the source of its vibrations be 1 foot or 100 billion miles distant. Now the most obvious distinction between one kind of light and another resides in color. But of this distinction the eye takes cognizance in an aesthetic, not in a scientific sense. It finds gladness in the 1,000 tints of nature, but can neither analyze nor define them. Here the refracting prism, or the combination of prisms known as the spectroscope, comes to its aid, teaching it to measure as well as to perceive. It furnishes, in a word, an accurate scale of color. The various rays which, entering the eye together in a confused crowd, produce a compound impression made up of undistinguishable elements, are, by the mere passage through a triangular piece of glass, separated one from the other, and ranged side by side in orderly succession, so that it becomes possible to tell at a glance what kinds of light are present, and what absent. Thus, if we could only be assured that the various chemical substances when made to glow by heat, emit characteristic rays, that is, occupying a place in the spectrum reserved for them, and for them only, we should at once be in possession of a mode of identifying such substances with the utmost readiness and certainty. This assurance, which forms the solid basis of spectrum analysis, was obtained slowly and with difficulty. The first to employ the prism in the examination of various flames, for it is only in a state of vapor that matter emits distinctive light, was a young Scotchman named Thomas Melville, who died in 1753, at the age of 27. He studied the spectrum of burning spirits, into which were successively introduced sal ammoniac, potash, alum, niter, and sea salt, and observed the singular predominance, under almost all circumstances, of a particular shade of yellow light. Perfectly definite in its degree of refrangibility, in other words, taking up a perfectly definite position in the spectrum. His experiments were repeated by Morgan, Wollaston, and, with far superior precision and diligence, by Fraunhofer. The great Munich optician, whose work was completely original, rediscovered Melville's deep yellow ray and measured its place in the color scale. It has since become well known as the sodium line, and has played a very important part in the history of spectrum analysis. Nevertheless, its ubiquity and conspicuousness long impeded progress. It was elicited by the combustion of a surprising variety of substances: sulfur, alcohol, ivory, wood, paper. Its persistent visibility suggesting the accomplishment of some universal process of nature rather than the presence of one individual kind of matter. But if spectrum analysis were to exist as a science at all, it could only be by attaining certainty as to the unvarying association of one special substance with each special quality of light. Thus perplexed, Fox Talbot hesitated in 1826 to announce this fundamental principle. He was inclined to believe that the presence in the spectrum of any individual ray told unerringly of the volatilization in the flame under scrutiny of some body as whose badge or distinctive symbol that ray might be regarded. But the continual prominence of the yellow beam staggered him. It appeared, indeed, without fail where sodium was, but it also appeared where it might be thought only reasonable to conclude that sodium was not. Nor was it until 30 years later that William Swan, by pointing out the extreme delicacy of the spectral test, and the singularly wide dispersion of sodium, made it appear probable, but even then only probable, that the questionable yellow line was really due invariably to that substance. Common salt, chloride of sodium, is, in fact, the most diffusive of solids. It floats in the air, it flows with water, every grain of dust has its attendant particle, its absolute exclusion approaches the impossible. And withal, the light that it gives in burning is so intense and concentrated, that if a single grain be divided into 180 million parts, and one alone of such inconceivably minute fragments be present in a source of light, the spectroscope will show unmistakably its characteristic beam. Amongst the pioneers of knowledge in this direction were Sir John Herschel, who, however, applied himself to the subject in the interests of optics, not of chemistry, W. Miller, and Wheatstone. The last especially made a notable advance when, in the course of his studies on the prismatic decomposition of the electric light, he reached the significant conclusion that the rays visible in its spectrum were different for each kind of metal employed as electrodes. Thus indications of a wider principle were to be found in several quarters, but no positive certainty on any single point was obtained, until, in 1859, Gustav Kirchhoff, professor of physics in the University of Heidelberg, and his colleague, the eminent chemist Robert Bunsen, took the matter in hand. By them the general question as to the necessary and invariable connection of certain rays in the spectrum with certain kinds of matter, was first resolutely confronted, and first definitely answered. It was answered affirmatively, else there could have been no science of spectrum analysis, as the result of experiments more numerous, more stringent, and more precise than had previously been undertaken. And the assurance of their conclusion was rendered doubly sure by the discovery, through the peculiarities of their light alone, of two new metals, named from the blue and red rays by which they were respectively distinguished, cesium and rubidium. Both were immediately afterwards actually obtained in small quantities by evaporation of the Durkheim mineral waters. The link connecting this important result with astronomy may now be indicated. In the year 1802 it occurred to William Hyde Wollaston to substitute for the round hole used by Newton and his successors for the admittance of light to be examined with the prism, an elongated crevice 1/20th of an inch in width. He thereupon perceived that the spectrum, thus formed of light, as it were, purified by the abolition of overlapping images, was traversed by 7 dark lines. These he took to be natural boundaries of the various colors, and satisfied with this quasi-explanation, allowed the subject to drop. It was independently taken up after 12 years by a man of higher genius. In the course of experiments on light, directed towards the perfecting of his achromatic lenses, Fraunhofer, by means of a slit and a telescope, made the surprising discovery that the solar spectrum is crossed, not by 7, but by thousands of obscure transverse streaks. Of these he counted some 600, and carefully mapped 324, while a few of the most conspicuous he set up, if we may be permitted the expression, as landmarks, measuring their distances apart with a theodolite, and affixing to them the letters of the alphabet, by which they are still universally known. Nor did he stop here. The same system of examination applied to the rest of the heavenly bodies showed the mild effulgence of the moon and planets to be deficient in precisely the same rays as sunlight. While in the stars it disclosed the differences in likeness which are always an earnest of increased knowledge. The spectra of Sirius and Castor, instead of being delicately ruled crosswise throughout, like that of the sun, were seen to be interrupted by 3 massive bars of darkness, 2 in the blue and 1 in the green. The light of Pollux, on the other hand, seemed precisely similar to sunlight attenuated by distance or reflection, and that of Capella, Betelgeuse, and Procyon to share some of its peculiarities. One solar line especially, that marked in his map with the letter D, proved common to all the 4 last-mentioned stars. And it was remarkable that it exactly coincided in position with the conspicuous yellow beam, afterwards, as we have said, identified with the light of glowing sodium, which he had already found to accompany most kinds of combustion. Moreover, both the dark solar and the bright terrestrial D lines were displayed by the refined Munich appliances as double. In this striking correspondence, discovered by Fraunhofer in 1815, was contained the very essence of solar chemistry. But its true significance did not become apparent until long afterwards. Fraunhofer was by profession, not a physicist, but a practical optician. Time pressed, he could not and would not deviate from his appointed track. All that was possible to him was to indicate the road to discovery, and exhort others to follow it. Partially and inconclusively at first this was done. The fixed lines, as they were called, of the solar spectrum took up the position of a standing problem, to the solution of which no approach seemed possible. Conjectures as to their origin were indeed rife. An explanation put forward by Zantedeschi and others, and dubiously favored by Sir David Brewster and Dr. J.H. Gladstone, was that they resulted from interference, that is, a destruction of the motion producing in our eyes the sensation of light, by the superposition of 2 light waves in such a manner that the crests of one exactly fill up the hollows of the other. This effect was supposed to be brought about by imperfections in the optical apparatus employed. A more plausible view was that the atmosphere of the Earth was the agent by which sunlight was deprived of its missing beams. For a few of them this is actually the case. Brewster found in 1832 that certain dark lines, which were invisible when the sun stood high in the heavens, became increasingly conspicuous as he approached the horizon. These are the well-known atmospheric lines. But the immense majority of their companions in the spectrum remain quite unaffected by the thickness of the stratum of air traversed by the sunlight containing them. They are then obviously due to another cause. There remained the true interpretation, absorption in the sun's atmosphere, and this, too, was extensively canvassed. But a remarkable observation made by Professor Forbes of Edinburgh on the occasion of the annular eclipse of May 15, 1836, appeared to throw discredit upon it. If the problematical dark lines were really occasioned by the stoppage of certain rays through the action of a vaporous envelope surrounding the sun, they ought, it seemed, to be strongest in light proceeding from his edges, which, cutting that envelope obliquely, passed through a much greater depth of it. But the circle of light left by the interposing moon, and of course derived entirely from the rim of the solar disk, yielded to Forbes's examination precisely the same spectrum as light coming from its central parts. This circumstance helped to baffle inquirers, already sufficiently perplexed. It still remains an anomaly, of which no satisfactory explanation has been offered. Convincing evidence as to the true nature of the solar lines was however at length, in the autumn of 1859, brought forward at Heidelberg. Kirchhoff's experimentum crucis in the matter was a very simple one. He threw bright sunshine across a space occupied by vapor of sodium, and perceived with astonishment that the dark Fraunhofer line D, instead of being effaced by flame giving a luminous ray of the same refrangibility, was deepened and thickened by the superposition. He tried the same experiment, substituting for sunbeams light from a Drummond lamp, and with similar result. A dark furrow, corresponding in every respect to the solar D line, was instantly seen to interrupt the otherwise unbroken radiance of its spectrum. The inference was irresistible, that the effect thus produced artificially was brought about naturally in the same way, and that sodium formed an ingredient in the glowing atmosphere of the sun. This first discovery was quickly followed up by the identification of numerous bright rays in the spectra of other metallic bodies with others of the hitherto mysterious Fraunhofer lines. Kirchhoff was thus led to the conclusion that, besides sodium, iron, magnesium, calcium, and chromium, are certainly solar constituents, and that copper, zinc, barium, and nickel are also present, though in smaller quantities. As to cobalt, he hesitated to pronounce, but its existence in the Sun has since been established. These memorable results were founded upon a general principle first enunciated by Kirchhoff in a communication to the Berlin Academy, December 15, 1859, and afterwards more fully developed by him. It may be expressed as follows: substances of every kind are opaque to the precise rays which they emit at the same temperature, that is to say, they stop the kinds of light or heat which they are then actually in a condition to radiate. But it does not follow that cool bodies absorb the rays which they would give out if sufficiently heated. Hydrogen at ordinary temperatures, for instance, is almost perfectly transparent, but if raised to the glowing point, as by the passage of electricity, it then becomes capable of arresting, and at the same time of displaying in its own spectrum light of 4 distinct colors. This principle is fundamental to solar chemistry. It gives the key to the hieroglyphics of the Fraunhofer lines. The identical characters which are written bright in terrestrial spectra are written dark in the unrolled sheaf of sunrays. The meaning remains unchanged. It must, however, be remembered that they are only relatively dark. The substances stopping those particular tints in the neighborhood of the sun are at the same time vividly glowing with the very same. Remove the dazzling solar background, by contrast with which they show as obscure, and they will be seen, and, at critical moments, actually have been seen, in all their native splendor. It is because the atmosphere of the sun is cooler than the globe it envelopes that the different kinds of vapor constituting that atmosphere take more than they give, absorb more light than they are capable of emitting. Raise them to the same temperature as the sun itself, and their powers of emission and absorption being brought exactly to the same level, the thousands of dusky rays in the solar spectrum will be at once obliterated. The establishment of the terrestrial science of spectrum analysis was due, as we have seen, equally to Kirchhoff and Bunsen, but its celestial application to Kirchhoff alone. He effected this object of the aspirations, more or less dim, of many other thinkers and workers, by the union of 2 separate, though closely related lines of research, the study of the different kinds of light emitted by various bodies, and the study of the different kinds of light absorbed by them. The latter branch appears to have been first entered upon by Dr. Thomas Young in 1803, it was pursued by the younger Herschel, by William Allen Miller, Brewster, and Gladstone. Brewster indeed made, in 1833, a formal attempt to found what might be called an inverse system of analysis with the prism based upon absorption, and his efforts were repeated, just a quarter of a century later, by Gladstone. But no general point of view was attained, nor, it may be added, was it by this path attainable. Kirchhoff's map of the solar spectrum, drawn to scale with exquisite accuracy, and printed in 3 shades of ink to convey the graduated obscurity of the lines, was published in the Transactions of the Berlin Academy for 1861 and 1862. Representations of the principal lines belonging to various elementary bodies formed, as it were, a series of marginal notes accompanying the great solar scroll, enabling the various tyro in the new science to decipher its meaning at a glance. Where the dark solar and bright metallic rays agreed in position, it might safely be inferred that the metal emitting them was a solar constituent, and such coincidences were numerous. In the case of iron alone, no less than 60 occurred in 1/2 of the spectral area, rendering the chances absolutely overwhelming against mere casual conjunction. The preparation of this elaborate picture proved so trying to the eyes that Kirchhoff was compelled by failing vision to resign the latter half of the task to his pupil Hoffmann. The complete map measured nearly 8 feet in length. The conclusions reached by Kirchhoff were no sooner announced than they took their place, with scarcely a dissenting voice, among the established truths of science. The broad result, that the dark lines in the spectrum of the Sun afford an index to its chemical composition no less reliable than any of the tests used in the laboratory, was equally captivating to the imagination of the vulgar, and authentic in the judgment of the learned. And, like all genuine advances in the knowledge of nature, it stimulated curiosity far more than it gratified it. Now the history of how discoveries were missed is often quite as instructive as the history of how they were made. It may then be worth while to expend a few words on the thoughts and trials by which, in the present case, the actual event was heralded. 3 times it seemed on the verge of being anticipated. The experiment, which in Kirchhoff's hands proved decisive, of passing sunlight through glowing vapors and examining the superposed spectra, was performed by Professor W. Miller of King's College in 1845. Nay, more, it was performed with express reference to the question, then already, as has been noted, in debate, of the possible production of Fraunhofer's lines by absorption in a solar atmosphere. Yet it led to nothing. Again, at Paris in 1849, with a view to testing the asserted coincidence between the solar D-line and the bright yellow beam in the spectrum of the electric arc, really due to the unsuspected presence of sodium, Léon Foucault threw a ray of sunshine across the arc and observed its spectrum. He was surprised to see that the D-line was rendered more intensely dark by the combination of lights. To assure himself still further, he substituted a reflected image of one of the white-hot carbon points for the sunbeam, with an identical result. The same ray was missing. It needed but another step to have generalized this result, and thus laid hold of a natural truth of the highest importance, but that step was not taken. Foucault, keen and brilliant though he was, rested satisfied with the information that the voltaic arc had the power of stopping the kind of light emitted by it. He asked no further question, and was consequently the bearer of no further intelligence on the subject. The truth conveyed by this remarkable experiment was, however, divined by one eminent man. Professor Stokes of Cambridge stated to Sir William Thomson, now Lord Kelvin, shortly after it had been made, his conviction that an absorbing atmosphere of sodium surrounded the Sun. And so forcibly was his hearer impressed with the weight of the argument based upon the absolute agreement of the D-line in the solar spectrum with the yellow ray of burning sodium, then freshly certified by W. H. Miller, combined with Foucault's reversal of that ray, that he regularly inculcated, in his public lectures on natural philosophy at Glasgow, 5 or 6 years before Kirchhoff's discovery. Not only the fact of the presence of sodium in the solar neighborhood, but also the principle of the study of solar and stellar chemistry in the spectra of flames. Yet it does not appear to have occurred to either of these 2 distinguished professors, themselves among the foremost of their time in the successful search for new truths, to verify practically a sagacious conjecture in which was contained the possibility of a scientific revolution. It is just to add, that Kirchhoff was unacquainted, when he undertook his investigation, either with the experiment of Foucault or the speculation of Stokes. For C. J. Ångström, on the other hand, perhaps somewhat too much has been claimed in the way of anticipation. His optical researches appeared at UPS in 1853, and in their English garb 2 years later. They were undoubtedly pregnant with suggestion, yet made no epoch in discovery. The old perplexities continued to prevail after, as before their publication. To Ångström, indeed, belongs the great merit of having revived Euler's principle of the equivalence of emission and absorption. But he revived it in its original crude form, and without the qualifying proviso which alone gave it value as a clue to new truths. According to his statement, a body absorbs all the series of vibrations it is, under any circumstances, capable of emitting, as well as those connected with them by simple harmonic relations. This is far too wide. To render it either true or useful, it had to be reduced to the cautious terms employed by Kirchhoff. Radiation strictly and necessarily corresponds with absorption only when the temperature is the same. In point of fact, Ångström was still, in 1853, divided between adsorption and interference as the mode of origin of the Fraunhofer dark rays. Very important, however, was his demonstration of the compound nature of the spark spectrum, which he showed to be made up of the spectrum of the metallic electrode superposed upon that of the gas or gases across which the discharge passed. It may here be useful, since without some clear ideas on the subject no proper understanding of recent astronomical progress is possible, to take a cursory view of the elementary principles of spectrum analysis. To many of our readers they are doubtless already familiar, but it is better to appear trite to some than obscure even to a few. The spectrum, then, of a body is simply the light proceeding from it spread out by refraction into a brilliant variegated band, passing from brownish red through crimson, orange, yellow, green, and azure into dusky violet. The reason of this spreading out or dispersion is that the various colors have different wavelengths, and consequently meet with different degrees of retardation in traversing the denser medium of the prism. The shortest and quickest vibrations, producing the sensation we call violet, are thrown farthest away from their original path, in other words, suffer the widest deviation, the longest and slowest, the red, travel much nearer to it. Thus the sheaf of rays which would otherwise combine into a patch of white light are separated through the divergence of their tracks after refraction by a prism, so as to form a tinted riband. This visible spectrum is prolonged invisibly at both ends by a long range of vibrations, either too rapid or too sluggish to affect the eye as light, but recognizable through their chemical and heating effects. Now all incandescent solid or liquid substances, and even gases ignited under great pressure, give what is called a continuous spectrum, that is to say, the light derived from them is of every conceivable hue. Sorted out with the prism, its tints merge imperceptibly one into the other, uninterrupted by any dark spaces. No colors, in short, are missing. But gases and vapors rendered luminous by heat emit rays of only a few tints, which accordingly form an interrupted spectrum, usually designated as one of lines or bands. And since these rays are perfectly definite and characteristic, not being the same for any two substances, it is easy to tell what kind of matter is concerned in producing them. We may suppose that the inconceivably minute particles which by their rapid thrilling agitate the ethereal medium so as to produce light, are free to give out their peculiar tone of vibration only when floating apart from each other in gaseous form. But when crowded together into a condensed mass, the clear ring of the distinctive note is drowned, so to speak, in a universal molecular clang. Thus prismatic analysis has no power to identify individual kinds of matter, except when they present themselves as glowing vapors. A spectrum is said to be reversed when lines previously seen bright on a dark background appear dark on a bright background. In this form it is equally characteristic of chemical composition with the direct spectrum, being due to absorption, as the latter is to emission. And absorption and emission are, by Kirchhoff's law, strictly correlative. This is easily understood by the analogy of sound. For just as a tuning fork responds to sound waves of its own pitch, but remains indifferent to those of any other, so those particles of matter whose nature it is, when set swinging by heat, to vibrate a certain number of times in a second, thus giving rise to light of a particular shade of color, appropriate those same vibrations, and those only, when transmitted past them, or, phrasing it otherwise, are opaque to them, and transparent to all others. It should further be explained that the shape of the bright or dark spaces in the spectrum has nothing whatever to do with the nature of the phenomena. The lines and bands so frequently spoken of are seen as such for no other reason than because the light forming them is admitted through a narrow, straight opening. Change that opening into a fine crescent or a sinuous curve, and the lines will at once appear as crescents or curves. Resuming in a sentence what has been already explained, we find that the prismatic analysis of the heavenly bodies was founded upon three classes of facts. First, the unmistakable character of the light given by each different kind of glowing vapor. Secondly, the identity of the light absorbed with the light emitted by each. Thirdly, the coincidence observed between rays missing from the solar spectrum and rays absorbed by various terrestrial substances. Thus, a realm of knowledge, pronounced by Marinus in the 17th century, and no less dogmatically by Auguste Comte in the 19th, hopelessly out of reach of the human intellect, was thrown freely open. And the chemistry of the sun and stars took at once a leading place among the experimental sciences. The immediate increase of knowledge was not the chief result of Kirchhoff's labors. Still more important was the change in the scope and methods of astronomy, which, set on foot in 1852 by the detection of a common period affecting at once the spots on the sun and the magnetism of the earth, was extended and accelerated by the discovery of spectrum analysis. The nature of that change is concisely indicated by the heading of the present chapter. We would now ask our readers to endeavor to realize somewhat distinctly what is implied by the foundation of astronomical physics. Just 3 centuries ago, Kepler drew a forecast of what he called a physical astronomy, a science treating of the efficient causes of planetary motion, and holding the key to the inner astronomy. What Kepler dreamed of and groped after, Newton realized. He showed the beautiful and symmetrical revolutions of the solar system to be governed by a uniformly acting cause, and that cause no other than the familiar force of gravity, which gives stability to all our terrestrial surroundings. The world under our feet was thus for the first time brought into physical connection with the worlds peopling space. And a very tangible relationship was demonstrated as existing between what used to be called the corruptible matter of the earth and the incorruptible matter of the heavens. This process of unification of the cosmos, this leveling of the celestial with the sublunary, was carried no farther until the fact unexpectedly emerged from a vast and complicated mass of observations. That the magnetism of the earth is subject to subtle influences, emanating, certainly from some, and presumably from all of the heavenly bodies. The inference being thus rendered at least plausible, that a force not less universal than gravity itself, but with whose modes of action we are as yet unacquainted, pervades the universe, and forms, it might be said, an intangible bond of sympathy between its parts. Now for the investigation of this influence 2 roads are open. It may be pursued by observation either of the bodies from which it proceeds, or of the effects which it produces, that is to say, either by the astronomer or by the physicist, or, better still, by both concurrently. Their acquisitions are mutually profitable, nor can either be considered as independent of the other. Any important accession to knowledge respecting the sun, for example, may be expected to cast a reflected light on the still obscure subject of terrestrial magnetism. While discoveries in magnetism or its alter ego electricity must profoundly affect solar inquiries, the establishment of the new method of spectrum analysis drew far closer this alliance between celestial and terrestrial science. Indeed, they have come to merge so intimately one into the other, that it is no easier to trace their respective boundaries than it is to draw a clear dividing line between the animal and vegetable kingdoms. Yet up to the middle of the last century, astronomy, while maintaining her strict union with mathematics, looked with indifference on the rest of the sciences. It was enough that she possessed the telescope and the calculus. Now the materials for her inductions are supplied by the chemist, the electrician, the inquirer into the most recondite mysteries of light and the molecular constitution of matter. She is concerned with what the geologist, the meteorologist, even the biologist, has to say. She can afford to close her ears to no new truth of the physical order. Her position of lofty isolation has been exchanged for one of community and mutual aid. The astronomer has become, in the highest sense of the term, a physicist, while the physicist is bound to be something of an astronomer. This, then, is what is designed to be conveyed by the foundation of astronomical or cosmical physics. It means the establishment of a science of nature whose conclusions are not only presumed by analogy, but are ascertained by observation. To be valid wherever light can travel and gravity is obeyed, a science by which the nature of the stars can be studied upon the earth, and the nature of the earth can be made better known by study of the stars, a science, in a word, which is, or aims at being, one and universal, even as nature, the visible reflection of the invisible highest unity, is one and universal. It is not too much to say that a new birth of knowledge has ensued. The astronomy so signally promoted by Bessel, the astronomy placed by Kant at the head of the hierarchy of the physical sciences, was the science of the movements of the heavenly bodies. And there were those who began to regard it as a science which, from its very perfection, had ceased to be interesting, whose tale of discoveries was told, and whose farther advance must be in the line of minute technical improvements. Not of novel and stirring disclosures. But the science of the nature of the heavenly bodies is one only in the beginning of its career. It is full of the audacities, the inconsistencies, the imperfections, the possibilities of youth. It promises everything, it has already performed much. It will doubtless perform much more. The means at its disposal are vast and are being daily augmented. What has so far been secured by them it must now be our task to extricate from more doubtful surroundings and place in due order before our readers. Footnotes. Wolf, Gesch. Der Astre, page 655. Manuel Johnson, MEM. RAS, volume 26, page 197. Astronomie théorique et pratique, T3, page 20. Wolf, Gesch. Der Astre, page 654. Month. Not, volume 17, page 241. MEM. RAS, volume 26, page 200. Astre. Knock, number 495. Gellers Physikalisches Wörterbuch, Art. Sonnenflecken, page 851. Zweit Apth. Page 401. Annalen der Physik, Poggendorfs, BD, 84, page 580. Phil. Trans, volume Xlii, page 103. Mitteilungen der Naturforschenden Gesellschaft, 1852, page 183. Archives des Sciences, T. 21, page 194. Neue Untersuchungen, Myth. Naderf. Guess. 1852, page 249. Phil. Trans, volume 91, page 316. Evidence of an 11-yearly fluctuation in the price of food grains in India was collected some years ago by Mr. Frederick Chambers. Nature, volume 34, page 100. Bibl und Geneve, T. Lee, page 336. Neue Untersuchungen, page 269. Die und ihr Flecken, page 30. Arago was the first who attempted to decide the question by keeping, through a series of years, a parallel register of sunspots and weather. But the data regarding the solar condition amassed at the Paris Observatory from 1822 to 1830 were not sufficiently precise to support any inference. Phil. Trans, volume 29, page 421. Ibid, volumes Xlii, page 558, Xlv, page 505. Observations on Light and Colors, page 35. Phil. Trans, volume 75, page 190. Denkschriften, Munich. AC, of SC, 1814, 1815, BD, v, page 197. Edinburgh Journal of Science, volume 5, page 77. See also Phil. Mag, February, 1834, volume 4, page 112. Ed. Phil. Trans, volume 21, page 411. On the Absorption of Light by Colored Media, Ed. Phil. Trans, volume 9, page 445, 1823. Phil. Mag, Volume 27, Ser. 3, page 81. Report Brit. As, 1835, page 11, pt 2. Electrodes are the terminals from one to the other of which the electric spark passes, volatilizing and rendering incandescent in its transit some particles of their substance. The characteristic light of which accordingly flashes out in the spectrum. Phil. Mag, Volume 20, page 93. Annalen der Physik, BD, XI, page 357. Phil. Trans, Volume 92, page 378. Denkschriften, BD, V, page 202. Ibid, page 220, Eden. Jour of Science, Volume 8, page 9. Denkschriften, BD, V, page 222. Arch. The Sciences, 1849, page 43. Phil. Trans, Volume CL, page 159, note. Ed. Phil. Trans, Volume 12, page 528. Phil. Trans, Volume XVI, page 453. I conceive, he says, that this result proves decisively that the Sun's atmosphere has nothing to do with the production of this singular phenomenon, page 455. And Brewster's well-founded opinion that it had much to do with it was thereby, in fact, overthrown. Monitzbericht, Berlin, 1859, page 664. Abhandlungen, Berlin, 1861, pages 80, 81. Ibid, 1861, page 77, Annalen der Physik, BD, 6, page 275. A similar conclusion, reached by Balfour Stewart in 1858, for heat rays, ed. Phil. Trans, Volume 22, page 13, was, in 1860, without previous knowledge of Kirchhoff's work, extended to light, Phil. Mag, Volume 20, page 534. But his experiments wanted the precision of those executed at Heidelberg. Miscellaneous Works, Volume 1, page 189. Ed. Phil. Trans, Volume 9, page 458. Ibid, Volume 12, page 519. Quart. Jour, Chemistry Associe, Volume 10, page 79. A facsimile accompanied Sir H. Roscoe's translation of Kirchhoff's Researches on the Solar Spectrum, London, 1862-63. Estimated by Kirchhoff's at 1,000,000,000 to 1. Abhandel, 1861, page 79. Phil. Mag, Volume 27. Third Series, page 90. L'Institut, February 7, 1849, page 45, Phil. Mag. Volume 19. Fourth Series, page 193. And D. Phys, Volume XVI, page 110. Phil. Mag, Volume 9. Fourth Series, page 327. Spectra may be produced by diffraction as well as by refraction, but we are here only concerned with the subject in its simplest aspect. Astrologia Gallica, 1661, page 189. Pos Phil, Volume 1, pages 114, 115, Martineau's Trans. Pro M Astronomii Pars Optica, 1640, Op. T. 2. Pop Vorl, pages 14, 19, 408. Pos Phil, page 115. Chapter 2. Solar Observations and Theories. The zeal with which solar studies have been pursued during the last half-century has already gone far to redeem the neglect of the two preceding ones. Since Schwab's discovery was published in 1851, observers have multiplied, new facts have been rapidly accumulated, and the previous comparative quiescence of thought on the great subject of the constitution of the sun has been replaced by a bewildering variety of speculations, conjectures, and more or less justifiable inferences. It is satisfactory to find this novel impulse not only shared, but to a large extent guided, by our countrymen. William Rutter Dawes, one of many clergymen eminent in astronomy, observed, in 1852, with the help of a solar eyepiece of his own devising, some curious details of spot structure. The umbra, heretofore taken for the darkest part of the spot, was seen to be suffused with a mottled, nebulous illumination, in marked contrast with the striated appearance of the penumbra. While through this cloudy stratum a black opening permitted the eye to divine farther unfathomable depths beyond. The whole thus disclosed, evidently the true nucleus, was found to be present in all considerable, as well as in many small maculae. Again, the whirling motions of some of these objects were noticed by him. The remarkable form of one sketched at Wateringbury, in Kent, January 17, 1852, gave him the means of detecting and measuring a rotatory movement of the whole spot round the black nucleus at the rate of 100 degrees in 6 days. It appeared, he said, as if some prodigious ascending force of a whirlwind character, in bursting through the cloudy stratum and the two higher and luminous strata, had given to the whole a movement resembling its own. An interpretation founded, as is easily seen, on the Herschelian theory, then still in full credit. An instance of the same kind was observed by Mr. W. R. Burt in 1860, and cyclonic movements are now a recognized feature of sunspots. They are, however, as Father Secchi concluded from his long experience, but temporary and casual. Scarcely 3% of all spots visible exhibit the spiral structure which should invariably result if a conflict of opposing, or the friction of unequal, currents were essential, and not merely incidental to their origin. A whirlpool phase not unfrequently accompanies their formation, and may be renewed at periods of recrudescence or dissolution. But it is both partial and inconstant, sometimes affecting only one side of a spot, sometimes slackening gradually its movement in one direction, to resume it, after a brief pause, in the opposite. Persistent and uniform notions, such as the analogy of terrestrial storms would absolutely require, are not to be found. So that the cyclonic theory of sunspots, suggested by Herschel in 1847, and urged, from a different point of view, by Faye in 1872, may be said to have completely broken down. The drift of spots over the sun's surface was first systematically investigated by Carrington, a self-constituted astronomer, gifted with the courage and the instinct of thoughtful labor. Born at Chelsea in May, 1826, Richard Christopher Carrington entered Trinity College, Cambridge, in 1844. He was intended for the church, but Professor Challis's lectures diverted him to astronomy, and he resolved, as soon as he had taken his degree, to prepare, with all possible diligence, to follow his new vocation. His father, who was a brewer on a large scale at Brentford, offered no opposition, ample means were at his disposal. Nevertheless, he chose to serve an apprenticeship of 3 years as observer in the University of Durham, as though his sole object had been to earn a livelihood. He quitted the post only when he found that its restricted opportunities offered no farther prospect of self-improvement. He now built an observatory of his own at Redhill in Surrey, with the design of completing Bessel's and Argelander's survey of the northern heavens by adding to it the circumpolar stars omitted from their view. This project, successfully carried out between 1854 and 1857, had another and still larger one superposed upon it before it had even begun to be executed. In 1852, while the Redhill Observatory was in course of erection, the discovery of the coincidence between the sunspot and magnetic periods was announced. Carrington was profoundly interested, and devoted his enforced leisure to the examination of records, both written and depicted, of past solar observations. Struck with their fragmentary and inconsistent character, he resolved to appropriate, as he said, by close and methodical research, the 11-year period next ensuing. He calculated rightly that he should have the field pretty nearly to himself. For many reasons conspire to make public observatories slow in taking up new subjects, and amateurs with freedom to choose, and means to treat them effectually, were scarcer then than they are now. The execution of this laborious task was commenced November 9, 1853. It was intended to be merely a paragon, a second subject, upon which daylight energies might be spent, while the hours of night were reserved for cataloguing those stars that are bereft of the baths of ocean. Its results, however, proved of the highest interest, although the vicissitudes of life barred the completion, in its full integrity, of the original design. By the death, in 1858, of the elder Carrington, the charge of the brewery devolved upon his son, and eventually absorbed so much of his care that it was found advisable to bring the solar observations to a premature close, on March 24, 1861. His scientific life may be said to have closed with them. Attacked 4 years later with severe, and, in its results, permanent illness, he disposed of the Brentford business, and withdrew to Churt, near Farnham, in Surrey. There, in a lonely spot, on the top of a detached conical hill known as the Devil's Jump, he built a second observatory, and erected an instrument which he was no longer able to use with pristine effectiveness. And there, November 27, 1875, he died of the rupture of a blood vessel on the brain, before he had completed his 50th year. His observations of sunspots were of a geometrical character. They concerned positions and movements, leaving out of sight physical peculiarities. Indeed, the prudence with which he limited his task to what came strictly within the range of his powers to accomplish, was one of Carrington's most valuable qualities. The method of his observations, moreover, was chosen with the same practical sagacity as their objects. As early as 1847, Sir John Herschel had recommended the daily self-registration of sunspots, and he enforced the suggestion, with more immediate prospect of success, in 1854. The art of celestial photography, however, was even then in a purely tentative stage, and Carrington wisely resolved to waste no time on dubious experiments, but employ the means of registration and measurement actually at his command. These were very simple, yet very effective. To the helioscope employed by Father Scheiner 2 centuries and a quarter earlier, a species of micrometer was added. The image of the sun was projected upon a screen by means of a firmly clamped telescope, in the focus of which were placed 2 crosswires forming angles of 45 degrees with the meridian. The 6 instants were then carefully noted at which these were met by the edges of the disk as it traversed the screen, and by the nucleus of the spot to be measured. A short process of calculation then gave the exact position of the spot as referred to the sun's center. From a series of 5,290 observations made in this way, together with a great number of accurate drawings, Carrington derived conclusions of great importance on each of the 3 points which he had proposed to himself to investigate. These were, the law of the sun's rotation, the existence and direction of systematic currents, and the distribution of spots on the solar surface. Grave discrepancies were early perceived to exist between determinations of the sun's rotation by different observers. Galileo, with comfortable generality, estimated the period at about a lunar month, Scheiner, at 27 days. Cassini, in 1678, made it 25:58, D'Alembert, in 1775, no more than 25 days. Later inquiries brought these divergences within no more tolerable limits. Logier's result of 25:34 days, obtained in 1841, enjoyed the highest credit, yet it differed widely in one direction from that of Bohm, 1852, giving 25:52 days, and in the other from that of Caesius, 1846, giving 25:09 days. Now the cause of these variations was really obvious from the first, although for a long time strangely overlooked. Scheiner pointed out in 1630 that different spots gave different periods, adding the significant remark that one at a distance from the solar equator revolved more slowly than those nearer to it. But the hint was wasted. For upwards of 2 centuries ideas on the subject were either retrograde or stationary. What were called the proper motions of spots were, however, recognized by Schroeder, and utterly baffled Logier, who despaired of obtaining any concordant result as to the sun's rotation except by taking the mean of a number of discordant ones. At last, in 1855, a valuable course of observations made at Capo di Monte, Naples, in 1845-6, enabled C.H.F. Peters to set in the clearest light the insecurity of determinations based on the assumption of fixity in objects plainly affected by movements uncertain both in amount and direction. Such was the state of affairs when Carrington entered upon his task. Everything was in confusion. The most that could be said was that the confusion had come to be distinctly admitted and referred to its true source. What he discovered was this, that the sun, or at least the outer shell of the sun visible to us, has no single period of rotation, but drifts round, carrying the spots with it, at a rate continually accelerated from the poles to the equator. In other words, the time of axial revolution is shortest at the equator and lengthens with increase of latitude. Carrington devised a mathematical formula by which the rate or law of this lengthening was conveniently expressed. But it was a purely empirical one. It was a concise statement, but implied no physical interpretation. It summarized, but did not explain the facts. An assumed mean period for the solar rotation of 38 days, 25 days 9 hours, very nearly, was thus found to be actually conformed to only in two parallels of solar latitude, 14 degrees north and south. While the equatorial period was slightly less than 25, and that of latitude 50 degrees rose to 27 days and a half. These curious results gave quite a new direction to ideas on solar physics. The other two elements of the sun's rotation were also ascertained by Carrington with hitherto unattained precision. He fixed the inclination of its axis to the ecliptic at 82 degrees 45, the longitude of the ascending node at 73 degrees 40, for the epoch 1850 AD. These data, which have scarcely yet been improved upon, suffice to determine the position in space of the sun's equator. Its north pole is directed towards a star in the coils of the Dragon, midway between Vega and the pole star. Its plane intersects that of the Earth's orbit in such a way that our planet finds itself in the same level on or about the 3rd of June and the 5th of December, when any spots visible on the disk cross it in apparently straight lines. At other times, the paths pursued by them seem curved, downward, to an observer in the northern hemisphere, between June and December, upward between December and June. A singular peculiarity in the distribution of sunspots emerged from Carrington's studies at the time of the minimum of 1856. Two broad belts of the solar surface, as we have seen, are frequented by them, of which the limits may be put at 6 degrees and 35 degrees of north and south latitude. Individual equatorial spots are not uncommon, but nearer to the poles than 35 degrees they are a rare exception. Carrington observed, as an extreme instance, in July, 1858, one in south latitude 44 degree. And Peters, in June, 1846, watched, during several days, a spot in 50 degrees 24 north latitude. But beyond this no true macula has ever been seen. For Lahir's reported observation of one in latitude 70 degrees is now believed to have had its place on the solar globe erroneously assigned. And the veiled spots, described by Trouvelot in 1875 as occurring within 10 degrees of the pole can only be regarded as, at the most, the same kind of disturbance in an undeveloped form. But the novelty of Carrington's observations consisted in the detection of certain changes in distribution concurrent with the progress of the 11-year period. As the minimum approached, the spot zones contracted towards the equator, and there finally vanished. Then, as if by a fresh impulse, spots suddenly reappeared in high latitude, and spread downwards with the development of the new phase of activity. Scarcely had this remark been made public, when Wolf found a confirmation of its general truth in Bohm's observations during the years 1833–36, and a perfectly similar behavior was noted both by Spörer and Secchi at the minimum epoch of 1867. The ensuing period gave corresponding indications. And it may now be looked upon as established that the spot zones close in towards the equator with the advance of each cycle, their activity culminating, as a rule, in a mean latitude of about 16 degrees, and expiring when it is reduced to 6 degrees. Before this happens, however, a completely new disturbance will have manifested itself some 35 degrees north and south of the equator, and will have begun to travel over the same course as its predecessor. Each series of sunspots is thus, to some extent, overlapped by the succeeding one, so that while the average interval from one maximum to the next is 11 years, the period of each distinct wave of agitation is 12 or 14. Curious evidence of the retarded character of the maximum of 1883-4 was to be found in the unusually low latitude of the spot zones when it occurred. Their movement downward having gone on regularly while the crisis was postponed, its final symptoms were hence displaced locally as well as in time. The law of zones was duly obeyed at the minima of 1890 and 1901, and Sporer found evidence of conformity to it so far back as 1619. His researches, however, also showed that it was in abeyance during some 70 years previously to 1716, during which period sunspots remained persistently scarce, and auroral displays were feeble and infrequent even in high northern latitudes. An unaccountable suspension of solar activity is, in fact, indicated. Gustav Sporer, born at Berlin in 1822, began to observe sunspots with the view of assigning the law of solar rotation in December, 1860. His assiduity and success with limited means attracted attention, and a government endowment was procured for his little solar observatory at Anklam, in Pomerania. The Crown Prince, afterwards Emperor Frederick, adding a 5-inch refractor to its modest equipment. Unaware of Carrington's discovery, not made known until January, 1859, he arrived at and published, in June, 1861, a similar conclusion as to the equatorial quickening of the sun's movement on its axis. Appointed observer in the new astrophysical establishment at Potsdam in 1874, he continued his sunspot determinations there for 20 years, and died July 7, 1895. The time had now evidently come for a fundamental revision of current notions respecting the nature of the sun. Herschel's theory of a cool, dark, habitable globe, surrounded by, and protected against, the radiations of a luminous and heat-giving envelope, was shattered by the first dicta of spectrum analysis. Traces of it may be found for a few years subsequent to 1859, but they are obviously survivals from an earlier order of ideas, doomed to speedy extinction. It needs only a moment's consideration of the meaning at last found for the Fraunhofer lines to see the incompatibility of the new facts with the old conceptions. They implied not only the presence near the sun, as glowing vapors, of bodies highly refractory to heat, but that these glowing vapors formed the relatively cool envelope of a still hotter internal mass. Kirchhoff, accordingly, included in his great memoir, On the Solar Spectrum, read before the Berlin Academy of Sciences, July 11, 1861, an exposition of the views on the subject to which his memorable investigations had led him. They may be briefly summarized as follows. Since the body of the sun gives a continuous spectrum, it must be either solid or liquid, while the interruptions in its light prove it to be surrounded by a complex atmosphere of metallic vapors, somewhat cooler than itself. Spots are simply clouds due to local depressions of temperature, differing in no respect from terrestrial clouds except as regards the kinds of matter composing them. These sun clouds take their origin in the zones of encounter between polar and equatorial currents in the solar atmosphere. This explanation was liable to all the objections urged against the cumulus theory, on the one hand, and the tradewind theory, on the other. Setting aside its propounder, it was consistently upheld perhaps by no man eminent in science except Sporer, and his advocacy of it proved ineffective to secure its general adoption. M. Fay, of the Paris Academy of Sciences, was the first to propose a coherent scheme of the solar constitution covering the whole range of new discovery. The fundamental ideas on the subject now in vogue here made their first connected appearance. Much, indeed, remained to be modified and corrected, but the transition was finally made from the old to the new order of thought. The essence of the change may be conveyed in a single sentence. The sun was thenceforth regarded, not as a mere heated body, or, still more remotely from the truth, as a cool body unaccountably spun round with a cocoon of fire, but as a vast heat-radiating machine. The terrestrial analogy was abandoned in one more particular besides that of temperature. The solar system of circulation, instead of being adapted, like that of the Earth, to the distribution of heat received from without, was seen to be directed towards the transportation towards the surface of the heat contained within. Polar and equatorial currents, tending to a purely superficial equalization of temperature, were replaced by vertical currents bringing up successive portions of the intensely heated interior mass, to contribute their share in turn to the radiation into space which might be called the proper function of a sun. Faye's views, which were communicated to the Academy of Sciences, January 16, 1865, were avowedly based on the anomalous mode of solar rotation discovered by Carrington. This may be regarded either as an acceleration increasing from the poles to the equator, or as a retardation increasing from the equator to the poles, according to the rate of revolution we choose to assume for the unseen nucleus. Faye preferred to consider it a retardation produced by ascending currents continually left behind as the sphere widened in which the matter composing them was forced to travel. He further supposed that the depth from which these vertical currents rose, and consequently the amount of retardation effected by their ascent to the surface, became progressively greater as the poles were approached, owing to the considerable flattening of the spheroidal surface from which they started. But the adoption of this expedient has been shown to involve inadmissible consequences. The extreme internal mobility betrayed by Carrington's and Sporer's observations led to the inference that the matter composing the Sun was mainly or wholly gaseous. This had already been suggested by Father Secchi a year earlier, and by Sir John Herschel in April, 1864, but it first obtained general currency through Faye's more elaborate presentation. A physical basis was afforded for the view by Cagnier de la Tour's experiments in 1822, proving that, under conditions of great heat and pressure, the vaporous state was compatible with a very considerable density. The position was strengthened when Andrews showed, in 1869, that above a fixed limit of temperature, varying for different bodies, true liquefaction is impossible, even though the pressure be so tremendous as to retain the gas within the same space that enclosed the liquid. The opinion that the mass of the Sun is gaseous now commands a very general assent, although the gaseity admitted is of such a nature as to afford the consistence rather of honey or pitch than of the aeriform fluids with which we are familiar. On another important point the course of subsequent thought was powerfully influenced by Faye's conclusions in 1865. Arago somewhat hastily inferred from experiments with the polariscope the wholly gaseous nature of the visible disk of the Sun. Kirchhoff, on the contrary, believed, erroneously, as we now know, that the brilliant continuous spectrum derived from it proved it to be a white-hot solid or liquid. Herschel and Secchi indicated a cloud-like structure as that which would best harmonize the whole of the evidence at command. The novelty introduced by Faye consisted in regarding the photosphere no longer as a defined surface, in the mathematical sense, but as a limit to which, in the general fluid mass, ascending currents carry the physical or chemical phenomena of incandescence. Uprushing floods of mixed vapors with strong affinities, say of calcium or sodium and oxygen, at last attain a region cool enough to permit their combination. A fine dust of solid or liquid compound particles, of lime or soda, for example, there collects into the photospheric clouds, and descending by its own weight in torrents of incandescent rain, is dissociated by the fierce heat below, and replaced by ascending and combining currents of similar constitution. This first attempt to assign the part played in cosmical physics by chemical affinities was marked by the importation into the theory of the Sun of the now familiar phrase dissociation. It is indeed tolerably certain that no such combinations as those contemplated by Faye occur at the photospheric level, since the temperature there must be enormously higher than would be needed to reduce all metallic earths and oxides. But molecular changes of some kind, dependent perhaps in part upon electrical conditions, in part upon the effects of radiation into space, most likely replace them. The conjecture was emitted by Dr. Johnstone Stoney in 1867 that the photospheric clouds are composed of carbon particles precipitated from their mounting vapor just where the temperature is lowered by expansion and radiation to the boiling point of that substance. But this view, though countenanced by Ångström, and advocated by Hastings of Baltimore, and other authorities, is open to grave objections. In Faye's theory, sunspots were regarded as simply breaks in the photospheric clouds, where the rising currents had strength to tear them asunder. It followed that they were regions of increased heat, regions, in fact, where the temperature was too high to permit the occurrence of the precipitations to which the photosphere is due. Their obscurity was attributed, as in Dr. Brester's more recent theory du Soleil, to deficiency of emissive power. Yet here the verdict of the spectroscope is adverse and irreversible. After every deduction, however, has been made, we still find that several ideas of permanent value were embodied in this comprehensive sketch of the solar constitution. The principal of these were, first, that the Sun is a mainly gaseous body. Secondly, that its stores of heat are rendered available at the surface by means of vertical convection currents, by the bodily transport, that is to say, of intensely hot matter upward, and of comparatively cool matter downward. Thirdly, that the photosphere is a surface of condensation, forming the limit set by the cold of space to this circulating process, and that a similar formation must attend, at a certain stage, the cooling of every cosmical body. To Warren de la Rue belongs the honor of having obtained the earliest results of substantial value in celestial photography. What had been done previously was interesting in the way of promise, but much could not be claimed for it as actual performance. Some pioneering experiments were made by Dr. J. W. Draper of New York in 1840, resulting in the production of a few moon pictures, 1 inch in diameter, but slight encouragement was derived from them either to himself or others. Bond of Cambridge, U.S. However, secured in 1850 with the Harvard 15-inch refractor that daguerreotype of the moon with which the career of extraterrestrial photography may be said to have formally opened. It was shown in London at the Great Exhibition of 1851, and determined the direction of de la Rue's efforts. Yet it did little more than prove the art to be a possible one. Warren de la Rue was born in Guernsey in 1815, and died in London April 19, 1889. Educated at the École Sainte-Barbe in Paris, he made a large fortune as a paper manufacturer in England, and thus amply and early provided the material supplies for his scientific campaign. Towards the end of 1853 he took some successful lunar photographs. They were remarkable as the first examples of the application to astronomical light painting of the collodion process, invented by Archer in 1851. And also of the use of reflectors. De la Rue's was one of 13 inches, constructed by himself, for that kind of work. The absence of a driving apparatus was, however, very sensibly felt. The difficulty of moving the instrument by hand so as accurately to follow the moon's apparent motion being such as to cause the discontinuance of the experiments until 1857, when the want was supplied. De la Rue's new observatory, built in that year at Cranford, was expressly dedicated to celestial photography. And there he applied to the heavenly bodies the stereoscopic method of obtaining relief, and turned his attention to the delicate business of photographing the sun. A solar daguerreotype was taken at Paris, April 2, 1845, by Foucault and Fizeau, acting on a suggestion from Arago. But the attempt, though far from being unsuccessful, does not, at that time, seem to have been repeated. Its great difficulty consisted in the enormous light power of the object to be represented, rendering an inconceivably short period of exposure indispensable, under pain of getting completely burnt-up plates. In 1857 de la Rue was commissioned by the Royal Society to construct an instrument specially adapted to the purpose for the Kew Observatory. The resulting photoheliograph may be described as a small telescope, of 3½ inches aperture and 50 focus, with a plate holder at the eye end, guarded in front by a spring slide. The rapid movement of which across the field of view secured for the sensitive plate a virtually instantaneous exposure. By its means the first solar light pictures of real value were taken, and the autographic record of the solar condition recommended by Sir John Herschel was commenced and continued at Kew during 14 years, 1858 to 72. The work of photographing the sun is now carried on in every quarter of the globe, from Mauritius to Massachusetts, and the days are few indeed on which the self-betrayal of the camera can be evaded by our chief luminary. In the year 1883 the incorporation of Indian with Greenwich pictures afforded a record of the state of the solar surface on 340 days, and 364 were similarly provided for in 1897 and 1899. The conclusions arrived at by photographic means at Kew were communicated to the Royal Society in a series of papers drawn up jointly by De La Rue, Balfour Stewart, and Benjamin Loewy, in 1865 and subsequent years. They influenced materially the progress of thought on the subject they were concerned with. By its rotation, the Sun itself offers opportunities for bringing the stereoscope to bear upon it. Two pictures, taken at an interval of 26 minutes, show just the amount of difference needed to give, by their combination, the maximum effect of solidity. De La Rue thus obtained, in 1861, a stereoscopic view of a sunspot and surrounding faculae, representing the various parts in their true mutual relations. I have ascertained in this way, he wrote, that the faculae occupy the highest portions of the Sun's photosphere, the spots appearing like holes in the penumbræ, which appeared lower than the regions surrounding them. In one case, parts of the faculae were discovered to be sailing over a spot apparently at some considerable height above it. Thus Wilson's inference as to the depressed nature of spots received, after the lapse of not far from a century, proof of the most simple, direct, and convincing kind. A careful application of Wilson's own geometrical test gave results only a trifle less decisive. Of 694 spots observed, 78% showed, as they traversed the disk, the expected effects of perspective. And their absence in the remaining 22% might be explained by internal commotions producing irregularities of structure. The absolute depth of spot cavities, at least of their sloping sides, was determined by Father Secchi through measurement of the parallax of profundity, that is, of apparent displacements attendant on the Sun's rotation, due to depression below the Sun's surface. He found that in every case it fell short of 4,000 miles, and averaged not more than 1,321, corresponding, on the terrestrial scale, to an excavation in the Earth's crust of 1 1/5 miles. Of late, however, the reality of even this moderate amount of depression has been denied. Mr. Howlett's persevering observations, extending over a third of a century, the results of which were presented to the Royal Astronomical Society in December, 1894. Availed to shatter the consensus of opinion which had so long been maintained on the subject of spot structure. It has become impossible any longer to hold that it is uniformly cavernous, and what seem like actually protruding umbræ are occasionally vouched for on unimpeachable authority. We can only infer that the forms of sunspots are really more various than had been supposed, that they are peculiarly subject to disturbance, and that the level of the nuclei may rise and fall during the phases of commotion, like lavas within volcanic craters. The opinion of the Kew observers as to the nature of such disturbances was strongly swayed by another curious result of the statistical method of inquiry. They found that of 1,137 instances of spots accompanied by faculae, 584 had those faculae chiefly or entirely on the left, 508 showed a nearly equal distribution, while 45 only had faculous appendages mainly on the right side. Now the rotation of the Sun, as we see it, is performed from left to right, so that the marked tendency of the faculae was a lagging one. This was easily accounted for by supposing the matter composing them to have been flung upwards from a considerable depth, whence it would reach the surface with the lesser absolute velocity belonging to a smaller circle of revolution, and would consequently fall behind the cavities or spots formed by its abstraction. An attempt, it is true, made by M. Wilsing at Potsdam in 1888 to determine the solar rotation from photographs of faculae had an outcome inconsistent with this view of their origin. They unexpectedly gave a uniform period. No trace of the retardation poleward from the equator, shown by the spots, could be detected in their movements. But the experiment was obviously inconclusive, and M. Stratonoff's repetition of it with ampler materials gave a full assurance that faculae rotate like spots in periods lengthening as latitude augments. The ideas of M. Fay were, on two fundamental points, contradicted by the Kew investigators. He held spots to be regions of uprush and of heightened temperature. They believed their obscurity to be due to a downrush of comparatively cool vapors. Now M. Chacornac, observing, at Villeurbanne, March 6, 1865, saw floods of photospheric matter visibly precipitating themselves into the abyss opened by a great spot and carrying with them small neighboring maculae. Similar instances were repeatedly noted by Father Secchi, who considered the existence of a kind of suction in spots to be quite beyond question. The tendency in their vicinity, to put it otherwise, is centripetal, not centrifugal. And this alone seems to negative the supposition of a central uprush. A fresh witness was by this time at hand. The application of the spectroscope to the direct examination of the Sun's surface dates from March 4, 1866, when Sir Norman Lockyer, to give him his present title, undertook an inquiry into the cause of the darkening in spots. It was made possible by the simple device of throwing upon the slit of the spectroscope an image of the Sun, any part of which could be subjected to special scrutiny, instead of, as had hitherto been done, admitting rays from every portion of his surface indiscriminately. The answer to the inquiry was prompt and unmistakable, and was again, in this case, adverse to the French theorist's view. The obscurations in question were found to be produced by no deficiency of emissive power, but by an increase of absorptive action. The background of variegated light remains unchanged, but more of it is stopped by the interposition of a dense mass of relatively cool vapors. The spectrum of a sunspot is crossed by the same set of multitudinous dark lines, with some minor differences, visible in the ordinary solar spectrum. We must then conclude that the same vapors, speaking generally, which are dispersed over the unbroken solar surface are accumulated in the umbral cavity. The compression incident to such accumulation being betrayed by the thickening of certain lines of absorption. But there is also a general absorption, extending almost continuously from one end of the spot spectrum to the other. Using, however, a spectroscope of exceptionally high dispersive power, Professor Young of Princeton, New Jersey, succeeded in 1883 in resolving the supposed continuous obscurity of spot spectra into a countless multitude of fine dark lines set very close together. Their structure was seen still more perfectly, about 5 years later, by M. Dünner, director of the UPS Observatory, who traced beside some shadowy vestiges of the crowded doublets and triplets forming the array, from the spots on to the general solar surface. They cease to be separable in the blue part of the spectrum. And the ultraviolet radiations of spots show nothing distinctive. As to the movements of the constipated vapors forming spots, the spectroscope is also competent to supply information. The principle of the method by which it is procured will be explained farther on. Suffice it here to say that the transport, at any considerable velocity, to or from the eye of the gaseous material giving bright or dark lines, can be measured by the displacement of such lines from their previously known normal positions. In this way movements have been detected in or above spots of enormous rapidity, ranging up to 320 miles per second. But the result, so far, has been to negative the ascription to them of any systematic direction. Uprushes and downrushes are doubtless, as Father Corti remarks, correlated phenomena in the production of a sunspot, but neither seem to predominate as part of its regular internal economy. The same kind of spectroscopic evidence tells heavily against a theory of sunspots started by Faye in 1872. He had been foremost in pointing out that the observations of Carrington and Sporer absolutely forbade the supposition that any phenomenon at all resembling our trade winds exists in the Sun. They showed, indeed, that beyond the parallels of 20 degrees there is a general tendency in spots to a slow poleward displacement, while within that zone they incline to approach the equator. But their proper movements gave no evidence of uniformly flowing currents in latitude. The systematic drift of the photosphere is strictly a drift in longitude, its direction is everywhere parallel to the equator. This fact being once clearly recognized, the solar tornado hypothesis at once fell to pieces, but M. Faye perceived another source of vorticose motion in the unequal rotating velocities of contiguous portions of the photosphere. The pores, with which the whole surface of the Sun is studded, he took to be the smaller eddies resulting from these inequalities, the spots to be such eddies developed into whirlpools. It only needs to thrust a stick into a stream to produce the kind of effect designated. And it happens that the differences of angular movement adverted to attain a maximum just about the latitudes where spots are most frequent and conspicuous. There are, however, grave difficulties in identifying the two kinds of phenomena. One, already mentioned, is the total absence of the regular swirling motion, in a direction contrary to that of the hands of a watch north of the solar equator. In the opposite sense south of it, which should impress itself upon every lineament of a sunspot if the cause assigned were a primary producing, and not merely, as it possibly may be, a secondary determining one. The other, pointed out by Young, is that the cause is inadequate to the effect. The difference of movement, or relative drift, supposed to occasion such prodigious disturbances, amounts, at the utmost, for two portions of the photosphere 123 miles apart, to about 5 yards a minute. Thus the friction of contiguous sections must be quite insignificant. A view better justified by observation was urged by Secchi in and after the year 1872, and was presented in an improved form by Professor Young in his excellent little book on the Sun, published in 1882. Spots are manifestly associated with violent eruptive action, giving rise to the faculae and prominences which usually garnish their borders. It is accordingly contended that upon the withdrawal of matter from below by the flinging up of a prominence must ensue a sinking in of the surface, into which the partially cooled erupted vapors rush and settle, producing just the kind of darkening by increased absorption told of by the spectroscope. Round the edges of the cavity the rupture of the photospheric shell will form lines of weakness provocative of further eruptions, which will, in their turn, deepen and enlarge the cavity. The phenomenon thus tends to perpetuate itself, until equilibrium is at last restored by internal processes. A sunspot might then be described as an inverted terrestrial volcano, in which the outbursts of heated matter take place on the borders instead of at the center of the crater, while the cooled products gather in the center instead of at the borders. But on the Earth, the solid crust forcibly represses the steam gathering beneath until it has accumulated strength for an explosion, while there is no such restraining power that we know of in the Sun. Zollner, indeed, adapted his theory of the solar constitution to the special purpose of procuring it, yet with very partial success, since almost every new fact has proved adverse to his assumptions. Volcanic action is essentially spasmodic. It implies habitual constraint varied by temporary outbreaks, inconceivable in a gaseous globe, such as we believe the Sun to be. If the volcanic hypothesis represented the truth, no spot could possibly appear without a precedent eruption. The real order of the phenomenon, however, is exceedingly difficult to ascertain, nor is it perhaps invariable. Although, in most cases, the opening shows first, that may be simply because it is more easily seen. According to Father Sidgreaves, the disturbance has then already passed the incipient stage. He considers it indeed highly probable that the preparatory sign of a new spot is always a small, bright patch of facula. This sequence, if established, would be fatal to Lockyer's theory of sunspots, communicated to the Royal Society, May 6, 1886, and further developed some months later in his work on the chemistry of the Sun. Spots are represented in it as incidental to a vast system of solar atmospheric circulation, starting with the polar out and up flows indicated by observations during some total eclipses, and eventuating in the plunge downward from great heights upon the photosphere of prodigious masses of condensed materials. From these falls result, primarily, spots, secondarily, through the answering uprushes in which chemical and mechanical forces cooperate, their girdles of flame prominences. The evidence is, however, slight that such a circulatory flow as would be needed to maintain this supposed cycle of occurrences really prevails in the Sun's atmosphere. And a similar objection applies to an anticyclonic theory, so to designate it, elaborated by Egon von Oppolzer in 1893. August Schmidt's optical rationale of solar phenomena was, on the other hand, a complete novelty, both in principle and development. Attractive to speculators from its recondite nature and far-reaching scope, it by no means commended itself to practical observers. Intolerant of finding the all but palpable realities of their daily experience dealt with as illusory products of circular refraction. A singular circumstance has now to be recounted. On the 1st of September, 1859, while Carrington was engaged in his daily work of measuring the positions of sunspots, he was startled by the sudden appearance of two patches of peculiarly intense light within the area of the largest group visible. His first idea was that a ray of unmitigated sunshine had penetrated the screen employed to reduce the brilliancy of the image. But, having quickly convinced himself to the contrary, he ran to summon an additional witness of an unmistakably remarkable occurrence. On his return he was disappointed to find the strange luminous outburst already on the wane. Shortly afterwards the last trace vanished. Its entire duration was 5 minutes, from 11:18 to 11:23 a.m., Greenwich time, and during those 5 minutes it had traversed a space estimated at 35,000 miles. No perceptible change took place in the details of the group of spots visited by this transitory conflagration, which, it was accordingly inferred, took place at a considerable height above it. Carrington's account was precisely confirmed by an observation made at Highgate. Mr. R. Hodgson described the appearance seen by him as that of a very brilliant star of light, much brighter than the sun's surface, most dazzling to the protected eye, illuminating the upper edges of the adjacent spots and streaks. Not unlike in effect the edging of the clouds at sunset. This unique phenomenon seemed as if specially designed to accentuate the inference of a sympathetic relation between the Earth and the Sun. From the 28th of August to the 4th of September, 1859, a magnetic storm of unparalleled intensity, extent, and duration, was in progress over the entire globe. Telegraphic communication was everywhere interrupted, except, indeed, that it was, in some cases, found practicable to work the lines without batteries, by the agency of the earth currents alone. Sparks issued from the wires. Gorgeous aurorae draped the skies in solemn crimson over both hemispheres, and even within the tropics, the magnetic needle lost all trace of continuity in its movements, and darted to and fro as if stricken with inexplicable panic. The coincidence was drawn even closer. At the very instant of the solar outburst witnessed by Carrington and Hodgson, the photographic apparatus at Kew registered a marked disturbance of all the three magnetic elements. While, shortly after the ensuing midnight, the electric agitation culminated, thrilling the earth with subtle vibrations, and lighting up the atmosphere from pole to pole with the coruscating splendors which, perhaps, dimly recall the times when our ancient planet itself shone as a star. Here then, at least, the sun was, in Professor Balfour Stewart's phrase, taken in the act of stirring up terrestrial commotions. Nor have instances since been wanting of an indubitable connection between outbreaks of individual spots and magnetic disturbances. For such were registered in 1882. And symptoms of the same kind, including the beautiful rose aurora, marked the progress across the sun of the enormous spot group of February, 1892, the largest ever recorded at Greenwich. This extraordinary formation, which covered about 1/300 of the sun's disk, survived through 5 complete rotations. It was remarkable for a persistent drift in latitude, its place altering progressively from 17 degrees to 30 degrees south of the solar equator. Again, the central passage of an enormous spot on September 9, 1898, synchronized with a sharp magnetic disturbance and brilliant aurora. And the coincidence was substantially repeated in March, 1899, when it was emphasized by the prevalent cosmic calm. The theory of the connection is indeed far from clear. Lord Kelvin, in 1892, pronounced against the possibility of any direct magnetic action by the sun upon the earth, on the ground of its involving an extravagant output of energy. But the fact is unquestionable that, in Professor Bigelow's words, abnormal agitations affect the sun and the earth as a whole and at the same time. The nearer approach to the event of September 1, 1859, was photographically observed by Professor George E. Hale at Chicago, July 15, 1892. An active spot in the southern hemisphere was the scene of this curiously sudden manifestation. During an interval of 12 m. Between 2 successive exposures, a bridge of dazzling light was found to have spanned the boundary line dividing the twin nuclei of the spot, and these, after another 27 m. were themselves almost obliterated by an overflow of far-spreading brilliancy. Yet 2 hours later, no trace of the outburst remained, the spot and its attendant faculae remaining just as they had been previously to its occurrence. Unlike that seen by Carrington, it was accompanied by no exceptional magnetic phenomena, although a storm set in next day. Possibly a terrestrial analogue to the former might be discovered in the auroral beam, which traversed the heavens during a vivid display of polar lights, November 17, 1882, and shared, there is every reason to believe, their electrical origin and character. Meantime Rudolf Wolf, transferred to the direction of the Zurich Observatory, where he died, December 6, 1893, had relaxed none of his zeal in the investigation of sunspot periodicity. A laborious revision of the entire subject with the aid of fresh materials led him, in 1859, to the conclusion that while the mean period differed little from that arrived at in 1852 of 11 years, very considerable fluctuations on either side of that mean were rather the rule than the exception. Indeed, the phrase, sunspot period, must be understood as fitting very loosely the great fact it is taken to represent. So loosely, that the interval between two maxima may rise to 16.5 or sink below 7.5 years. In 1861 Wolf showed, and the remark was fully confirmed at Kew, that the shortest periods brought the most acute crises, and vice versa. As if for each wave of disturbance a strictly equal amount of energy were available, which might spend itself lavishly and rapidly, or slowly and parsimoniously, but could in no case be exceeded. The further inclusion of recurring solar commotions within a cycle of 55.5 years was simultaneously pointed out, and Hermann Fritz showed soon afterwards that the aurora borealis is subject to an identical double periodicity. The same inquirer has more recently detected both for aurorae and sunspots a secular period of 222 years, and the Kew observations indicate for the latter oscillations accomplished within 26 and 24 days, depending, most likely, upon the rotation of the Sun. This is certainly reflected in magnetic, and perhaps in auroral periodicity. The more closely, in fact, spot fluctuations are looked into, the more complex they prove. Maxima of one order are superposed upon, or in part neutralized by, maxima of another order, originating causes are masked by modifying causes. The larger waves of the commotion are indented with minor undulations, and these again crisped with tiny ripples, while the whole rises and falls with the swell of the great secular wave. Scarcely perceptible in its progress because so vast in scale. The idea that solar maculation depends in some way upon the position of the planets occurred to Galileo in 1612. It has been industriously sifted by a whole bevy of modern solar physicists. Wolf in 1859 found reason to believe that the 11-year curve is determined by the action of Jupiter, modified by that of Saturn, and diversified by influences proceeding from the Earth and Venus. Its tempting approach to agreement with Jupiter's period of revolution round the Sun, indeed, irresistibly suggested a causal connection, yet it does not seem that the most skillful, coaxing, of figures can bring about a fundamental harmony. Carrington pointed out in 1863, that while, during 8 successive periods, from 1770 downwards, there were approximate coincidences between Jupiter's aphelion passages and sunspot maxima. The relation had been almost exactly reversed in the 2 periods preceding that date. And Wolf himself finally concluded that the Jovian origin must be abandoned. M. de Ponchal's prediction, nevertheless, of an abnormal retardation of the maximum due in 1881 through certain peculiarities in the positions of Uranus and Neptune about the time it fell due, was partially verified by the event, since, after an abortive phase of agitation in April, 1882, the final outburst was postponed to January, 1894. The interval was thus 13.5 instead of 11.1 years. And it is noticeable that the delay affected chiefly the southern hemisphere. Alternations of activity in the solar hemispheres were indeed a marked feature of the maximum of 1884, which, in M. phase view, derived thence its indecisive character, while sharp, strong crises arise with the simultaneous advance of agitation north and south of the solar equator. The curve of magnetic disturbance followed with its usual strict fidelity the anomalous fluctuations of the sunspot curve. The ensuing minimum occurred early in 1889, and was succeeded in 1894 by a maximum slightly less feeble than its predecessor. It cannot be said that much progress has been made towards the disclosure of the cause, or causes, of the sunspot cycle. No external influence adequate to the effect has, at any rate, yet been pointed out. Most thinkers on this difficult subject provide a quasi-explanation of the periodicity in question through certain assumed vicissitudes affecting internal processes. Sir Norman Lockyer and E. Von Oppolzer reached the same end by establishing self-compensatory fluctuations in the solar atmospheric circulation. Dr. Schuster resorts to changes in the electrical conductivity of space near the Sun. In all these theories, however, the course of transition is arbitrarily arranged to suit a period, which imposes itself as a fact peremptorily claiming admittance, while obstinately defying explanation. The question so much discussed, as to the influence of sunspots on weather, does not admit of a satisfactory answer. The facts of meteorology are too complex for easy or certain classification. Effects owning dependence on one cause often were the livery of another. The meaning of observed particulars may be inverted by situation, and yet it is only by the collection and collocation of particulars that we can hope to reach any general law. There is, however, a good deal of evidence to support the opinion, the grounds for which were primarily derived from the labors of Dr. Meldrum at Mauritius, that increased rainfall and atmospheric agitation attend spot maxima. While Herschel's conjecture of a more copious emission of light and heat about the same epochs has recently obtained some countenance from Savelief's measures showing a gain in the strength of the Sun's radiation pari passu with increase in the number of spots visible on his surface. The examination of what we may call the texture of the Sun's surface derived new interest from a remarkable announcement made by Mr. James Naismith in 1862. He had made, as he supposed, the discovery that the entire luminous stratum of the Sun is composed of a multitude of elongated, shining objects on a darker background, shaped much like willow leaves, of vast size, crossing each other in all possible directions, and possessed of unceasing relative motions. A lively controversy ensued. In England and abroad the most powerful telescopes were directed to a scrutiny encompassed with varied difficulties. Mr. Dawes was especially emphatic in declaring that Naismith's willow leaves were nothing more than the nodules of Sir William Herschel seen under a misleading aspect of uniformity, and there is little doubt that he was right. It is, nevertheless, admitted that something of the kind may be seen in the penumbræ and bridges of spots, presenting an appearance compared by Dawes himself in 1852 to that of a piece of coarse straw thatching left untrimmed at the edges. The term granulated, suggested by Dawes in 1864, best describes the mottled aspect of the solar disk as shown by modern telescopes and cameras. The grains, or rather the floccules, with which it is thickly strewn, have been resolved by Langley, under exceptionally favorable conditions, into granules not above 100 miles in diameter. And from these relatively minute elements, composing, jointly, about 1/5 of the visible photosphere, he estimates that 3/4 of the entire light of the Sun are derived. Janssen agrees, so far as to say that if the whole surface were as bright as its brightest parts, its luminous emission would be 10 to 20 times greater than it actually is. The rapid changes in the forms of these solar cloud summits are beautifully shown in the marvelous photographs taken by Janssen at Meudon, with exposures reduced at times to 1/100,000 of a second. By their means, also, the curious phenomenon known as the réseau photosphérique has been made evident. This consists in the diffusion over the entire disk of fleeting blurred patches, separated by a reticulation of sharply outlined and regularly arranged granules. The imperfect definition in the smudged areas may be due to agitations in the solar or terrestrial atmosphere, unless it be, as Dr. Schiemer thinks possible, merely a photographic effect. M. Janssen considers that the photospheric cloudlets change their shape and character with the progress of the sunspot period, but this is as yet uncertain. The grains, or more brilliant parts of the photosphere, are now generally held to represent the upper termination of ascending and condensing currents, while the darker interstices, Herschel's pores, mark the positions of descending cooler ones. In the penumbræ of spots, the glowing streams rushing up from the tremendous subsolar furnace are bent sideways by the powerful indraut, so as to change their vertical for a nearly horizontal motion, and are thus taken, as it were, in flank by the eye, instead of being seen end-on in mamelon form. This gives a plausible explanation of the channeled structure of penumbræ which suggested the comparison to a rood thatch. Accepting this theory as in the main correct, we perceive that the very same circulatory process which, in its spasms of activity, gives rise to spots, produces in its regular course the singular, marbled, appearance. For the recording of which we are no longer at the mercy of the fugitive or delusive impressions of the human retina. And precisely this circulatory process it is which gives to our great luminary its permanence as a sun, or warming and illuminating body. Footnotes. MEM. R.A.S., Volume 21, page 157. Ibid, page 160. Month. Not, Volume 21, page 144. Le Soleil, T.I. Pages 87 to 90, second edition, 1871. See ante, page 58. Observations at Red Hill, 1863, Introduction. Month. Not, Volume 36, page 142. Cape Observations, page 435, note. Month. Not, Volume 10, page 158. Rosa Acina, Lib 3, page 348. Observations at Red Hill, p. 8. Op. T. 3, page 402. Rosa Acina, Lib 4, page 601. Both Galileo and Scheiner spoke of the apparent or synodical period, which is about 1 1/3 days longer than the true or sidereal one. The difference is caused by the revolution of the Earth in its orbit in the same direction with the Sun's rotation on its axis. Rosa Acina, Lib 3, page 260. Fay, Comptes Rendus, T. Lx, page 818. Ibid, T. 12, page 648. Proc. A.M. Ass. ADV. Of Science, 1885, page 85. Observations at Red Hill, page 221. A.M. Jour of Science, volume 11, page 169. Month. Not, volume 19, page 1. Viertelgerschrift der Naderfers. Gesellschaft, Zurich, 1859, page 252. Lockyer, Chemistry of the Sun, page 428. Maunder, Knowledge, volume 15, page 130. Month. Mon, volume 50, page 251. Maunder, Knowledge, volume 17, page 173. Astre. Nock, number 1315. As late as 1866 an elaborate treatise in its support was written by F. Coyto, entitled Cesc le Soleil. Put il etre habite? And answering the question in the affirmative. The subsequent researches of Plucker, Frankland, Woolner, and others, showed that gases strongly compressed give an absolutely unbroken spectrum. Comptes Rendus, T. Lx, pp. 89, 138. Ibid, T. C., page 595. Bull. Meteor. Dell'Osservatorio del Colram, January 1, 1864, page 4. Quart. Jour of Science, volume 1, page 222. And de Chim. Etida Phys, T. 22, page 127. Phil. Trans, volume Clicks, page 575. Les Mondes, December 22, 1864, page 707. Comptes Rendus, T. Lx, page 147. Proc. Roy. Society, volume 16, page 29. Recherches sur le spectre solaire, page 38. A.M. Jour of Science, 1881, volume 21, page 41. Hastings stipulated only for some member of the triad, carbon, silicon, and boron. Ranyard, Knowledge, Volume 16, page 190. Young, The Sun, page 337, edition 1897. H. Draper, Quart. Journ. Of SC, Volume 1, page 381, also Phil. Mag, Volume 17, 1840, page 222. Reproduced in Arago's Popular Astronomy, Plate 12, Volume 1. Report Brit. Ass, 1859, page 148. Phil. Trans, Volume Cly, page 407. Researches in Solar Physics, Part 1, page 20. Both the phrase and the method were suggested by Faye, who estimated the average depth of the luminous sheath of spots at 2,160 miles. Comptes Rendus, T. LXI, page 1082, T. 96, page 356. Month. Knot, Volume 55, page 74. Sitgreaves, Ibid, page 282. Cordy, Ibid, Volume 58, page 91. Explained by East as refraction effects. Jour, Brit. Astre. Ass, Volume 8, page 187. Proc. Roy. SOC, Volume 14, page 39. Potsdam Publicationen, Number 18, Astre. Nock, Numbers 3000, 3287. Faye, Comptes Rendus, T. Xi. Page 77, Belopolsky, Astre. Nock, Number 2991. Ibid, Numbers 3275, 3344. Lockyer, Contributions to Solar Physics, page 70. Le Soleil, page 87. Proc. Roy. SOC, Volume 15, page 256. Phil. Mag, Volume 16, page 460. Recherches sur la rotation du Soleil, page 12. Hale, Astre. And Astrophysics, Volume 11, page 814. Jour, Brit. Astre. Ass, Volume 1, page 177. Comptes Rendus, T. 75, page 1664, Revue Scientifique, T. V., page 359, 1883. Mr. Herbert Spencer had already, in the Reader, February 25, 1865, put forward an opinion that spots were of the nature of cyclonic clouds. The Sun, page 174. For Faye's answer to the objection, see Comptes Rendus, T. 95, page 1310. A revised edition appeared in 1897. Astre. And Astrophysics, Volume 12, p. 832. Proc. Roy. SOC, Number 244. Astre. Nock, Number 3146, Astre. And Astrophysics, Volume 12, pages 419, 736. Sirius, September, 1893, Ibid, Volume 23, page 97, Astrophy. Jour, Volume 1, page 112, Wilczynski, page 178, Keeler, Volume 2, page 73, Hale. Month. Knot, Volume 20, page 13. Ibid, page 15. AM. Jour, Volume 29. Second Series, pages 94, 95. The magnetic disturbance took place at 11:15 a.m., 3 minutes before the solar blaze compelled the attention of Carrington. Phil. Trans, Volume CLI, page 428. Maunder, Journal Brit. Astre. Ass, Volume 2, page 386, Miss E. Brown, Ibid, page 210, Month. Knot, Volume 52, page 354. Observatory, Volume 21, page 387, Maunder, Knowledge, Volume 21, page 228, Fenny, Astroph. Jour, Volume 10, page 333. Ibid, page 336, W. Anderson, Observatory, Volume 22, page 196. Proc. Roy. Society, Volume 52, page 307, Reverend W. Sidgreaves, MEM. R.A.S., Volume 54, page 85. Report on Solar and Terrestrial Magnetism, Washington, 1898, page 27. Astro. and Astrophysics, Volume 11, page 611. Ibid, page 819, Sidgreaves. C. J. Rand Capron, Phil. Mag, Volume 15, page 318. Mitteilungen über die Sonnenflecken, No. 9, Viertelgeschrift der Niederforschenden Gesellschaft in Zurich, Jahrgang 4. Myth, No. Lee, page 58, 1881. Ibid, No. 12. Page 192. Baxendale, of Manchester, reached independently a similar conclusion. See Month. Not, Volume 21, page 141. Wolf, Myth, No. 15, page 107, etc. Olmsted, following Hanstein, had already, in 1856, sought to establish an auroral period of 65 years. Smithsonian Contributions, Volume 8, page 37. Hahn, über die Riesigungen der Sonnenfleckenperiode zu meteorologischen Erscheinungen, p. 99, 1877. Report Brit. As, 1881, page 518, 1883, page 418. The Reverend A. Cordy, Month. Not, Volume 60, page 538, detects the influence of a short subsidiary cycle, drive W. J. S. Lockyer that of a 35-year period, Nature, June 20, 1901. Professor Newcomb, Astroph. Jour, Volume 13, page 11, considers that solar activity oscillates uniformly in 11.13 years, with superposed periodic variations. Opere, T. 3, page 412. Myth, Numbers 7. and 18. Observations at Red Hill, page 248. Comptes rendus, T. 95, page 1249. Ibid, T. 93, page 827, T. 96, page 1418. Ibid, T. C. page 593. Ellis, Proc. Roy. Society, Volume 63, page 70. Schultz, Astro. Nock, Numbers 2817-18, 2847-8, Wilsing, Ibid, Number 3039, Belopolsky, Ibid, Number 2722. Report Brit. As, 1892, page 635. A. W. Auger, Astroph. Jour, Volume 13, page 346. Report Brit. As, 1862, page 16, pt 2. MEM. R.A.S., Volume 21, page 161. Month. Not, Volume 24, page 162. A.M. Jour of Science, Volume 7, 1874, page 92. Young, The Sun, page 103. And, Berlong, 1879, page 679. Ibid, 1878, page 689. Himmelsphotography, page 273. Ranyard, Knowledge, Volumes 14, page 14, 16, page 189, see also the accompanying photographs. Chapter 3. Recent Solar Eclipses. By observations made during a series of 5 remarkable eclipses, comprised within a period of 11 years, knowledge of the solar surroundings was advanced nearly to its present stage. Each of these events brought with it a fresh disclosure of a definite and unmistakable character. We will now briefly review this orderly sequence of discovery. Photography was first systematically applied to solve the problems presented by the eclipse Sunday, July 18, 1860. It is true that a daguerreotype, taken by Berkowski with the Königsberg heliometer during the eclipse of 1851, is still valuable as a record of the corona of that year. And some subsequent attempts were made to register partial phases of solar occultation, notably by Professor Bartlett at West Point in 1854, but the ground remained practically unbroken until 1860. In that year the track of totality crossed Spain, and thither, accordingly, Warren de la Rue transported his photoheliograph, and Father Secchi his 6-inch Cauchois refractor. The question then primarily at issue was that relating to the nature of the red protuberances. Although, as already stated, the evidence collected in 1851 gave a reasonable certainty of their connection with the Sun, objectors were not silenced. And when the side of incredulity was supported by so considerable an authority as M. Fay, it was impossible to treat it with contempt. Two crucial tests were available. If it could be shown that the fantastic shapes suspended above the edge of the dark moon were seen under an identical aspect from two distant stations, that fact alone would annihilate the theory of optical illusion or mirage. While the certainty that they were progressively concealed by the advancing moon on one side, and uncovered on the other, would effectually detach them from dependence on our satellite, and establish them as solar appendages. Now both these tests were eminently capable of being applied by photography. But the difficulty arose that nothing was known as to the chemical power of the rosy prominence light, while everything depended on its right estimation. A shot had to be fired, as it were, in the dark. It was a matter of some surprise, and of no small congratulation, that, in both cases, the shot took effect. De la Rue occupied a station at Rivabellosa, in the upper Ebro Valley. Secchi set up his instrument at Desierto de las Palmas, about 250 miles to the southeast, overlooking the Mediterranean. From the totally eclipsed sun, with its strange garland of flames, each observer derived several perfectly successful impressions, which were found, on comparison, to agree in the most minute details. This at once settled the fundamental question as to the substantial reality of these objects. While their solar character was demonstrated by the passage of the moon in front of them, indisputably attested by pictures taken at successive stages of the eclipse. That forms seeming to defy all laws of equilibrium were, nevertheless, not wholly evanescent, appeared from their identity at an interval of 7 minutes, during which the lunar shadow was in transit from one station to the other. And the singular energy of their actinic rays was shown by the record on the sensitive plates of some prominences invisible in the telescope. Moreover, photographic evidence strongly confirmed the inference, previously drawn by Grant and others, and now with fuller assurance by Secchi, that an uninterrupted stratum of prominence matter encompasses the Sun on all sides, forming a reservoir from which gigantic jets issue, and into which they subside. Thus, first fruits of accurate knowledge regarding the solar surroundings were gathered, while the value of the brief moments of eclipse gained indefinite increase. By supplementing transient visual impressions with the faithful and lasting records of the camera. In the year 1868 the history of eclipse spectroscopy virtually began, as that of eclipse photography in 1860, that is to say, the respective methods then first gave definite results. On the 18th of August, 1868, the Indian and Malayan peninsulas were traversed by a lunar shadow producing total obscuration during 5 minutes and 38 seconds. 2 English and 2 French expeditions were dispatched to the distant regions favored by an event so propitious to the advance of knowledge, chiefly to obtain the verdict of the prism as to the composition of prominences. Nor were they dispatched in vain. An identical discovery was made by nearly all the observers. At Jamkandi, in the Western Ghats, where Lieutenant, now Colonel, Herschel was posted, unremitting bad weather threatened to baffle his eager expectations. But during the lapse of the critical 5.5 minutes the clouds broke, and across the driving rack a long, finger-like projection jutted out over the margin of the dark lunar globe. In another moment the spectroscope was pointed towards it, 3 bright lines, red, orange, and blue, flashed out, and the problem was solved. The problem was solved in this general sense, that the composition out of glowing vapors of the objects infelicitously termed protuberances, or prominences, was no longer doubtful. Although further inquiry was needed for the determination of the particular species to which those vapors belonged. Similar, but more complete observations were made, with less atmospheric hindrance, by Tennant and Janssen at Guntur, by Pogson at Masulipatam, and by Rayet at Watan, on the coast of the Malay Peninsula. The last observer counting as many as 9 bright lines. Among them it was not difficult to recognize the characteristic light of hydrogen, and it was generally, though over hastily, assumed that the orange ray matched the luminous emissions of sodium. But fuller opportunities were at hand. The eclipse of 1868 is chiefly memorable for having taught astronomers to do without eclipses, so far, at least, as one particular branch of solar inquiry is concerned. Inspired by the beauty and brilliancy of the variously tinted prominence lines revealed to him by the spectroscope, Janssen exclaimed to those about him, "Je verrai ces lignes là en dehors de eclipses." On the following morning he carried into execution the plan which formed itself in his brain while the phenomenon which suggested it was still before his eyes. It rests upon an easily intelligible principle. The glare of our own atmosphere alone hides the appendages of the sun from our daily view. To a spectator on an airless planet, the central globe would appear attended by all its splendid retinue of crimson prominences, silvery corona, and far-spreading zodiacal light projected on the star-spangled black background of an absolutely unilluminated sky. Now the spectroscope offers the means of indefinitely weakening atmospheric glare by diffusing a constant amount of it over an area widened ad libitum. But monochromatic or bright-line light is, by its nature, incapable of being so diffused. It can, of course, be deviated by refraction to any extent desired, but it always remains equally concentrated, in whatever direction it may be thrown. Hence, when it is mixed up with continuous light, as in the case of the solar flames shining through our atmosphere, it derives a relative gain in intensity from every addition to the dispersive power of the spectroscope with which the heterogeneous mass of beams is analyzed. Employ prisms enough, and eventually the undiminished rays of persistent color will stand out from the continually fading rainbow-tinted band, by which they were at first effectually veiled. This Janssen saw by a flash of intuition while the eclipse was in progress, and this he realized at 10 a.m. next morning, August 19, 1868, the date of the beginning of spectroscopic work at the margin of the unobscured sun. During the whole of that day and many subsequent ones, he enjoyed, as he said, the advantage of a prolonged eclipse. The intense interest with which he surveyed the region suddenly laid bare to his scrutiny was heightened by evidences of rapid and violent change. On the 18th of August, during the eclipse, a vast spiral structure, at least 89,000 miles high, was perceived, planted in surprising splendor on the rim of the interposed moon. It was formed as General Tennant judged from its appearance in his photographs, by the encounter of 2 mounting torrents of flame, and was distinguished as the Great Horn. Next day it was in ruins. Hardly a trace remained to show where it had been. Janssen's spectroscope furnished him besides with the strongest confirmation of what had already been reported by the telescope and the camera as to the continuous nature of the scarlet Sierra lying at the base of the prominences. Everywhere at the sun's edge the same bright lines appeared. It was not until the 19th of September that Janssen thought fit to send news of his discovery to Europe. It seemed little likely to be anticipated. Yet a few minutes before his dispatch was handed to the secretary of the Paris Academy of Sciences, a communication similar in purport had been received from Sir Norman Lockyer. There is no need to discuss the narrow and wearisome question of priority. Each of the competitors deserves, and has obtained, full credit for his invention. With noteworthy and confident prescience, Lockyer, in 1866, before anything was yet known regarding the constitution of the red flames, ordered a strongly dispersive spectroscope for the express purpose of viewing, apart from eclipses, the bright line spectrum which he expected them to give. Various delays, however, supervened, and the instrument was not in his hands until October 16, 1868. On the 20th he picked up the vivid rays, of which the presence and, approximately, the positions had in the interim become known. But there is little doubt that, even without that previous knowledge, they would have been found, and that the eclipse of August 18 only accelerated a discovery already assured. Sir William Huggins, meanwhile, had been tending towards the same goal during 2.5 years in his observatory at Tulse Hill. The principle of the spectroscopic visibility of prominence lines at the edge of an uneclipsed sun was quite explicitly stated by him in February, 1868, and he devised various apparatus for bringing them into actual view. But not until he knew where to look did he succeed in seeing them. Astronomers, thus liberated, by the acquisition of power to survey them at any time, from the necessity of studying prominences during eclipses, were able to concentrate the whole of their attention on the corona. The first thing to be done was to ascertain the character of its spectrum. This was seen in 1868 only as a faintly continuous one. For Rayet, who seems to have perceived its distinctive bright line far above the summits of the flames, connected it, nevertheless, with those objects. On the other hand, Lieutenant Campbell ascertained on the same occasion the polarization of the coronal light in planes passing through the sun's center, thereby showing that light to be, in whole or in part, reflected sunshine. But if reflected sunshine, it was objected, the chief at least of the dark Fraunhofer lines should be visible in it, as they are visible in moonbeams, sky illumination, and all other sun-derived light. The objection was well founded, but was prematurely urged, as we shall see. On the 7th of August, 1869, a track of total eclipse crossed the continent of North America diagonally, entering at Bering Straits, and issuing on the coast of North Carolina. It was beset with observers. But the most effective work was done in Iowa. At Des Moines, Professor Harkness of the Naval Observatory, Washington, obtained from the corona an absolutely continuous spectrum, slightly less bright than that of the full moon, but traversed by a single green ray. The same green ray was seen at Burlington and its position measured by Professor Young of Dartmouth College. It appeared to coincide with that of a dark line of iron in the solar spectrum, numbered 1474 on Kirchhoff's scale. But in 1876 Young was able, by the use of greatly increased dispersion, to resolve the Fraunhofer line, 1474 into a pair, the more refrangible member of which he considered to be the reversal of the green coronal ray. Scarcely called in question for over 20 years, the identification nevertheless broke down through the testimony of the eclipse photographs of 1898. Sir Norman Lockyer derived from them a position for the line in question notably higher up in the spectrum than that previously assigned to it. Instead of 5,317, its true wavelength proved to be 5,303 10/millionths of a millimeter. Nor does it make any show by absorption in dispersed sunlight. The originating substance, designated coronium, of which nothing is known to terrestrial chemistry, continues luminous at least 300,000 miles above the sun's surface, and is hence presumably much lighter even than hydrogen. A further trophy was carried off by American skill 16 months after the determination due to it of the distinctive spectrum of the corona. The eclipse of December 22, 1870, though lasting only 2 minutes and 10 seconds, drew observers from the New, as well as from the Old World to the shores of the Mediterranean. Janssen issued from beleaguered Paris in a balloon, carrying with him the vital parts of a reflector specially constructed to collect evidence about the corona. But he reached Oran only to find himself shut behind a cloud curtain more impervious than the Prussian lines. Everywhere the sky was more or less overcast. Lockyer's journey from England to Sicily, and shipwreck in the Psyche, were recompensed with a glimpse of the solar aureola during 1.5 seconds. 3 parties stationed at various heights on Mount Etna saw absolutely nothing. Nevertheless important information was snatched in despite of the elements. The prominent event was Young's discovery of the reversing layer. As the surviving solar crescent narrowed before the encroaching moon, the dark lines of the spectrum, he tells us, and the spectrum itself, gradually faded away, until all at once, as suddenly as a bursting rocket shoots out its stars. The whole field of view was filled with bright lines more numerous than one could count. The phenomenon was so sudden, so unexpected, and so wonderfully beautiful, as to force an involuntary exclamation. Its duration was about 2 seconds, and the impression produced was that of a complete reversal of the Fraunhofer spectrum, that is, the substitution of a bright for every dark line. Now something of the kind was theoretically necessary to account for the dusky rays in sunlight which have taught us so much, and have yet much more to teach us. So that, although surprising from its transitory splendor, the appearance could not strictly be called unexpected. Moreover, its premonitory symptom in the fading out of these rays had been actually described by Secchi in 1868, and looked for by Young as the moon covered the sun in August 1869. But with the slit of his spectroscope placed normally to the sun's limb, the bright lines gave a flash too thin to catch the eye. In 1870 the position of the slit was tangential, it ran along the shallow bed of incandescent vapors, instead of cutting across it, hence his success. The same observation was made at Xerez de la Frontera by Mr. Pye, a member of Young's party. And, although an exceedingly delicate one, has since frequently been repeated. The whole Fraunhofer series appeared bright, omitting other instances, to Maclear, Herschel, and Fires in 1871, at the beginning or end of totality. To Pogson, at the breakup of an annual eclipse, June 6, 1872, to Stone at Klipfontein, April 16, 1874, when he saw the field full of bright lines. But between the picture presented by the veritable pluie de líneas brillantes, which descended into M. Trepid spectroscope for 3 seconds after the disappearance of the Sunday, May 17, 1882, and the familiar one of the dark line solar spectrum, certain differences were perceiving. Showing their relation to be not simply that of a positive to a negative impression. A reversing layer, or stratum of mixed vapors, glowing, but at a lower temperature than that of the actual solar surface, was an integral part of Kirchhoff's theory of the production of the Fraunhofer lines. Here it was assumed that the missing rays were stopped, and here also it was assumed that the missing rays would be seen bright, could they be isolated from the overpowering splendor of their background. This isolation is effected by eclipses, with the result, beautifully confirmatory of theory, of reversing, or turning from dark to bright, the Fraunhofer spectrum. The completeness and precision of the reversal, however, could not be visually attested, and a quarter of a century elapsed before a successful snapshot provided photographic evidence on the subject. It was taken at Novaya Zemlya by Mr. Shackleton, a member of the late Sir George Baden-Powell's expedition to observe the eclipse of August 9, 1896. And similar records in abundance were secured during the Indian eclipse of January 22, 1898, and the Spanish-American eclipse of May 28, 1900. The result of their leisurely examination has been to verify the existence of a reversing layer, in the literal sense of the term. It is true that no single flash photograph is an inverted transcript of the Fraunhofer spectrum. The lines are, indeed, in each case, speaking broadly, the same, but their relative intensities are widely different. Yet this need occasion no surprise when we remember that the Fraunhofer spectrum integrates the absorption of multitudinous strata, various in density and composition. While only the upper section of the formation comes within view of the sensitive plates exposed at totalities, the low-lying vaporous beds being necessarily covered by the moon. The total depth of this glowing envelope may be estimated at 500 to 600 miles, and its normal state seems to be one of profound tranquility, judging from the imperturbable aspect of the array of dark lines due to its sifting action upon light. The last of the 5 eclipses which we have grouped together for separate consideration was visible in southern India and Australia, December 12, 1871. Some splendid photographs were secured by the English parties on the Malabar coast, showing, for the first time, the remarkable branching forms of the coronal emanations. But the most conspicuous result was Jansen's detection of some of the dark Fraunhofer lines, long vainly sought in the continuous spectrum of the corona. Chief among these was the D line of sodium, the original index, it might be said, to solar chemistry. No proof could be afforded more decisive that this faint echoing back of the distinctive notes of the Fraunhofer spectrum, that the polariscope had spoken the truth in asserting a large part of the coronal radiance to be reflected sunlight. But it is usually so drenched in original luminosity, that its special features are almost obliterated. Jansen's success in seizing them was due in part to the extreme purity of the air at Chaleur, in the Neilgherries, where he was stationed. In part to the use of an instrument adapted by its large aperture and short focus to give an image of the utmost brilliancy. His observation, repeated during the Caroline Island eclipse of 1883, was photographically verified 10 years later by M. de la Baume Pluvinel in Senegal. An instrument of great value for particular purposes was introduced into eclipse work in 1871. The slitless spectroscope consists simply of a prism placed outside the object glass of a telescope or the lens of a camera, whereby the radiance encompassing the eclipsed sun is separated into as many differently tinted rings as it contains different kinds of light. These tinted rings were simultaneously viewed by Respighi at Puttacotta, and by Lockyer at Baikal. Their photographic registration by the latter in 1875 initiated the transformation of the slitless spectroscope into the prismatic camera. Meanwhile, the use of an ordinary spectroscope by Herschel and Tennant at Dodabetta showed the green ray of coronium to be just as bright in a rift as in the adjacent streamer. The visible structure of the corona was thus seen to be independent of the distribution of the gases which enter into its composition. By means, then, of the 5 great eclipses of 1860–71 it was ascertained, first, that the prominences, and at least the lower part of the corona, are genuine solar appurtenances. Secondly, that the prominences are composed of hydrogen and other gases in a state of incandescence, and rise, as irregular outliers, from a continuous envelope of the same materials, some thousands of miles in thickness. Thirdly, that the corona is of a highly complex constitution, being made up in part of glowing vapors, in part of matter capable of reflecting sunlight. We may now proceed to consider the results of subsequent eclipses. These have raised, and have helped to solve, some very curious questions. Indeed, every carefully watched total eclipse of the sun stimulates as well as appeases curiosity, and leaves a legacy of outstanding doubt, continually, as time and inquiry go on, removed, but continually replaced. It cannot be denied that the corona is a perplexing phenomenon, and that it does not become less perplexing as we know more about it. It presented itself under quite a new and strange aspect on the occasion of the eclipse which visited the western states of North America, July 29, 1878. The conditions of observation were peculiarly favorable. The weather was superb. Above the Rocky Mountains the sky was of such purity as to permit the detection of Jupiter's satellites with the naked eye on several successive nights. The opportunity for advancing knowledge was made the most of. Nearly 100 astronomers, including several Englishmen, occupied 12 separate posts, and prepared for an attack in force. The question had often suggested itself, and was a natural one to ask, whether the corona sympathizes with the general condition of the sun. Whether, either in shape or brilliancy, it varies with the progress of the sunspot period. A more propitious moment for getting this question answered could hardly have been chosen than that at which the eclipse occurred. Solar disturbance was just then at its lowest ebb. The development of spots for the month of July, 1878, was represented on Wolff's system of relative numbers, by the fraction 0.1, as against 135.4 for December, 1870, an epoch of maximum activity. The chromosphere was, for the most part, shallow and quiescent. Its depth, above the spot zones, had sunk from about 6,000 to 2,000 miles, prominences were few and faint. Obviously, if a type of corona corresponding to a minimum of sunspots existed, it should be seen then or never. It was seen, but while, in some respects, it agreed with anticipation, in others it completely set it at naught. The corona of 1878, as compared with those of 1869, 1870, and 1871, was generally admitted to be shrunken in its main outlines and much reduced in brilliancy. Lockyer pronounced it 10 times fainter than in 1871. Harkness estimated its light at less than 1/7 that derived from the mist-blotted aureola of 1870. In shape, too, it was markedly different. When sunspots are numerous, the corona appears to be most fully developed above the spot zones, thus offering to our eyes a rudely quadrilateral contour. The four great luminous sheaves forming the corners of the square are made up of rays curving together from each side into synclinal or ogival groups, each of which may be compared to the petal of a flower. To Janssen, in 1871, the eclipsing moon seemed like the dark heart of a gigantic dahlia, painted in light on the sky. And the similitude to the ornament on a compass card, used by Airy in 1851, well conveys the decorative effect of the beamy, radiated kind of aureola, never, it would appear, absent when solar activity is at a tolerably high pitch. In his splendid volume on eclipses, with which the systematic study of coronal structure may be said to have begun, Mr. Ranyard first generalized the synclinal peculiarity by a comparison of records. But the symmetry of the arrangement, though frequently striking, is liable to be confused by secondary formations. He further pointed out, with the help of careful drawings from the photographs of 1871 made by Mr. Wesley, the curved and branching shapes assumed by the component filaments of massive bundles of rays. Nothing of all this, however, was visible in 1878. Instead, there was seen, as the groundwork of the corona, a ring of pearly light, nebulous to the eye, but shown by telescopes and in photographs to have a fibrous texture, as if made up of tufts of fine hairs. North and south, a series of short, vivid, electrical-looking flame brushes diverged with conspicuous regularity from each of the solar poles. Their direction was not towards the center of the sun, but towards each summit of his axis, so that the farther rays on either side started almost tangentially to the surface. But the leading, and a truly amazing, characteristic of the phenomenon was formed by two vast, faintly luminous wings of light, expanded on either side of the sun in the direction of the ecliptic. These were missed by very few careful onlookers. But the extent assigned to them varied with skill in, and facilities for seeing. By far the most striking observations were made by Newcomb at Separation, Wyoming, by Cleveland Abbe from the shoulder of Pike's Peak, and by Langley at its summit, an elevation of 14,100 feet above the sea. Never before had an eclipse been viewed from anything approaching that altitude, or under so translucent a sky. A proof of the great reduction in atmospheric glare was afforded by the perceptibility of the corona for minutes after totality was over. For the 165 seconds of its duration, the remarkable streamers above alluded to continued, persistently visible, stretching away right and left of the sun to a distance of at least 10 million miles. One branch was traced over an apparent extent of fully 12 lunar diameters, without sign of a definite termination having been reached, and there were no grounds for supposing the other more restricted. The resemblance to the zodiacal light was striking, and a community of origin between that enigmatical member of our system and the corona was irresistibly suggested. We should, indeed, expect to see, under such exceptionally favorable atmospheric conditions as Professor Langley enjoyed on Pike's Peak, the roots of the zodiacal light presenting near the sun just such an appearance as he witnessed. But we can imagine no reason why their visibility should be associated with a low state of solar activity. Nevertheless, this seems to be the case with the streamers which astonished astronomers in 1878. For in August, 1867, when similar equatorial emanations, accompanied by similar symptoms of polar excitement, were described and depicted by Grosch of the Santiago Observatory, sunspots were at a minimum. While the corona of 1715, which appears from the record of it by Roger Coates to have been of the same type, preceded by 3 years the ensuing maximum. The eclipsed sun was seen by him at Cambridge, May 2, 1715, encompassed with a ring of light about 1/6 of the moon's diameter in breadth, upon which was superposed a luminous cross formed of long bright branches lying very nearly in the plane of the ecliptic, and shorter polar arms so faint as to be only intermittently visible. The resemblance between his sketch and Cleveland Abbe's drawing of the corona of 1878 is extremely striking. It should, nevertheless, be noted that some conspicuous spots were visible on the sun's disk at the time of Coates's eclipse, and that the preceding minimum, according to Wolf, occurred in 1712. Thus, the coincidence of epochs is imperfect. Professor Cleveland Abbe was fully persuaded that the long rays carefully observed by him from Pikes Peak were nothing else than streams of meteorites rushing towards or from perihelion. And it is quite certain that the solar neighborhood must be crowded with such bodies. But the peculiar structure at the base of the streamers displayed in the photographs, the curved rays meeting in pointed arches like Gothic windows, the visible upspringing tendency, the filamentous texture, speak unmistakably of the action of forces proceeding from the sun, not of extraneous matter circling round him. A further proof of sympathetic change in the corona is afforded by the analysis of its light. In 1878 the bright line so conspicuous in the coronal spectrum in 1870 and 1871 had faded to the very limit of visibility. Several skilled observers failed to see it at all, but Young and Eastman succeeded in tracing the green, coronium, ray all round the sun, to a height estimated at 340,000 miles. The substance emitting it was thus present, though in a low state of incandescence. The continuous spectrum was relatively strong, faint traces of the Fraunhofer lines attested for it an origin, in part by reflection. And polarization was undoubted, increasing towards the limb, whereas in 1870 it reached a maximum at a considerable distance from it. Experiments with Edison's decimeter seem to show that the corona radiates a sensible amount of heat. The next promising eclipse occurred May 17, 1882. The concourse of astronomers which has become usual on such occasions assembled this time at Sohag, in Upper Egypt. Rarely have 74 seconds been turned to such account. To each observer a special task was assigned, and the advantages of a strict division of labor were visible in the variety and amount of the information gained. The year 1882 was one of numerous sunspots. On the eve of the eclipse 23 separate maculae were counted. If there were any truth in the theory which connected coronal forms with fluctuations in solar activity, it might be anticipated that the vast equatorial expansions and polar brushes of 1878 would be found replaced by the star-like structure of 1871. This expectation was literally fulfilled. No lateral streamers were to be seen. The universal failure to perceive them, after express search in a sky of the most transparent purity, justifies the emphatic assertion that they were not there. Instead, the type of corona observed in India 11 years earlier, was reproduced with its shining aigrettes, complex texture and brilliant radiated aspect. Concordant testimony was given by the spectroscope. The reflected light derived from the corona was weaker than in 1878, while its original emissions were proportionately intensified. Nevertheless, most of the bright lines recorded as coronal were really due, there can be no doubt, to diffused chromospheric light. On this occasion, the first successful attempt was made to photograph the coronal spectrum procured in the ordinary way with a slit and prisms, while the prismatic camera was also profitably employed. It served to bring out at least one important fact, that of the uncommon strength in chromospheric regions of the twin violet beams of calcium, designated H and K. And prominence photography signalized its improvement by the registration, in the spectrum of one such object, of 29 rays, including many of the ultraviolet hydrogen series discovered by Sir William Huggins in the emission of white stars. Dr. Schuster's photographs of the corona itself were the most extensive, as well as the most detailed, of any yet secured. One rift imprinted itself on the plates to a distance of nearly a diameter and a half from the limb. And the transparency of the streamers was shown by the delineation through them of the delicate tracery beyond. The singular and picturesque feature was added of a bright comet, self-depicted in all the exquisite grace of swift movement betrayed by the fine curve of its tail, hurrying away from one of its rare visits to our sun, and rendered momentarily visible by the withdrawal of the splendor in which it had been, and was again quickly veiled. From a careful study of these valuable records Sir William Huggins derived the idea of a possible mode of photographing the corona without an eclipse. As already stated, its ordinary invisibility is entirely due to the glare, or reflected light diffused through our atmosphere. But Huggins found, on examining Schuster's negatives, that a large proportion of the light in the coronal spectrum, both continuous and interrupted, is collected in the violet region between the Fraunhofer lines G and H. There, then, he hoped that, all other rays being excluded, it might prove strong enough to vanquish inimical glare, and stamp on prepared plates, through local superiority in illuminative power, the forms of the appendage by which it is emitted. His experiments were begun towards the end of May, 1882, and by September 28 he had obtained a fair earnest of success. The exclusion of all other qualities of light save that with which he desired to operate, was accomplished by using chloride of silver as his sensitive material. That substance being chemically inert to all other but those precise rays in which the corona has the advantage. Plates thus sensitized received impressions which it was hardly possible to regard as spurious. Not only the general features, Captain Abney affirmed, are the same, but details, such as rifts and streamers, have the same position and form. It was found, moreover, that the corona photographed during the total eclipse of May 6, 1883, was intermediate in shape between the coronas photographed by Sir William Huggins before and after that event. Each picture taking its proper place in a series of progressive modifications highly interesting in themselves, and full of promise for the value of the method employed to record them. But experiments on the subject were singularly interrupted. The volcanic explosion in the Straits of Sunda in August, 1883, brought to astronomers a peculiarly unwelcome addition to their difficulties. The magnificent sunglows due to the diffractive effects on light of the vapors and fine dust flung in vast volumes into the air, and rapidly diffused all round the globe, betokened an atmospheric condition of all others the most prejudicial to delicate researches in the solar vicinity. The filmy coronal forms, accordingly, which had been hopefully traced on the Tulse Hill plates ceased to appear there, nor were any substantially better results obtained by Mr. C. Ray Woods, in the purer air either of the Riffel or the Cape of Good Hope, during the 3 ensuing years. Moreover, attempts to obtain coronal photographs during the partial phases of the eclipse of August 29, 1886, completely failed. No part of the lunar globe became visible in relief against circumfluous solar radiance on any of the plates exposed at Granada. And what vestiges of structure there were, came out almost better upon the moon than beside her, thus stamping themselves at once as of atmospheric origin. That the effect sought is a perfectly possible one is proved by the distinct appearance of the moon projected on the corona, in photographs of the partially eclipsed sun in 1858, 1889, and 1890, and very notably in 1898 and 1900. In the spring of 1893, Professor Hale attacked the problem of coronal daylight photography, employing the double-slit method so eminently serviceable for the delineation of prominences. But neither at Kenwood nor at the summit of Pike's Peak, whither, in the course of the summer, he removed his apparatus, was any action of the desired kind secured. Similar ill success attended his and Professor Rico's employment, on Mount Etna in July, 1894, of a specially designed coronograph. Yet discouragement did not induce despair. The end in view is indeed too important to be readily abandoned. But it can be reached only when a more particular acquaintance with the nature of coronal light than we now possess indicates the appropriate device for giving it a preferential advantage in self-portraiture. Moreover, the effectiveness of this device may not improbably be enhanced, through changes in the coronal spectrum at epochs of sunspot maximum. The prosperous result of the Sohag observations stimulated the desire to repeat them on the first favorable opportunity. This offered itself 1 year later, May 6, 1883, yet not without the drawbacks incident to terrestrial conditions. The eclipse promised was of rare length, giving no less than 5 minutes and 23 seconds of total obscurity, but its path was almost exclusively a water track. It touched land only on the outskirts of the Marquesas group in the southern Pacific, and presented, as the one available foothold for observers, a coral reef named Caroline Island, 7.5 miles long by 1.5 wide. Unknown previously to 1874, and visited only for the sake of its stores of guano. Seldom has a more striking proof been given of the vividness of human curiosity as to the condition of the worlds outside our own, than in the assemblage of a group of distinguished men from the chief centers of civilization, on a barren ridge. Isolated in a vast and tempestuous ocean, at a distance, in many cases, of 11,000 miles and upwards from the ordinary scene of their labors. And all these sacrifices, the cost and care of preparation, the transport and readjustment of delicate instruments, the contrivance of new and more subtle means of investigating phenomena, on the precarious chance of a clear sky during one particular 5 minutes. The event, though fortunate, emphasized the hazard of the venture. The observation of the eclipse was made possible only by the happy accident of a serene interval between two storms. The American expedition was led by Professor Edward S. Holden, and to it were courteously permitted to be attached Messrs. Lawrence and Woods, photographers, sent out by the Royal Society of London. M. Janssen was chief of the French Academy mission. He was accompanied from Meudon by Trouvelot, and joined from Vienna by Palisa, and from Rome by Tacchini. A large share of the work done was directed to assuring or negativing previous results. The circumstances of an eclipse favor illusion. A single observation by a single observer, made under unfamiliar conditions, and at a moment of peculiar excitement, can scarcely be regarded as offering more than a suggestion for future inquiry. But incredulity may be carried too far. Janssen, for instance, felt compelled, by the survival of unwise doubts, to devote some of the precious minutes of obscurity at Caroline Island to confirming what, in his own persuasion, needed no confirmation, that is, the presence of reflected Fraunhofer lines in the spectrum of the corona. Trouvelot and Palisa, on the other hand, instituted an exhaustive, but fruitless search for the spurious intramercurian planets announced by Swift and Watson in 1878. New information, however, was not deficient. The corona proved identical in type with that of 1882, agreeably to what was expected at an epoch of protracted solar activity. The characteristic aigrettes were of even greater brilliancy than in the preceding year, and the chemical effects of the coronal light proved unusually intense. Janssen's photographs, owing to the considerable apertures, 6 and 8 inches, of his object glasses, and the long exposures permitted by the duration of totality, were singularly perfect. They gave a greater extension to the coronal than could be traced with the telescope, and showed its forms as absolutely fixed and of remarkable complexity. The English pictures, taken with exposures up to 60 seconds, were likewise of great value. They exhibited details of structure from the limb to the tips of the streamers, which terminated definitely, and as it seemed actually, where the impressions on the plates ceased. The coronal spectrum was also successfully photographed, and although the reversing layer in its entirety evaded record, a print was caught of some of its more prominent rays just before and after totality. The use of the prismatic camera was baffled by the anomalous scarcity of prominences. Using an ingenious apparatus for viewing simultaneously the spectrum from both sides of the Sun, Professor Hastings noticed at Caroline Island alternations, with the advance of the Moon. In the respective heights above the right and left solar limbs of the coronal green line, which were thought to imply that the corona, with its rifts and sheaves and tangled hanks of rays, is, after all, merely an elusive appearance produced by the diffraction of sunlight at the Moon's edge. But the observation was assuredly misleading or misinterpreted. Atmospheric diffusion may indeed, under favoring circumstances, be effective in deceptively enlarging solar appendages, but always to a very limited extent. The controversy is an old one as to the part played by our air in producing the radiance visible round the eclipsed Sun. In its original form, it is true, it came to an end when Professor Harkness, in 1869, pointed out that the shadow of the Moon falls equally over the air and on the Earth, and that if the Sun had no luminous appendages, a circular space of almost absolute darkness would consequently surround the apparent places of the superposed Sun and Moon. Mr. Proctor, with his usual ability, impressed this mathematically certain truth upon public attention, and Sir John Herschel calculated that the diameter of the negative halo thus produced would be, in general, no less than 23 degrees. But about the same time a noteworthy circumstance relating to the state of things in the solar vicinity was brought into view. On February 11, 1869, Messrs. Franklin and Lockyer communicated to the Royal Society a series of experiments on gaseous spectra under varying conditions of heat and density, leading them to the conclusion that the higher solar prominences exist in a medium of excessive tenuity. And that even at the base of the chromosphere the pressure is far below that at the Earth's surface. This inference was fully borne out by the researches of Woolner, and Janssen expressed the opinion that the chromospheric gases are rarefied almost to the degree of an air pump vacuum. Hence was derived a general and fully justified conviction that there could be outside, and incumbent upon the chromosphere, no such vast atmosphere as the corona appeared to represent. Upon the strength of which conviction the glare theory entered, chiefly under the auspices of Sir Norman Lockyer, upon the second stage of its existence. The genuineness of the inner corona to the height of 5 or 6 from the limb was admitted. But it was supposed that by the detailed reflection of its light in our air the far more extensive outer corona was optically created. The irregularities of the moon's edge being called into account for the rays and rifts by which its structure was varied. This view received some countenance from Admiral Maclear's observation, during the eclipse of 1870, of bright lines everywhere, even at the center of the lunar disk. Here, indeed, was an undoubted case of atmospheric diffusion. But here, also, was a safe index to the extent of its occurrence. Light scatters equally in all directions. So that when the moon's face at the time of an eclipse shows, as is the common case, a blank in the spectroscope, it is quite certain that the corona is not noticeably enlarged by atmospheric causes. A sky drifted over with thin cirrus clouds and air changed with aqueous vapor amply accounted for the abnormal amount of scattering in 1870. But even in 1870 positive evidence was obtained of the substantial reality of the radiated outer corona, in the appearance on the photographic plates exposed by Willard in Spain and by Brothers in Sicily of identical dark rifts. The truth is, that far from being developed by misty air, it is peculiarly liable to be effaced by it. The purer the sky, the more extensive, brilliant, and intricate in the details of its structure the corona appears. Take as an example General Meyer's description of the eclipse of 1869, as seen from the summit of White Top Mountain, Virginia, at an elevation above the sea of 5,523 feet, in an atmosphere of peculiar clearness. To the unaided eye, he wrote, the eclipse presented, during the total obscuration, a vision magnificent beyond description. As a center stood the full and intensely black disk of the moon, surrounded by the aureola of a soft bright light, through which shot out, as if from the circumference of the moon, straight, massive, silvery rays. Seeming distinct and separate from each other, to a distance of 2 or 3 diameters of the solar disk. The whole spectacle showing as on a background of diffused rose-colored light. On the same day, at Des Moines, Newcomb could perceive, through somewhat hazy air, no long rays, and the 4-pointed outline of the corona reached at its farthest only a single semi-diameter of the moon from the limb. The plain fact, that our atmosphere acts rather as a veil to hide the coronal radiance than as the medium through which it is visually formed, emerges from further innumerable records. No observations of importance were made during the eclipse of September 9, 1885. The path of total obscurity touched land only on the shores of New Zealand, and 2 minutes was the outside limit of available time. Hence local observers had the phenomenon to themselves, nor were they even favored by the weather in their efforts to make the most of it. One striking appearance was, however, disclosed. It was that of 2 white prominences of unusual brilliancy, shining like a pair of electric lamps hung one at each end of a solar diameter, right above the places of 2 large spots. This coincidence of diametrically opposite disturbances is of too frequent occurrence to be accidental. M. Trouvelot observed at Meuton, June 26, 1885, 2 active and evanescent prominences thus situated, each rising to the enormous height of 300,000 miles, and on August 16, one scarcely less remarkable, balanced by an antipodal spot group. It towered upward, as if by a process of unrolling, to 250,000 of miles, after which, in 2 minutes, the light died out of it, it had become completely extinct. The development, again from the ends of a diameter, of a pair of similar objects was watched, September 19 and 20, 1893, by Father Fenny, director of the Caloxa Observatory, and the phenomenon has been too often repeated to be accidental. The eclipse of August 29, 1886, was total during about 4 minutes over tropical Atlantic regions. And an English expedition, led by Sir Norman Lockyer, was accordingly dispatched to Grenada in the West Indies, for the purpose of using the opportunity it offered. But the rainy season was just then at its height, clouds and squalls were the order of the day, and the elaborately planned program of observation could only in part be carried through. Some good work, nonetheless, was done. Professor Tacchini, who had been invited to accompany the party, ascertained besides some significant facts about prominences. From a comparison of their forms and sizes during and after the eclipse, it appeared that only the growing vaporous cores of these objects are shown by the spectroscope under ordinary circumstances. Their upper sections, giving a faint continuous spectrum, and composed of presumably cooler materials, can only be seen when the veil of scattered light usually drawn over them is removed by an eclipse. Thus all modestly tall prominences have silvery summits, but all do not appear to possess the red heart of flame, by which alone they can be rendered perceptible to daylight observation. Some prove to be ordinarily invisible, because silvery throughout, sheeted ghosts, as it were, met only in the dark. Specimens of the class had been noted as far back as 1842, but Tacchini first drew particular attention to them. The one observed by him in 1886 rose in a branching form to a height of 150,000 miles, and gave a brilliantly continuous spectrum, with bright lines at H and K, but no hydrogen lines. Hence the total invisibility of the object before and after the eclipse. During the eclipse, it was seen framed, as it were, in a pointed arch of coronal light, the symmetrical arrangement of which with regard to it was obviously significant. Both its unspringing shape, and the violet rays of calcium strongly emitted by it, contradicted the supposition that white prominences represent a downrush of refrigerated materials. The corona of 1886, as photographed by Dr. Schuster and Mr. Maunder, showed neither the petals and plumes of 1871, nor the streamers of 1878. It might be called of a transition type. Wide polar rifts were filled in with tufted radiations, and bounded on either side by irregularly disposed, compound luminous masses. In the southwestern quadrant, a triangular ray, conspicuous to the naked eye, represented, Mr. W. H. Pickering thought, the projection of a huge, hollow cone. Branched and recurving jets were curiously associated with it. The intrinsic photographic brightness of the corona proved, from Pickering's measures, to be about 1/54th that of the average surface of the full moon. The Russian eclipse of August 19, 1887, can only be remembered as a disastrous failure. Much was expected of it. The shadow path ran overland from Leipzig to the Japanese Sea, so that the solar appurtenances would, it was hoped, be disclosed to observers echeloned along a line of 6,000 miles. But the incalculable element of weather rendered all forecasts nugatory. The clouds never parted, during the critical 3 minutes, over central Russia, where many parties were stationed, and Professor D. P. Todd was equally unfortunate in Japan. Some good photographs were, nevertheless, secured by Professor Arai, director of the Tokyo Observatory, as well as by M. Belopolsky and Glaisnap at Petrovsk and Djurdjevic respectively. They showed a corona of simpler form than that of the year before, but not yet of the pronounced type first associated by Mr. Ranyard with the lowest stage of solar activity. The genuineness of the association was ratified by the duplicate spectacle of the next ensuing minimum year. 2 total eclipses of the sun distinguished 1889. The first took place on New Year's Day, when a narrow shadow path crossed California, allowing less than 2 minutes for the numerous experiments prompted by the varied nature of modern methods of research. American astronomers availed themselves of the occasion to the full. The heavens were propitious. Photographic records were obtained in unprecedented abundance, and of unusual excellence. Their comparison and study placed it beyond reasonable doubt that the radiated corona belonging to periods of maximum sunspots gives place, at periods of minimum, to the winged type of 1878. Professor Holden perceived further that the equatorial extensions characterizing the latter tend to assume a trumpet shape. Their extremities diverge, as if mutually repellent, instead of flowing together along a medial plane. The maximum actinic brilliancy of the corona of January 1, 1889, was determined at Lick to be 21 times less than that of the full moon. Its color was described as, of an intense luminous silver, with a bluish tinge, similar to the light of an electric arc. Its spectrum was comparatively simple. Very few bright lines besides those of hydrogen and coronium, and apparently no dark ones, stood out from the prismatic background. The marked structural features of the corona, as presented by the negatives taken by Professors Niffer and Cherepin, were the filaments and the streamers. The filaments issued from polar calottes of 20 degrees radius. The impression conveyed to the eye, Professor Pritchett wrote, is that the equatorial stream of denser coronal matter extends across and through the filaments, simply obscuring them by its greater brightness. The effect is just as if the equatorial belt were superposed upon, or passed through, the filamentary structure. There is nothing in the photographs to prove that the filaments do not exist all round the Sun. The testimony from negatives of different lengths of exposure goes to show that the equatorial streamers are made up of numerous interlacing parts inclined at varying angles to the Sun's equator. The coronal extensions, perceptible with the naked eye to a distance of more than 3 degrees from the Sun, appeared barely 1/3 of that length on the best negatives. Little more could be seen of them either in Barnard's exquisite miniature pictures, or in the photographs obtained by W. H. Pickering with a 13-inch refractor, the largest instrument so far used in eclipse photography. The total eclipse of December 22, 1889, held out a prospect, unfortunately not realized, of removing some of the doubts and difficulties that impeded the progress of coronal photography. Messrs. Burnham and Skeeberl secured at Cayenne some excellent impressions, showing enough of the corona to prove its identical character with that depicted in the beginning of the year. But not enough to convey additional information about its terminal forms or innermost structure. Any better result was indeed impossible, the moisture-laden air having cut down the actinic power of the coronal light to 1/4 its previous value. 2 English expeditions organized by the Royal Astronomical Society fared still worse. Mr. Taylor was stationed on the west coast of Africa, 100 miles south of Luanda. Father Perry chose as the scene of his operations the Salad Islands, off French Guiana. Each was supplied with a reflector constructed by Dr. Common, endowed, by its extremely short focal length of 45, combined with an aperture of 20 inches, with a light concentrating force capable, it was hoped, of compelling the very filmiest coronal branches to self-registration. Had things gone well, 2 sets of coronal pictures, absolutely comparable in every respect, and taken at an interval of 2 hours and a half, would have been at the disposal of astronomers. But things went very far from well. Clouds altogether obscured the Sun in Africa, they only separated to allow of his shining through a saturated atmosphere in South America. Father Perry's observations were the last heroic effort of a dying man. Stricken with malaria, he crawled to the hospital as soon as the eclipse was over, and expired 5 days later, at sea, on board the Comus. He was buried at Barbados. And the sacrifice of his life had, after all, purchased no decisive success. Most of the plates exposed by him suffered deterioration from the climate, or from an inevitably delayed development. A drawing from the best of them by Miss Violet Common represented a corona differing from its predecessor of January 1, chiefly through the oppositely unsymmetrical relations of its parts. Then the western wing had been broader at its base than the eastern, now the inequality was conspicuously the other way. The next opportunity for retrieving the mischances of the past was offered April 16, 1893. The line of totality charted for that day ran from Chile to Senegambia. American parties appropriated the Andes, both shores of the Atlantic were in English occupation. French expeditions, led by Deslandres and Bigourdan, took up posts south of Cape Verde. A long totality of more than 4 minutes was favored by serene skies, hence an ample store of photographic data was obtained. Professor Skeeberl, of the Lick Observatory, took, almost without assistance, at Mina Bronces, a mining station 6,600 feet above the Pacific, 52 negatives, 8 of them with a 40-foot telescope. On a scale of 4.5 inches to the solar diameter. Not only the inner corona, but the array of prominences then conspicuous, appeared in them to be composed of fibrous jets and arches, held to be sections of elliptic orbits described by luminous particles about the Sun's center. One plate received the impression of a curious object, entangled amidst coronal streamers, and the belief in its cometary nature was ratified by the bestowal of a comet medal in recognition of the discovery. Similar paraboloidal forms had, nevertheless, occasionally been seen to make an integral part of earlier coronas, and it remains extremely doubtful whether Skeeberl's eclipse comet was justly entitled to the character claimed for it. The eclipse of 1893 disclosed a radiated corona such as a year of spot maximum was sure to bring. An unexpected fact about it was, however, ascertained. The coronal has been believed to have much in common with the chromospheric spectrum. It proved, on investigation with a large prismatic camera, employed under Sir Norman Lockyer's directions by Mr. Fowler at Fundium, to be absolutely distinct from it. The fundamental green ray had, on the West African plates, 7 more refrangible associates, but all alike are of unknown origin. They may be due to many substances, or to one, future research will perhaps decide. We can at present only say that the gaseous emission of the corona include none from hydrogen, helium, calcium, or any other recognizable terrestrial element. Deslandres' attempt to determine the rotation of the corona through opposite displacements, east and west of the interposed moon, of the violet calcium lines supposed to make part of the coronal spectrum, was thus rendered nugatory. Yet it gave an earnest of success, by definitely introducing the subject into the constantly lengthened program of eclipse work. There is, however, little prospect of its being treated effectively until the green line is vivified by a fresh access of solar activity. The flight of the moon's shadow was, on August 9, 1896, dogged by atrocious weather. It traversed, besides, some of the most inhospitable regions on the Earth's surface, and afforded, at the best, but a brief interval of obscurity. At Novaya Zemlya, however, of all places, the conditions were tolerably favorable, and, as we have seen, the trophy of a flash spectrograph was carried off. Some coronal photographs, moreover, taken by the late Sir George Baden-Powell and by M. Hansky, a member of a Russian party, were marked by features of considerable interest. They made apparent a close connection between coronal outflows and chromospheric jets, cone-shaped beams serving as the sheaths, or envelopes, of prominences. M. Hansky, indeed, thought that every streamer had a chromospheric eruption at its base. Further, dark veinings of singular shapes unmistakably interrupted the coronal light, and bordered brilliant prominences, reminding us of certain black lines traced by Swift across the anvil protuberance, August 7, 1869. In type the corona of 1896 reproduced that of 1886, as befitted its intermediate position in the solar cycle. The eclipse track on January 22, 1898, crossed the Indian Peninsula from Viziadrug, on the Malabar coast, to Mount Everest in the Himalayas. Not a cloud obstructed the view anywhere, and an unprecedented harvest of photographic records was garnered. The flash spectrum, in its successive phases, appeared on plates taken by Sir Norman Lockyer, Mr. Evershed, Professor Campbell, and others. Professor Turner set on foot a novel mode of research by picturing the corona in the polarized ingredient of its light, Mrs. Maunder practically solved the problem of photographing the faint coronal extensions, one ray on her plates running out to nearly 6 diameters from the moon's limb. Yet she used a Dallmeyer lens of only 1.5 inches aperture. Her success accorded perfectly with Professor Wadsworth's conclusion that effectiveness in delineation by slight contrasts of luminosity varies inversely with aperture. Triple-coated plates, and a comparatively long exposure of 20 seconds, contributed to a result unlikely, for some time, to be surpassed. The corona of 1898 presented a mixed aspect. The polar plumes due at minimum were combined in it with the quadrilateral ogives belonging to spot maxima. A slow course of transformation, in fact, seemed in progress. And it was found to be completed in 1900, when the eclipse of May 28 revealed the typical halo of a quiescent sun. The obscurity on this occasion was short, less than 100 seconds, but was well observed east and west of the Atlantic. No striking gain in knowledge, however, resulted. Important experiments were indeed made on the heat of the corona with Langley's bolometer, but their upshot can scarcely be admitted as decisive. They indicated a marked deficiency of thermal radiations, implying for coronal light, in Professor Langley's opinion, an origin analogous to that of the electric glow discharge, which, at low pressures, was found by K. Ångström in 1893 to have no invisible heat spectrum. The corona was photographed by Professor Barnard, at Wadesboro, North Carolina, with a 61.5-foot horizontal coelostat. In this instrument, of a type now much employed in eclipse operations and first recommended by Professor Turner, a 6-inch photographic objective preserved an invariable position, while a silvered plane mirror, revolving by clockwork once in 48 hours, since the angle of movement is doubled by reflection, supplied the light it brought to a focus. A temporary wooden tube connected the lens with the photographic house where the plates were exposed. Pictures thus obtained with exposures of from 1 to 14 seconds, were described as remarkably sharp and perfectly defined, showing the prominences and inner corona very beautifully. The polar fans came out magnificently. The Great Sumatra eclipse left behind it manifold memories of foiled expectations. A totality of above 6 minutes drew observers to the Far East from several continents, each cherishing a plan of inquiry which few were destined to execute. All along the line of shadow, which, on May 18, 1901, crossed Réunion and Mauritius, and again met land at Sumatra and Borneo, the meteorological forecast was dubious, and the meteorological actuality in the main deplorable. Nevertheless, the corona was seen, and fairly well photographed through drifting clouds, and proved to resemble in essentials the appendage viewed a year previously. Negatives taken by members of the Lick Observatory expedition led by Mr. Perrine disclosed the unique phenomenon of a violent coronal disturbance, with a small compact prominence as its apparent focus. Tumbling masses and irregular streamers radiating from a point subsequently shown by the Greenwich photographs to be the seat of a conspicuous spot, suggested the recent occurrence of an explosion, the far-reaching effects of which might be traced in the confused floccular luminosity of a vast surrounding region. Again, photographs in polarized light attested the radiance of the outer corona to be in large measure reflected, while that of the inner ring was original. And the inference was confirmed by spectrographs, recording many Fraunhofer lines when the slit lay far from the sun's limb, but none in its immediate vicinity. On plates exposed by Mr. Dyson and Dr. Humphreys with special apparatus, the coronal spectrum, continuous and linear, impressed itself more extensively in the ultraviolet than on any previous occasion, and Dr. Mitchell succeeded in photographing the reversing layer by means of a grating spectroscope. Finally, Mrs. Maunder, at Mauritius, despite mischievous atmospheric tremors, obtained with the Newbegin telescope an excellent series of coronal pictures. The principles of explanation applied to the corona may be briefly described as eruptive and electrical. The first was adopted by Professor Skeeberl in his Mechanical Theory, advanced in 1890. According to this view, the eclipse halo consists of streams of matter shot out with great velocity from the spot zones by forces acting perpendicularly to the sun's surface. The component particles return to the sun after describing sections of extremely elongated ellipses, unless their initial speed happen to equal or exceed the critical rate of 383 miles a second, in which case they are finally driven off into space. The perspective overlapping and interlacing of these incandescent outflows was supposed to occasion the intricacies of texture visible in the corona, and it should be recorded that a virtually identical conclusion was reached by Mr. Perrine in 1901, by a different train of reasoning, based upon a distinct set of facts. A theory on very much the same lines was, moreover, worked out by M. Belopolsky in 1897. Skibrel, however, had the merit of making the first adequate effort to deduce the real shape of the corona, as it exists in 3 dimensions, from its projection upon the surface of the sphere. He failed, indeed, to account for the variation in coronal types by the changes in our situation with regard to the Sun's equator. It is only necessary to remark that, if this were so, they should be subject to an annual periodicity, of which no trace can be discerned. Electromagnetic theories have the charm, and the drawback, of dealing largely with the unknown. But they are gradually losing the vague and intangible character which long clung to them, and the improved definition of their outlines has not, so far, brought them into disaccord with truth. The most promising hypothesis of the kind is due to Professor Bigelow of Washington. His able discussion of the eclipse photographs of January 1, 1889, showed a striking agreement between the observed coronal forms and the calculated effects of a repulsive influence obeying the laws of electric potential. Also postulated by Huggins in 1885. Finely subdivided matter, expelled from the Sun along lines of force emanating from the neighborhood of his poles, thus tends to accumulate at equipotential surfaces. In deference, however, to a doubt more strongly felt then than now, whether the presence of free electricity is compatible with the solar temperature, he avoided any express assertion that the coronal structure is an electrical phenomenon. Merely pointing out that, if it were, its details would be just what they are. Later, in 1892, Pupin in America, and Ebert in Germany, imitated the coronal streamers by means of electrical discharges in low vacua between small conducting bodies and strips of tinfoil placed on the outside of the containing glass receptacles. Finally, a critical experiment made by Ebert in 1895 served, as Bigelow justly said, to clear up the entire subject, and put the theory on a working basis. Having obtained coronoidal effects in the manner described, he proceeded to subject them to the action of a strong magnetic field, with the result of marshalling the scattered rays into a methodical and highly suggestive array. They followed the direction of the magnetic lines of force, and, forsaking the polar collar of the magnetized sphere, surrounded it like a ruffle. The obvious analogy with the aurora polaris and the solar corona was insisted upon by Ebert himself, and has been further developed by Bigelow. According to a recent modification of his hypothesis, the latter appendage is controlled by 2 opposing systems of forces. The magnetic causing the rays to diverge from the poles towards the equator, and the electrostatic urging their spread, through the mutual repulsion of the particles accumulated in the wings, from the equator towards either pole. The cyclical change in the corona, he adds, is probably due to a variation in the balance of power thus established, the magnetic polar influence dominating at minima, the electrostatic at maxima. And he may well feel encouraged by the fortunate combination of many experimental details into one explanatory whole, no less than by the hopeful prospect of further developments, both practical and theoretical, along the same lines. What we really know about the corona can be summed up in a few words. It is certainly not a solar atmosphere. It does not gravitate upon the Sun's surface and share his rotation, as our air gravitates upon and shares the rotation of the Earth. And this for the simple reason that there is no visible growth of pressure downwards, of which the spectroscope would infallibly give notice, in its gaseous constituents. Whereas under the sole influence of the Sun's attractive power, their density should be multiplied many million times in the descent through a mere fraction of their actual depth. They are apparently in a perpetual state of efflux from, and influx to our great luminary, under the stress of opposing forces. It is not unlikely that some part, at least, of the coronal materials are provided by eruptions from the body of the Sun. It is almost certain that they are organized and arranged round it through electromagnetic action. This, however, would seem to be influential only upon their white-hot or reflective ingredients, out of which the streamers and aigrettes are composed. Since the coronal gases appear, from observations during eclipses, to form a shapeless envelope, with condensations above the spot zones, or at the bases of equatorial extensions. The corona is undoubtedly affected both in shape and constitution by the periodic ebb and flow of solar activity, its low-tide form being winged, its high-tide form stellate. While the rays emitted by the gases contained in it fade, and a continuous spectrum brightens, at times of minimum sunspots. The appendage, as a whole, must be of inconceivable tenuity, since comets cut their way through it without experiencing sensible retardation. Not even Sir William Crookes's vacua can give an idea of the rarefaction which this fact implies. Yet the observed luminous effects may not in reality bear witness contradictory of it. One solitary molecule in each cubic inch of space might, in Professor Young's opinion, produce them. While in the same volume of ordinary air at the sea level, the molecules number, according to Dr. Johnstone Stoney, 20,000 trillions. The most important lesson, however, derived from eclipses is that of partial independence of them. Some of its fruits in the daily study of prominences the next chapter will collect. And the harvest has been rendered more abundant, as well as more valuable, since it has been found possible to enlist, in this department too, the versatile aid of the camera. Footnotes. Viertelgerschrift Astra. Guess, Jarg. 26, page 274. Astra. Jour, volume 4, page 33. Proc. Roy. SOC, volume 17, page 116. Comptes Rendus, T. 67, page 757. Comptes Rendus, T. 67, page 839. Month. Not, volume 27, page 88. Proc. Roy. SOC, volume 17, page 123. Washington Observations, 1867, App. 2. Harkness's Report, page 60. A.M. Jour, volume 48. Second Series, page 377. A.M. Jour, volume 11. Third Series, page 429. Campbell, Astroph. Jour, volume 10, page 186. Keeler, Reports on Eclipse of January 1, 1889, page 47. Everything in such observations depends upon the proper manipulation of the slit of the spectroscope. MEM. R.A.S., volume 41, page 435. Comptes Rendus, T. 67, page 1019. MEM. R.A.S., volume 41, page 43. Comptes Rendus, T. 94, page 1640. Young, Pop Astra, October, 1897, page 333. J. Evershed, Indian Eclipse, 1898, page 65, month. Not, volume 58, page 298, Proc. Roy. SOC, January 17, 1901. Frost, Astroph. Jour, volume 12, page 85, Lord, Ibid, volume 13, page 149. Comptes Rendus, T. Xvi. Number 1, Jour, Brit. Astra. As, volume 3, page 532. Lockyer, Phil. Trans, volume Clovii, page 551. The rosy envelope of prominence matter was so named by Lockyer in 1868, Phil. Trans, volume Clicks, page 430. According to Trivlot, Washington OBS, 1876, App. 3, page 80, the subtracted matter was, at least to some extent, accumulated in the polar regions. Bull. Phil. SOC Washington, volume 3, page 118. MEM. R.A.S., volume 41, 1879. Astra. Nock, number 1737. Correspondence with Newton, pages 181 to 184. Ranyard, MEM. Astra. SOC, volume 41, page 501. S. P. Langley, Washington OBS, 1876, App. 3, page 209, Nature, volume 61, page 443. Schuster, Proc. Roy. SOC, volume 35, page 154, measured and photographed about 30. AGNES, Phil. Trans, Volume CLXXV, p. 267. Proc. Roy. SOC, Volume 34, page 409. Experiments directed to the same end had been made by Dr. O. Losey at Potsdam, 1878-80. Astr. Knock, number 2486. The sensitiveness of chloride of silver extends from H to H. That is, over the upper or more refrangible half of the space in which the main part of the coronal light is concentrated. Proc. Roy. SOC, Volume 34, page 414. Report Brit. Association, 1883, page 351. Maunder, Indian Eclipse, page 125, Eclipse of 1900, p. 143. Astr. and Astrophysics, Volume 13, page 662. See Infra, page 197. AGNES, Phil. Trans, Volume CLXXX, page 119. Comptes Rendus, T. 97, page 592. Memoirs National A.C. of Sciences, Volume 2, page 102. Washington OBS, 1867, App. 2, page 64. The Sun, page 357. Proc. Roy. SOC, Volume 17, page 289. Comptes Rendus, T. 73, page 434. Washington OBS, 1867, App. 2, page 195. Stokes, Anniversary Address, Nature, Volume 35, page 114. Comptes Rendus, T. CI, page 50. Harvard Annals, Volume 18, page 99. Wesley, Phil. Trans, Volume CLXXX, page 350. Harvard Annals, Volume 18, page 108. Lick Report, page 20. Ibid, page 14. Ibid, page 155. Pub Astra. SOC of the Pacific, Volume 3, page 158. Professor Holden concluded, with less qualification, that so-called polar rays exist at all latitudes on the Sun's surface. Lick Report, page 19. Holden, Report on Eclipse of December, 1889, page 18, Charapin, Pub Astra. SOC of the Pacific, Volume 3, page 26. Published as the frontispiece to the Observatory, number 160. Wesley, Ibid, page 107. Lick Observatory Contributions, number 4, page 108. Astra. and Astrophysics, volume 13. Page 307. Lockyer, Phil. Trans, volume Klexvi, page 592. He died in London, November 20, 1898. Bull. Academic, St. Petersburg, T. 6, page 253. W. H. Wesley, Phil. Trans, volume CXC, page 204. Lick Reports on Eclipse of January 1, 1889, page 204. Astroph. Jour, volume 11, page 226. Observatory, volume 21, page 157. The Indian Eclipse, 1898, page 114. Science, June 22, 1900, Astroph. Jour, volume 12, page 370. And Der Physik, BD, 48, page 528. See also Wood, Physical Review, volume 4, page 191, 1896. Science, August 3, 1900. Lick Observatory Bulletin, number 9. Observatory, volume 24, pages 321, 375. Lick Report on Eclipse of December 22, 1889, page 47, month. Knot, volume 50, page 372. Lick OBS Bull, number 9. Bull. De l'Académique. St. Petersburg, T. 4, page 289. The solar corona discussed by Spherical Harmonics, Smithsonian Institution, 1889. Bakerian Lecture, Proc. Roy. SOC, Volume 39. Astra. and Astrophysics, Volume 11, page 483. Ibid, Volume 12, page 804. A.M. Journ. of Science, Volume 11, page 253, 1901. C. Huggins, Proc. Roy. SOC, Volume 39, page 108, Young, North A.M. Review, February, 1885, page 179. Professor W. A. Norton, of Yale College, appears to have been the earliest formal advocate of the expulsion theory of the solar surroundings, in the second, 1845, and later editions of his treatise on astronomy. Chapter 4. Solar Spectroscopy. The new way struck out by Janssen and Lockyer was at once and eagerly followed. In every part of Europe, as well as in North America, observers devoted themselves to the daily study of the chromosphere and prominences. Foremost among these were Lockyer in England, Zollner at Leipzig, Sporer at Anclam, Young at Hanover, New Hampshire, Secchi and Respighi at Rome. There were many others, but these names stood out conspicuously. The first point to be cleared up was that of chemical composition. Leisurely measurements verified the presence above the Sun's surface of hydrogen in prodigious volumes, but showed that sodium had nothing to do with the orange-yellow ray identified with it in the haste of the eclipse. From its vicinity to the deep hair, than which it is slightly more refrangible, the prominence line was, however, designated D_3, and the unknown substance emitting it was named by Lockyer, helium. Its terrestrial discovery ensued after 26 years. In March, 1895, Professor Ramsay obtained from the rare mineral clevite a volatile gas, the spectrum of which was found to include the yellow prominence ray. Helium was actually at hand, and available for examination. The identification cleared up many obscurities in chromospheric chemistry. Several bright lines, persistently seen at the edge of the Sun, and early suspected by Young to emanate from the same source as D_3, were now derived from helium in the laboratory. And all the complex emissions of that exotic substance ranged themselves into 6 sets or series, the members of which are mutually connected by numerical relations of a definite and simple kind. Helium is of rather more than twice the density of hydrogen, and has no chemical affinities. In almost evanescent quantities it lurks in the Earth's crust, and is diffused through the Earth's atmosphere. The importance of the part played in the prominent spectrum by the violet line of calcium was noticed by Professor Young in 1872, but since H and K lie near the limit of the visible spectrum, photography was needed for a thorough investigation of their appearances. Aided by its resources, Professor George E. Hale, then at the beginning of his career, detected in 1889 their unfailing and conspicuous presence. The substance emitting them not only constitutes a fundamental ingredient of the chromosphere, but rises, in the fantastic jets thence issuing, to greater heights than hydrogen itself. The isolation of H and K in solar prominences from any other of the lines usually distinctive of calcium was experimentally proved by Sir William and Lady Huggins in 1897 to be due to the extreme tenuity of the emitting vapor. Hydrogen, helium, and calcium form, then, the chief and unvarying materials of the solar Sierra and its peaks, but a number of metallic elements make their appearance spasmodically under the influence of disturbances in the layers beneath. In September, 1871, Young drew up at Dartmouth College a list of 103 lines significant of injections into the chromosphere of iron, titanium, chromium, magnesium, and many other substances. During 2 months' observation in the pure air of Mount Sherman, 8,335 feet high, in the summer of 1872, these telltale lines mounted up to 273, and he believes their number might still be doubled by steady watching. Indeed, Both Young and Lockyer have more than once seen the whole field of the spectroscope momentarily inundated with bright rays, as if the reversing layer had been suddenly thrust upwards into the chromosphere, and as quickly allowed to drop back again. The opinion would thus appear to be well grounded that the two form one continuous region, of which the lower parts are habitually occupied by the heaviest vapors, but where orderly arrangement is continually overturned by violent eruptive disturbances. The study of the forms of prominences practically began with Huggins's observation of one through an open slit, February 13, 1869. At first it had been thought possible to examine them only in sections, that is, by admitting mere narrow strips or lines of their various kinds of light. While the actual shape of the objects emitting those lines had been arrived at by such imperfect devices as that of giving to the slit of the spectroscope a vibratory moment rapid enough to enable the eye to retain the impression of one part while others were successively presented to it, it was an immense gain to find that their rays had strength to bear so much of dilution with ordinary light as was involved in opening the spectroscopic shutter wide enough to exhibit the tree-like, or horn-like, or flame-shaped bodies rising over the sun's rim in their undivided proportions. Several diversely colored images of them are formed in the spectroscope, each may be seen under a crimson, a yellow, a green, and a deep blue aspect. The crimson, however, built up out of the C-line of hydrogen, is the most intense, and is commonly used for purposes of observation and illustration. Friedrich Zollner was, by a few days, beforehand with Huggins in describing the open-slit method, but was somewhat less prompt in applying it. His first survey of a complete prominence, pictured in, and not simply intersected by, the slit of his spectroscope, was obtained July 1, 1869. Shortly afterwards the plan was successfully adopted by the whole band of investigators. A difference in kind was very soon perceived to separate these objects into two well-marked classes. Its natural and obvious character was shown by its having struck several observers independently. The distinction of cloud prominences from flame prominences was announced by Lockyer, April 27, by Zollner, June 2, and by Respighi, December 4, 1870. The first description are tranquil and relatively permanent, sometimes enduring without striking change for many days. Certain of the included species mimic terrestrial cloud scenery, now appearing like fleecy cirrus transpenetrated with the red glow of sunset, now like prodigious masses of cumulostratus hanging heavily above the horizon. The solar clouds, however, have the peculiarity of possessing stems. Slender columns can ordinarily be seen to connect the surface of the chromosphere with its outlying portions. Hence the fantastic likeness to forest scenery presented by the long ranges of fiery trunks and foliage occasionally seeming to fringe the sun's limb. But while this mode of structure suggests an actual outpouring of incandescent material, certain facts require a different interpretation. At a distance, and quite apart from the chromosphere, prominences have been perceived, both by Secchi and Young, to form, just as clouds form in a clear sky, condensation being replaced by ignition. Filaments were then thrown out downward towards the chromosphere, and finally the usual appearance of a stemmed prominence was assumed. Still more remarkable was an observation made by Trouvelot at Harvard College Observatory, June 26, 1874. A gigantic comma-shaped prominence, 82,000 miles high, vanished from before his eyes by a withdrawal of light as sudden as the passage of a flash of lightning. The same observer has frequently witnessed a gradual illumination or gradual extinction of such objects, testifying to changes in the thermal or electrical condition of matter already in situ. The first photograph of a prominence, as shown by the spectroscope in daylight, was taken by Professor Young in 1870. But neither his method, nor that described by Dr. Braun in 1872, had any practical success. This was reserved to reward the efforts towards the same end of Professor Hale. Begun at Harvard College in 1889, they were prosecuted soon afterwards at the Kenwood Observatory, Chicago. The great difficulty was to extricate the colored image of the gaseous structure, spectroscopically visible at the sun's limb, from the encompassing glare, a very little of which goes a long way in fogging sensitive plates. To counteract its mischievous effects, a second slit, besides the usual narrow one in front of the collimator, was placed on guard, as it were, behind the dispersing apparatus, so as to shut out from the sensitized surface all light save that of the required quality. The sun's image being then allowed to drift across the outer slit, while the plate holder was kept moving at the same rate, the successive sectional impressions thus rapidly obtained finally built up a complete picture of the prominence. Another expedient was soon afterwards contrived. The H and K rays of calcium are always, as we have seen, bright in the spectrum of prominences. They are besides fine and sharp, while the corresponding absorption lines in the ordinary solar spectrum are wide and diffuse. Hence, prominences formed by the spectroscope out of these particular qualities of violet light, can be photographed entire and at once, for the simple reason that they are projected upon a naturally darkened background. Atmospheric glare is abolished by local absorption. This beautiful method was first realized by Professor Hale in June, 1891. A spectroheliograph, consisting of a spectroscopic and a photographic apparatus of special type, attached to the eye end of an equatorial 12 inches in aperture, was erected at Kenwood in March, 1891. And with its aid, Professor Hale entered upon original researches of high promise for the advancement of solar physics. Noteworthy above all is his achievement of photographing both prominences and faculae on the very face of the sun. The latter had, until then, been very imperfectly observed. They were only visible, in fact, when relieved by their brilliancy against the dusky edge of the solar disk. Their convenient emission of calcium light, however, makes it possible to photograph them in all positions, and emphasizes their close relationship to prominences. The simultaneous picturing, moreover, of the entire chromospheric ring, with whatever trees or fountains of fire chance to be at the moment issuing from it, has been accomplished by a very simple device. The disk of the sun itself having been screened with a circular metallic diaphragm, it is only necessary to cause the slit to traverse the virtually eclipsed luminary, in order to get an impression of the whole round of its fringing appendages. And the record can be extended to the disk by removing the screen, and carrying the slit back at a quicker rate, when an image of the sun's surface, with the faculae in spots, is formed on the plate exactly within the image of the chromosphere formed during the first exposure. The whole operation, Professor Hale continues, is completed in less than a minute, and the resulting photographs give the first true pictures of the sun, showing all of the various phenomena at its surface. Most of these novel researches were, by a remarkable coincidence, pursued independently and contemporaneously by M. Deslandres, of the Paris Observatory. The ultraviolet prominence spectrum was photographed for the first time from an uneclipsed sun, in June, 1891, at Chicago. Besides H and K, 4 members of the Huggins series of hydrogen lines imprinted themselves on the plate. Meanwhile M. Deslandres was enabled, by fitting quartz lenses to his spectroscope, and substituting a reflecting for a refracting telescope, to get rid of the obstructive action of glass upon the shorter light waves, and thus to widen the scope of his inquiry into the peculiarities of those derived from prominences. As the result, not only all the 9 white star lines were photographed from a brilliant sun flame, but 5 additional ones were found to continue the series upward. The wavelengths of these last had, moreover, been calculated beforehand with singular exactness, from a simple formula known as Balmer's law. The new lines, accordingly, filled places in a manner already prepared for them, and were thus unmistakably associated with the hydrogen spectrum. This is now known to be represented in prominences by 27 lines, forming a kind of harmonic progression, only. Plate I. Photographs of the solar chromosphere and prominences. Taken with the spectroheliograph of the Kenwood Observatory, Chicago. By Professor George E. Hale. 4 of which are visibly darkened in the Fraunhofer spectrum of the sun. The chemistry of cloud prominences is simple. Hydrogen, helium, and calcium are their chief constituents. Flame prominences, on the other hand, show, in addition, the characteristic rays of a number of metals, among which iron, titanium, barium, strontium, sodium, and magnesium are conspicuous. They are intensely brilliant. Sharply defined in their varying forms of jets, spikes, fountains, waterspouts, of rapid formation and speedy dissolution, seldom attaining to the vast dimensions of the more tranquil kind. Eruptive or explosive by origin, they occur in close connection with spots, whether causally, the materials ejected as flames cooling and settling down as dark, depressed patches of increased absorption, or consequentially, as a reactive effect of falls of solidified substances from great heights in the solar atmosphere. The two classes of phenomena, at any rate, stand in a most intimate relation. They obey the same law of periodicity, and are confined to the same portions of the Sun's surface, while quiescent prominences may be found right up to the poles and close to the equator. The general distribution of prominences, including both genera, follows that of faculae much more closely than that of spots. From Father Secchi's and Professor Respighi's observations, 1869–71, were derived the first clear ideas on the subject, which have been supplemented and modified by the later researches of Professors Tacchini and Rico at Rome and Palermo. The results are somewhat complicated, but may be stated broadly as follows. The district of greatest prominence frequency covers and overlaps by several degrees that of the greatest spot frequency. That is to say, it extends to about 40 degrees north and south of the equator. There is a visible tendency to a second pair of maxima nearer the poles. The poles themselves, as well as the equator, are regions of minimum occurrence. Distribution in time is governed by the spot cycle, but the maximum lasts longer for prominences than for spots. The structure of the chromosphere was investigated in 1869 and subsequent years by Professor Respighi, director of the Capitoline Observatory, as well as by Sporer and Bredikhin of the Moscow Observatory. They found this supposed solar envelope to be of the same eruptive nature as the vast protrusions from it, and to be made up of a congeries of minute flames set close together like blades of grass. The appearance, Professor Young writes, which probably indicates a fact, is as if countless jets of heated gas were issuing through vents and spiracles over the whole surface, thus clothing it with flame which heaves and tosses like the blaze of a conflagration. The summits of these filaments of fire are commonly inclined, as if by a wind sweeping over them, when the sun's activity is near its height, but erect during his phase of tranquility. Sporer, in 1871, inferred the influence of permanent polar currents, but Tacchini showed in 1876 that the deflections upon which this inference was based ceased to be visible as the spot minimum drew near. Another peculiarity of the chromosphere, denoting the remoteness of its character from that of a true atmosphere, is the irregularity of its distribution over the sun's surface. There are no signs of its bulging out at the equator, as the laws of fluid equilibrium in a rotating mass would require, but there are some that the fluctuations in its depth are connected with the phases of solar agitation. At times of minimum it seems to accumulate and concentrate its activity at the poles, while maxima probably bring a more equable general distribution, with local depressions at the base of great prominences and above spots. A low-lying stratum of carbon vapor was, in 1897, detected in the chromosphere by Professor Hale with a grating spectroscope attached to the 40-inch Yerkes refractor. The eclipse photographs of 1893 disclosed to Hartley's examination the presence there of gallium, and those taken by Evershed in 1898 were found by Joule to be crowded with ultraviolet lines of the equally rare metal scandium. The general rule had been laid down by Sir Norman Lockyer that the metallic radiations from the chromosphere are those enhanced in the electric spark. Hence, the comparative study of conditions prevalent in the arc and the spark has acquired great importance in solar physics. The reality of the appearance of violent disturbance presented by the flaming kind of prominence can be tested in a very remarkable manner. Christian Doppler, professor of mathematics at Prague, announced in 1842 the theorem that the color of a luminous body, like the pitch of a sonorous body, must be changed by movements of approach or recession. The reason is this. Both color and pitch are physiological effects, depending, not upon absolute wavelength, but upon the number of waves entering the eye or ear in a given interval of time. And this number, it is easy to see, must be increased if the source of light or sound is diminishing its distance, and diminished if it is decreasing it. In the one case, the vibrating body pursues and crowds together the waves emanating from it. In the other, it retreats from them, and so lengthens out the space covered by an identical number. The principle may be thus illustrated. Suppose shots to be fired at a target at fixed intervals of time. If the marksman advances, say 20 paces between each discharge of his rifle, it is evident that the shots will fall faster on the target than if he stood still. If, on the contrary, he retires by the same amount, they will strike at correspondingly longer intervals. The result will of course be the same whether the target or the marksman be in movement. So far Doppler was altogether right. As regards sound, anyone can convince himself that the effect he predicted is a real one, by listening to the alternate shrilling and sinking of the steam whistle when an express train rushes through a station. But in applying this principle to the colors of stars he went widely astray. For he omitted from consideration the double range of invisible vibrations which partake of, and to the eye exactly compensate, changes of refrangibility in the visible rays. There is, then, no possibility of finding a criterion of velocity in the hue of bodies shining, like the sun and stars, with continuous light. The entire spectrum is slightly shifted up or down in the scale of refrangibility. Certain rays normally visible become exalted or degraded, as the case may be, into invisibility, and certain other rays at the opposite end undergo the converse process, but the sum total of impressions on the retina continues the same. We are not, however, without the means of measuring this subsensible transportation of the light gamut. Once more the wonderful Fraunhofer lines came to the rescue. They were called by the earlier physicists, fixed lines. But it is just because they are not fixed that, in this instance, we find them useful. They share, and in sharing betray, the general shift of the spectrum. This aspect of Doppler's principle was adverted to by Fizeau in 1848, and the first tangible results in the estimation of movements of approach and recession between the Earth and the stars were communicated by Sir William Huggins to the Royal Society, April 23, 1868. 18 months later, Zollner devised his reversion spectroscope for doubling the measurable effects of line displacements, aided by which ingenious instrument, and following a suggestion of its inventor, Professor H.C. Vogel succeeded at Bothkamp, June 9, 1871, in detecting effects of that nature due to the solar rotation. This application constitutes at once the test and the triumph of the method. The eastern edge of the Sun is continually moving towards us with an equatorial speed of about 1.25 miles per second, the western edge retreating at the same rate. The displacements, towards the violet on the east, towards the red on the west, corresponding to this velocity are very small, so small that it seems hardly credible that they should have been laid bare to perception. They amount to but 1/150th part of the interval between the two constituents of the D-line of sodium, and the D-line of sodium itself can be separated into a pair only by a powerful spectroscope. Nevertheless, Professor Young was able to show quite satisfactorily, in 1876, not only deviations in the solar lines from their proper places indicating a velocity of rotation, 142 miles per second, slightly in excess of that given by observations of spots, but the exemption of terrestrial lines, those produced by absorption in the Earth's atmosphere, from the general push upwards or downwards. Shortly afterwards, Professor Langley, then director of the Allegheny Observatory, having devised a means of comparing with great accuracy light from different portions of the Sun's disk, found that while the obscure rays in two juxtaposed spectra derived from the solar poles were absolutely continuous, no sooner was the instrument rotated through 90 degrees, so as to bring its luminous supplies from opposite extremities of the equator, then the same rays became perceptibly notched. The telluric lines, meanwhile, remained unaffected, so as to be virtually mapped by the process. This rapid and unfailing mode of distinction was used by Cornu with perfect ease during his investigation of atmospheric absorption near Loire in August and September, 1883. A beautiful experiment of the same kind was performed by M. Tholen, of M. Bischofsheim's observatory at Nice, in the summer of 1880. He confined his attention to one delicately defined group of 4 lines in the orange, of which the inner pair are solar, iron, and the outer terrestrial. At the center of the sun the intervals separating them were sensibly equal. But when the light was taken alternately from the right and left limbs, a relative shift in alternate directions of the solar, towards and from the stationary telluric rays became apparent. A parallel observation was made at Nineteenth, December 14, 1883, when it was noticed that a strong iron line in the yellow part of the solar spectrum is permanently double on the sun's eastern, but single on his western limb. Opposite motion displacements bringing about this curious effect of coincidence with, and separation from, an adjacent stationary line of our own atmosphere's production. According as the spectrum is derived from the retreating or advancing margin of the solar globe. Statements of fact so precise and authoritative amount to a demonstration that results of this kind are worthy of confidence, and they already occupy an important place among astronomical data. The subtle method of which they served to assure the validity was employed in 1887-9 by M. Dünner to test and extend Carrington's and Sporer's conclusions as to the anomalous nature of the sun's axial movement. His observations for the purpose, made with a fine diffraction spectroscope, just then mounted at the observatory of UPS, were published in 1891. Their upshot was to confirm and widen the law of retardation with increasing latitude derived from the progressive motions of spots. Determinations made within 15 degrees of the pole, consequently far beyond the region of spots, gave a rotation period of 38.5, that of the equatorial belt being of 25.5 days. Spots near the equator indeed complete their rounds in a period shorter by at least half a day, and proportionate differences were found to exist elsewhere in corresponding latitudes. But Dünner's observations, it must be remembered, apply to a distinct part of the complex solar machine from the disturbed photospheric surface. It is amply possible that the absorptive strata producing the Fraunhofer lines, significant, by their varying displacements at either limb, of the inferred varying rates of rotation, may gyrate more slowly than the spot-generating level. Moreover, faculae appear to move at a quicker pace than either. So that we have, for 3 solar formations, 3 different periods of average rotation, the shortest of which belongs to the faculae, one of intermediate length to the spots, and the most protracted to the reversing layer. All, however, agree in lengthening progressively from the equator towards the poles. Professor Holden aptly compared the Sun to a vast whirlpool where the velocities of rotation depend not only on the situation of the rotating masses as to latitude, but also as to depth beneath the exterior surface. Sir Norman Lockyer promptly perceived the applicability of the surprising discovery of line shiftings through end-on motion to the study of prominences. The discontinuous light of which affords precisely the same means of detecting movement without seeming change of place, as do lines of absorption in a continuous spectrum. Indeed, his observations at the sun's edge almost compelled recourse to an explanation made available just when the need of it began to be felt. He saw bright lines, not merely pushed aside from their normal places by a barely perceptible amount, but bent, torn, broken, as if by the stress of some tremendous violence. These remarkable appearances were quite simply interpreted as the effects of movements varying in amount and direction in the different parts of the extensive mass of incandescent vapors falling within a single field of view. Very commonly they are of a cyclonic character. The opposite distortions of the same colored rays betray the fury of counter-gales rushing along at the rate of 120 miles a second. While their undisturbed sections prove the persistence of a heart of peace in the midst of that unimaginable fiery whirlwind. Velocities up to 250 miles a second, or 15,000 times that of an express train at the top of its speed, were thus observed by Young during his trip to Mount Sherman, August 2, 1872. And these were actually doubled in an extraordinary outburst observed by Father Jules Fenyi, on June 17, 1891, at the Hainold Observatory in Hungary, as well as by M. Trouvelot at Meudon. Motions ascertainable in this way near the limb are, of course, horizontal as regards the sun's surface. The analogies they present might, accordingly, be styled meteorological rather than volcanic. But vertical displacements on a scale no less stupendous can also be shown to exist. Observations of the spectra of spots centrally situated, where motions in the line of sight are vertical, disclose the progress of violent uprushes and downrushes of ignited gases, for the most part in the penumbral or outlying districts. They appear to be occasioned by fitful and irregular disturbances, and have none of the systematic quality which would be required for the elucidation of sunspot theories. Indeed, they almost certainly take place at a great height above the actual openings in the photosphere. As to vertical motions above the limb, on the other hand, we have direct visual evidence of a truly amazing kind. The projected glowing matter has, by the aid of the spectroscope, been watched in its ascent. On September 7, 1871, Young examined at noon a vast hydrogen cloud 100,000 miles long, as it showed to the eye, and 54,000 high. It floated tranquilly above the chromosphere at an elevation of some 15,000 miles, and was connected with it by 3 or 4 upright columns, presenting the not uncommon aspect compared by Lockyer to that of a grove of banyans. Called away for a few minutes at 12.30, on returning at 12.55 the observer found that in the meantime the whole thing had been literally blown to shreds by some inconceivable uprush from beneath. In place of the quiet cloud I had left, the air, if I may use the expression, was filled with flying debris, a mass of detached, vertical, fusiform filaments, each from 10 to 30 long by 2 or 3 wide. Brighter and closer together where the pillars had formerly stood, and rapidly ascending. They rose, with a velocity estimated at 166 miles a second, to fully 200,000 miles above the sun's surface, then gradually faded away like a dissolving cloud, and at 1:15 only a few filmy wisps, with some brighter streamers low down near the photosphere, remained to mark the place. A velocity of projection of at least 500 miles per second was, by Proctor's calculation, required to account for this extraordinary display, to which the Earth immediately responded by a magnetic disturbance, and a fine aurora. It has proved by no means an isolated occurrence. Young saw its main features repeated, October 7, 1881, on a still vaster scale, for the exploded prominence attained, this time, an altitude of 350,000 miles, the highest yet chronicled. Lockyer, moreover, has seen a prominence 40,000 miles high shattered in 10 minutes, while uprushes have been witnessed by Respighi, of which the initial velocities were judged by him to be 400 or 500 miles a second. When it is remembered that a body starting from the sun's surface at the rate of 383 miles a second would, if it encountered no resistance, escape forever from his control, it is obvious that we have in the enormous forces of eruption or repulsion manifested in the outbursts just described, the means of accounting for the vast diffusion of matter in the solar neighborhood. Nor is it possible to explain them away, as Cornu, Fay, and others have sought to do, by substituting for the rush of matter in motion, progressive illumination through electric discharges, chemical processes, or even through the mere reheating of gases cooled by expansion. All the appearances are against such evasions of the difficulty presented by velocities stigmatized as fabulous and improbable, but which, there is the strongest reason to believe, really exist. On the 12th of December, 1878, Sir Norman Lockyer formally expounded before the Royal Society his hypothesis of the compound nature of the chemical elements. An hypothesis, it is true, over and over again propounded from the simply terrestrial point of view. What was novel was the superterrestrial evidence adduced in its support. And even this had been, in a general and speculative way, anticipated by Professor F. W. Clarke of Washington. Lockyer had been led to his conclusion along several converging lines of research. In a letter to M. Dumas, dated December 3, 1873, he had sketched out the successive stages of celestial dissociation, which he conceived to be represented in the sun and stars. The absence from the solar spectrum of metalloidal absorption he explained by the separation, in the fierce solar furnace, of such substances as oxygen, nitrogen, sulfur, and chlorine, into simpler constituents possessing unknown spectra. While metals were at that time still admitted to be capable of existing there in a state of integrity. 3 years later he shifted his position onward. He announced, as the result of a comparative study of the Fraunhofer and electric arc spectra of calcium, that the molecular grouping of that metal, which at low temperatures gives a spectrum with its chief line in the blue, is nearly broken up in the Sun into another or others with lines in the violet. This came to be regarded by him as a truly typical case. During 4 years, 1875 to 78 inclusive, this diligent observer was engaged in mapping a section of the more refrangible part of the solar spectrum, wavelengths 3800 to 4000, on a scale of magnitude such that, if completed down to the infrared, its length would have been about half a furlong. The attendant laborious investigation, by the aid of photography, of metallic spectra, seemed to indicate the existence of what he called basic lines. These held their ground persistently in the spectra of 2 or more metals after all possible impurities had been eliminated, and were therefore held to attest the presence of a common substratum of matter in a simpler state of aggregation than any with which we are ordinarily acquainted. Later inquiries have shown, however, that between the spectral lines of different substances there are probably no absolute coincidences. Basic lines are really formed of doublets or triplets merged together by insufficient dispersion. Of Thalin's original list of 70 rays common to several spectra, very few resisted Thalin's and Young's powerful spectroscopes, and the process of resolution was completed by Rowland. Thus the argument from community of lines to community of substance has virtually collapsed. It was replaced by one founded on certain periodical changes on the spectra of sunspots. They emerged from a series of observations begun at South Kensington under Sir Norman Lockyer's direction in 1879, and continued for 15 years. The principle of the method employed is this. The whole range of Fraunhofer lines is visible when the light from a spot is examined with the spectroscope, but relatively few are widened. Now these widened lines alone constitute, presumably, the true spot spectrum. They, and they alone, tell what kinds of vapor are thrust down into the strange dusky pit of the nucleus, the unaffected lines taking their accustomed origin from the overlying strata of the normal solar atmosphere. Here then we have the criterion that was wanted, the means of distinguishing, spectroscopically and chemically, between the cavity and the absorbing layers piled up above it. By its persistent employment some marked peculiarities have been brought out, such as the unfamiliar character of numerous lines in spot spectra, especially at epochs of disturbance, and the strange individuality in the behavior of every one of these darkened and distended rays. Each seems to act on its own account, it comports itself as if it were the sole representative of the substance emitting it. Its appearance is unconditioned by that of any of its terrestrial companions in the same spectrum. The most curious fact, however, elicited by these inquiries was that of the attendance of chemical vicissitudes upon the advance of the sunspot period. As the maximum approached, unknown replaced known components of the spot spectra in a most pronounced and unmistakable way. It seemed as if the vapors emitting lines of iron, titanium, nickel, etc., had ceased to exist as such, and their room been taken by others, total strangers in terrestrial laboratories. These were held by Lockyer to be simply the finer constituents of their predecessors, dissociation having been effected by the higher temperature ensuing upon increased solar activity. But Father Cordy's supplementary investigations at Stonyhurst modified, while they in the main substantiated, the South Kensington results. They showed that the substitution of unknown for known lines characterizes disturbed spots, at all stages of the solar cycle, so that no systematic course of chemical change can be said to affect the Sun as a whole. They showed further, from evidence independent of that obtained by Young in 1892, the remarkable conspicuousness in spot spectra of vanadium lines excessively faint in the Fraunhofer spectrum. Lockyer's unknown lines may probably thus be accounted for. They represent absorption, not by new, but by scarce elements, especially, Father Cordy thinks, those with atomic weights of about 50. The circumstance of their development in solar commotions, largely to the exclusion of iron, is none the less curious, but it cannot be explained by any process of dissociation. The theory has, however, to be considered under still another aspect. It frequently happens that the contortions or displacements due to motion are seen to affect a single line belonging to a particular substance, while the other lines of that same substance remain imperturbable. Now, how is this most singular fact, which seems at first sight to imply that a body may be at rest and in motion at one and the same instant, to be accounted for? It is accounted for, on the present hypothesis, easily enough, by supposing that the rays thus discrepant in their testimony, do not belong to one kind of matter, but to several, combined at ordinary temperatures to form a body in appearance elementary. Of these different vapors, one or more may of course be rushing rapidly towards or from the observer, while the others remain still. And since the line of sight across the average prominence region penetrates, at the sun's edge, a depth of about 300,000 miles, all the incandescent materials separately occurring along which line are projected into a single flame or cloud, it will be perceived that there is ample room for diversities of behavior. The alternative mode of escape from the perplexity consists in assuming that the vapor in motion is rendered luminous under conditions which reduce its spectrum to a few rays, the unaffected lines being derived from a totally distinct mass of the same substance shining with its ordinary emissions. Thus, calcium can be rendered virtually monochromatic by attenuation, and analogous cases are not rare. Sir Norman Lockyer only asks us to believe that effects which follow certain causes on the Earth are carried a stage further in the Sun, where the same causes must be vastly intensified. We find that the bodies we call compound split asunder at fixed degrees of heat within the range of our resources. Why should we hesitate to admit that the bodies we call simple do likewise at degrees of heat without the range of our resources? The term element simply expresses terrestrial incapability of reduction. That, in celestial laboratories, the means and their effect here absent should be present, would be an inference challenging, in itself, no expression of incredulity. There are indeed theoretical objections to it which, though probably not insuperable, are unquestionably grave. Our 70 chemical elements, for instance, are placed by the law of specific heats on a separate footing from their known compounds. We are not, it is true, compelled by it to believe their atoms to be really and absolutely such, to contain, that is, the irreducible minimum of material substance. But we do certainly gather from it that they are composed on a different principle from the salts and oxides made and unmade at pleasure by chemists. Then the multiplication of the species of matter with which Lockyer's results menace us, is at first sight startling. They may lead, we are told, to eventual unification, but the prospect appears remote. Their only obvious outcome is the disruption into several constituents of each terrestrial element. The components of iron alone should be counted by the dozen. And there are other metals, such as cerium, which, giving a still more complex spectrum, would doubtless be still more numerously resolved. Sir Norman Lockyer interprets the observed phenomena as indicating the successive combinations, in varying proportions, of a very few original ingredients, but no definite sign of their existence is perceptible. Protyle seems likely long to evade recognition, and the only intelligible underlying principle for the reasonings employed, that of one line, one element, implies a throng beyond counting of formative material units. Thus, added complexity is substituted for that fundamental unity of matter which has long formed the dream of speculators. And it is extremely remarkable that Sir William Crookes, working along totally different lines, has been led to analogous conclusions. To take only one example. As the outcome of extremely delicate operations of sifting and testing carried on for years, he finds that the metal yttrium splits up into 5, if not 8 constituents. Evidently, old notions are doomed, nor are any preconceived ones likely to take their place. It would seem, on the contrary, as if their complete reconstruction were at hand. Subversive facts are steadily accumulating. The revolutionary ideas springing from them tend, if we interpret them aright, towards the substitution of electrical for chemical theories of matter. Dissociation by the brute force of heat is already nearly superseded, in the thoughts of physicists, by the more delicate process of ionization. Precisely what this implies and involves we do not know. But the symptoms of its occurrence are probably altogether different from those gathered by Sir Norman Lockyer from the collation of celestial spectra. A. J. Ångström of UPS takes rank after Kirchhoff as a subordinate founder, so to speak, of solar spectroscopy. His great map of the normal solar spectrum was published in 1868, 2 years before he died. Robert Thalen was his coadjutor in its execution, and the immense labor which it cost was amply repaid by its eminent and lasting usefulness. For more than a score of years it held its ground as the universal standard of reference in all spectroscopic inquiries within the range of the visible emanations. Those that are invisible by reason of the quickness of their vibrations were mapped by Dr. Henry Draper, of New York, in 1873, and with superior accuracy by M. Cornu in 1881. The infrared part of the spectrum, investigated by Langley, Abney, and Knut Ångström, reaches perhaps no definite end. The radiations oscillating too slowly to affect the eye as light may pass by insensible gradations into the long Hertzian waves of electricity. Professor Rowland's photographic map of the solar spectrum, published in 1886, and in a second enlarged edition in 1889, opened fresh possibilities for its study, from far down in the red to high up in the ultraviolet. And the accompanying scale of absolute wavelengths has been, with trifling modifications, universally adopted. His new table of standard solar lines was published in 1893. Through his work, indeed, knowledge of the solar spectrum so far outstripped knowledge of terrestrial spectra, that the recognition of their common constituents was hampered by intolerable uncertainties. Thousands of the solar lines charted with minute precision remained unidentified for want of a corresponding precision in the registration of metallic lines. Rowland himself, however, undertook to provide a remedy. Aided by Louis E. Jewell, he redetermined, at the Johns Hopkins University, the wavelengths of about 16,000 solar lines, photographing for comparison with them the spectra of all the known chemical elements except gallium, of which he could procure no specimen. The labor of collation was well advanced when he died at the age of 52, April 16, 1901. Investigations of metallic arc spectra have also been carried out with signal success by Hasselberg, Kaiser and Runge, O. Losey, and others. Another condition sine qua non of progress in this department is the separation of true solar lines from those produced by absorption in our own atmosphere. And here little remains to be done. Thalen's great atlas was designed for this purpose of discrimination. Each of its 33 maps exhibits in quadruplicate a subdivision of the solar spectrum under varied conditions of weather and zenith distance. Telluric effects are thus made easily legible, and they account wholly for 866, partly for 246, out of a total of 3,200 lines. But the death of the artist, April 8, 1887, unfortunately interrupted the half-finished task of the last 7 years of his life. A most satisfactory record, meanwhile, of selective atmospheric action has been supplied by the experiments and determinations of Janssen, Cornu and Egorov, by Dr. Becker's drawings, and Mr. Maclean's photographs of the analyzed light of the sun at high, low, and medium altitudes, and the autographic pictures obtained by Mr. George Higgs, of Liverpool, of certain rhythmical groups in the red, emerging with surprising strength near sunset, excite general and well-deserved admiration. The main interest, however, of all these documents resides in the information afforded by them regarding the chemistry of the sun. The discovery that hydrogen exists in the atmosphere of the sun was made by Ångström in 1862. His list of solar elements published in that year, the result of an investigation separate from, though conducted on the same principle as Kirchhoff's, included the substance which we now know to be predominant among them. Dr. Plucker of Bonn had identified in 1859 the Fraunhofer line F with the green ray of hydrogen, but drew no inference from his observation. The agreement was verified by Ångström, 2 further coincidences were established. And in 1866 a fourth hydrogen line in the extreme violet, named H, was detected in the solar spectrum. With Thalen, he besides added manganese, titanium, and cobalt to the constituents of the sun enumerated by Kirchhoff, and raised the number of identical rays in the solar and terrestrial spectra of iron to no less than 460. Thus, when Sir Norman Lockyer entered on that branch of inquiry in 1872, 14 substances were recognized as common to the Earth and Sun. Early in 1878 he was able to increase the list provisionally to 33, all except hydrogen metals. This rapid success was due to his adoption of the test of length in lieu of that of strength in the comparison of lines. He measured their relative significance, in other words, rather by their persistence through a wide range of temperature, than by their brilliancy at any one temperature. The distinction was easily drawn. Photographs of the electric arc, in which any given metal had been volatilized, showed some of the rays emitted by it stretching across the axis of the light to a considerable distance on either side, while many others clung more or less closely to its central hottest core. The former, long lines, regarded as certainly representative, were those primarily sought in the solar spectrum, while the attendant, short lines, often, in point of fact, due to foreign admixtures, were set aside as likely to be misleading. The criterion is a valuable one, and its employment has greatly helped to quicken the progress of solar chemistry. Carbon was the first nonmetallic element discovered in the Sun. Messrs. Trowbridge and Hutchins of Harvard College concluded in 1887, on the ground of certain spectral coincidences, that this protein substance is vaporized in the solar atmosphere at a temperature approximately that of the voltaic arc. Partial evidence to the same effect had earlier been alleged by Lockyer, as well as by Living and Dewar, and the case was rendered tolerably complete by photographs taken by Kaiser and Runge in 1889. It was by Professor Rowland shown to be irresistible. 200 carbon lines were, through his comparisons, sifted out from sunlight, and it contains others significant of the presence of silicon, a related substance, and one as important to rock building on the Earth as carbon is to the maintenance of life. The general result of Rowland's labors was the establishment among solar materials, not only of these 2 out of the 14 metalloids, or nonmetallic substances, but of 33 metals, including silver and tin. Gold, mercury, bismuth, antimony, and arsenic were discarded from the catalogue. Platinum and uranium, with 6 other metals, remained doubtful, while iron was recorded as crowding the spectrum with over 2,000 obscure rays. Gallium absorption was detected in it by Hartley and Ramage in 1889. Dr. Henry Draper announced, in 1877, his imagined discovery, in the solar spectrum, of 18 especially brilliant spaces corresponding to oxygen emissions. But the agreement proved, when put to the test of very high dispersion, to be wholly illusory. Nor has it yet been found possible to identify, in analyzed sunlight, any significant bright beams. The book of solar chemistry must be read in characters exclusively of absorption. Nevertheless, the whole truth is unlikely to be written there. That a substance displays none of its distinctive beams in the spectrum of the Sun or of a star, affords scarcely a presumption against its presence. For it may be situated below the level where absorption occurs, or under a pressure such as to efface lines by widening and weakening them. It may be at a temperature so high that it gives out more light than it takes up, and yet its incandescence may be masked by the absorption of other bodies. Finally, it may just balance absorption by emission, with the result of complete spectral neutrality. An instructive example is that of the chromospheric element helium. Father Secchi remarked in 1868 that there is no dark line in the solar spectrum matching its light, and his observation has been fully confirmed. Helium absorption is, however, occasionally noticed in the penumbrae of spots. Our terrestrial vital element might then easily subsist unrecognizably in the Sun. The inner organization of the oxygen molecule is a considerably plastic one. It is readily modified by heat, and these modifications are reflected in its varying modes of radiating light. Dr. Schuster enumerated in 1879 4 distinct oxygen spectra, corresponding to various stages of temperature, or phases of electrical excitement, and a 5th has been added by M. Egeroff's discovery in 1883 that certain well-known groups of dark lines in the red end of the solar spectrum, Fraunhofer's A and B, are due to absorption by the cool oxygen of our air. These persist down to the lowest temperatures, and even survive a change of state. They are produced essentially the same by liquid, as by aerial oxygen. It seemed, however, possible to M. Janssen that these bands owned a joint solar and terrestrial origin. Oxygen in a fit condition to produce them might, he considered, exist in the outer atmosphere of the Sun, and he resolved to decide the point. No one could bring more skill and experience to bear upon it than he. By observations on the summit of the Fallhorn, as well as by direct experiment, he demonstrated, nearly 30 years ago, the leading part played by water vapor in generating the atmospheric spectrum. And he had recourse to similar means for appraising the share in it assignable to oxygen. An electric beam, transmitted from the Eiffel Tower to Meudon in the summer of 1888, having passed through a weight of oxygen about equal to that piled above the surface of the Earth, showed the groups A and B just as they appear in the high sun spectrum. Atmospheric action is then adequate to produce them. But M. Janssen desired to prove, in addition, that they diminish proportionately to its amount. His ascent of Mont Blanc in 1890 was undertaken with this object. It was perfectly successful. In the solar spectrum, examined from that eminence, oxygen absorption was so much enfeebled as to leave no possible doubt of its purely telluric origin. Under another form, nevertheless, it has been detected as indubitably solar. A triplet of dark lines low down in the red, photographed from the Sun by Higgs and McLean, was clearly identified by Runge and Paschen in 1896 with the fundamental group of an oxygen series. First seen by Piazzi Smith in the spectrum of a vacuum tube in 1883. The pabulum vitae of our Earth is then to some slight extent effective in arresting transmitted sunlight, and oxygen must be classed as a solar element. The rays of the Sun, besides being stopped selectively in our atmosphere, suffer also a marked general absorption. This tells chiefly upon the shortest wavelengths. The ultraviolet spectrum is in fact closed, as if by the interposition of an opaque screen. Nor does the screen appear very sensibly less opaque from an elevation of 10,000 feet. Dar. Simonet's spectral photographs, taken on the peak of Tenerife, extended but slightly further up than M. Cornu's, taken in the valley of the Loire. Could the veil be withdrawn, some indications as to the originating temperature of the solar spectrum might be gathered from its range. Since the proportion of quick vibrations given out by a glowing body grows with the intensity of its incandescence. And this brings us to the subject of our next chapter. Footnotes. Phil. Mag, Volume 42, page 380, 1871. Astre. Knock, number 3053, America Jour, Volume 42, page 162, Deslandres, Comptes Rendus, T. Xi, page 307. Proc. Roy. Society, Volume 61, page 433. Phil. Mag, Volume 42, page 377. Frostscheiner, Astre. Spectroscopy, pages 184, 423. Proc. Roy. SOC, Volume 17, p. 302. Astre. Knock, number 1769. A.M. Jour of Science, Volume 15, page 85. Journ. Franklin Institute, Volume 40, p. 232a. Pog. Annalen, B.D. Xlv, page 475, Astre. Knock, number 3014. Astre. Knock, numbers 3006, 3037. This device was suggested by Janssen in 1869. Astre. And Astrophysics, Volume 11, pages 70, 407. Astre. And Astrophysics, Volume 11, page 604. Comptes Rendus, T. Xi, page 307. Astre. And Astrophysics, Volume 11, page 50. Ibid, pages 60, 314. Weidmann's Annalen der Physik, BD, 25, page 80. Evershed, Knowledge, Volume 21, page 133. Secchi, Le Soleil, T. 2, page 294. Lockyer, Chemistry of the Sun, page 418. L'Astronomie, August, 1884, p. 292, Rico, see also Evershed, Jour. British Astra. As, Volume 2, page 174. Averaging about 100 miles across and 300 high. Le Soleil, T. 2, page 35. The Sun, page 192. Astra. Nock, number 1854. MEM. Degli Spettroscopisti Italiani, T.V., page 4. Secchi, Ibid, T. 6, page 56. Its non-atmospheric character was early defined by Proctor, Month. Not, Volume 31, page 196. Astroph. Jour, Volume 6, page 412. Ibid, Volume 11, page 165. Ibid, page 243. Sun's Place in Nature, pages 111, 288. ABH. D. Con. Bohm Guess. D. Wis, BD, 2, 1841-42, page 467. In a paper read before the Société Philomathique de Paris, December 23, 1848, and first published in extenso in and de Chim. Études Phys. T. 19, page 211, 1870. Hippolyte Fauzeau died in September, 1896. Astra. Nock, number 1772. Ibid, number 1864. A. Cornu, Sur la méthode Doppler-Fauzeau, p.d. 23. A.M. Jour of SC, Volume 12, page 321. Ibid, Volume 14, page 140. Bull. Astronomy, February, 1884, page 77. Comptes Rendus, T. Sci, page 368. Month. Not, Volume 44, page 170. C. Anti, page 147. Recherches sur la rotation du Soleil, Uppsala, 1891. Harzer, Astra. Nock, number 3026, Stratonov, Ibid, number 3344. Publ, Astra. Pacific SOC, Volume 2, page 193. Proc. Roy. Society, Volume 17, page 415, 18, page 120. Comptes Rendus, T. Xi, page 1421, T. Xi, page 310. At the Sun's distance, 1 second of arc represents about 450 miles. America Jour of SC, Volume 2, page 468, 1871. Month. Not, Volume 32, p. 51. Nature, Volume 23, page 281. Comptes Rendus, T. 87, page 532. Ibid, T. 96, page 359. A. Brester, Theorie du Soleil, page 66. Such prominences as have been seen to grow by the spread of incandescence are of the quiescent kind, and present no deceptive appearance of violent motion. Proc. Roy. SOC, Volume 28, page 157. Evolution in the Spectroscope, Pop. Science Monthly, January, 1873. Proc. Roy. SOC, Volume 24, page 353. These are the H and K of prominences. H. W. Vogel discovered in 1879 a hydrogen line nearly coincident with H. Monetsp. Prusse. A.K., February, 1879, page 118. Proc. Roy. SOC, Volume 28, page 444. Many of these were referred by Lockyer himself, who first sifted the matter, to traces of the metals concerned. Chemistry of the Sun, page 312, Proc. Roy. Society, volume 57, page 199. Lockyer's Chemistry of the Sun, page 324. Month. Knott, volume 51, page 76. Ibid, volume 58, page 370. Astra. and Astrophysics, volume 11, page 615. Thalen's estimate, Comptes Rendus, t. 97, page 902, of 300,000 kilometers, seems considerably too low. Limiting the average prominence region to a shell 54,000 miles deep, 2 of arc as seen from the Earth, the visual line will, at mid-height, 27,000 miles from the Sun's surface, travel through, in round numbers, 320,000 miles of that region. Living and Doer, Phil. Mag, Volume 16. 5th Ser, page 407. Chemistry of the Sun, page 260. Nature, October 14, 1886. The normal spectrum is that depending exclusively upon wavelength, the fundamental constant given by nature as regards light. It is obtained by the interference of rays, in the manner first exemplified by Fraunhofer, and affords the only unvarying standard for measurement. In the refraction spectrum, upon which Kirchhoff's map was founded, the relative positions of the lines vary with the material of the prisms. Scheiner, Die Spektralanalyse der Gestern, page 168. Phil. Mag, volume 27, page 479. Astra. and Astrophysics, volume 12, page 321, Frost-Scheiner, Astra. Spectre, page 363. Published in Astroph. Jour, volumes I-6. Astra. and Astrophysics, volume 11, page 793. Astroph. Jour, volume 6, page 95. Annales de l'Observatoire de Nice, T3, 1890. Trans Royal Society of Edinburgh, volume 36, page 99. Reverend A. L. Cordy, Astra. and Astrophysics, volume 11, page 401. Specimens of his photographs were given by Ranyard in Knowledge, volume 13, page 212. And D. Phys. B.D. Xvi, page 296. Comptes Rendus, T. 63, page 647. Ibid, T. 86, page 317. Some half-dozen of these identifications have proved fallacious. Chemistry of the Sun, page 143. Amerika Jour, of Science, volume 34, page 348. Berlin Abhandlungen, 1889. Amerika Jour. of Science, volume 41, page 243. See Appendix, Table 2. Astrophy. Jour, volume 9, page 219, Fowler, Knowledge, volume 23, page 11. Amerika Jour, of Science, volume 14, page 89, Nature, volume 16, page 364, month. Knott, volume 39, page 440. Month. Knott, volume 38, page 473, Trowbridge and Hutchins, Amerika Jour, of Science, volume 34, page 263. Scheiner, Die Spektralanalyse, page 180. Comptes Rendus, T. 67, page 1123. Reverend A. L. Cordy, month. Knott, volume 51, page 18. Young, The Sun, page 135, Hale, Astra. and Astrophysics, volume 11, page 312. Buss, Jour, Brit. Astra. As, volume 9, page 253. Phil. Trans, volume CLXX, page 46. Comptes Rendus, T. 97, page 555, T. CI, page 1145. Living and Doer, Astra. and Astrophysics, volume 11, page 705. Comptes rendus, t. Lx, page 213, t. 63, page 289. Ibid, t. Xi, page 1035. Ibid, t. Xi, page 431. Astroph. Jour, volumes 4, page 317, 6, page 426. Trans Roy. SOC Eden, volume 32, page 452. Comptes rendus, t. Xi, page 941, Huggins, Proc. Roy. SOC, volume 46, p. 168. Chapter 5. Temperature of the Sun. Newton was the first who attempted to measure the quantity of heat received by the Earth from the Sun. His object in making the experiment was to ascertain the temperature encountered by the comet of 1680 at its passage through perihelion. He found it, by multiplying the observed heating effects of direct sunshine according to the familiar rule of the inverse squares of the distances, to be about 2,000 times that of red-hot iron. Determinations of the Sun's thermal power, made with some scientific exactness, date, however, from 1837. A few days previous to the beginning of that year, Herschel began observing at the Cape of Good Hope with an actinometer, and obtained results agreeing quite satisfactorily with those derived by Pouillet from experiments made in France some months later with a pyrheliometer. Pouillet found that the vertical rays of the Sun falling on each square centimeter of the Earth's surface are competent, apart from atmospheric absorption, to raise the temperature of 176.33 grams of water 1 degree centigrade per minute. This number, 176.33, he called the solar constant, and the unit of heat chosen is known as the calorie. Hence it was computed that the total amount of solar heat received during a year would suffice to melt a layer of ice covering the entire Earth to a depth of 3089 meters, or 100 feet. While the heat emitted would melt, at the Sun's surface, a stratum 1180 meters thick each minute. A careful series of observations showed that nearly half the heat incident upon our atmosphere is stopped in its passage through it. Herschel got somewhat larger figures, though he assigned only a third as the spoil of the air. Taking a mean between his own and Pouillet's, he calculated that the ordinary expenditure of the Sun per minute would have power to melt a cylinder of ice 184 feet in diameter, reaching from his surface to that of Alpha Centauri. Or, putting it otherwise, that an ice rod 3 miles across, continually darted into the Sun with the velocity of light, would scarcely consume, in dissolving, the thermal supplies now poured abroad into space. It is nearly certain that this estimate should be increased by about 2/3 in order to bring it up to the truth. Nothing would, at first sight, appear simpler than to pass from a knowledge of solar emission, a strictly measurable quantity, to a knowledge of the solar temperature. This being defined as the temperature to which a surface thickly coated with lampblack, that is, of standard radiating power, should be raised to enable it to send us, from the Sun's distance, the amount of heat actually received from the Sun. Sir John Herschel showed that heat rays at the Sun's surface must be 92,000 times as dense as when they reach the Earth. But it by no means follows that either the surface emitting, or a body absorbing those heat rays must be 92,000 times hotter than a body exposed here to the full power of the Sun. The reason is, that the rate of emission, consequently the rate of absorption, which is its correlative, increases very much faster than the temperature. In other words, a body radiates or cools at a continually accelerated pace as it becomes more and more intensely heated above its surroundings. Newton, however, took it for granted that radiation and temperature advance pari passu, that you have only to ascertain the quantity of heat received from, and the distance of a remote body in order to know how hot it is. And the validity of this principle, known as Newton's law of cooling, was never questioned until de la Roche pointed out, in 1812, that it was approximately true only over a low range of temperature. While 5 years later, Dulong and Petit generalized experimental results into the rule, that while temperature grows by arithmetical, radiation increases by geometrical progression. Adopting this formula, Pouillet derived from his observations on solar heat a solar temperature of somewhere between 1461 degrees and 1761 degrees Celsius. Now, the higher of these points, which is nearly that of melting platinum, is undoubtedly surpassed at the focus of certain burning glasses which have been constructed of such power as virtually to bring objects placed there within 250,000 miles of the photosphere. In the rays thus concentrated, platinum and diamond become rapidly vaporized, notwithstanding the great loss of heat by absorption, first in passing through the air, and again in traversing the lens. Pouillet's maximum is then manifestly too low, since it involves the absurdity of supposing a radiating mass capable of heating a distant body more than it is itself heated. Less demonstrably, but scarcely less surely, Mr. J. Waterston, who attacked the problem in 1860, erred in the opposite direction. Working up, on Newton's principle, data collected by himself in India and at Edinburgh, he got for the potential temperature of the Sun 12,880,000 degrees FAHR. Equivalent to 7,156,000 degrees Celsius. The phrase potential temperature, for which Vial substituted, in 1876, effective temperature, was designed to express the accumulation in a single surface, postulated for the sake of simplicity, of the radiations not improbably received from a multitude of separate solar layers reinforcing each other. And might thus, it was explained, be considerably higher than the actual temperature of any one stratum. At Rome, in 1861, Father Secchi repeated Waterston's experiments, and reaffirmed his conclusion. While Soret's observations, made on the summit of Mont Blanc in 1867, furnished him with materials for a fresh and even higher estimate of 10 million degrees centigrade. Yet from the very same data, substituting Dulong and Petit's for Newton's law, Becquerel deduced in 1872 a provisional solar temperature of 1398 degrees. This is below that at which iron melts, and we know that iron vapor exists high up in the sun's atmosphere. The matter was taken into consideration on the other side of the Atlantic by Ericsson in 1871. He attempted to re-establish the shaken credit of Newton's principle, and arrived, by its means, at a temperature of 4 million degrees Fahrenheit. Subsequently, an underrated computation, based upon observation of the quantity of heat received by his sun motor, gave him 3 million degrees. And the result, as he insisted, followed inevitably from the principle that the temperature produced by radiant heat is proportional to its density, or inversely as its diffusion. The principle, however, is demonstrably unsound. In 1876 the sun's temperature was proposed as the subject of a prize by the Paris Academy of Sciences, but although the essay of M. Jules Vial was crowned, the problem was declared to remain unsolved. Vial, who adhered to Dulong and Petit's formula, arrived at an effective temperature of 1,500 degrees Celsius, but considered that it might actually reach 2,500 degrees Celsius. If the emissive power of the photospheric clouds fell far short, as seemed probable, of the lamp-black standard. Experiments made in April and May, 1881, giving a somewhat higher result, he raised this figure to 3,000 degrees Celsius. Appraisements so outrageously discordant as those of Waterston, Secchi, and Ericsson on the one hand, and those of the French savants on the other, served only to show that all were based upon a vicious principle. Professor F. Rossetti, accordingly, of the Paduan University, at last perceived the necessity for getting out of the groove of laws, plainly in contradiction with facts. The temperature, for instance, of the oxyhydrogen flame was fixed by Bunsen at 2,800 degrees Celsius. An estimate certainly not very far from the truth. But if the two systems of measurement applied to the sun be used to determine the heat of a solid body rendered incandescent in this flame, it comes out, by Newton's mode of calculation, 45,000 degrees Celsius. By Dulong and Petit's, 870 degrees Celsius. Both, then, are justly discarded, the first as convicted of exaggeration, the second of undervaluation. The formula substituted by Rossetti in 1878 was tested successfully up to 2000 degrees Celsius. But since, like its predecessors, it was a purely empirical rule, guaranteed by no principle, and hence not to be trusted out of sight, it was, like them, liable to break down at still higher elevations. Radiation by this new prescription increases as the square of the absolute temperature, that is, of the number of degrees counted from the absolute zero of -273 degrees Celsius. Its employment gave for the Sun's radiating surface an effective temperature of 20,380 degrees Celsius, including a supposed loss of 1/2 in the solar atmosphere. And setting a probable deficiency in emission, as compared with lampblack, against a probable mutual reinforcement of superposed strata, Professor Rossetti considered effective as nearly equivalent to actual temperature. A law of cooling, proposed by M. Stefan at Vienna in 1879, was shown by Boltzmann, many years later, to have a certain theoretical validity. It is that emission grows as the fourth power of absolute temperature. Hence the temperature of the photosphere would be proportional to the square root of its heating effects at a distance, and appeared, by Stefan's calculations from Vial's measures of solar radiative intensity, to be just 6,000 degrees C. While M. H. Le Chatelier derived 7,600 degrees from a formula, conveying an intricate and unaccountable relation between the temperature of an incandescent body and the intensity of its red radiations. From a series of experiments carefully conducted at Daramona, Ireland, with a delicate thermal balance, of the kind invented by Boys and designated a radiomicrometer, Messrs. Wilson and Gray arrived in 1893, with the aid of Stefan's law, at a photospheric temperature of 7,400 degrees Celsius, reduced by the first-named investigator in 1901 to 6,590 degrees. Dar. Paschen, of Hanover, on the other hand, ascribed to the Sun a temperature of 5,000 degrees from comparisons between solar radiative intensity and that of glowing platinum, while F. W. Very showed in 1895 that a minimum value of 20,000 degrees Celsius. For the same datum resulted from Paschen's formula connecting temperature with the position of maximum spectral energy. A new line of inquiry was struck out by Zollner in 1870. Instead of tracking the solar radiations backward with the dubious guide of empirical formulae, he investigated their intensity at their source. He showed that, taking prominences to be simple effects of the escape of powerfully compressed gases, it was possible, from the known mechanical laws of heat and gaseous constitution, to deduce minimum values for the temperatures prevailing in the area of their development. These came out 27,700 degrees Celsius, for the strata lying immediately above, and 68,400 degrees Celsius. For the strata lying immediately below the photosphere, the former being regarded as the region into which, and the latter as the region from which the eruptions took place. In this calculation, no prominences exceeding 40,000 miles, 1/5, in height were included. But in 1884, G.A. Hearn of Colmar, having regard to the enormous velocities of projection observed in the interim, fixed 2 million degrees centigrade as the lowest internal temperature by which they could be accounted for. Although admitting the photospheric condensations to be incompatible with a higher external temperature than 50,000 degrees to 100,000 degrees Celsius. This method of going straight to the Sun itself, observing what goes on there, and inferring conditions, has much to recommend it, but its profitable use demands knowledge we are still very far from possessing. We are quite ignorant, for instance, of the actual circumstances attending the birth of the solar flames. The assumption that they are nothing but phenomena of elasticity is a purely gratuitous one. Spectroscopic indications, again, give hope of eventually affording a fixed point of comparison with terrestrial heat sources, but their interpretation is still beset with uncertainties. Nor can, indeed, the expression of transcendental temperatures in degrees of impossible thermometers be, at the best, other than a futile attempt to convey notions respecting a state of things altogether outside the range of our experience. A more tangible, as well as a less disputable proof of solar radiative intensity than any mere estimates of temperature, was provided in some experiments made by Professor Langley in 1878. Using means of unquestioned validity, he found the sun's disk to radiate 87 times as much heat, and 5,300 times as much light as an equal area of metal in a Bessemer converter after the air blast had continued about 20 minutes. The brilliancy of the incandescent steel, nevertheless, was so blinding, that melted iron, flowing in a dazzling white-hot stream into the crucible, showed deep brown by comparison, presenting a contrast like that of dark coffee poured into a white cup. Its temperature was estimated, not quite securely, at about 2000 degrees Celsius. And no allowances were made, in computing relative intensities, for atmospheric ravages on sunlight, for the extra impediments to its passage presented by the smoke-laden air of Pittsburgh, or for the obliquity of its incidence. Thus, a very large balance of advantage lay on the side of the metal. A further element of uncertainty in estimating the intrinsic strength of the sun's rays has still to be considered. From the time that his disk first began to be studied with the telescope, it was perceived to be less brilliant near the edges. Lucas Valerius, of the Linnaean Academy, seems to have been the first to note this fact, which, strangely enough, was denied by Galileo in a letter to Prince Sisai of January 25, 1613. Father Scheiner, however, fully admitted it, and devoted some columns of his bulky tome to the attempt to find its appropriate explanation. In 1729 Bugger measured, with much accuracy, the amount of this darkening. And from his data, Laplace, adopting a principle of emission now known to be erroneous, concluded that the sun loses 11/12 of his light through absorption in his own atmosphere. The real existence of this atmosphere, which is totally distinct from the beds of ignited vapors producing the Fraunhofer lines, is not open to doubt, although its nature is still a matter of conjecture. The separate effects of its action on luminous, thermal, and chemical rays were carefully studied by Father Secchi, who in 1870 inferred the total absorption to be 88/100 of all radiations taken together. And added the important observation that the light from the limb is no longer white, but reddish-brown. Absorptive effects were thus seen to be unequally distributed, and they could evidently be studied to advantage only by taking the various rays of the spectrum separately, and finding out how much each had suffered in transmission. This was done by H. C. Vogel in 1877. Using a polarizing photometer, he found that only 13% of the violet rays escape at the edge of the solar disk, 16 of the blue and green, 25 of the yellow, and 30% of the red. Midway between center and limb, 88.7 of violet light and 96.7 of red penetrate the absorbing envelope, the abolition of which would increase the intensity of the sun's visible spectrum above 2.5 times in the most, and 1.5 times in the least refrangible parts. The nucleus of a small spot was ascertained to be of the same luminous intensity as a portion of the unbroken surface about 2.5 minutes from the limb. These experiments having been made during a spot minimum when there is reason to think that absorption is below its average strength, Vogel suggested their repetition at a time of greater activity. They were extended to the heat rays by Edwin B. Frost. Detailed inquiries made at Potsdam in 1892 went to show that, were the sun's atmosphere removed, his thermal power, as regards ourselves, would be increased 1.7 times. They established, too, the practical uniformity in radiation of all parts of his disk. A confirmatory result was obtained about the same time by Wilson and Rambout, who found that the unveiled sun would be 1.5 times hotter than the actual sun. Professor Langley, now of Washington, gave to measures of the kind a refinement previously undreamt of. Reliable determinations of the energy of the individual spectral rays were, for the first time, rendered possible by his invention of the bolometer, in 1880. This exquisitely sensitive instrument affords the means of measuring heat, not directly, like the thermopile, but in its effects upon the conduction of electricity. It represents, in the phrase of the inventor, the finger laid upon the throttle valve of a steam engine. A minute force becomes the modulator of a much greater force, and thus from imperceptible becomes conspicuous. By locally raising the temperature of an inconceivably fine strip of platinum serving as the conducting wire in a circuit, the flow of electricity is impeded at that point, and the included galvanometer records a disturbance of the electrical flow. Amounts of heat were thus detected in less than 10 seconds, which, expended during 1,000 years on the melting of a kilogram of ice, would leave a part of the work still undone. And further improvements rendered this marvelous instrument capable of thrilling to changes of temperature falling short of 1/10,000,000th of a degree centigrade. The heat contained in the diffraction spectrum is, with equal dispersions, barely 1/10 of that in the prismatic spectrum. It had, accordingly, never previously been found possible to measure it in detail, that is, ray by ray. But it is only from the diffraction, or normal spectrum that any true idea can be gained as to the real distribution of energy among the various constituents, visible and invisible, of a sunbeam. The effect of passage through a prism is to crowd together the red rays very much more than the blue. To this prismatic distortion was owing the establishment of a pseudo-maximum of heat in the infrared, which disappeared when the natural arrangement by wavelength was allowed free play. Langley's bolometer has shown that the hottest part of the normal spectrum virtually coincides with its most luminous part, both lying in the orange, close to the D line. Thus the last shred of evidence in favor of the threefold division of solar radiations vanished, and it became obvious that the varying effects, thermal, luminous, or chemical, produced by them are due not to any distinction of quality in themselves, but to the different properties of the substances they impinge upon. They are simply bearers of energy, conveyed in shorter or longer vibrations. The result in each separate case depending upon the capacity of the material particles meeting them for taking up those shorter or longer vibrations, and turning them variously to account in their inner economy. A long series of experiments at Allegheny was completed in the summer of 1881 on the crest of Mount Whitney in the Sierra Nevada. Here, at an elevation of 14,887 feet, in the driest and purest air, perhaps, in the world, atmospheric absorptive inroads become less sensible, and the indications of the bolometer, consequently, surer and stronger. An enormous expansion was at once given to the invisible region in the solar spectrum below the red. Captain Abney had got chemical effects from undulations 12/10,000ths of a millimeter in length. These were the longest recognized as, or indeed believed, on theoretical grounds, to be capable of existing. Professor Langley now got heating effects from rays of above twice that wavelength, his delicate thread of platinum groping its way down nearly to 30/10,000ths of a millimeter, or 3 microns. The known extent of the solar spectrum was thus at once more than doubled. Its visible portion covers a range of about 1 octave, bolometric indications already in 1884 comprised between 3 and 4. The great importance of the newly explored region appears from the fact that 3/4 of the entire energy of sunlight reside in the infrared, while scarcely more than 1/100th part of that amount is found in the better-known ultraviolet space. These curious facts were reinforced, in 1886, by further particulars learned with the help of rock-salt lenses and prisms, glass being impervious to very slow, as to very rapid vibrations. Traces were thus detected of solar heat distributed into bands of transmission alternating with bands of atmospheric absorption, far beyond the measurable limit of 5-3 microns. In 1894, Langley described at the Oxford meeting of the British Association his new bolographic researches, in which the sensitive plate was substituted for the eye in recording deflections of the galvanometer responding to variations of invisible heat. Finally, in 1901, he embodied in a splendid map of the infrared spectrum 740 absorption lines of determinate wavelengths, ranging from 0.76 to 5.3 microns. Their chemical origin, indeed, remains almost entirely unknown, no extensive investigations having yet been undertaken of the slower vibrations distinctive of particular substances. But there is evidence that 7 of the 9 great bands crossing the new spectrum, as Langley calls it, are telluric and subject to seasonal change. Here, then, he thought, might eventually be found a sure standing ground for vitally important previsions of famines, droughts, and bonanza crops. Atmospheric absorption had never before been studied with such precision as it was by Langley on Mount Whitney. Aided by simultaneous observations from Lone Pine, at the foot of the Sierra, he was able to calculate the intensity belonging to each ray before entering the Earth's gaseous envelope, in other words, to construct an extra-atmospheric curve of energy in the spectrum. The result showed that the blue end suffered far more than the red, absorption varying inversely as wavelength. This property of stopping predominantly the quicker vibrations is shared, as both Vogel and Langley have conclusively shown, by the solar atmosphere. The effect of this double absorption is as if two plates of reddish glass were interposed between us and the Sun, the withdrawal of which would leave his orb, not only 3 or 4 times more brilliant, but in color distinctly greenish-blue. The fact of the uncovered Sun being blue has an important bearing upon the question of his temperature, to afford a somewhat more secure answer to which was the ultimate object of Professor Langley's persevering researches. For it is well known that as bodies grow hotter, the proportionate representation in their spectra of the more refrangible rays becomes greater. The lowest stage of incandescence is the familiar one of red heat. As it gains intensity, the quicker vibrations come in, and an optical balance of sensation is established at white heat. The final term of blue heat, as we now know, is attained by the photosphere. On this ground alone, then, of the large original preponderance of blue light, we must raise our estimate of solar heat, and actual measurements showed the same upward tendency. Until quite lately, Pouillet's figure of 1.7 calories per minute per square centimeter of terrestrial surface, was the received value for the solar constant. Forbes had, it is true, got 2.85 from observations on the Faulhorn in 1842, but they failed to obtain the confidence they merited. Pouillet's result was not definitely superseded until Vial, from actinometrical measures at the summit and base of Mont Blanc in 1875, computed the intensity of solar radiation at 2.54, and Crova, about the same time, at Montpellier, showed it to be above 2 calories. Langley went higher still. Working out the results of the Mount Whitney expedition, he was led to conclude atmospheric absorption to be fully twice as effective as had hitherto been supposed. Scarcely 60%. In fact, of those solar radiations which strike perpendicularly through a seemingly translucent sky, were estimated to attain the sea level. The rest are reflected, dispersed, or absorbed. This discovery involved a large addition to the original supply so mercilessly cut down in transmission, and the solar constant rose at once to 3 calories. Nor did the rise stop there. M. Saveleaf deduced for it a value of 3.47 from actinometrical observations made at Kief in 1890, and Knut Engström, taking account of the arrestive power of carbonic acid, inferred enormous atmospheric absorption, and a solar constant of 4 calories. In other words, the Sun's heat reaching the outskirts of our atmosphere is capable of doing without cessation the work of an engine of 4 horsepower for each square yard of the Earth's surface. Thus, modern inquiries tend to render more and more evident the vastness of the thermal stores contained in the great central reservoir of our system, while bringing into fair agreement the estimates of its probable temperature. This is in great measure due to the acquisition of a workable formula by which to connect temperature with radiation. Stefan's rule of a fourth power relation, if not actually a law of nature, is a colorable imitation of one. And its employment has afforded a practical certainty that the Sun's temperature, so far as it is definable, neither exceeds 12,000 degrees Celsius, nor falls short of 6,500 degrees Celsius. Footnotes. Principia, page 498, first edition. Comptes rendus, T. 7, page 24. Results of Astra. Observations, page 446. Est enim calor solis ut radiorum densitas, hoc est, recipros ut quadratum distantii locorum a sol. Principia, page 508, 3d edition, 1726. Jour de physique, T. 75, page 215. And de chimie, T. 7, 1817, p. 365. Phil. Mag, Volume 23. 4th Ser, page 505. Nuovo Cimento, T. 16, page 294. Comptes rendus, T. LXV, page 526. The direct result of 5 1/3 million degrees was doubled in allowance for absorption in the Sun's own atmosphere. Comptes rendus, t. 74, page 26. Ibid, page 31. Nature, volumes 4, page 204, v, page 505. Ibid, volume 30, page 467. And de Chim, T. X, 5th ser, page 361. Comptes rendus, t. 96, page 254. Phil. Mag, volume 8, page 324, 1879. Ibid, page 325. Sitzungsbericht, Wien, B.D. 79, 2, page 391. Weidmann's Annalen, B.D. 22, page 291, Scheiner, Strahlung und Temperatur der Sonne, page 27. Comptes rendus, March 28, 1892, Astra. And Astrophysics, volume 11, page 517. Phil. Trans, volume CLXXXV, page 361. Proc. Roy. Society, December 12, 1901. Scheiner, Tempter Sonne, page 36. Astroph. Jour, volume 2, page 318. Astra. Nock, numbers 1815-16. L'Astronomy, September, 1884, page 334. America Jour of Science, volume 1, 3rd ser, page 653. Young, The Sun, page 310. Op. T. 6, page 198. Rosa Acina, lib 4, page 618. Mech. Cell, liv. X, page 323. Le Soleil, 1st edition, page 136. Monitzber, Berlin, 1877, page 104. Astra. Nock, numbers 3105-6, Astra. And Astrophysics, volume 11, page 720. Proc. Roy. Irish Academic, volume 2, no. 2, 1892. A.M. Jour of SC, volume 21, page 187. America Jour of Science, volume 5, page 245, 1898. For J. W. Draper's partial anticipation of this result, see Ibid, volume 4, 1872, page 174. Phil. Mag, volume 14, page 179, 1883. The Solar and the Lunar Spectrum, Memoirs National Academic of Science, volume 32, on hitherto unrecognized wavelengths, America Jour of Science, volume 32, August, 1886. Astroph. Jour, volume 1, page 162. Annals of the Smithsonian Astroph. Observatory, volume 1, Comptes rendus, T. Xi, page 734, Astroph. Jour, volume 3, page 63. Phil. Mag, July, 1901. Comptes rendus, T. 92, page 701. Nature, volume 26, page 589. Phil. Trans, volume Xi, page 273. And de Chim, T. X, page 321. Ibid. T. 11, page 505. Comptes rendus, T. Xi, page 1200. Weed. And, B.D. 39, page 294, Scheiner, Temperatur der Sonne, pages 36, 38. Chapter 6. The Sun's Distance.